Hello friends, welcome back to our channel. So today we'll start one more concept called design and analysis of algorithms. So in today's session we'll see what is an algorithm and the complete introduction to designing of algorithm and algorithm analysis. So and analysis of algorithms. So many of the viewers were requesting me to start this subject, design and analysis of algorithms, because this subject will be the most important subject for all the computer science students. So in order to get a higher package, the students have to focus on this particular design and analysis of algorithms. So mainly the data structures and algorithms concepts, right? So first we'll see what is an algorithm. So most of you know about this. What is the definition of an algorithm? So algorithm is defined as a set of instructions, okay, which are involved to solve the problem or a specific task. So if any problem is given, if any task is given, so what are the steps we have to follow in order to solve that, in order to achieve that, right? So it is a set of instructions, or we can also call them as a steps, okay, to solve problem, or we can call it as a task. So separate set of instructions or steps to solve the problem or task. And see, this algorithm is a most fundamental blocks for any programming to solve the problems. So this is the most major part while solving the problems. Here, solving the problem means automation. In our language, we can call it as an automation. So we'll consider one problem and we have to provide the solution by giving some sort of programming, right? So in order to give that, the main aim is to get the optimal solution. So for every problem, there will be a lot of solutions, right? Solution 1, 2, 3, and so on. Solution n. That means one problem can be solved in many ways, right? But we have to consider the optimal solution. Optimal, that means the best solution. So for this, to better understanding, I'll tell you a small example. If you want to go from one place to another place, so there will be a lot of paths, but we have to select the shortest path, okay, so that the time will be saved and also the fuel will be saved. So it depends upon the constraints. We have to select a proper solution. So among all these solutions, we have to select a proper solution, right? So that's why this depends upon the methodology we are using to solve the problem. So there will be different methods to solve a problem, but we have to select a problem and a method which gives the best solution. So that we call it as an optimal solution. Based upon our requirement, we have to select the solution. So that's why the algorithm will be the most important fundamental block for all the problems to be get solved. So either it may be a simple problems or a complex problems. So both the problems can be solved by these algorithms. And there are many algorithm methodologies, right? So now we'll see the algorithm methodologies. So types or methodologies or methods are the first one, searching techniques. So there will be a lot of searching algorithms, linear search, binary search, etc. Similarly, sorting techniques. So we can use the sorting mechanism. So either, arranging the values in either increasing order or decreasing order. So sorting algorithms will be there. A lot of algorithms: bubble sort, quick sort, merge sort, etc., etc. And similarly, brute force methodology. So brute force methodology means checking all the possibilities. So we don't know the best one, so checking all the possibilities. So brute force method. Similarly, greedy method, dynamic programming. Divide and conquer method, recursive programming. So these are all the different methodologies we can use to solve any kind of problem. But one important point is, one particular method will not be suitable for all the problems to be get solved with a better solution. So based upon the problem, we have to analyze which method will be suitable to get the perfect solution. So we have to learn all these things so that we can have an idea about all the methodologies, so that based upon the problem, we can select one among these methodologies to solve the particular problem. So this plays a very crucial role, right? So, and this is the first part, designing of algorithm in this subject. So which methodology we are going to use in order to solve the problem. Whether we are using the brute force method or a dynamic programming method or a divide and conquer or a greedy method, etc., etc. And the next one is analysis. So algorithm analysis. And this algorithm analysis is used to evaluate the performance of the algorithm. So if we use the performance of the algorithm, so used in evaluating performance of algorithm. So here the word performance will be in terms of two things. One is the space complexity. So another one is the time complexity. Time complexity, space complexity, and the time complexity. That means how much space it requires to solve the problem. That means a memory, right? So how much time it takes to give the response or to get the complete solution. That's also an optimal solution. So these are the two terminologies we have to consider in this algorithm analysis. So there are different categories of analysis, different types of analysis. So one is a best case analysis, best case, worst case, average case, and amortized case, right? So based upon these things, we have to evaluate the performance of algorithm, right? In terms of space and time complexities. So it should use less space complexity and the less time complexity. Then that also with the help of the requirements, according to the requirements of the problem, right? So for example, let us consider if you want to travel from one place to another place. Okay, so from A to B. So there are two paths. One is a narrow road and the other one is wide road. So if you are using a two-wheeler, automatically it suits this path to reach the destination within a short time. Okay, and if you are using a four-wheeler, okay, this path doesn't suit for this four-wheeler to reach the destination, right? So this four-wheeler have to choose in this path. So that means based upon the requirements, we have to get the optimal solution. Based upon the requirement, we have to choose the method to get the optimal solution, and also in terms of the performance, the space and time complexity, right? So from our next sessions, we'll see each and every methodology, and also the algorithm analysis concept. So this will be the most useful for the students of a computer science, particularly a computer science. Very important. Types of time complexity. So in our previous session, we have discussed about the introduction to analysis of algorithms. So in that we have seen the two parameters, that is a time complexity and the space complexity, are the two parameters to evaluate the performance of an algorithm. So time complexity means how much time it takes to execute the algorithm or a problem or a task. So there are different types of time complexities. Now we'll see one by one, right? So first I list out the types of time complexities and then we'll go one by one. First one is a constant time complexity. Usually it is denoted as order of 1. Next, linear time complexity. It is denoted as order of n. So we'll see this order. What is the order, right? So there will be different asymptotic notations. So that we'll discuss in our further session. Just you can observe the denotations, just like a denotation. Order of n and order of n. Okay. Next, logarithmic time complexity. It is denoted as order of log n. Usually the base will be 2. Next, order of n log n. So there is no specific, so we can call it as a n log n time complexity. So in the name itself indicates, so then it will be denoted as order of n log n. So which will be similar with the logarithmic time complexity. And the next one is quadratic time complexity. So which will be denoted as order of n square. So these are the 5 different types of time complexities. So not every algorithm will have a single time complexity. Okay, so based upon the algorithm and based upon the inputs we are giving, the time complexity will be changed. So obviously the time complexity depends upon the input size. So the problem with the different input size will give a different time complexities. Right? So let us see one by one. First, coming with the constant time complexity. So just now we have said that time complexity means the time taken to execute the problem or to perform a particular task. So here, number of steps required to execute the problem is a constant. That means if the input size is increased, even though the number of steps required to execute the problem remains constant. So irrespective of the input size, the number of steps is constant. So the time doesn't affect with respect to the size of the input. So time doesn't affect or does not vary if the increase in input size. So if the input size is increased, then also the time taken to execute the problem will be remains the same. Okay, so best example for this one is all the arithmetic operations. So even though the number of, the input increases, the performance of this operation will be same. The addition or subtraction or multiplication or division. The time doesn't changes. So such type of statements, we can say the time complexity will be order of 1 or 2 or 3 or 4. It's a constant. We simply say it as a constant. Right? So next, coming to the second category, linear time complexity. Linear time complexity. So which is usually denoted as order of n. So here, the number of steps required to execute the problem depends upon the number of size, the input size. So if the input size is increased, automatically the time taken to execute the problem will also be increased. So number of steps required to complete or to execute the problem depends on input size. That means if input size increases, then time taken to execute will also increase. So that means directly proportional. Okay, so directly proportional. So the time is directly proportional to the input size. So if the input size is small, automatically the time taken to execute the problem will be low. And if the input size is more, the time taken to execute the problem will be more. That means a direct proportional. So best example for this one is linear search. Linear search. So I think most of you are aware about these searching and sorting algorithms, because so if you are watching this design and analysis of algorithms, obviously you might be having a knowledge on searching and sorting techniques, right? So linear search means irrespective of the order of the elements, the search will be keeps on going from one element. That means every element will be compared. Okay, every element will be compared. For example, if you want to search some 100, okay, in 10 elements. Okay, if you want to search one element in 10 elements, if the element is at the last position, what we have to do? So every element we are going to search until it gives the success. So it takes some 10 steps to complete its execution. For example, if we are having 100 elements, it will take 100 steps to complete its execution if the search element is at the last position. Okay, so similarly, linear search is the best example for this type, linear time complexity. That means if the size increases, the time will also be increased. So, and obviously, one more example, general example, if you are having a lock and you forgot the key and you are having a bunch of keys, what you will do to open the door? So you will try with each and every key. So if the correct key is the last key in the bunch, obviously you have to compare, you have to try for all the keys in the bunch. If the size of the keys, bunch of the keys increase, automatically the time taken to open the door will also be increased. So such type of complexity, we call it as a linear type complexity. Hope you understood. Then coming to the third one, logarithmic time complexity. Logarithmic time complexity, and it is denoted as order of log n. And here, the number of steps required to execute the problem will be reduced for every iteration. So the problem space will be reduced. So initially, if the problem space is n, after completion of the first iteration, the problem space will be reduced to n by 2. And obviously, again, the same problem will be divided into half, that means n by 4. So this process will be repeated until the problem has been solved. So such type of things, we call it as a logarithmic time complexity. Okay, here the problem will be divided into small bits or small parts. And after every division, the problem space will be reduced to half. Right? See, here, problem will be divided into small parts. So after each division, the space, the number of steps, or you can say number of steps, will be reduced to half. Okay, so such type of algorithms, the time complexity, we call it as a logarithmic time complexity, and it will be denoted as order of log n. Okay, now the best example for this one is a binary search. So most of you know about this binary search. Again, I will say that one. So the first constraint is, if you want to implement this binary search, the elements should be in a sorted order. All the elements should be in a sorted order. If the elements are in sorted order, if you are searching for a particular element, so first it will find out the middle element, and it will compare the search element with the middle element, and if it is less than, so then the search position will be shifted towards the left part, and if it is greater than, the search position will be shifted towards the right part. For example, so 10, 20, 30, 40, 50. So if search element is some 10. So first it will find out the mid. In the first iteration, it will find out the mid. So 10 is less than 30. So next search space will be this one. So that means after every division, the complete steps are reduced to half. And in next iteration again here we have to find out the mid and have to repeat the same process. So the same process will be repeated. That means the division of subproblems will be done until it reaches or it completes its execution. So binary search will be the best example for this logarithmic time complexity. Okay, reducing the search space or reducing the steps to execute the problem. Coming to the next one, that's also similar to this logarithmic, which is order of n log n. So the same thing happens here also. So we are saying that order of n log n, you can see here also the problem will be divided into small parts. Small parts. Again, say each part, okay, after each division, number of steps required to solve the problem will be reduced to half. So this is nothing but our logarithmic time complexity. After that, collaborating all such small parts. So collaborating all small parts to complete the execution. Right? For example, one problem is divided into n parts. Okay, one problem is divided into n parts. Sorry, 1, 2, 3, and so on. Okay, now you can see for each part again it is divided. Okay, so for this we'll say it as a log n. Again, here it is a log n, here it is a log n. So like this, if we are having some n problems, so then we can say it as a n log n. That means after dividing the parts, after completion of this one, again we have to collaborate all the parts to complete its execution. Right? So the example for this one is merge sort. So merge sort. So in this merge sort, what we are doing? So we are dividing the complete elements into two halves. Again, from the right half and from the left half, again we are dividing it in two halves. Again we are dividing the left half and right half into two halves. Later we are applying the merging operation, and again we are starting collaborating the left and right halves to combine the complete sorted order. Right? So that's the best example for the merge sort. Okay, and this type of algorithm is more efficient if the size of input is large. So this algorithm is efficient and works good for large inputs. For large inputs, that means if the input size is more, this is more suitable. Okay, this type of algorithm will be suitable, and the time complexity we call it as order of n log n. And the last one, quadratic time complexity. Quadratic time complexity, and usually we will denote it as n square. N square. So here the number of steps required is more than the input size. So if the input size is n, the steps required to execute the problem will be n square. So double the steps, double the input size. Okay, so that's why we will represent it as an order of n square. So steps required to execute the problem is double the input size. Double the input size. So if n is the input size, then n square will be the steps required. And this algorithm is very slow if the size of input is more, because it takes a double of the steps, right? So this type of algorithm will be slow for large inputs. So if the input is large, the number of steps required will also be large. Okay? The best example for this type of complexities we call it's a bubble sort. So the main logic of implementing the bubble sort is comparing the consecutive elements. So after first pass, the highest element will be residing at the last position. So in the first pass, we are going to compare consecutive elements. Okay, so in an array, if you want to compare the consecutive elements, first element and second element and third element and fourth element. So like that, if you want to compare the consecutive elements, then this complexity will be suited, and that will be the example for this particular complexity, quadratic time complexity. Right? So hope you understood this one. And apart from this, we are having a cubical time complexity, which is represented as n cube, and more time complexities are there. So these are the mostly we'll see these type of complexities in different algorithms. And one thing I'm just repeating, so the time complexity may vary according to the input size. So the time complexity will be not same for all the input sizes. So if you change the input size, the time complexity will also be changed. So that's why this time complexity, there are different types of time complexities. So this is the one more way to calculate the performance of an algorithm, right? So usually this is used to evaluate the performance of algorithm based on input size. So according to our discussions in our previous session, depends upon the input, the algorithm execution time will be changed. So this evaluation, these asymptotic notations will evaluate the performance of the algorithm based upon this input size, right? So there are three categories of asymptotic notations. So the first one, big O notation, omega notation, and theta notation, right? So first let us see this big O notation. So big O notation is used to represent upper bound of an algorithm, and coming to this omega notation is used to represent lower bound of an algorithm, and this is to represent average bound of an algorithm. So all the three depends upon the input size. So here upper bound of an algorithm means the maximum time the algorithm will take to complete its execution, and the lower bound means minimum time the algorithm will take to complete its execution. And the name itself indicates is an average bound, or some cases we call it as a tight bound. So that means in between the upper bound and the lower bound, that means an average time, right? The average time or the exact time the algorithm takes to complete its execution, that we call it as a theta notation. So this we can call it as maximum time algorithm takes to complete its execution, and here we can say minimum time an algorithm takes, and this is an average time an algorithm takes, right? So that we have to represent by using this big O. So the maximum time the algorithm takes to complete its execution is represented as a big O scenario. Similarly, the minimum time of algorithm which takes to complete its execution will be represented with omega scenario, and similarly the theta notation. And big O notation usually represented as, big O is represented as order of n. Okay, if n is a linear. So in our previous sessions we have seen different types of time complexities, right? So in that we have seen the constant time complexity, linear, logarithmic, okay, quadratic, etc. So if we are representing with a big O notation, so in our previous session everything we have represented with the order, right? So order of n, that means worst case time complexity. Okay, so it will be represented as big O, order of n. So this will be the worst case time complexity. Similarly, omega notation is represented as like this, omega of n. This is best case time complexity, because why we are calling it as a best case means the minimum time the algorithm requires to complete its execution. So that's what we require. So that will be the best case time complexity. So the best case time complexity will be represented with omega notation. So observe, if you are watching it as a big O of n, that will be the worst case. Okay, we are always calculating the worst case complexity, right? The maximum the algorithm can take. And omega, if you observe this symbol, omega of n, that will be the best case time complexity. And similarly theta, it is represented as theta of n, which is an average case time complexity. Average case. So for every algorithm we can have these three different cases. So best case time complexity, worst case time complexity, and the average case time complexity. Okay, so the representation will be different, three different symbols. And here we are taking the n. N means nothing but our linear time complexity. Okay, for example, consider searching. Okay, consider searching. So if we are having some 5 elements. Okay, so if the search key is 50, right? So how many iterations we have to done? How many comparisons we have to done? So the number of comparisons we have to done is total 5 comparisons. In the 5th comparison we get the success, right? So that will be the worst case. That means maximum time. So if the search key is 60, then also the search key should be compared each and every element until it goes to the end. So that implies this will be the worst case time complexity. And if the search key is 10, what happens? So in the first iteration itself we'll get the success. So the algorithm will be completed in the first case itself. So that will be the best case. So it requires only one iteration minimum, right? And when the search key will be 10, okay, that is the first element. And if the search key is 30, what happens? So it will iterate till the third position. That means the average. So first, last, and middle. So it have to iterate till the third element. So that means this will be the average case. So how much time the algorithm takes to complete its execution is called as a performance analysis or performance of algorithm, and that should be calculated with the help of these three notations, big O, omega, and theta. So mainly this is used for calculating the growth rate, representing the growth rate of algorithm. Okay, so hope you understood this asymptotic notations. So big O, omega, and theta. So growth rate is a rate at which the time complexity of the algorithm will be changing or increasing based upon the increase of input size. So it is a rate at which execution time of an algorithm increases on increase of input. And usually this complexity will be denoted with the help of asymptotic notations. So we have seen the asymptotic notations in our previous session. So I'll post the link in the description so you can go through that one. So the complexity is a time complexity, is represented using asymptotic notations. Asymptotic notations. So we know that asymptotic notations. So big O, big omega, and big theta, so which we call it as a worst case. Next, this is a best case scenario, and this one is an average case scenario. Now we have to see the order of growth rate. So also we have seen different types of functions, right? So different types of functions: the constant, logarithmic, okay, linear, quadratic, n log n, exponential, factorial. So like that, we will be having a lot of functions, and we have to know the growth rate from smallest to the largest. That means which one will be the best and which one will be the worst. So based upon the execution time with increase of input. So that we call it as a growth rate. And in order to calculate the time complexity, we have to know the growth rate order. So if you know the order of growth rate, it will be simple while calculating the time complexity of any algorithm or any pseudocode. Now we'll see the order of growth rate from smallest to largest. From smallest to largest. And always the time complexity will be represented using big O notation. That means a worst case notation, worst case scenario, right? So the order of growth rate of different functions, So from smallest to largest, I'll write here smallest to largest. So the first one will be the constant. Okay, so order big O of 1. Big O of 1, it is a constant. And the next category, that means at the next level, we will be having a one more which is a log n, which is a logarithmic. And the next one is order of n, which is a linear. Next, which is a n log n. That's nothing but we can call it as a linear arithmetic. And then order of n square. N square is nothing but a quadratic. Next, order of n cube, which is a cubic. Next, order of 2 power n, which is an exponential. Right? So example for this one is arithmetic operations. Okay, addition, subtraction, multiplication. And coming to log n, it's a binary search. Where the search space will be reduced every time. And this is a linear search. That means searching the element in a sorted order, searching the element in unsorted order. And n log n, we can say is a merge sort with divide and conquer. And quadratic, we can say it's a bubble sort, where we are comparing two consecutive elements. And n cube, so matrix multiplication. So where we are using some three different for loops, okay, 3 for loops, right? So this is a Towers of Hanoi, right? So Towers of Hanoi problem. So Towers of Hanoi problem comes with this exponential. Okay, so these are the functions, the names of the functions, and the example for these particular notations, right? And this is from smallest to largest. Okay, so the time taken for the constant will be less when compared to exponential, and exponential will be having more number of steps required to complete its execution when compared to the constant. So this will be from smallest to largest, and we can also call it as a best case to worst case. So already we have represented with an asymptotic notation order, that means a big O notation. That's a worst case scenario, right? So but here this will be the order, smallest to largest. And this table will be more important and will be more useful when you are trying to calculate the time complexity of any algorithm. Okay, so that's why I'm writing the complete overview of it, all the functions, growth rate, order of growth rate. Right? So hope you understood. In our further sessions, we'll see how to calculate the time complexities from simple code to complex code. How to calculate the time complexity of any algorithm or any pseudocode. So before going to calculate the time complexity, we'll see what are the steps we need to remember before calculating the time complexity. So the first step, we need to identify the number of blocks in algorithm or a pseudocode. So identify number of blocks in algorithm or pseudocode, right? Or in a program also. So here the number of blocks means declaration can be considered as a one block. Initialization statements may also be considered as one block. Similarly, iterations, the complete iterations. If it is a nested loops, then the complete nested loop should be considered as a one block. And similarly, conditional statements. So if the conditional statements used in the algorithm is if else, so both we have to consider as a single block. Okay, so first we have to identify the number of blocks, and for these two always the time complexity will be the constant. Okay, so time complexity will be constant. So constant means big O of 1. We can say constant as big O of 1. And for iterations and conditions, so here if it is a nested iterations, we have to use a multiplication for nested loops. Either it may be a for loop or a while loop. So if it is nested, then we have to use a multiplication. So we have to find out the time complexity for each and every loop and we have to multiply. Okay, so first we have to calculate the time complexity of the inner loop and the time complexity of the outer loop, and both we have to get multiplied. And if it is a conditional, then we have to choose either, because the conditional means only one block will be get executed, either if block or else block. So we have to consider only one case, either if case or else case. So we can write here, so maximum of if or else. So this is the time complexity of if block and time complexity of else block. So we have to consider only one thing. And if it is a nested if else, so calculate the time complexity of each and every block and find out the maximum among all those conditions. Right? So if our code is having some 2 conditions or 3 conditions, we have to calculate the time complexity of the 3 conditions and find out the maximum. So we have seen the growth rates from smallest to largest in our previous session. So select the maximum time complexity among this one if it is a conditional. So then what you have to do, avoid the constants. So you can avoid all the constants. For example, if time complexity is 2n, you can avoid 2. If the time complexity is n by 2, avoid 2. Okay, if the time complexity is n plus 1, avoid 1. So like this you can avoid all the constants in our time complexities. Okay, and simply add time complexity of all blocks. Time complexity of all the blocks we have to add. For example, so add the time complexity of declaration, add the time complexity of initialization, add the time complexity of iterations if it is having, and add the time complexity of conditional statement if it is having, right? So add each and every block, the time complexity of all the blocks. And finally, the time complexity will be the highest order in equation. So if we apply all the addition of all the time complexity of all the blocks, the highest order will be the time complexity, final time complexity. Okay, so these are the points we have to remember before calculating the time complexity. So if you understand this one, and it will be very easy to calculate the time complexity for any type of algorithm and any type of code. And here one thing is we have to remember, so coming to the iterations, there might be a dependency or there might be an independent. So there you have to carefully find out the time complexities, right? So in the iterations we'll be having the 2 categories, dependent, independent, right? So if they are independent, this process is final, right? So multiplication of nested loops. And if it is dependent, we have to trace out and we have to calculate the time complexity, right? So whatever the process we have we have explained here, the multiplication will be suitable if the iterations are independent, right? So hope you understood the rules or the points we have to remember, so before calculating the time complexity. Now we'll see small examples. So how we can calculate the time complexity, right? So simple codes. I write the simple codes and I tell you the time complexity in this video. In our further video, we'll go with the small complex, right? So example 1, let us take for I is equal to 0, I less than or equal to n, and I plus plus. So let it be any statement is here. Now just check. So this is the block of statements need to be get executed. How many times it is going to be executed? So how many times it will be executed? So until I value starts with 0 and until I becomes less than or equal to n, that means I greater than n. Until I greater than n, this block will be get executed. For example, n plus 1 times. Okay, so n times it will be executed. If it is n plus 1, then it will be false and it will not be get executed. So it will be n plus 1 times. Right, n plus 1 times. And what we have seen, so we have to avoid the constants. So avoid these constants. So the time complexity of this particular code will be order of n, big O of n. So always the time complexity will be represented using the worst case scenario, that means order of n, which gives the upper bound. So in the competitive questions, if you get this type of problems, so if you found any other time complexity like n square or order of n log n, right, order of n cube, right, so everything will be correct for this particular thing. So because this is the worst case and it gives the upper bound of the time complexity, that means so n and greater than this order of n can be correct for this particular code. Okay, so this is the time complexity of this one, order of n. So let us take one more example. So for I is equal to 0, I less than or equal to n, and I is equal to I into 2. So what happens here? How many times it will be executed? So now we have to trace. So when I is equal to 0, right, 0 less than or equal to n, if it is true, consider if it is true, I value will become, sorry, let us take 1. So I value become 2 less than or equal to n. If still it is true, I is equal to 3 less than or, sorry, I becomes 2 into 2, 4, right? So 4 less than or equal to n. Now I becomes 8 less than or equal to n. I becomes 16 less than or equal to n. So like so on. So whenever I becomes k, then k, sorry, you can see that, see 2, this can be written as 2, this can be written as 2 power 2, this can be written as 2 power 3, this can be written as 2 power 4, and so on. So we can get it, we can write it as 2 power k less than or equal to n. So this many times it will be repeated. So now what? So avoid this less than. So we can write it as 2k is equal to n. Now what is the k value? If you have this one, simply this is a formula logarithmic log n base 2. So the time complexity of this particular code will be log n base 2. So the time complexity is equal to, we can simply write it as order of log n. So always it will be base 2. Okay, you need not worry about that. Always it will be base 2. So log n base 2. So if it is 3, what happens? So I becomes 3 here, and here it becomes 9. Here it will becomes 27, and here it will becomes some 81. So here it will be 3 square, 3 cube, 3 power 4, and it will be 3 power k, and it will be log n base 3, and it will be base 3. Right? So like this we have to trace and we have to calculate the time complexity. So we'll see one more. So this is an order of n which we call it as a linear, and this is a log n which is called as a logarithmic. Now we'll check one more. For I is equal to 0, I less than or equal to n. Excuse me. Again, for j is equal to 0, j less than or equal to n, j plus plus. And see, this is the code. Let us see. So we know that this is a nested loop. So not only with the for loop, we can also go with the while loop also. The same procedure. So coming with the inner loop. So how many times this inner loop will be executed? So from 0 to n. So is there any dependency? There is no dependency because j will iterate from 0 to n, I will iterate from 0 to n. For example, if in between, n is replaced with I, okay, in the place of n if it is I, then it will be the dependency. So j should be depends on I, how much the I value, right? So that we'll see in our further sessions. So now we'll see only the simple things. So this is a independent, no, there is no dependency. So j will be iterating from 0 to n and I will be iterating from 0 to n. So there is no dependency. Now, so how many times if this inner loop will be executed? So n times. Then how many times the outer loop will be executed? Obviously n times. So in our first minutes we have discussed that if it is a nested loop and there is no dependency, we have to multiply the time complexity of each and every loop. So here we have to multiply. So time complexity will be order of n into n. We can call it as a n square. That's a quadratic. Such type of complexities. Right? So there is no dependency. And see, if the same thing happens with another for loop, for k is equal to 0, some k less than or equal to n, k plus plus, and see, for example, it is like this, the code is like this. Okay, so what happens? There is no dependency, 3 are independent, 3 loops are independent. So again calculate here, which is n times. So obviously the time complexity will be order of n into n, which is order of n cube, a cubic complexity, cubic function. Okay, and see, hope you understood this one. So if there is no dependency, simply we can multiply all the time complexity of each and every loop. And now consider this one and consider it is m and it is n, then we can say the order will be m into n. The time complexity will be order of m into n. So simply we have to multiply the time complexities of each and every loop. Yes. Now see, so we'll see write down some condition. If some I or any condition, write down any condition, no problem with the condition, any condition, and inside we are writing some loop for I is equal to 0, I less than or equal to n, I plus plus. There's a code, and here again else part, again here I am writing for j is equal to 0, j less than or equal to n, j is equal to j into 2. Right. So what happened here? So this is a condition. So if it is a conditional statement, what we have done? So we have to find out the time complexity of each and every case. That means if block and else block, and we have to consider the maximum order. So what is the time complexity of this one? So only one loop is there. So this loop will be terminated till n. I value greater than n. That means n steps. So n times. What about the time complexity of this one? J is equal to 0, j less than or equal to n, j is equal to j into 2. So just now we have seen a similar example which gives the logarithmic, right? So there is a log n times. So what we have to consider? So this is not an iterative, so we should not multiply these two things, right? So this is a conditional statements. So we have to consider a maximum order. So among these two, which one is the maximum, n or log n? So obviously we have to refer the growth rate from smallest to largest. So in that growth rate you can see n will be the largest among these two. So we have to consider this one, right? So now the time complexity of this type of problems, so which gives the time complexity order of n. It's a maximum of n and log n. So which gives this one order of n, right? So this is an iterative. One more example. We will see one more example. Hope you have understood, right? So I'm saying about all the different cases, right? So then you can practice on your own. See, for I is equal to 0, I less than or equal to n, I plus plus, and inside the for loop again I'm writing for j is equal to 0, j less than or equal to n, j is equal to j into 2. So this is the code, right? So what happens? So both are independent, no dependency, right? Both are independent. So the time complexity of this loop will be log n. Just now we have seen, right? Log n. And the time complexity of this one will be n times. So here there is no dependency. Here these are not the conditional statements. So what we have to do? We have to multiply the time complexity of each and every loop. So the time complexity of such case, what is the time complexity? We get n log n, or of big O of n log n, big O of n log n. So this will be the time complexity. Okay. See, last example. I'll close. So let's take void main int. Let us take some I is equal to 0, for I is equal to 0, I less than or equal to n, I plus plus, and I write here printf welcome. Right, close. So this is a code I'm having. Now how to find the time complexity? See, this is a declaration. This will be the one block, and this is another block. So you can consider it as a block 1, block 2, and this completely comes under block 3. Okay, so this will be executed only one time. So one time, and this will be executed only one time. And this one, how many times it will be get executed? N plus 1 times, because if I becomes n plus 1, then only the loop will be terminated. So n plus 1 will also be executed. So it will be n plus 1 times. So what we have to do? So we have to add the time complexities of all the blocks. So we have to add the time complexities of 1 plus 1 plus n plus 1. So how much we get? N plus 3. And then we have to avoid the constants, right? So avoid these constants. So the time complexity will be order of n. So like this, we have to calculate the time complexity, right? So first we have to identify the number of blocks, and then we have to find out the time complexity for each and every block, and next we have to add the time complexities of all the blocks, and we get some equation, avoid the constants in the equation, and consider the highest degree among all the terms in the equation, so that will be the worst case type complexity. So usually we represent it as big O of n, right? So hope you understood this one. So in this session I have explained you about the complete basic problems. So in our next session we'll move on with a little bit complexity, right? The code with a little bit complexity. So we'll see some problems, and then you'll be getting a complete idea about how to calculate the time complexity, and you have to keep on tracing the problems, and you have to solve the problems. Then you'll be strong in finding the time complexity of any kind of algorithm or a problem. So in our previous session we have seen a few examples, so how to calculate the time complexity, and today also we'll see a few examples. And before going to the examples, let us recall the procedure. So first of all, we have to consider an algorithm or a pseudocode and find out all the blocks, how many blocks, the number of blocks available in that particular code. And once you find out the blocks and find out the time complexity for each and every block, and then add time complexity of every block, and then you will be getting one equation, and from that equation you have to consider only the highest degree based upon the growth rate. Right? So by following the same procedure, we have seen a few examples in our previous session, and today we're going to see a few more examples. Yes. See, so the session will be again on time complexities. Time complexity. So let us take one code for I is equal to 1, I less than or equal to n, I plus plus. For j is equal to 1, j less than or equal to I, j plus plus. And let it be any sort of statements here. So you can see here there is a dependency. Okay, so how many times this will be repeated? How many times this will be repeated? So forget about this one, outer loop. How many times the outer loop is repeated? Obviously it will be repeated for n times. Obviously it will be repeated for n times, right? Because I is equal to 1 and 1 to n. Yes. Coming to the inner loop, how many times it will be repeated? So that depends upon I value. So in such case, we have to trace for a few iterations so that we can get an idea how many times it will be iterated. Now let us trace the problem. So when I is equal to 1, how many times j will be repeated? So j is equal to 1, so j will be repeated with, I write here. So j will be repeated one time. When I is equal to 2, that means second iteration, I is equal to 2, j will be repeated, you can see, j less than or equal to 2, that means 1 and 2, 2 times. When I is equal to 3, then j will be repeated, so 3, 1, 2 and 3 times. Okay, so you can say here how many times it will be repeated, 1 time plus 2 times plus 3 times plus and so on. Okay, how many times? 1 plus 1 time, 2 time, 3 time, 4 time. You can observe 1, 2, 3, and again if you trace the for I is equal to 4, j will be repeated for 4 times. So this is nothing but our sum of n natural numbers. 1 plus 2 plus 3 plus and so on. So obviously this will be repeated with n into n plus 1 divided by 2 times. So that will be n square plus n divided by 2. So obviously what happens? This will be removed, the highest order will be n square. So like this we have to trace the problem if there is any dependency. If there is no dependency, obviously we can directly go with it. If there is a dependency, we have to trace it and we have to find out how many times the loop will be iterated. So you can observe here. So we'll go with a few more examples. Now let us take with one more example. See, I is equal to 1, I less than or equal to n by 2, I plus plus. For j is equal to 1, j less than or equal to n by 4, j plus plus. So if you consider this type of code, so this how many times it will be repeated? Obviously there is no dependency. So I iterating from 1 to n by 2, j is iterating from 1 to n by 4. So there is no dependency. So if there is no dependency, we can simply multiply both the things. So this will be n by 2 times and this will be n by 4 times. And what we have to do, we have to multiply. So order of n by 2 into n by 4. So that will be the order of this particular problem. Okay. So hope you understood. If there is a dependency, so we should not multiply, but we have to trace the problem. We have to find out few iterations, and we can find the number of number of times the loop will be iterating, right? So just like in our previous example. So here there is no dependency. So obviously we can find out the time complexity of each and every loop, and we can multiply. So in our previous example, we are not multiplying that one, right? So because there is a dependency, so we should not multiply. Okay. So hope you understood. So if coming to the loops, nested loops, there are two things. One is dependency and no dependency. So if there is a dependency, trace and find. And there is no dependency, multiply time complexity of each block or each loop. Okay, right? So here there is no dependency, we are just multiplying. So we'll see a few more examples with similar. So here I have taken two examples. So we'll see the time complexity for these two examples. So in the for loop, we have taken the two initializations here, one condition and two updations, right? So let us trace and find out. So here in this case, okay, so when I is equal to n, then j will be 0 and condition n greater than 0 and updation will be the next. Okay, here I write j is equal to 0 and j will become 1. J becomes 1 and I becomes n by 2. So n by 2 greater than 0. So observe. Next I value will become n by 4. So n by 4 greater than 0. Next I value n by 8. Okay, n by 8 greater than 0. So for every iteration n will be reducing to half. N will be reducing to half. So what we can say, n by 2 power k greater than or equal to 0. Okay, greater than or equal to 0. So this we can simply write it as n is equal to 2 power k, okay, which we can call it as k is equal to log n base 2. So already we have discussed it, the same situation we got it, right? So the time complexity of this one will be, time complexity will be order of log n base 2. Okay, so like that we can trace it and we can find out the number of iterations that happens here. Okay, hope you understood this one. So n and every time, so the comparison is on I greater than 0. Okay, so I value is keep on reducing to half. So by studying about the time complexity, different time complexities, we have studied the log n. That means if the search space or the space is reduced gradually to half for every iteration, that will be the logarithm n. So that will be the log n base 2, the order of log n. Right? And coming to this example, let us take the same thing. Let us follow the same thing. So here I is equal to 0 and j is equal to n. And see, n greater than 0. N greater than 0, true. Again, I becomes half. So I by 2. J becomes 1. So j becomes n plus 1. So n plus 1 greater than 0. And I becomes I by 4. And you can eliminate I because we are comparing the condition. We have to, so when the loop will be terminated, that depends upon the condition. So we have to consider the condition. So here the condition, the variable is j. So focus on the j. And in the above example, you can see the condition, the variable will be on I. Right? So we have to focus on I. So you need not bother about j, whether it is incremented or decremented. So because whenever the I value becomes greater than 0, then only it will be iterating. Whenever the I value becomes less than 0, immediately it will be terminated. And I value will be decrementing with a half for every iteration. So similarly here also, we are taking two variables and one variable is decrementing by half and one variable is incrementing and we are using only one variable in the condition, right? So we have to focus on the condition because based upon the condition only, the loop will be terminated. So in the condition, we are using j. So focus on j, not on I. So j is equal to n plus 1 greater than 0. So n plus 2 greater than 0. J is equal to n plus 2. N plus 3 greater than 0. So j is equal to n plus 3 and so on. So what happens? Always the j value will be keep on incrementing and always the n value will be greater than 0. Right? So the loop will not be terminated. So this will be the infinite loop. Infinite loop. So if it is an infinite loop, the time complexity is undetermined. The time complexity of any infinite loop will be undetermined. So we can't determine, right? So we can't assume or we can't calculate the time complexity because this is an infinite loop. Okay, so simply iterate a few steps and you can easily guess the number of iterations it will apply or it will follow. Okay, so we'll see a few more examples. So let us take one more example, and here also we are having a two for loops, nested loop. So first we have to, so if it is a nested loop as we have discussed just now, so first we have to think about the dependency, whether there is any dependency to iterating the inner loop. So you can see the inner loop j will be varying from 1 to n and outer loop I is varying from 1 to n. So there is no dependency. So we can calculate the time complexity of the inner loop and we can multiply it with the time complexity of the outer loop. So what is the time complexity of the outer loop? So in our previous sessions we can see the similarity, right? So the time complexity is log n. So if anyone missed about the previous session, so that will be available in the description playlist. So you can go through and you can easily understand how we are getting the log n base 2. And in this session itself we have taken this example and this came it as a n by 2. Okay, so that means we can avoid the constant, so n. So the time complexity of this one, the time complexity of this type of algorithm will be order of multiply both one, n log n base 2. So this will be the time complexity. Okay, this is one example. So let us see the last example. See, let us see this example. I is equal to 1, k is equal to 1, and we have initialized two variables. We are checking the condition k less than or equal to n, and we are iterating the two statements here. And see, here the condition depends upon the k value, and k value depends upon the I value. So there is a dependency. Hope you understood. So here the condition is k and n. So k value depends upon I because we are updating the k with I value. right? So I values will be keep on incrementing. Now we have to find out the time complexity. Test here. So when I is equal to 1, then k will also be 1, and so 1 less than or equal to n. Then I becomes 2 and k becomes 3. So 3 less than or equal to n. Again, I is equal to 3. Okay, now k is equal to k plus I. What's the key? 3. I is 3. 6. 6 less than or equal to n. Next, I is equal to 4 and k will be k plus I. K is 6 and I is 4. 10. So 10 less than or equal to n, and so on. So you can trace it. How we are getting this one? So you can see for I is equal to 1. Okay, so 1. I is equal to 2. It is 3. I is equal to 3. It becomes 6. And I is equal to 4. It becomes 10. That implies sum of all the previous numbers. You can see when I is equal to 2, 2 plus 1, 3. I is equal to 3, 3 plus 2 plus 1, 6. You can observe here. So I. So that will be only 1. And here 2 plus 1. And here 3 plus 2 plus 1. And here 4 plus 3 plus 2 plus 1. You can observe. So 4, 3, 2, 1. So I values will be keep on adding. So that means sum of n natural numbers. So this can be written as I into I plus 1 divided by 2 less than or equal to n. Okay. So you can simply write it because this is nothing but sum of n natural numbers. So avoid the constants. So you can avoid the constants. So it becomes I square plus I less than or equal to n. I square plus I less than or equal to n. So simply you can consider the highest grade. So I square is equal to n and I becomes root n. So that implies the complexity of this one, the time complexity of this particular code will be order of root n, right? So like this we have to trace and we have to find out how we are getting the condition, and from that we can get the time complexity, right? So hope you understood this one. So previous examples, in our previous session we have seen all the simple examples, and in today's session we have gone with a few complex examples. So with this you might be knowing how to calculate the time complexities, and definitely by practicing more problems you will be getting strong with calculating the time complexity of any kind of algorithm or any kind of pseudocode. So in our previous session we have seen a few examples, so how to calculate the time complexity, and today also we'll see a few examples. And before going to the examples, let us recall the procedure. So first of all we have to consider an algorithm or a pseudocode and find out all the blocks, how many blocks, the number of blocks available in that particular code. And once you find out the blocks and find out the time complexity for each and every block, and then add time complexity of every block, and then you will be getting one equation, and from that equation you have to consider only the highest degree based upon the growth rate. Right? So by following the same procedure, we have seen a few examples in our previous session, and today we're going to see a few more examples. Yes. See. So the session will be again on time complexities. Time complexity. So let us take one code for I is equal to 1, I less than or equal to n, I plus plus. For j is equal to 1, j less than or equal to I, j plus plus. And let it be any sort of statements here. So you can see here there is a dependency. Okay, so how many times this will be repeated? How many times this will be repeated? So forget about this one, outer loop. How many times the outer loop is repeated? Obviously it will be repeated for n times. Obviously it will be repeated for n times, right? Because I is equal to 1 and 1 to n. Yes. Coming to the inner loop, how many times it will be repeated? So that depends upon I value. So in such case we have to trace for a few iterations so that we can get an idea how many times it will be iterated. Now let us trace the problem. So when I is equal to 1, how many times j will be repeated? So j is equal to 1, so j will be repeated with, I write here. So j will be repeated one time. When I is equal to 2, that means second iteration, I is equal to 2, j will be repeated, you can see j less than or equal to 2, that means 1 and 2, 2 times. When I is equal to 3, then j will be repeated, so 3, 1, 2 and 3 times. Okay, so you can say here how many times it will be repeated, 1 time plus 2 times plus 3 times plus and so on. Okay, how many times? 1 plus 1 time, 2 times, 3 times, 4 times. You can observe 1, 2, 3, and again if you trace the for I is equal to 4, j will be repeated for 4 times. So this is nothing but our sum of n natural numbers. 1 plus 2 plus 3 plus and so on. So obviously this will be repeated with n into n plus 1 divided by 2 times. So that will be n square plus n divided by 2. So obviously what happens? This will be removed, the highest order will be n square. So like this we have to trace the problem if there is any dependency. If there is no dependency, obviously we can directly go with it. If there is a dependency, we have to trace it and we have to find out how many times the loop will be iterated. So you can observe here. So we'll go with a few more examples. Now, let us check with one more example. See, I is equal to 1, I less than or equal to n by 2, I plus plus. For j is equal to 1, j less than or equal to n by 4, j plus plus. So if you consider this type of code, so this how many times it will be repeated? Obviously there is no dependency. So I iterating from 1 to n by 2, j is iterating from 1 to n by 4. So there is no dependency. So if there is no dependency, we can simply multiply both the things. So this will be n by 2 times and this will be n by 4 times. And what we have to do, we have to multiply. So order of n by 2 into n by 4. So that will be the order of this particular problem. Okay. So hope you understood. If there is a dependency, so we should not multiply, but we have to trace the problem. We have to find out few iterations, and we can find the number of number of times the loop will be iterating, right? So just like in our previous example. So here there is no dependency. So obviously we can find out the time complexity of each and every loop, and we can multiply. So in our previous example, we are not multiplying that one, right? So because there is a dependency, so we should not multiply. Okay. So hope you understood. So if coming to the loops, nested loops, there are two things. One is dependency and no dependency. So if there is a dependency, trace and find. And if there is no dependency, multiply time complexity of each block or each loop. Okay, right? So here there is no dependency, we are just multiplying. So we'll see a few more examples with similar. So here I have taken two examples. So we'll see the time complexity for these two examples. So in the for loop, we have taken the two initializations here, one condition and two updations, right? So let us trace and find out. So here in this case, okay, so when I is equal to n, then j will be 0 and condition n greater than 0 and the updation will be the next. Okay, here I write j is equal to 0 and j will become 1. J becomes 1 and I becomes n by 2. So n by 2 greater than 0. So observe. Next I value will become n by 4. So n by 4 greater than 0. Next I value n by 8. Okay, n by 8 greater than 0. So for every iteration, n will be reducing to half. N will be reducing to half. So what we can say, n by 2 power k greater than or equal to 0. Okay, greater than or equal to 0. So this we can simply write it as n is equal to 2 power k. Okay, which we can call it as k is equal to log n base 2. So already we have discussed it, the same situation we got it, right? So the time complexity of this one will be, time complexity will be order of log n base 2. Okay, so like that we can trace it and we can find out the number of iterations that happens here. Okay, hope you understood this one. So n and every time, so the comparison is on I greater than 0. Okay, so I value is keep on reducing to half. So by studying about the time complexity, different time complexities, we have studied the log n. That means if the search space or the space is reduced gradually to half for every iteration, that will be the logarithm mean. So that will be the log n base 2, the order of log n. Right? And coming to this example, let us take the same thing. Let us follow the same thing. So here I is equal to 0 and j is equal to n. And see, n greater than 0. N greater than 0, true. Again, I becomes half. So I by 2. J becomes 1, so j becomes n plus 1, so n plus 1 greater than 0, and I becomes I by 4, and you can eliminate I because we are comparing the condition. We have to, so when the loop will be terminated, that depends upon the condition, so we have to consider the condition. So here the condition, the variable is j, so focus on the j, and in the above example you can see the condition, the variable will be on I, right? So we have to focus on I, so you need not bother about j, whether it is incremented or decremented. So because whenever the I value becomes greater than 0, then only it will be iterating. Whenever the I value becomes less than 0, immediately it will be terminated, and I value will be decrementing with a half for every iteration. So similarly here also, we are taking two variables, and one variable is decrementing by half, and one variable is incrementing, and we are using only one variable in the condition, right? So we have to focus on the condition because based upon the condition only, the loop will be terminated. So in the condition, we are using j. So focus on j, not on I. So j is equal to n plus 1, n plus 1 greater than 0. So n plus 2 greater than 0, j is equal to n plus 2, n plus 3 greater than 0. So j is equal to n plus 3 and so on. So what happens? Always the j value will be keep on incrementing, and always the n value will be greater than 0, right? So the loop will not be terminated. So this will be the infinite loop. Infinite loop. So if it is an infinite loop, the time complexity is undetermined. The time complexity of any infinite loop will be undetermined. So we can't determine, right? So we can't assume, or we can't calculate the time complexity because this is an infinite loop. Okay, so simply iterate a few steps and you can easily guess the number of iterations it will apply or it will follow. Okay, so we'll see a few more examples. So let us take one more example, and here also we are having a two for loops, nested loop. So first we have to, so if it is a nested loop as we have discussed it just now, so first we have to think about the dependency, whether there is any dependency to iterating the inner loop. So you can see the inner loop j will be varying from 1 to n, and outer loop I is varying from 1 to n. So there is no dependency. So we can calculate the time complexity of the inner loop and we can multiply it with the time complexity of the outer loop. So what is the time complexity of the outer loop? So in our previous sessions we can see the similarity, right? So the time complexity is log n. So if anyone missed about the previous session, so that will be available in the description playlist, so you can go through and you can easily understand how we are getting the log n base 2. And in this session itself we have taken this example, and this came it as a n by 2. Okay, so that means we can avoid the constant, so n. So the time complexity of this one, the time complexity of this type of algorithm will be order of multiply both one, n log n base 2. So this will be the time complexity. Okay, this is one example. So let us see the last example. See, let us see this example. I is equal to 1, k is equal to 1, and we have initialized two variables. We are checking the condition k less than or equal to n, and we are iterating the two statements here. And see, here the condition depends upon the k value, and k value depends upon the I value. So there is a dependency. Hope you understood. So here the condition is k and n. So k value depends upon I because we are updating the k with I value, right? So I values will be keep on incrementing. Now we have to find out the time complexity. Test here. So when I is equal to 1, then k will also be 1, and so 1 less than or equal to n. Then I becomes 2 and k becomes 3. So 3 less than or equal to n. Again, I is equal to 3. Okay, now k is equal to k plus I. What is the key? 3. I is 3. 6. 6 less than or equal to n. Next, I is equal to 4 and k will be k plus I. K is 6 and I is 4. 10. So 10 less than or equal to n, and so on. So you can trace it, how we are getting this one. So you can see for I is equal to 1, okay, so 1, I is equal to 2, it is 3, I is equal to 3, it becomes 6, and I is equal to 4, it becomes 10. That implies sum of all the previous numbers. You can see when I is equal to 2, 2 plus 1, 3, I is equal to 3, 3 plus 2 plus 1, 6. You can observe here. So I, so that will be only 1, and here 2 plus 1, and here 3 plus 2 plus 1, and here 4 plus 3 plus 2 plus 1. You can observe. So 4, 3, 2, 1. So I values will be keep on adding. So that means sum of n natural numbers. So this can be written as I into I plus 1 divided by 2 less than or equal to n. Okay, so you can simply write it because this is nothing but sum of n natural numbers. So avoid the constants. So you can avoid the constants. So it becomes I square plus I less than or equal to n. I square plus I less than or equal to n. So simply you can consider the highest grade. So I square is equal to n, and I becomes root n. So that implies the complexity of this one, the time complexity of this particular code will be order of root n, right? So like this we have to trace and we have to find out how we are getting the condition, and from that we can get the time complexity, right? So hope you understood this one. So previous examples, in our previous session we have seen all the simple examples, and in today's session we have gone with a few complex examples. So with this you might be knowing how to calculate the time complexities, and definitely by practicing more problems you will be getting strong with calculating the time complexity of any kind of algorithm or any kind of pseudocode. So in our previous sessions we have seen how to find out the time complexity of any kind of algorithm, as well as the asymptotic notations, that is a big O, big theta and big omega notations, which will give the worst case, best case and the average case complexities. And coming to this amortized analysis, this is mainly used to analyze the average performance of the algorithm for a set of operations. Okay, so it is basically to find out the average time complexity. Okay, so that is also for a set of operations. So I write here, it is used to analyze average performance of an algorithm. This is most important next. For a set of operations. So that means it will calculate the average cost for all the set of operations. So calculates average cost of all operations. So for example, if an algorithm consists of some 10 instructions, okay, or 10 operations, if some operations gives the worst case and some operations gives the best case, and we need to average the cost of all the operations, so that will give the amortized analysis. For example, okay, so let us take a person who runs a family, and if he needs an amount, the monthly expenses, what is the monthly expenses and how much amount he requires to run a family. Okay, so for example, in January, the monthly expenses, so I write here monthly expenses. So the monthly expenses are some 10,000 rupees, and in the month of February, let it be some 8,000 rupees. In the month of March, let it be some 6,000 rupees. So according to these statements, okay, according to this content, how much a family, a man can run a family with the amount, right? So obviously we'll say it will be 10,000. That will be the worst case. That will be the worst case. So here the amortized analysis means averaging the cost of each and every operation. So you can average all these things. So what is the average of all these things? So 10,000 plus 8,000 plus 6,000 divided by 3, because we are calculating for the 3 months. So it will be, so 10, 18, 24. So 24,000 by 3, which is nothing but 8,000. So a man can have an 8,000 rupees to run a family on an average of 8,000. So in the January, he might be having a few expenses, more expenses. In the month of March, there will be a little bit of expenses, right? So this average is 8,000, which is less than the worst case. So this type of thing, we call it as amortized analysis. So the same thing we have to do for algorithm. Okay, so based upon the operation, we should not consider the highest complexity. So we need to calculate the average cost of all the operations so that we can get the amortized time complexity or amortized analysis. Right? Now we'll take an actual example. We'll consider one data structure array and we'll see what is the complexity, worst case complexity to insert an element into a dynamic array. And the same thing we'll apply the amortized analysis and we'll compare the time complexities of both. Right? Yes. So let us see that now. So let us take an example as an array. See the worst case time complexity. So complexity of element insertion into an array. Obviously, it will be some order of n, right? So one element. If the same thing applies for multiple elements, so n elements insertion. So the time complexity will be n into some order of n, which will be order of n square, right? So this is the worst case time complexity for inserting n elements into an array. So this is the order of n square. I write here order of n square, right? So this is the worst case time complexity. Now calculating this amortized analysis. Okay, so that means we have to trace each and every operation and we have to find out the cost and then we have to average all the different costs. See what happens. So if I write here insertion, element insertion, and here I write the size of array, and here I write it as a cost. Okay, cost. So one thing we have to remember, the element can be easily inserted into an array, and if the array is full, what we have to do, we have to double the array and we have to copy all the elements into the array and then we have to insert it. So the complexity or the cost will be 1 if array is not full or overflow, we can simply say, right? So if it is full, what we have to do? So size should be double. Okay, size should be double plus copy all elements, because all the elements should be occupied in continuous memory locations, plus element insertion. So three things will be happen if the array is full. That means we have to increase the size of an array. So with the help of different functions, we know that in C we are having some dynamic memory allocations, so we can increase the memory, and in Java we can use a new keyword to increase the size. So like that, whatever it may be, so we have to double the size of the array. And next step, we have to copy all the elements because every element should be in the continuous memory location, and then only we have to insert the element. So this happens. See, I'll write here. Don't get confused. And it will be 1 if array is not full. This should be happens if array is full. That is overflow. If array is full, size should be doubled. That is the first one. Copy all the elements. That is the second one. Elements insertion will be the next one. Now, so what happens if you are inserting one element and if the array size is 1? Okay, so if the array size is 1, so simply we can insert and the cost will be 1. And if you want to insert 2, the array size is 1, there is no empty, the array is full. Now it should be double. Double means 2. So here it is 1 and here it is 2. So then insertion of copy the element. First we need to copy the element. So 1 plus how many elements? So sorry, the first thing is double the size. So now the size of array 2. Next, copy all the elements. One element will be copied and element of insertion 1. So the cost will be this one. And coming to the third, insertion of the third one. So there is a blank. Okay, so the array is not full because, sorry. Yes, so array is full. So array is full means third element can't be inserted into the size of array 2. So then that should be increased. So 1, 2, and size should be increased. Size should be double. So 2, now it should be 4. Copy all the elements. How many elements? 2 elements. 2 elements should be copied plus element to be inserted 1. So here it is. Coming to the 4, element 4. So here the array is not full. So obviously we can simply insert the element. So 1, 2, 3, 4. So the cost is 1. Insertion of element. If array is not full, the cost is 1. Okay. And then fifth element. So there is no free space. So the array is completely full. What we have to do? Size should be doubled. So now the size of array will be 8. Right. So size should be doubled. So it will be 8 plus copy all the elements. How many elements? 4 elements. 4 elements will be copied. 1, 2, 3, 4. And 1 element should be inserted. 1. So 5. Okay. And then for 6, 7 and 8, you can observe the array is not full. So obviously 6, 7 and 8, the cost will be 1, 1, 1. Right? Because full. And if it is again 9th element, the cost will be how much? So the array is full. So it will be 16. First size should be double. 16 plus copy all the elements. 8 elements should be copied and plus 1. So if you want to insert the 9 elements, so that will be the cost. So like this, we have to analyze each and every step. And what we have to do next? We have to average the cost of all the operations. So this will be the first operation, second operation, third, 4, 5, 6, 7. Okay, so different operations, all are the different operations. So we have to apply the same thing for n elements, and we have to take the average because of this amortized analysis. This is the average performance of an algorithm. Now, let us consider. So we have to find the cost of all the operations, and this will be keeps on moving, right? So I have to average. So average 1 plus, let us say 2 plus 1 plus 1 plus, you can apply 4 plus 2 plus 1 plus 1 plus 8 plus 4 plus 1 plus 1 plus 1 plus 1 plus 1. So like this and so on. It will be like, it will be keeps on moving and divided by n because we have to average. So these are all the cost of n operations. So you can observe, we can replace this with, okay, we can replace this with, so 1 plus 2 plus 4 plus 8 plus and so on, and similarly plus see 1, 2, 4, 8, again 1, 2, 4 and so on, and again we get 8 here, right? So again 1 plus 2 plus 4 plus 8 plus and so on, plus finally we get all ones, right? And so on, plus we get all ones divided by n. So this also keeps on moving. Okay, so we get only these type of iterations. So we get 1 plus 2 plus 4 plus 8, again 1 plus 2 plus 4 plus 8, again 1 plus 2 plus 4 plus 8, again so on, all ones. We can write like this. So we know the complexity for this particular series. Okay, see, if you want to get like this, simply you can analyze I is equal to 1, I less than or equal to n, I is equal to I into 2. So we have already seen such kind of time complexity, so which will be incremented with a 2 times, so that we call it as a log n base 2. So simply we can replace this with log n base 2, and this is also log n base 2, and this is total n terms. So n times 1 will be added, so n terms. So what we can write here, order of log n base 2 plus order of log n base 2 plus n divided by n. So what happens here? 2 log n base 2. So this becomes 2 log n base 2 plus n divided by 2, divided by n. So you can see we have to consider the highest degree. So among log n and n, which will be having the highest degree? If we are having some function and we are trying to calculate the time complexity, we have to find out the highest degree. So what is the highest degree in this equation? So n, according to the growth rate. So just visit our previous sessions so that you will be understanding how we got this log n and how we are selecting this n, right? So calculating the time complexities and the growth rate. So these two sessions you just go through so that you'll be getting clarity about that one. So I'll share the complete playlist in the description box. Okay, right. So we have to consider this one, and this will becomes order of n divided by n, which is nothing but order of 1. See, order of 1. So the same problem. What's the worst case time complexity is the order of n square. And if you are using this amortized analysis, particularly the aggregate method, so this amortized analysis is also having a different methods, right? So counting method, then aggregate method, potential method, right? So this is an aggregate method. So here we have to calculate the cost of each and every operation, and then we have to perform the average so that we'll get the amortized time complexity, which we call it as an average performance of an algorithm over a set of operations. That's the most important. Okay, so order of n, and this is order of 1. This is amortized time complexity. Amortized time complexity, and this is the worst case time complexity. Worst case time complexity, right? So there you can find the difference. So worst case time complexity of order of n square, and where amortized time complexity will be the order of n, inserting an element into a dynamic array. So this problem is for inserting an element into a dynamic array. So previously we are having some order of n square. So in our previous example we have seen, so if a person needs some monthly expenses to run a family, so how much he requires to run a family on an average, we have find out, we have calculated that average. So the same process we have to do here, and that we call it as an amortized analysis, the average performance of an algorithm over a set of operations. Divide and conquer strategy. Divide and conquer. So in today's session we'll see the introduction, what is about this divided and conquer strategy, and what are the different applications which will follow this strategy, divide and conquer, in order to solve the problem. So in our first sessions we have seen there are different strategies like divide and conquer, dynamic programming, greedy method, etc., in order to solve any problem. So the main goal is to achieve the optimal solution, right, the better solution. So one of the strategies is divide and conquer, and so here there will be three parts: divide, conquer, and combine. So for the first part is a divide part, so where the complete problem can be decomposed into multiple subproblems. So first the problem will be divided into multiple subproblems. So that will be done in this divide part. Okay, so the problem is decomposed to multiple subproblems. The second part is a conquer. So as the name itself indicates, it's a conquer. So conquer means applying some recursive calls or recursive procedure to solve each and every subproblem, right? So the second part, conquer, so providing solution or finding the solution for every subproblem. So finding solution for every subproblem. And there's also a third part which is called a combine. So after finding the solution for all the subproblems, the next part will be the combine. So we have to combine the solutions of all subproblems to get the main solution. So the third part will be combine. Combine. So the name itself indicates, combines means so joining or integrating the solutions of all subproblems. So combining solutions of all subproblems. Right. So these are the three steps involved in this divide and conquer. Usually some materials or some textbooks or some online information will be having as a D and C, right? So it will be represented as a D and C, divide and conquer, right? So, and the applications, what are the different applications that follows this particular divide and conquer? So the main applications which follows this divide and conquer are binary search, so where the complete elements should be in a sorted order, so that we have to find the middle element and we are trying to compare the search element with the middle element, so that we are deciding whether the element, the search element, is available at the left part of the middle element or the right part of the middle element, right? So the search space, in the second iteration the search space will be reduced to half. So in the second iteration we will follow the search space from either first to middle or middle to last. So that approach will follow this divide and conquer. So first we are dividing the problem, and again we are applying the same procedure, and we are, based upon the result, we are proceeding with the further division, or we are combining the solutions. So first one will be the binary search. Next, quick sort. So as we know that sort means arranging the elements in a ascending order or either descending order. Usually the elements will be arranged in a ascending order. So here also we will be having a lot of elements. So usually that will be stored in an array. So we have to consider a pivot element, and based upon the pivot element, all the elements that are less than the pivot should be arranged towards the left side, and all the elements greater than the pivot elements will be arranged towards the right side. Now the complete array is divided into two halves, left half and right half. And again from the left half, again we have to select the pivot element, and again based upon the pivot we are arranging two sub-arrays. And coming to the rightmost array, again we are dividing the rightmost array based upon the pivot, two sub-arrays. So this is again the process which follows the divide and conquer. So dividing the problem and providing the solution, finding the solution, and again combining all the solutions. So quicksort is also an application which follows this divide and conquer methodology. And merge sort. So this is also one sorting technique. So where here also the elements will be arranged in a sorted order. So here first of all we have to divide the complete array into two halves, and further again this left sub array and right sub array will be further divided into again two halves until it reaches to the two elements, right? So then again the process will be from bottom to top. So for every sub problem, for every sub array, we have to arrange the elements, we have to compare the elements, and we have to arrange the elements in a sorted order, and again we have to merge two arrays, and again we have to compare and we have to apply the sorting technique, and again we have to apply the we have to combine both the arrays. So merge sort means, again, first we are going to divide the complete array into sub arrays, and again we are just combining all the merged elements, all the sorted elements. So merge sort is also one application that follows this divide and conquer. So don't worry about it. So one by one we'll solve each and everything. So we'll see how to apply the divide and conquer. And one thing you have to remember, either you are using the binary search or quick sort or a merge sort. So two things are common. So one is formula. So formula means, at what point we have to divide the complete problem into subproblems. So according to which condition we have to divide it. Okay, so that is the formula, because in binary search we are finding the middle element, and based upon the middle element we are comparing the search element, and then we are dividing. Coming to the quick sort, we are finding the pivot element, and based upon the pivot element we are dividing. And coming to the merge sort, this also we are finding the middle element, and we are dividing the complete array into sub-array. So we require some formula to divide the problem into subproblems. And the next one, stop case. So stop case means how far we have to divide the problem into subproblems. So at particular time we have to stop that division. So that is the most important, stop case. Right? So identifying the stop case or base condition is somewhat difficult. So that may be one disadvantage of divide and conquer. And also, not all applications will follow this divide and conquer, and this will be not suitable for all the applications to get the optimal solution. So right, so you can see these are the few applications. So I'll draw the simple diagrammatic representation about these three parts. Right? So you can see first a complete problem. So one advantage is complex problems can be easily solved by using this divide and conquer. So for example, this is a problem. This is a problem. So this is again divided into two subproblems. Right? So subproblem 1 and subproblem 2. This is a complete problem. Right? So based upon the formula and based upon the stop case, again this subproblem can be divided into further. Right? So for example, again this is divided. Subproblem 1, subproblem 2, and again subproblem 1. So this process will be keeps on moving, right? Keeps on moving. So once it was done, now finding the solution, and here also finding the solution, and here also we'll be having solution, and here also we'll be having solution. Now division is completed and conquer is completed, right? So up to here there is a divide part, and up to here this is a conquer part, that means finding the solutions. And after that we have to combine both the solution, right? So this is a combined part. So again here we have to combine both the solutions, and later again we have to combine complete solution, right? So this part is nothing but combine. So three parts: divide, conquer, and combine. Dividing the problem into subproblems, right? So this is the part, and this is the conquer part, and this will be the combine part. Okay, this is completely the combined part. So identifying the problem, subproblem, and applying the same procedure in order to find the solution, finding the solution, and combine the solution. So finally we get the complete solution for this particular problem. Okay, so the same approach will be applied for, we have seen the applications merge sort, quick sort, or Traversals problem, and as well as the binary search. Okay, multiplication methods, finding the minimum and maximum elements. We can also use the same strategy in order to find the maximum and minimum elements. Right? So hope you understood the complete introduction. What is this divide and conquer strategy? So to get the optimal solution. So let's stop here, and in our further sessions we'll see each and every application that follows this divide and conquer and how we can get the optimal solutions. Right? So in this session we'll see one application, that is finding the minimum and maximum element from a given array using this divide and conquer methodology. Right? So usually this is called as a min and max algorithm. So the problem statement is to find the minimum element and a maximum element from the given array. Right? So using this divide and conquer. So absence of this divide and conquer, so how can we find the minimum and maximum value? So for example, array is having some 5 elements, and let us assume these elements are not in a sorted order. Okay, so not in sorted order. So what happens? So in order to find the minimum element, how many comparisons we require? So we have to compare the first element with all the other elements, whether it is a minimum value or a maximum value. If it is a maximum value, we have to swap, right? So finally we require 4 comparisons. 4 comparisons, right? So similarly, in order to find the maximum also, it requires 4 comparisons. 4 comparisons. And if array is having some n elements, so in order to find the minimum value, it requires n minus 1 comparisons and for finding the maximum value also requires some n minus 1 comparisons. So finally, if you want to find minimum and maximum in the same algorithm, it requires n minus 1 plus n minus 1. That implies 2n minus 2 comparisons are required. So if the elements are not in a sorted order, right? If the elements are not in a sorted order, so in order to find this minimum and maximum elements, we require some 2n minus 2 comparisons. So obviously the time complexity will be order of n, because we need to avoid the constants, right? So the time complexity will be order of n itself. But practically, how many comparisons were we required? So 2n minus 1 in the absence of divide and conquer. This is a normal method, right? So remember this one. So 2n minus 2 comparisons. Okay, conventional model, or we can call it as a linear model. Now we'll see how many comparisons we required if we solve the same problem by using a divide and conquer, right? So that means dividing the problem into subproblems and solving each subproblem using recursion, and then combining the solutions of all subproblems. Right? Now let us see one by one. In this session, I'll mainly focus on example. First, we'll see the example how we can find the minimum and maximum element from the unsorted array using divide and conquer, and then we'll see the algorithm. We'll write the algorithm. Okay, how we can based upon the example, and then we'll find the time complexity, right? So obviously the time complexity will be order of n. That's no doubt. But we'll see how many comparisons it requires if we solve with the divide and conquer. Okay, so in linear we are having some 2n minus 2. Now we'll see the comparisons. Right? So we'll see in terms of comparisons, how many comparisons it requires. Right? So I'm going to cover all these three in today's session. Right? Yeah. Let's start with an example. So we'll take a few elements. So random elements, so the elements are not in a sorted order, right? So I'll take some 40, 60, 50, 30, 20, and let us take it 10, right? So there are a few elements. So usually 6 elements, we are considering the 6 elements. Now what we have to do, we have to divide it into subproblems. For division, here we are taking the formula as a middle element, right? So 2 things we have to remember. In our previous session we have discussed about that one. 2 things, that is, which criteria we need to consider to divide the complete problem. And the second one, the stop condition. So at which position we have to stop the recursion. That means we have to stop the division. Right? So the formula is a middle value. We need to find the middle value. Right? So let us consider it as a low, and let us consider it as a high. And let us consider the index values 0, 1, 2, 3, 4, and 5. So this is an array. Okay, this is an array, and these are the index values. And low is initialized to 0, and high is initialized to 5. Right? That means n minus 1 if n is equal to 6. Now find out the middle value. So I'll write here. Middle is equal to, so middle value how we can get? Low plus high divided by 2. So here how much we get? 0 plus 5 divided by 2. How much we get? 5 divided by 2. So we need to consider only integer. So it will be 2. We need to consider only integer. So we need to divide the complete problem into 2 sub arrays. That means complete array into 2 sub arrays. So the first array will be from 0 to 2. That means low to mid, and the second array, what's the second array? Obviously the second array will be from 3 to 5. Usually we call it as a mid plus 1 to high. So based upon the middle value, we are going to divide the complete array into 2 sub arrays. Now consider, so let it be, so 40, 60, 50. So 40, 50, sorry, 60 and 50. And here also the second array consists of 3 elements. So what are the 3 elements? 30, 20, 10. 30, 20, 10. So again, we have to repeat the same process. That means recursion should be done. Recursively, we have to solve each and every problem. So we are having the complete problem, and after first step, we are having 2 subproblems. And now from these 2 subproblems, again each subproblem should be solved by using the same procedure. That means a recursion, right? That we call it as a conquer. So again, here let it be 0, 1, and 2, and here also 0, 1, and 2, and let it be here a low value, and this is a high value, and again here is a low value, and this is a high value. So here mid is equal to low plus high by 2, 0 plus 2 by 2, and here also mid is equal to 0 plus 2 by 2. So how much we get? 2 by 2 is 1, and here also we get 1. So we are applying the same procedure. And based upon this, we are again dividing the same array into different parts. So again, this will be divided from 0 to mid, that means low to mid, and mid plus 1 to high. See. So I am taking low to mid, that means 40 and 60, and mid plus 1 to high. So obviously mid plus 1 and high both are equal. So we are having only one element, 50. And here also the same procedure. So what happens? Again 2 elements, it was divided into 2 elements, 30 and 20, and again the same single element, which is a 10. So complete problem, subproblem, and again subproblem. So we need to stop here, because if the total number of elements are equal to 2, then only one comparison is required. So we can compare 40 and 60 so that we can get the minimum and maximum value, right? So among these two values, we can simply say that with one comparison, we can say which one is the minimum value and which one will be the maximum value. And if the array consists of only one element, so then the minimum and maximum value will be the same. So we need to stop this recursion whenever the division, after division, if the count is equal to 2, okay, we can stop it. So stop procedure. So I write here, stop. When we have to stop? Stop condition. So whenever it becomes 2 power I is equal to 2. Okay, so or simply we can say it as a k. So anything we can represent simply 2 power k. Means here we have divided into n2. Okay, and further we have divided into 2. So that means here we can write it as n by 2, and here we can write it as n by 4, because n by 2 again we are dividing it into 2 halves. Okay, so we have to repeat the same process: n by 2, n by 4, n by 8, n by 16, and this process will be repeated until that equal to 2. Okay, this is a stop condition. Whenever it becomes 2, then we have to stop it. Now we are stopping here, right? Now directly we need to compare these two values. So compare these two values and we can find what is the minimum and what is the maximum. So here you can say minimum is equal to 40, maximum is equal to 60. And here we are having only one element. So the minimum value and maximum value will be the same. So a minimum is equal to 50, maximum is equal to 50. And apply the same process on the second half also. So here also the minimum value will be 20. So we need to compare. Okay, we need to compare whether 30 is greater or 40 is greater. So obviously 20 is greater, right? Only one comparison is required. And a maximum is equal to 30. And here only one element, so minimum is equal to 10 and maximum is equal to 10. Right? So two conditions we have done. If the number of elements are 1, then there is no comparison. So the minimum element and maximum element will be the same element. And the second condition, if the number of elements are 2, it requires one comparison. And based upon that one comparison, we can consider or we can assume what is the minimum value and what is the maximum value. Now we have to, we solved their subproblems. So this subproblem has been solved. So we got minimum value and maximum value. And this subproblem also solved. We got minimum and maximum. This subproblem we got a solution minimum and maximum. This subproblem we got a solution minimum and maximum. Now the third part should be started. So what's the third part? So third part is combining. So I'm combining both the solutions, all the solutions. Okay. So first we have to combine these two solutions. So combining these two solutions, we have to compare this minimum with this minimum. So 40 and 50. So what's the minimum value here? So here minimum value from this one and this one, the minimum value will be 40. And similarly, maximum should also be compared, 60 and 50. Which one will be the maximum? So obviously 60. So after combining these two solutions, we got a solution minimum 40 and maximum 60. And apply the same procedure for these two halves. So minimum 20 and minimum 10. When we compare these two things, the minimum value will be 10. And compare these two things, maximum 30 and maximum 10. So it will be a maximum 30. So after combining these two solutions, we got a solution min is equal to 10 and max is equal to 30. Now we have to compare these two things. Okay, these two things, and this one and this one. So when we compare this one, minimum 40 and minimum 10. So compare the minimum value from both the solutions. Compare the maximum value from both the solutions. So from these two solutions, the minimum value will be 40 and 10, 10, and maximum value will be 60 and 30, 60. So this is the final solution. Final solution. So from the given elements, you can observe which one is the minimum element, that is a 10, and which one is the maximum element, that is 60. So we have applied the divide and conquer method. So we have divided the complete problem into subproblems, and then we have solved each subproblem, and then we have combined the solutions of all subproblems. Right? So this is the procedure and this is the example. I think everyone understood this example. Now based upon this example, we will write the algorithm. Okay, so hope everyone understood this example, right? So we'll write the algorithm for this one. So I don't want to erase all these things because further we'll use the thing, right? See. See, algorithm or pseudocode, whatever it may be, we can write. So I'll give the name it as a min max. The algorithm name is min max. So it will take a few arguments like low, high, min, and max. So I write this one. Now what we have to do? So first we have to check whether the array elements are equal to 1 or 2. So if low is equal to high. So we have to initialize low with a 0 and high with the n minus 1. Okay, if it is having some n elements, we have to initialize high with the n minus 1. So after that, if we get a low is equal to high, that means only one value is there. If the array consists of only one value, then obviously what happens here, we have seen both the min and maximum will be the same. Right? So what we have to do, so the minimum is equal to some array of low or high, anything is common, right? Similarly, maximum is equal to a of high or low, whatever it may be. You can write anything because both are equal, right? Yes. Now the second condition, if it is having two elements, okay, the same thing which happens here in the last step. Okay, so we got one array with two elements, one array with one element. So what happens here? Else if low is equal to high minus 1, that means if it is having two elements, okay, if it is having two elements, what we have to do? We have to compare. So what we have to compare? If a of low is less than a of high, so we are comparing both the things. Okay, if only two elements, we are comparing both the elements. So if a is low is less than a of high, we can simply say minimum is equal to a of low and the maximum will be a of high, obviously. And else, that means a of low is less than, greater than a of high. That means if the first element is greater than the second element, obviously the minimum element will be a of high, maximum element will be a of low. Right? So this is the first condition when the number of elements are 1, and this is the second condition when the number of elements are 2. Now, when the elements are greater than 2, what happens? Again we have to divide. And we have to apply the same process. So else part, and what we have to do? We have to calculate the middle element. So middle element is equal to low plus high divided by 2. And then we have to divide the two arrays. What is the two arrays? The first one, the name is min max, and we have to apply the same procedure. So min max of low. What is the high value here? So obviously it will be mid, and we'll take it as a min 1 and max 1. And second array, this is the first array. Second array, min max, what we have to consider? Mid plus 1 to high, and from here we will going to get minimum 2 and maximum 2. So after completion of these things, we will get only minimum and maximum, both the cases, min 1, max 1, min 2 and max 2. Now we have to compare these two things. So after that, we have to compare if min 1 is less than min 2. So min 1 is less than min 2. So what we have to consider? Minimum value is equal to, okay, min 1. Else, min 1 is equal to, min is equal to min 1, else min is equal to min 2. Okay, so if minimum 1 is less than minimum 2, so that means the last step, if both we have to compare both the minimum values, right? And the same thing should be applied for maximum also. If max 1 is greater than max 2, what happens? So max will be max 1, else max will be max 2. So this is the algorithm for finding the minimum and maximum values, from the single array, unsorted array, by using the divide and conquer method. So hope you understood. What we have done in the example, the same thing we have written in algorithm, right? So first condition, this is n is equal to 1 element, n is equal to 2 elements, and this part is n is greater than 2 elements. This is n is greater than 2 elements, right? So three conditions, we have writing these three conditions, and this part will be repeated until n by 2 power k is equal to 2, right? So hope you understood. Now we'll see how many comparisons we require if we apply this kind of algorithm, okay, divide and conquer algorithm. So by using the linear algorithm, so linear method, the time complexity or the number of comparisons will be 2n minus 2, and now we'll see the time complexity, that means the number of comparisons for this particular algorithm. See, if there are n elements, so we are dividing into n by 2 and n by 2, and again this is divided into n by 2 and n by 2. This is divided by n by 2, n by 2. Further it is divided by n by 2, n by 2. Okay, and this process will be repeated. And when we have to stop, whenever n by 2 power k is equal to 2. That means after division, if the number of elements are 2, then we have to stop the division operation. Now, see the complexity of the comparisons, whatever it may be, we write here T of n is equal to 0. That means 0 comparisons if n is equal to 1. That means only one element is there, 0 comparisons will be there. Then it will be 1 if n is equal to 2 elements. If n is equal, if array is having 2 elements, only one comparison is required. And if it is, right. So if it is greater than 2, then what we are doing, we are dividing the complete array into two halves. So n by 2, okay, plus n by 2, right, plus 1 plus 1. And this is if n is greater than 2. And this is the time complexity of first half plus time complexity of second half, and this is for divide and this is for combine the results. So if the number of elements are greater than 2, then it will be n by 2 plus n by 2, so plus 1 plus 1. So this we can write it as 2t n by 2 plus 2. So like this we can write it. Okay, if n is, if the elements are greater than 2, then the complexity will be this one. So we have to divide the two halves, and again further we have to divide the two halves. Then we can see t of n by 2 will be, so apply the same. This is for t of n. No, t of n by 2, then it will be 2 into 2t of n by 2 divided by 2 plus 2. Okay, so this is this one plus 2. Okay, we are just substituting n by 2 here. Okay, now this happens with, so 4t, and this will be n by 4 plus 2 2s are 4 plus 2. Similarly, again divide it into n by 2. Again divide it into n by 2. So again we'll apply the n by 2 here itself. Okay, or simply we can go with the n by 4 also. Okay, if it is n by 4, apply the same thing. Okay, so let us take further, it is divided. So 4 into 2t of n by 4 divided by 2. So further we are dividing. Okay, so plus 2, and write down all those things. 4 plus 2. So if you solve this one, it will be 8t into n by 8 plus 8 plus 4 plus 2. Right? So, and if you go with the next one, right? So t of, again further division. So 8 into 2t of n by 8 divided by 2 plus 2 plus 8 plus 4 plus 2. So which will be 16t n by 16 plus 8 plus 4 plus 2. So you can use a generic formula. So if it is 8, obviously we are getting, see, third division we are getting here like this. Okay, so this can be written as 2 power k of t n by 2 power k plus, so this can be written as 2 power k plus 2 power k minus 1 plus and so on plus 2. Okay, so if it is 4, it will be 2 power 4, and here it will be 2 power 4, 2 power 4, 2 power 3, 2 power 2, 2 power 1. So like this we can write it. And see from here, so when we are applying the stop condition, this is a stop condition. From here we can consider n is equal to 2 power k plus 1. Okay, so simply we can write it as 2 power k into 2, so which can be written as 2 power k plus 1, or simply we can write 2 power k is equal to n by 2. So remember these two formulas. Now what we have to do, so you can observe this particular pattern, which is a geometric progression, a formula of geometric progression. So geometric progression formula is, so a into r power n minus 1 by r minus 1, where a is a first term, and r is the second term divided by first term. Right? And if it is like 2 plus 2 square plus 2 cube plus and so on 2 power n. If the series is in this way, the formula will be a into r power n minus 1 by r minus 1. Just remember this one, right? So here a is the first term. So here a will be first term, that is a 2 into r is the second term by first term. What is the second term? 4 by 2. Again it is 2. And here n. So here we are representing that as a k. Okay, here it is n, but here we are representing it as a k. So 2k minus 1 divided by 2 minus 1. So this can be considered in the place of this one. Okay, so hope you understood. So forget about this term, 2 power k into t of n by 2 power k, right? So forget about this one. Just remember about this series. So this is like in the same way. 2 power 1, 2 power 2. So you can observe here 2 power 1, 2 square, 2 cube. 2 square, 2 cube, 2 power 4. So it will keep on moving until 2 power k, right? From 2. So that will be in the form of this series. Now what we have done? We have applied the direct progression formula, a into r power n minus 1 by r minus 1, where a will be the first term and r will be the second term by first term. So it will be this one. Now apply the same thing in the place of this one. So I'll erase this one, right? So hope you understood. I'll erase these calculations. I'll apply the same thing here. So 2 power k into t of n by 2 power k plus, instead of this series we can write this one. So 2 into 2 power k minus 1 by 2 minus 1. So this can be written as 2 power k into t of n by 2 power k plus, it will be, so denominator will be 1, so it becomes 2 power k plus 1 minus 2. Okay, so 2 power k plus 1 minus 2. And here you can see So 2 power k t into, in the place of n, we can write it as 2 power k plus 1. So 2 power k plus 1 divided by 2 power k plus 2 power k plus 1 minus 2. Okay, so I'll address this one also. So what happens here? So 2 power k into t, what happens? This we can write it as 2 power k into 2 by 2 power k plus 2 power k plus 1 minus 2. So you can remove these two things. So now the formula will be 2 power k into t of 2 plus 2 power k plus 1 minus 2. Right? Now you can observe 2 power k. So what's the value of 2 power k? N by 2. So n divided by 2 into t of 2. That means we are having two elements. Okay, in the n we are having two elements. If it is two elements, see, if n is equal to 2, the result will be 1, complexity will be 1, the comparisons will be 1. So we can simply substitute as 1 plus 2 power k plus 1. 2 power k plus 1, it is n. So n minus 2. Okay, so from this we can write it as n by 2 plus n minus 2, which will be treated as 3n by 2 minus 2. So this is the number of comparisons we required in order to find the minimum and maximum elements using divide and conquer. So here also, if you observe, the worst case complexity will be order of n, because the highest degree is n. The complexity will be, here also the complexity will be order of n. Okay, in the linear model also, that the highest degree is n, the complexity will be order of n. Now you can check. So if you are having a 10 elements, okay, so we need to find the minimum and maximum from the 10 elements. If you apply the linear approach, how many comparisons will be required? So the comparisons will be 2n minus 2. That implies 2 into 10, 20 minus 2. 18 comparisons are required. 18 comparisons. And if you go with the divide and conquer, then the same comparisons will be 3n by 2 minus 2, which will be 30 divided by 2. Okay, 3 into 10, 30 divided by 2, 15 minus 2, 13 comparisons. So now you can observe, so if it is a linear approach, it requires 18 comparisons, and if you go with the divide and conquer, the comparison has been reduced to 13, which is an optimal solution. So you can feel the difference. So without using the divide and conquer, and after, applying the divide and conquer, so obviously the number of comparisons will be reduced if you use the divide and conquer strategy. So final goal for every problem is to find the optimal solution in terms of complexity or time complexity or space complexity, whatever it may be. But the final goal is to get the optimal solutions. Now we can see clearly by using the divide and conquer method, we will be having the optimal solution. So it requires a minimum comparisons, less comparisons when compared to the conventional model or a linear approach. Right? So hope you understood. So this is the stop condition. First we have to start dividing the complete problem into subproblems, and we have to continue the same process until the division results to two elements. So then we have to apply the algorithm. An example for the binary search, and then the algorithm, and finally we'll see the time complexity. Right? So today's concept is a binary search. So search means searching or finding an element whether it is present in the given list of elements or not. So if it is there, automatically we'll return that element or a position, or we can say that element is found in the list. Otherwise we'll say it is not found. And in order to solve this one, we are going to use this divide and conquer. That means we are going to divide the complete list into two halves, and we are going to solve the problem by selecting either one of the half. Right? So every time we are going to reduce the search space. For example, if a list contains some 5 elements or 6 elements, in the second, after first iteration, after dividing the list, so then the search space will be reduced to around 3 elements or 2 elements. So like this, we are going to reduce the search space after every iteration until it gets only one element. Okay, so let us consider an example first. First, let us see the procedure, how we are going to solve that one, and then we'll move on with the algorithm and then time complexity. Now, consider a list of elements, and first thing, very important, if you want to perform this binary search, make sure that the element should be in a sorted order. That is one important constraint before starting this binary search procedure. Right? So very, very important. So elements should be in sorted order. So this is important for binary search. And if you are moving with another one, linear search, so there will be no constraints. The elements can be of any order so that we can find the element, that we can perform the linear search. But coming to the binary search, make sure that the element should be in a sorted order before starting the binary search. Now consider an example. So we are going to take some sorted elements. So I take it 10, 15, 35, 42, 58. So I take a small elements, okay, only 5 elements. So here I am considering 5 elements, 5 elements. So now consider this one as a low, this one as a high. Okay, low and high. First we need to find out the middle element, okay, middle. So consider the index values 0, 1, 2, 3, 4, and this is the 5 elements. These are the 5 elements. And now we need to know the key value, that means the search key. So which element we are going to find. Let it be the search value is 10. Search value is 10. Now in the first step, find out the middle value. So mid is equal to, so low plus high divided by 2. So which gives, so 0 plus 4 divided by 2 is equal to 2. So middle is a 2. Okay, middle is 2. So what we have to check, see, the low is a starting element and high is a last element. Okay, low is a starting element, high is the last element. So always we know that low will be less than high. We know the process, right? So always low will be less than or equal to high. Because if the elements are only one element, the same element will be pointing towards the low and high. So low is less than or equal to high. And if low is greater than high, then such is not possible. Such is not possible, or we can say that element is not found. Okay, if low is greater than high, then such will be not possible, right? So we need to repeat the same process. Okay, we need to repeat the middle, calculating the mid value until the low becomes greater than high. Now see, middle. Now what is the element of a middle, right? This one is a middle. This one is a middle. Okay, so now compare the middle element with the search element. Compare middle element with the search element. So I need to compare search element, and let it be, the name of array is capital A. So A of mid. A of mid. So we need to compare this one, right? So what happens? K is a 10 is equal to 35. Is it true or not? If it is true, that implies our search value is equal to the low of mid, A of mid. So obviously we can say that the element is found in the list. So if it is false, check 10 is less than 5 or 10 is greater than 5. First let us take the greater than, because it's a false condition. So 10 is a greater than 35. That means we are comparing the search with middle element. This is the middle element, right? So 10 is greater than 35. So it is false. Next, 10 is less than 35. So if you want to compare two values, only these three are possible. Whether either both are equal, either the first element is less than the second element, or either first element will be greater than the second element. Only the three possibilities. Now check 10 is less than 35. Yes, this is true. What happens, that what says this one means search element is less than 35, and the constraint is elements should be in a sorted order, and from this point 10 is less than 35. Obviously that implies the search element may be less than the middle element, less than the portion of middle element. Okay, hope you understood. So here from low to high we are finding the middle value, and in the middle value we are checking a comparison. So we are comparing the middle element, and based upon this one we are selecting either we have to choose the left portion of the middle or right portion of the middle. And here 10 less than high, okay, 10 less than 35, it is true, then we have to select the left portion, because all the elements which are less than 35 will be towards the left side of the elements. Now what we have to do, we have to change the search space, and here the search space is low to high, and now the search space will be low to, and already we have compared this middle element, right? Here we have compared the middle element, so the search space will be reduced to mid minus 1. Mid minus 1. Okay, mid minus 1. For example, if the search element, if the key is some 42, what happens? So up to this one, the same procedure. So 42 is equal to 35. Wrong. 42 greater than 35. True. That means whatever the element we are going to search, that is on right side portion because of this sorted order. So what happens? So the portion, the search space will be reduced towards the right side portion. What is the right side portion? Already the middle element has been compared. So we need to change the low value. So low value, so the search space will be mid plus 1 to high. Mid plus 1 to high. So we need to search only this portion. If it is less than this portion. Okay. So like this we have to repeat, and we have to check, and we have to stop this procedure whenever the low is greater than high. If the element is not found, automatically we will get the low greater than high. So then we have to stop this procedure and see. So we are performing the division operation and one comparison. Division operation and one comparison. Right. See, we'll check. Now you can see 10 less than 35, then it is low to mid minus 1, and now the elements are, so 10 and 15, and we should not consider 35. Mid minus 1 means here low 0, mid minus 1 2 minus 1 is 1. So the search space is reduced to index values from 0 to 1, and here also 0 to 1. And you can see this one will be 0, this one will be 1, and we need to find out again a mid value. So this will be a low value, and repeat the same process, which we have done is the same, right? So again, calculate a mid is equal to low plus high divided by 2, which gives 0 plus 1 divided by 2 is equal to 0. So compare key value and 10. Sorry, key value and A of mid. So which gives key value is 10, middle value and A of 0. That means A of 0. A of 0 is 10. 10 is equal to 10. So obviously we found the element. If it is not found, again we have to repeat the same process. Okay. So hope you understood. So first the search space will be from low to high, and if after the first iteration, that means after finding the first middle element, we are based upon the middle element comparison, we are reducing the search space from either left portion or the right portion. If it's a left portion, the range will be from 0 to mid minus 1, and if it is a right portion, the range, the search space will be from mid plus 1 to high, and we have to repeat the same process. Okay, now we'll write the algorithm. Recursive algorithm, right? We can write the recursive algorithm. So I'll write here. It's a very simple algorithm. Binary search. So we can take a lot of parameters, like array. We can pass the array low, high, and key. So I'll take it as some array low, high, key. So we need to follow this order. First one is an array, second one is a low, third one is a high, and fourth one is a key. Now first we have to find whether low is less than or equal to high, and if it is low is greater than high, then simply we can say it is not possible. So if low greater than high, so we can simply return false. We can write return false or element not found, whatever it may be, based upon our logic, based upon our presentation, we can write it. And else, that means if low is not less than, low is not greater than high, next we have to find out the procedure. What we have to do? First we have to calculate the middle value. So middle value is equal to, so the same thing, low plus high divided by 2. So after getting the mid value, this is an index, right? Now we have to compare middle, the key with the middle element. So here, if mid is equal to some array of, if key is equal to array of mid, then try to return true, or you can write it, yes, the element found at the position mid is the position, right? Else, again we have to check the condition, else if key is less than array of mid, what happens? If that search element is less than the middle element, obviously the search space will be left hand side. So what we have to do on the left hand side means the search space will be reduced. So low will be same, and high becomes mid minus 1. So you can write it the recursive call. So we can simply call the same thing. So binary search. What we have to do? The first one is array, low value is same, and the high value will be mid minus 1 and a key. Okay. Then yes, if both the cases are false, that implies the key is greater than array of mid. So again we can write binary search, and now also array, the search space will be now reduced to right half. Right half means low value will be changed to mid plus 1. So mid plus 1 to high key. So this is a simple and very easy algorithm. So everything is, the complete problem will be divided, and based upon the division, based upon the comparison, we have to change the search space. Search space means from where to where, either low is changed or high is changed. So we have to repeat the same process until the low value is greater than high. So if this problem came low greater than high, that implies the element is not found in the array. Okay, so now we'll see the time complexity. Hope this is very simple. So hope you understood this one. Now we'll go with the time complexity. What is the time complexity? So the best case time complexity is order of 1, because if you are searching the search element is the middle element. For example, if key is equal to 35, how many comparisons you require? So here in this case, that is the middle element. Obviously, in the first comparison itself, we get the search. Okay, so it will be order of 1. It's a best case, and always we have to consider the worst case, right? So consider the worst case. So T of n is equal to, what we are doing? We are dividing and we are doing the comparison. So what we have to do? T of n divided by 2 plus 1. So we are not solving two portions. Okay, we are solving only one portion, either left half or right half. So that's why I am writing only one time, T of n by 2. And after that, we are comparing, one comparison. And see, we need to find out the n, what is n? And see, in the first step, we are finding n divided by 2. Okay, so in the next step, we are finding n divided by 4. See, now we are checking n divided by 2. That becomes n divided by 4 plus 1 plus 1. And again, we are performing the same thing in the next half. So n by 4 half. That means n by 8 plus 1 plus 1 plus 1. And similarly, t of n by 16 plus 1 plus 1 plus 1 plus 1. So what happens? Every time we are dividing the search space into half. So first we are having some 5 elements. From that we are dividing the 5 to 2, and then we are dividing the 2 to 1. Okay, so we are keep on repeating the same process until we get the element, only one element. So you can simply say that this is t of n by 2 power k plus k terms. Okay, now when we are stopped, when we have to stop, so that is also most important here, stop condition. So when we are going to stop this division, so n by 2 power k is equal to 1 element. So we are keep on repeatedly dividing the complete list, and we are stopping whenever n divided by 2k becomes 1 element. Okay, so from this equation we can say n is equal to 2 power k. So substitute the same thing here. So what happens here? So the same process will be repeated, and the t of n by 2k is n plus, from this one, what is the k value? So log n base 2. So we can represent it as log n base 2. Okay, now what happens is equal to t of 1 plus log n base 2. So if there is only one element, then automatically it will be 1. So 1 plus log n base 2. So the time complexity, we can say the time complexity is equal to order of log n base 2. So this is the time complexity for binary search. Okay, using divide and conquer. So here we are not combining all the solutions. So just we are dividing the complete problem into sub-problems, and we are considering only one portion, not the two portions. And we are repeating the same process until it reaches to one element, and we are comparing. And if it is not found, we are saying that element is not available. So the only one constraint here is elements. All the elements should be in a sorted order. So that is the most important constraints we have to follow while starting this binary search process. So the sorting is arranging the elements either in ascending order or descending order. So by default we'll go with the ascending order, right? That means a lower to higher. So one type of that process is a merge sort. So by using this merge sort also we can sort the elements, and this will follow the divide and conquer strategy, right? So we know about the divide and conquer. So it will be having some 3 stages. One is dividing the problem into sub-problems, and second one is a conquer. So that means providing the solution or finding the solution for each sub-problem recursively, and the last one will be the combine. So we need to combine the solutions of all the sub-problems to get the main solution. So the same process will be applied for this particular merge sort, right? So here in this session we'll see an example, so that we'll be getting an idea how the merge sort will be implemented, and then we'll go with the algorithm or a pseudocode. So based upon the procedure which we have known in this example, so we'll write the algorithm and we'll check, and finally we'll see what is the time complexity, the worst case time complexity of a merge sort, right? So we'll see one by one. So first let us start with the example. So let us take a few elements, unordered elements, and then we're going to use the divide and conquer method. So 50, 60, 10, 70, 30 and 40. So let us take these elements. Now we know that these elements are not in a sorted order. So we have to arrange them in the sorted order. So initially we'll write the index values 0, 1, 2, 3, 4 and 5, and we know, so this is a low, we will represent this one as a low and this one as a high. So the first step is divide. So we need to divide the complete problem into sub-problems. So formula, so by which formula or by which criteria we need to divide the complete elements into 2 halves. So that is based upon the middle value, so mid value. So we need to calculate the mid. So mid is equal to, so low plus high divided by 2. So we need to consider only the integral part. So that will be low plus high by 2. That means 0 plus high 5 divided by 2. So which is 5 divided by 2, which is 2.5, and we need to consider only integer. So that will be 2. So mid is 2. Mid value is 2. So here I write mid is equal to 2. Now what happens? We need to divide the complete problem into 2 halves based upon this mid. Okay, so what's the mid value? 2. So this is a mid. Okay, so where we have to divide. So one part is from low to mid, and the second part is from mid plus 1 to high. So based upon this one, we need to divide the complete elements into 2 halves. So here we'll write, so 50, 60, 10, 70, 30, 40. So this is one part, and this will be the another part. So again we need to divide the elements further based upon the middle. So we have to solve these two parts individually and recursively. So what happens here? This is 0, 1 and 2, and we need to calculate the mid. Mid is equal to 0 plus 2 by 2. 0 plus 2 by 2. So which will be 1. Which will be 1, right? So we need to divide this one into two halves. So 50 and 60. That means low and mid plus 1 and mid plus 1. Mid plus 1, right? So here also we need to apply the same process. So mid is equal to 0 plus 1. So 0 plus 2 by 2. So which is 1, right? So this is 1, 2. So now here also the same process. It was divided into 70 and 30 and again 40. So two parts. So complete data is divided into two parts, and each part is again further divided into two parts. And similarly here also it is 0, 1 and it is 0, 0, 1 and it is 0. So here again we need to divide. So mid is equal to 0 plus 1 by 2, which is equal to 0. So we need to consider 50, we need to consider 60, and here is only one part, that is 10, and here also the same. So mid is equal to 0 plus 1 by 2, because this is a L, this is a high, low and high, low and high. So low plus high by 2. So here also we need to use the same thing. So 70, 30, 40. So right, this is the process. This is the process. Right? This is the process. Now we got a complete elements here. Now what we have to do? We have to compare each and every element, and we need to arrange the elements in a sorted order. What we have to do? So we need to compare this 50 and 60. Okay. So 50 and 60, obviously both are in the same, right? And this is 10. And apply the same process here also. So 30 is greater than 70. So 30 is less than 70. So we can see 30 and 70 both comes in the same thing. And now it will be the 40. See what we have to do. So let us assume this one as I and this one as J, and this one as I, this one as J. So we need to compare I and J. Here also you can see this is I and this is J. This is I and this is J. So we need to compare the I value and the J value. And if the element whichever it is lower, that should be loaded in the new array. So this is the new array. You can observe this is a new array, right? So compare 50 and 10. Which is the highest? So which is the lowest? 10. So obviously 10 will be placed here first, and this value will be incremented. That means it will be moved to the next one, next element. And here also now there is no element in J. If in such cases, whatever the elements remaining in this particular sub array, so that will be loaded into the new array. So 50 and 60. See, 50 and 60. So after combining this one, so we got these elements. Similarly here also, let us assume the new array. See, 30 is compared with 40. So which is lower? 30. So 30 will be stored in new array, 30. And immediately I value will be incremented. So now I value is pointing towards 70. Again repeat the same process. 70 and 40. So 40 is a lower. So now place 40 here and J is incremented. So there is no other value in this particular array. So whatever the elements remaining in this sub array, that will be loaded into the new one. So 70 will be copied here. So you can observe after every step we are getting the elements in a sorted order. So here you can see 10, 50, 60. These elements are in sorted order. 30, 40, 70. These elements are in sorted order. Now what we have to do? So we have to combine these two arrays. So after first division you can see 50, 60, 10, and now it is 10, 50, 60. After division 70, 30, 40, here you can see 30, 40, 70. So we have to compare each and every element of both the arrays, and we have to create a new array, and if whatever the element which is lesser, that element should be copied into the new array, and that index should be incremented towards next one. So if there is no other element in the array, then automatically whatever the elements remain in the next array or the other array should be copied into this one. Now, if you are still having any doubts, so let us solve this one so that you will be understanding, right? So here we are having 3 elements and here we are having 3 elements. Now we'll solve this one. So I'll arrange this one. Right. So let us consider 10, 50, 60. So 3 elements, and here also we are having 3 elements, 30, 40 and 70. See, now what we have to do, so we have to compare each and every element, right? See, so let us consider this as I, this as J. Okay, this as I and this as J. Now what we have to do, so we have to compare 10 and 30. We have to compare 10 and 30. So this is a new array. Okay, this is a new array. So 10 and 30. So which one is less? 10 is less. So obviously 10 will be stored in the new array. So 10 will be stored in new array, and I will be incremented to the next one, because 10 is already here, right? So I will be incremented to the next one. J remains same. Okay, J remains same. Now 50 is compared with 30. So which one is low? 30. So 30 will be copied into the new array. Right? 30 will be copied to the new array. Now J will be incremented. J will be incremented. Again compare 50 and 40. Which one is low? 40. So 40 will be stored here, and again J will be incremented towards here. And again 50 and 70. So 50 is less. So 50 will be copied here, and I will be incremented towards here. So 60 and 70, 60 is less. So 60 will be copied here and I will be incremented and there is no element in the array. So it goes beyond the index. So then immediately what we have to do? So we have to go with the next another array and whatever the elements remaining in that array will be directly copied to the new array. So only one element is there. So already 10 we have copied, then 30 is copied, then 40 is copied, 50 is copied, 60 is copied. So only one element is remains here. So we'll simply write 70 in this place. Okay, now we have taken the elements here, 6 elements, 50, 60, 10, 70, 30, 40, and now we are getting the elements in a sorted order. So 10, 30, 40, 50, 60, and 70, right? So here we have done the division. So where we have divided the complete problem into two halves based on middle value, and then conquer. So recursively we are keep on solving by comparisons, and then combine. So we are merging or combining all the different subproblems so that we are getting the final solution, right? So hope you understood this one. So based upon this explanation, we'll write the algorithm, right? Yes. So what we have to do, we have to divide the complete elements into two different halves. So let us write merge sort. Okay, merge sort. So here we can write yes, one is array, another one is low, and another one is high. Okay, now what we have to do? So if low is equal to high, that means only one element, right? There is no comparison. Okay, there is no comparison. Nothing can be done. So we can return a direct elements. Return element. Okay, so only one element means that will be in the sorted order. Else, what we have to do? We have to divide. So recursive call. Again, apply the merge sort. And what we have to divide? So array of elements, and then low to mid. And then again we have to divide merge sort a mid plus 1 to high. So once the division has been completed, then we have to combine. So that we call it as merge. So don't get confused. Merge sort is different, merge is different. Merge function. So here we'll write low, high, mid. Okay. So what we are doing? So first we are checking whether it contains a multiple elements or a single element. If it is single element, simply we can return the element. And if it is a multiple elements, then we have to divide the multiple elements into two parts. One is from low to mid and mid plus 1 to high. And once it was completed recursively, then we have to start merging both, all the solutions, right? So we'll write the merge part here. Merge three things, that is low, high, mid. Okay, also we can take array because we need to pass the array. So also we can write array. Four parameters, array of elements, low, mid, and high. Now, okay, so what we have to do? So we have to check, so we have to initialize first. Initialize. Let us initialize I is equal to low and j is equal to what we are doing. So we are taking two parts, and here I am writing I and here I am writing j. So, right? So I is a low. J will be the first element of the second array. So which is nothing but mid plus 1. Hope you understood, right? So j will be the first element of second array. I will be the first element of first array. So automatically I will be low, that is 0, and j will be mid plus 1. And we need to continue this process until the two conditions satisfies. I less than or equal to low and j less than or equal to high. So here, here it is not low, it is mid, because so until I reaches mid, and here until j reaches high, because this position is mid and this position is high. So we are keep on comparing each and every element, and we are incrementing the I value and j value. And this process should be repeated until I reaches to mid or j reaches to high. So I less than or equal to mid and j less than or equal to high, we have to repeat it. What we are doing, we are comparing this element and this element. So what is the element? So comparison is a condition, right? So if a of I less than a of j, what we are doing? So if a is less than, this element is less than this element, what we are doing? We are copying this element to a new array. Let us consider here a new array. Some b is equal to, okay, so let us take index value 0. B is equal to index value 0, and b is some array of multiple size. Let us take some 10 array. Okay. So what we have to do? So b of I plus plus. So here we have taken b is an array, and let us take the index value as 0. So b of k plus plus is equal to a of I plus plus. So what happens? This is a postfix. Okay, postfix. First it will be copied and then automatically it will be incremented. And you can also write the same thing in this way. B of k is equal to a of I, and you have to increment the I value. So once you copy this element into this one, we have to increment the I value, right? So we have incremented the I value. And simply you can write else. What happens? If it is false, that implies a of j is less than a of I. So a of j should be copied here. So this element should be copied here. So b of k is equal to a of j, and j should be incremented. j should be incremented. So j should be incremented to the next. And both the cases we have to increment the k plus plus, because once the element is inserted here, the k should be incremented so that the k points towards here. So k should be incremented, right? So once all this is done, then if it reaches to here, what happens? We have to move all the elements of first array to the new array, or all the elements of second array to the new array. So for that we can simply write loops. So y, simply write it I less than or equal to mid. Okay, I less than or equal to mid. Simply write down b of k is equal to e of I, and simply write one more thing, j is equal to j less than or equal to mid, b of k is equal to e of j. See, this will be happened. Okay, this will be happened. Sorry, here we have to close, and this is outside the loop. Outside the loop. Okay, so what we are doing, we are comparing the elements, and we are selecting the lowest element, and that element will be copied to the first position here, and then we are incrementing the I value. So the same thing happens here. This code is the similar, right? So once I reaches to mid, what happens? So we need to check whether the elements are remaining in the either of the array. So if they are remaining, so we need to copy all the elements to new array. Okay, and here also we need to increment the k value and the I value. So in both the cases, I value and k value will be incremented. So simply we can write it as k plus plus I plus plus. So because of this post increment, first the value will be copied and then the this one will be incremented. Okay, so this is an algorithm or a pseudocode, so whatever it may be. So based upon our explanation on an example, right? So hope you understood this one. Now we'll move on to the time complexity. So what is the time complexity of this merge sort? Right? So we'll see what is the time complexity. So what we are doing? So time complexity of 1. If it is one element, that will be 1, right? So T of n is equal to. So first the problem is divided into two parts, and we are solving both the parts. So T of n by 2 plus T of n by 2. So two halves. And we are considering both the things because we are solving both the parts. Okay, whereas coming to the binary search, so we are moving on with only one part, right? So that's why we have not included both the parts, right? But here, so we need to solve both the arrays. We are dividing the problem into different parts, and we have to solve all the parts. So we have to consider this one. And plus, what we are doing? We are doing n comparisons. So how many elements are there? Then that many comparisons we are doing. So we are comparing each and every element, and we are performing the operations. So plus n. So this we can write it as 2t of n by 2 plus n. Okay. Then coming to the relation. So if n is equal to n by 2, right? Then t of n by 2 is equal to 2 into t of n by 2, right? So 2t of n by 2 divided by 2 plus n plus n. So it will be 4t of n by 4 plus. So what happens here? So this is n by 2, right? So 2 into n by 2, it will be n plus n. So which gives a 4t of n by 4 plus 2n. Okay. So the same thing, right? Plus n means here we are in the place of n we are dividing the n by 2. So once again in the further process, right? So first there are some 6 elements, then 3 elements. Again 3 is divided into 2 parts. Further division, so we can write 4 into 2t of n by 2 divided by 4 plus n by 4 plus 2n. So it will be 8t n by 8 plus n plus 2n, which will be 8t n by 8 plus 3n. So this will be keeps on moving, right? This will be keeps on going. So that can be written as 2 cube. 8 can be written as 2 cube t of n by 2 cube plus 3n. So this can be written as t of n is equal to 2 power k t of n by 2 power k plus k into n. So this process will be repeated. So what is the stop condition here? So when we are going to stop the division, right? So here I'll write stop condition. So this is the most important, right? Like calculating the time complexity. So whenever it will be, so we are keep on dividing the problem and we'll stop when it becomes one element. When it becomes one element. So obviously we can write it as n is equal to 2 power k and k is equal to log n base 2. So this is the stop condition. Now you can know, so k value you know and 2 power k value you know. So substitute the same thing here. So 2 power k, which is nothing but n into t of n into t of n, it's a 2 power k, or simply we can write n by n plus what's the value of k? Log n. So log n base 2 into n. So this will be n into t of 1 plus n into log n base 2, and this becomes 1. So that will be n plus n log n base 2, and obviously you can see the highest degree, that is n into log n base 2. So the time complexity, the worst case or average case time complexity for the method will be n into log n. That means we have to write by using the asymptotic notation. So big O of n log n. So this is the time complexity for merge sort. This will be the time complexity of merge sort.
So this sorting mechanism will follow the divide and conquer method. Divide and conquer. So the name itself indicates. So divide and conquer means first the complex problem is divided into subproblems, and each subproblem will be implemented. So like that, here also the complete large elements will be divided into different partitions, and each partition will be applied for sorting technique. So each partition will be implemented by using the recursive methods. Okay. Next, so let us see the procedure first, and then we'll go with the example. Then, first step. Here we have to select the pivot, and we have to find the position of the pivot element. So here we will go with the pivot element, right? So first we have to find the position of a pivot. Position of a pivot such that all the elements which are left towards this pivot are less than the pivot element, and whatever the elements which are on right side to this position are greater than a pivot, right? So this position, first we have to find this position, then consider this as one partition, consider this as another partition. So see, this is less than pivot, this is a greater than pivot, don't get confused. Okay, this is a less than symbol and a greater than symbol. Okay, so less than pivot is one partition, greater than pivot is another partition. So recursively call the same procedure for this partition. Again consider a pivot and find the position of the pivot for this partition, and again divide that into two positions, right? So like this we have to find this quick sort. First, this pivot can be considered as the pivot element can be considered as first element, middle element, last element, right? So we can consider any element as a pivot element, and based upon the pivot element we have to find the position of that particular pivot element, right? For example, if the numbers are 10, 50, 40, 10, 30 and 20, this element can be considered as a pivot, or this element can be considered as a pivot, or this element can be considered as a pivot. So after considering the element as a pivot, we have to find the position of that particular pivot point such that all the elements which are less than pivot should be on the left hand side, and all the elements which are greater than the pivot should be arranged on right hand side. So in such a way we have to find the position of the pivot. First we have to consider the pivot element. What is the pivot element, right? So in our example we will consider this one, first one. So let us consider the first element as a pivot and find the pivot position. See, first consider first element as a pivot. Consider the first element as a pivot. Next, initialize I to low index, j to high index. That means the starting element, j is the last element. Next, we have to repeat the procedure. Repeat the following steps until I less than j. So until I less than j, until the condition is true, we have to repeat the following procedure. So first, keep on incrementing I. Keep on incrementing I while A of I is less than or equal to pivot. So unless this condition becomes false, we have to keep on incrementing the I value. Right. Next, similarly, keep on decrementing the j while A of j is greater than pivot. So similarly, from the starting, we have to incrementing the I towards the right, and we have to decrementing the j towards the left. Okay, so while incrementing and decrementing I and j values, we have to check these conditions, whether A of I is less than or equal to pivot, and whether the A of j is greater than pivot. Right. Next, so if this two condition fails, if these two at some condition, this condition, I mean at some point this condition will be failed, so we have to stop incrementing the I. At some statement element, this condition will be false, so we have to stop decrementing the j. Now check the condition. If I is less than j, I is less than j, yes, then if it is true, then swap the elements A of I, comma A of j, A of I, comma A of j. So we have to swap the elements of I value, the elements which are available in ith index and jth index. Next, if this becomes false, I less than j. So if I is greater than j, the index value of I is greater than j, then also we have to swap a of j element with the pivot. A of j element with the pivot. So this is nothing but, this is nothing but a of low, because here the pivot is the first element, right? Pivot is the first element. So we have to change the swap between the jth element and pivot value. So here j is the position of pivot. So this is very important, right? J is the position of a pivot, so that all the elements which are less than pivot are on the right hand side, left hand side, and all the elements which are greater than the pivot will be on right hand side. So here, after completion of this one, the pivot value will be fixed. The pivot position is fixed, right? Not the pivot value. Pivot position will be fixed, right? So we are supposed to find the position of a pivot. Now divide the two partitions. So one is after getting the pivot value, right? So this is one partition and this is another partition. So this is 0 to p minus 1, and here p to high, p plus 1 to high. Okay, p plus 1 to high. Instead of writing 0, we will write low. Right. Low to p minus 1. So this is one partition, this is another partition. So consider this partition, and here also consider repeat the same process. So recursively repeat the same process. Consider this partition as an array of elements. Now consider the pivot, first element as a pivot, and starting I to low index and j to high index. So I will be low, j will be p minus 1, and then repeat the following steps until I less than j. So keep on incrementing I while ia of I is less than or equal to pivot, and then keep on decrementing the j while a of j is greater than pivot, right? Then if I is less than j, the index values of I is less than j, then simply swap the positions of I and j, the elements which are at positions of I and j. Then if I is greater than j, the index value of I is greater than the index value of j, then simply swap the low value with the a of j, that means the value present at the position j. So here a of low means nothing but a pivot value, because in the first step we are considering the first element as a pivot. So here again the pivot, the position j is the position of pivot. So the pivot position is fixed, so that all the elements which are less than pivot will be on left hand side, and all the elements which are greater than pivot are available in the right hand side. And again do the partitions and again repeat the same process. Right. So this is how we will implement. We are going to implement this quicksort. Right. So based upon this algorithm, let us solve an example so that your doubts will be clarified. So our aim is to find the position of a pivot, and we will implement the same thing recursively for all the partitions. So once the pivot is fixed, then we have to divide it into partitions, and considering each partition, and we have to repeat the same. Okay. Example. Let us take some elements. Consider these elements. Okay. See. So these are the elements of an array. So this is array elements. These are the indexes. This is the I value. This is the j value. I value, j value. Okay, right. Then consider this as a pivot. Consider this element as a pivot. Now repeat the process. So first step, consider the pivot as a first element. So we have considered this one, and next I is initialized to low and j is initialized to high. So I less than j, that is here 0 less than 5. The condition is 2. So this condition is true. We have to repeat the process. So what we have to repeat? We have to keep on incrementing I until a of I is less than or equal to pivot. So a of I less than or equal to pivot. See this condition I plus plus. We have to repeat the same process. Okay. So here see first 30 less than or equal to 30. So I plus plus. So that means 1 it will be. Next 20 less than or equal to 30. I plus plus 2. Right. Next 10 less than or equal to 30. I plus plus 3. Index value 3. So 50 less than or equal to 30. So fails. Okay. Fail. Here the fail. Condition fails. Now here at what condition it is failing? I is equal to 3. So I is equal to 3. Right. Condition I is equal to 3 fails. So after completion of this one, I is pointing at here. Okay. Now keep on decrementing the j value. So a of j is greater than pivot if I j minus minus. So repeat this process. So a of j is nothing but a high value, low high value 5. So 40 greater than or equal to greater than 30, j minus minus, so it will be 4. Next, 60 greater than 30, j minus minus, it's again 4, sorry 3, after decrementing it will be 3. Next, 50 greater than 30, again j minus minus, 2. Next, 10 greater than 30, fails. So at where it fails, j is equal to 2, right? So at some condition, at some element, both the condition will be fails. Now we have to check whether I is less than or j. So what is the, see, if I less than j, then swap a of I element with a of j element, right? Else we have to change, swap a of j element with pivot, right? Now let us take the condition here. So I less than j, so 3 less than 2, I less than j, 3 less than 2, which is false, right? So we have to swap a of j. A of j means, say j is 2, a of 2 comma pivot. What's the pivot? 30, or a of low, okay, a of 0, because here the pivot is a of 0, right? So swapping j position is pivot. So what is the j position? 2. Second position is a pivot element. Second position is the pivot element for the first thing. So after getting this one, see, just swap the positions, a of 2 comma a of 0. A of 2 means 10, so 10 will be here, 20, 30, then 50, 60 and a 40. See, 0, 1, 2, 3, 4 and 5. So second position is a pivot. Second position is a pivot, right? So here if you observe, all the elements which are on the left hand side of the pivot are less than this pivot, 10 and 20. So it may be in a sorted order, or it may not be in a sorted order, right? So whatever the elements which are on the right hand side of the pivot are greater than the pivot elements, right? So this is maybe in a sorted order, and this may not be in a sorted order. So this is the partition 1, this is the partition 2, right? So now we have to consider, so this position is fixed, right? Pivot position is fixed. So we have to take care about the partition 1 and partition 2, excluding this pivot position. So that's why we are writing from 0 to lower to p minus 1, and here p plus 1 to high. So we are not considering the pivot position because it's already fixed. So hope you understood this one. So after the first iteration, first recursion, this is the elements. Now let us write these elements, okay? I will write down here. So 10, 20, 30, 50, 60 and 40. Right. So I will erase all these things. So first recursion, this is about the first recursion. Now so this is the pivot element, okay, fixed. So this will be the partition 1 and this will be the partition 2, right? So let us consider these partitions. So 10 and 20, 0 with index, first index. So obviously this will be I, this will be j, and also pivot. We know that we are considering the pivot as a first element, so this one. So what we have to check? We have to repeat until I is less than j. Here it is 0 less than 1, condition true. Then keep on incrementing. So a of I is less than or equal to pivot I plus plus. So for this we have to go with this. So 10 less than or equal to 10, I plus plus, that will be 1, and the 20 less than or equal to 10, okay, so false. So I is equal to 1. Oh, sorry. Alright, I is equal to 1. So I value is changed from here to here, okay. Next, a of j greater than pivot, we have to keep on decrementing the j value. We have to keep on decrementing the j value. So 20 is greater than or equal, 20 is greater than 10, j minus minus, right? J minus minus, and the value will be 0 now because initially j is equal to 1. And 10 is greater than 20, which is a false. So j is equal to 0. See, at I is equal to 1, the condition fails. At j is equal to 0, condition fails. Here, if you observe, I is less than j, then what we have to do? Swap a of I comma a of j. Else, oh sorry, we can write the condition. Okay, I greater than j, then swap a of j comma pivot. Right? Pivot. Right? So here we can observe here at what positions the condition fails. I is equal to 1 and j is equal to 1, 0. So 1 less than 0. The condition is false. So this will be happens. So swap a of j means 0, comma pivot. Here pivot means again a of 0. So that implies so both the j position, both the j value and the pivot are at the same position, so we need not swap anything, right? So already those are in sorted order. That means these are in a sorted order because we need not swap any element. Okay, only two elements are there, we need not swap any element. So this will be the pivot position. Okay, so here see, j position is a pivot position, isn't it? Right. What is the j position? 0. So 0th is a pivot position. So if 0th is a pivot position, see, left hand side we are not having any elements. Right hand side we are having only one element which is also greater than 10. So it implies this partition is already in sorted order. Right. Next, hope you understood. Next we will go with the partition 2. We will go with the partition 2. So this is already in sorted order. Now we will repeat the same process with the partition 2. So 50, 60 and 40. So 0, 1 and 2. So this is the I value, this is the j value. Okay, this is the I value, this is the j value, and this is the pivot. Right. So continue the process. So I less than j, that is 0 less than 2. So this condition true. Then a of I less than or equal to pivot I plus plus. So keep on doing all these things. So a of I, that means a 50 less than or equal to 50 I plus plus, that means I becomes 1, initially 0. Next 60 less than or equal to 50 fail. At I is equal to 1. At I is equal to 1, it fails. So now I becomes here. Then similarly a of j is greater than pivot j minus minus. So repeat this process. So j value is a 40, 40 greater than a 50, 40 greater than 50. Condition false. So at j is equal to 0 position. At j, at j is equal to 2. At j is equal to 2, the condition fails. Okay. Then see, if you observe here, check the condition I greater than j. Here I is 1 greater than 2. I greater than j. It is a false. So swap. I'm extremely sorry. I less than j. So if I is less than j, we have to swap the elements a of I and a of j. If I is greater than j, then we have to swap the elements a of j and pivot. So here the first condition, I is less than j. I value is 1, j value is 2. So I is less than j. So swap a of I, comma a of j. So what are the elements we have to swap? Swap the 60 and 40. So the elements will be, after the iteration, the elements will be 50, 40, 60. 50, 40, 60. The positions of I and j are same. Okay. So the index values is 0, 1 and 2. And this is the pivot we are considering. Right. So after swapping 60 and 40, we will get this one. Okay. Now, again repeat the same process. So a of I is less than or equal to pivot. So I plus plus, answer this one. A of I, that means a 40 less than or equal to 50. I plus plus, which becomes 2. Similarly, 60 less than or equal to 50 fail. At I is equal to 2. Right? At I is equal to 2, it fails. Now I and j are positioning at the same point. I and j are positioning at the same point. Similarly, a of j is greater than pivot. Then simply decrement the j. Repeat the process. So 60 greater than or equal to 50, not equal, greater than 50, j minus minus, which becomes 1. Similarly, 40 greater than 50, which fails at position j is equal to 1. Now j is positioned at 1. Right? Now check the condition. So if I is less than j, then swap a of I, comma a of j. Just a minute. Else swap a of j, comma pivot. Right. Now here I is 2, j is 1. 2 less than 1. False. So we have to swap, false condition, swap a of j, comma pivot, which is nothing but swap a of j means a of 1, 40, comma a of pivot, 50. And we know that j is pivot. J is pivot. That means 1 is pivot here. Okay. So here 1 is pivot. So after completion of this, okay, after completion of this, so I will erase this one. Okay. Right. So here j is a pivot. J is pivot. Here what is the value of j? 1. So 1 is a pivot position. 1 is pivot position. So we have to swap. After swapping 40, 50, the elements are 40, 50 and 60. The positions 0, 1, 2, the position, this is the pivot position. So left hand side of the pivot is having the values less than pivot, and the right side of the pivot position are having the elements greater than pivot. So here again, this is the one partition, this is another partition. So here the partition is having only one value, so need not apply the sorting technique. And here also the partition is having only one value. Here also we need not apply the sorting technique. So finally, after completion of all these things, we can simply have 44, 50, and 60. Okay, so this is a procedure we are supposed to apply. So hope you all you understood this one, right? After the first iteration, 2 is a pivot, so that 2 partitions are there. First partition, again 0 is a pivot. Second partition, 1 is a pivot. 1 is the position 1, index 1. Okay, index 0 and index 1. Right? So hope you understood this one, the quicksort algorithm, how it apply for this, how we are dividing the complete elements into different partitions, and how we are applying the recursive functions, right? So simple thing. So first we have to consider the pivot element, and first to find out the position of that particular pivot element, and then based upon that particular pivot element, we have to divide it into the partitions and recursively apply the same procedure.
Now we'll see the time complexity of this quicksort, and hope you enjoyed the example and the algorithm, the procedure, how we can sort the elements by using this quicksort using divide and conquer. Now we'll see the time complexity. So the time complexity of this particular quicksort is, so we are selecting the pivot element and we are dividing the complete elements into 2 partitions. Okay, 2 partitions. So one partition, let it be the pivot element is of middle element, right? So obviously it will be T of n by 2 plus T of n by 2. So worst case, let it be the pivot element is a middle element. So what we are doing, we are dividing the complete elements into 2 halves. So from 0 to, low to mid minus 1 and mid plus 1 to high, because the middle element will be the pivot. So we need to sort out all the elements of left partition and the right partition. That means pivot, left of the pivot and right of the pivot. So this way. And for everything, for every partition, we have to do some n comparisons, because we are applying the sorting up, right? So we require n comparisons. So n. So finally we can write it as 2t n by 2 plus n. So this will be the complexity. Now for the next iteration, in the next iteration, so the half partition, again it will be divided into 2 halves. So then if it is n by 2, then 2t of, apply 2t of n by 2 divided by 2 plus n by 2 plus n. So we are applying only this one, right? So t of n is this one, t of n by 2 is this one. And if it is n by 4, what happens? See, before applying the n by 4, what's the resultant here? So 4t of n by 4 plus n and n, that will be 2n. And if it is n by 4, what happens? And that means again we are dividing the complete elements into 2 halves. So if it is n by 4, then again it will be, so 4 into 2t of n by 8 plus n by 4 plus 2n. So then what happens here? 8t of n by 8 plus n, okay, plus 2n, then it will be 3n. So this will be the, and this will be continued, okay, this will be continued. And what is the stop conditions? Here also the most important, stop condition. From that only we will get some values. So we are dividing the complete elements into halves, and we are repeatedly doing the same thing until we get one element. That means n by 2, n by 3, n by 4, n by 8, n by 16, and so on, n by 2 power k. And when it will be stopped? Whenever this becomes 1. That means whenever the partition becomes one element. So from this we can write it as n is equal to 2 power k and k is equal to log n. So this is the most important, because from this only we are supposed to calculate this n and substitute the n and k values. So in general we can write it as, so t of n is equal to, so 8, that means 2 power k, okay, or simply we can represent this one 2 power 3 into t of n by 2 power 3 plus 3n. So in the generic we can write this one as 2 power k t of n by 2 power k plus k into n. So we can write the complexity in a generic format like this one, 2 power k, right? Now you can substitute the n value and k value here. So 2 power k, what is it from? N into t of n by n plus k value log n into n. So this becomes n into t of 1 plus n log n. So you can know that if there is only one element, so we need not do all the procedure, the complexity will be 1, because the element itself will be in the sorted order, because we are not having more elements, right? So we are having only one element, so obviously we can say that will be in the sorted order, right? So there is no comparisons. So obviously this becomes 1, so n plus n log n. So in this equation, we know the highest degree is n log n. So obviously, the time complexity of quicksort, T of n is equal to big O of n log n. So this is the time complexity of the quicksort algorithm, right? So hope you understood. So we are just dividing this one, and this is most important in every time complexity calculation. So from this only we are going to substitute these n and k values. So we are keep on dividing the partitions. So this is a complex problem. So after first iteration, we are dividing the problem into half, and this process will be repeated until the partition elements becomes only one. So from that we got n value and k value, and we are substituting the same in this particular time complexity. So here the name itself indicates this is mainly used for calculating the matrix multiplication. So before this Strassen matrix multiplication, we know that a general method how to calculate the matrix multiplication, and then we can also solve this matrix multiplication by using divide and conquer method. And then we will see what are the disadvantages of using this general method and divide and conquer method, and then we'll go with this particular Strassen matrix multiplication. Now we'll see the general method. So which we know that, right? So we'll take n by n order, right? N by n order. So for example, let it be so A11, A12, A21, A22, and if it is multiplied with B11, B12, B21, and B22, then the result will be C11, C12, C21, C22. So this is the thing we are multiplying. So what is the value of C11? How will we be getting C11? I'll write here C11 is equal to A11 into B11, A11 into B11 plus A12 into B21, A12 into B21. So before going to that, what is the order of this one? 2 into 2. What's the order of this one? 2 into 2. So we know the constraint before calculating the matrix multiplication. What is the constraint? The columns of A should be equal to rows of B. So this is a constraint for any matrix multiplication. If A and B are the two different matrices, and if you want to calculate the multiplication between A and B, then the columns of A should be equal to rows of B. Then only the multiplication is possible. So here we are having a 2 and 2. So obviously both are equal, then definitely the multiplication is possible, and the resultant matrix will be the resultant matrix will be rows of A into columns of B. The resultant matrix will be rows of A into columns of B. So what's the rows of A? This one. Columns of B, this one. So the resultant will be 2 into 2. So this is a general method, we know that, right? Now we can apply this to C11. Now C12 is equal to A11 into B12. A11 into B12 plus A12 into B22. A12 into B22. And then the next one, C21 is equal to C21. A21 into B11. A21 into B11 plus A22 into B21. A22 into B21. And then what about the next one? C22 is equal to A21 into B12. A21 into B12 plus A22 into B22. A22 into B22. So what are the values we are taking? So we need to calculate this matrix with row and column order. So this is the formula we are usually using in the general method, right? So if you go with the logic, so obviously we'll go with the for loop for iterating of rows. So I is equal to I less than n, I plus plus, and then and this is for columns. So j is equal to 0, j less than n, and j plus plus. And then the third loop is for multiplication. So for k is equal to 0, k less than n, and k plus plus. And now the logic is C of I comma j. That means the C11, C12, C21, C22 plus is equal to A of I comma k plus, sorry, this is a multiplication, B of k comma j. So this is a logic we are using in a general method for calculating the matrix multiplication. Now coming to the calculation of time complexity, you can see we are having three different for loops, and each for loop is an independent for loop. There is no dependency upon these three for loops, right? So this is completely with I, this is completely with j, and this is completely with k. There is no dependency among one with another. So this iterates n times, and this iterates n times, and this iterates n times. So obviously the time complexity for this one is order of n cube, for general method. So I'll write here. So the time complexity will be order of n cube. Now the same problem can be solved by using divide and conquer method. So coming to the divide and conquer method, the name itself indicates. So first we have to divide the problem into subproblems, and each subproblem will be get solved recursively, and if possible or if required, all the solutions of those subproblems will be combined. So that will happen in the divide and conquer method. Now we'll see, and only one constraint for applying this divide and conquer method for calculating this matrix multiplication is the order should be this, it should be a power of 2. Then only the divide and conquer method can be applied. So that is a very important constraint before calculating the matrix multiplication using divide and conquer. Right? So for general method, it's not required, right? The order can be anything. But coming to the divide and conquer, the order of matrix should be a power of 2. See, I'll tell you. First, make sure the order of matrix are a power of 2. So the next one is divide and conquer method. Divide and conquer method. So one constraint is order should be with a power of 2. That means the order can be either 2 by 2 or 4 by 4 or 8 by 8 or 16 by 16 and so on. So this is 2 power 1, this is 2 power 2, this is 2 power 3, this is 2 power 4. Okay, so like that the order should be only with power of 2. So let us consider this one for our example. Okay, let us consider this one for our example. So I'll take the matrix A11, A12, A13 and A14. Similarly A21, A22, A23 and A24. A31, A32, A33 and A34. Similarly A41, A42, A43 and A44. So this is one matrix. This is one matrix. Similarly, there will be another matrix called B. So B11, B12, B13 and B14 and B21, B22, B23, B24 and B31, B32, B33, B34 and B41, B42, B43 and B44. So this is the resultant matrix. I mean second matrix. Now what is the order of this one? This is a 4 by 4 and this is a 4 by 4. So we have to check whether the multiplication is possible because the columns of first matrix should be equal with the rows of second matrix. So here 4 and 4 both are equal. Then the matrix multiplication is possible. And the second one, if the order is in power of 2, then we can apply the divide and conquer. Yes, the order is in power of 2. So 2 square, 2 square, 2 square, 2 square. Then what we have to do? So we have to divide it with a 2. We have to divide it with a 2 so that we'll be getting a lot of 2 by 2 matrices. So simply make it a half. Make an array as a half. So what we'll be observing? So this is one 2 by 2 matrix. This is another. This is another. This is another. So we are getting a 4 2 by 2 matrices. And here also we are getting 4 different 2 by 2 matrices. So you can represent it as A11, A12, A13, A14. So I'll round it. Okay. I'll round it. And similarly, this is a B11, B12, B21, B22. Again, I'll round these things. Okay, so previously we are saying the same thing: A11, B11, A11, A12, B21, B22, B11, B21, B12, and B22. So all these are the values, but here we are saying A11, A12, B11, B12, similarly A13, A14. All these are the matrices, not the values. So for differentiating, I am representing the small letters indicates the values, uppercase letters indicating the matrices. So here we are having 4 different matrices. So you can apply the same formula for calculating this one. So instead of using small a, you can also give a capital A. Okay, you can use a capital A, right? So same. You can apply the same thing. So C11 is equal to capital A11 and into B11 plus A12 into B21. So here the multiplication is in between 2 by 2 matrices. Again we are applying matrices, but here it is a values. Now up to where we have to divide it. For example, if it is 4 by 4, we are dividing into 2. What about if it is 8 by 8? Then it should be divided 2 times. First it will be 4 and then it will be 2. So we have to write down these one in a recursive call. So we are dividing up to where we have to divide up to whenever the order becomes 2. Whenever the order becomes 2, we can stop dividing, right? So I'll write the formula. So hope you understood. Small letters represents the values, capital letter represents the matrices. So in the multiplication also same thing happens. So C11, so instead of small a, use a capital A. C12, instead of small a, use a capital A. Instead of small b, use a capital B. So same thing will be repeated. Now I'll write the algorithm for this particular divide and conquer method. So what we have to do? So we have to write. For example, I will write it as matrix multiplication, and it takes 3 parameters. So number of parameters, it depends upon your logic. So I'm taking a, comma, b, comma, the order of this one, because it is a square matrix, and also this is a power of 2, so I'm giving only n. So the order of matrix will be n by n. So what we are doing, if n is equal to 2, what we have to do? So in this case, we have to write down all these formulas: C11, C12, C21, C22. So we have to write down all the formula, whatever the formula we are writing here. So the same formula will be written here. So if the order is 2 by 2, then it will be the general method, right? So what is the general method? This is the general method you are using, right? So you can write all these things. And if it is else, then what we have to do? So we have to recursively call this one. We have to recursively call this one by dividing the order by 2. So simply what we can do, so we can call the recursive matrix multiplication with what's the values? So A11 comma B11 comma n by 2 plus, okay, and similarly matrix multiplication of A12 comma B21 n by 2. Okay, so this is a formula. See, simply we are, okay, so here these are the values, but these are the matrices. So first we have to calculate this matrix value, and then we have to add with the other value. So whatever the things we are writing here, that will be recursively called here. So first we have to calculate the matrix multiplication for two matrices A and B, and then again two matrices A and B. Similarly, the next one, matrix multiplication of A11 comma B12 with n by 2, and again matrix multiplication of A12 comma B22 with n by 2. Similarly, matrix multiplication of A21 comma B11 n by 2 plus matrix multiplication of A22 comma B21 n by 2. Similarly, the last recursive call, matrix multiplication of A21 comma B12 comma n by 2 plus matrix multiplication of A22 comma B22 n by 2. So these are all the different recursive calls. First we are dividing, and we are dividing the matrix until the order reaches to 2 by 2. So if n is equal to 2, then we are applying the same thing here. Okay, we are applying the same thing here. Else, okay, if n is not equal to 2, again we are subdividing, again we are dividing the problem with n by 2 times. Okay, so you can see what is the time complexity for this one. What will be the time complexity for this one? So the time complexity for this one will be, count the matrix multiplications, how many multiplications it requires. So you can see this is 1 multiplication, 2, 3, 4, 5, 6, 7, and 8. 8 multiplications are required here. So 8 multiplications for every n by 2 terms. Okay, so we are dividing, okay, and we are solving. Every division we are solving, right? So we are saying it as a 8 into t of n by 2. That is the number of multiplications. Now what about the other operators? That is the addition. So 1, 2, 3, and 4. 4 additions. So this is normal value addition. Okay, no problem. Coming to here, so this addition is, so whatever the addition we are writing here, it is in between the matrices, because here these are the values. Here capital A11 B11 means it's a matrix, and these two are the addition of two matrices, but here the addition of two values. So we have to consider this one. So if for adding of two matrices, what will be the time complexity? So we are using two different for loops. Okay, two different for loops, and one constraint is both the orders should be same. So two for loops will be there. Two for loops are independent for loops. So obviously that will be n square. Okay, n square, right? So n square. And how many additions are required? 4 additions are required here. 4 additions are required. So we can simply write it as a 4 addition, right? So that may be varied. So you can give it as a constant like a into n square. A into n square. Okay, so this is for multiplications and this is for additions. This is for additions. Multiplications 8 into t of n by 2 plus a of n square. Now calculate the recurrence relation. So first calculate n by 2. So which will be 8 into t of n by 4 plus a n square by 4. In the place of n, we are giving n by 4. And if it is further divided, we will be writing t of n by 4. So calculate here. So 8 into t of n by 8 plus a into n square by 16. And again, if it is further divided, it will be t of n by 8. Then 8 into t of n by 16 plus a into n square by 64. Right? And this will be keep on going. So first let us consider only these things. Analyzing the algorithm, right? So this is algorithm. Now we are finding the time complexity. So we can use a recurrence relation. So I am substituting this value in this one. So obviously it will become t of n is equal to 8 into, so in the place of this one we have to write all these things. So 8 t of n by 4 plus a into n square by 4 plus a n square. So here it will be written as 8 square t of n by 4 plus 8 into a n square by 4 plus a n square. Now what happens? So this is the t of n. Now you can use t of n by 4, this one in this position. Okay. So substitute this t of n by 4 here. So t of n is equal to 8 square, and here what is this one? 8 t of n by 8 plus a into n square by 16 plus a n square into 8 by 4 plus a n square. And you can elaborate 8 cube t of n by 8 plus 8 square into a n square by 16 plus 8 into a n square by 4 plus a n square. And this can be written as 8 cube t of n by 2 cube plus a n square into, okay, a n square into 1 plus 8 by 4 plus, here it is 8 square by 16, which can be written as 8 by 4 whole square. So 8 by 4 whole square. So this is in the form of 8 power k t of n by 2 power k plus a n square into 8 by 4 power k. 8 by 4 power k. So this is the time complexity after recurrence relation, and this process will be keep on going, and where it will be stopped. So this process will be stopped. That means a division will be stopped when n by 2 power k is equal to 2. Okay. So whenever it becomes n by 2k is equal to 2. So whenever the order becomes 2, we'll be stopping. So this becomes n is equal to 2 power k plus 1. So k plus 1 is equal to log n base 2. So k is equal to log n base 2 plus 1, and you can avoid the constant, and simply we can say k is equal to log n base 2. And simply you can apply this one here. You can apply this particular thing here itself. So after applying here, so I'll use this one, k is equal to log n base 2. Hope you understood. Let us take t of n is equal to 8 power k, 8 power log n base 2, t of n by 2 power k means n, right? So here we have said n is equal to 2 power k. So 2 power k means n plus a n square 8 by 4 power log n, Okay. Now what we can do? So this can be written as a 2 cube into log n base 2, and this becomes 1. This becomes 1 plus a n square, and you can write it as 8 power log n by 4 power log n, which is a base 2. So which will be n cube. Okay, just refer the logarithmic formulas. So it becomes n cube plus a n square into, and this is also n cube by n square. So this is in the formula. So 2 power log n cube 2. So which will be written as n cube. Okay, this can be written as 2 power log n cube 2 base 2. So if these 2 equal, then it will be n cube. So directly I have taken it as a n cube. So this can be removed, and this will be n cube plus a into n cube, and the order, highest order is t of n is n cube only. So order of n cube. The highest order, we have to consider highest order, so which is order of n cube. See, if you are using the general method, we got the time complexity as order of n cube. And if you are using the divide and conquer, then also we are getting the order of n cube. So there is no difference. So of using general method and the divide and conquer method. So then what we have to do in order to reduce the time complexity? So here also the time complexity will be order of n cube only. Order of n cube only. So that both are equal. Applying the same method is having equal time complexity. That is the order of n cube. So in order to reduce this time complexity of order of n cube, we are going to use this Strassen matrix multiplication. Okay, so where we'll be having some formulas, and with the help of that formulas, we are going to reduce the time complexity from order of n cube to lower one. Okay, now I'll write the formulas. Just relax. So this is the Strassen matrix multiplication. So everything has been reduced, and we are applying these kind of formula for finding the solution, right? So we are taking some 7 values from P1 to P7, and we are applying these formula to find out the C11, C12, C21, C22. So all these things are the resultant matrix. All these things are the resultant matrix. Right? So in order to find out the C11, we have to add P5 plus P4 minus P2 plus P6. So what is the P5 means? Here this is a P5. A11 plus A22 into B11 plus B22. So like that we are taking some 7 variables or 7 formula, and using these 7 formula we are finding out the resultant matrix. So this is the Strassen formula. Okay, this is the Strassen formula. This is Strassen. Okay, now you calculate. The remaining is same. Okay, whatever the information, whatever we have learned, everything is same. So, but instead of using all these kind of things, we are using this one. Okay, so if n is greater than 2, we are dividing it, and we are calling the recursive calls. Everything is same, but what is the difference means here we are using this formula instead of that one. So because this one is having some 8 multiplications and some 4 or something else additions, right? But here we are having how many multiplications? You can count 1, 2, 3, 4, 5, 6, 7. So one multiplication has been reduced. Total multiplications are only 7 multiplications. Okay, the multiplications are reduced. So here the main complexity is to find the multiplication, not the addition and subtraction. Right? So if you apply the same thing instead of this one, so what will be the time complexity? You can say T of n is equal to, earlier it will be 8 into T of n by 2 because of multiplications. Now it will be 7 into T of n by 2 plus the addition is common, right? If you are performing some addition, the time complexity will be n square, and the number of additions and subtractions will be represented with a constant, so it will be a into n square. So this is the time complexity for Strassen multiplication, not for the divide and conquer general method. It is for Strassen multiplication. Now again use the same recursive relation. So first let us find n by 2. So it will be 7 t of n by 4 plus a into n square by 4, and similarly use n by 4. So this is also further divided, right? N by 4 is equal to 7 t of n by 8 plus a n square by 16, and this will be keep on moving. N by 4, n by 8, n by 16, n by 32, etc., until it reaches n by 2k. N by 2k reaches to 2. So which is nothing but, so earlier we have calculated k is equal to log n base 2. So till this we are going to divide this one. Now we'll apply the same thing for the instead of t of n by 2. So recurrence relation, amortized analysis, right? So I'm erasing this formula. Just note down these formulas. So in this Strassen we have to use these formulas instead of that one. Okay. Now, so here the main we are using, so we are reducing the multiplications, number of multiplications in the Strassen method other than the general and the divide and conquer. Obviously the time complexity should be reduced. So previously the time complexity is order of n cube in both general method and divide and conquer. Now we'll see what happens. So I'm substituting this t n by 2 here. So t of n is equal to 7, and what is this one? 7 into t of n by 4 plus a n square by 4 plus a n square, and this can be written as 7 square t n by 4 plus 7 into a n square by 4 plus a n square. What happens? Now again we can calculate n by 4 here. Okay, recurrence. So t of n is equal to 7 square, and write down all these things in the place of t of n by 4. So 7 into t of n by 8 plus a n square by 16 plus a n square into 7 by 4 plus a n square. Now you can elaborate this one. 7 cube t of n by 2 cube plus 7 square, sorry, a n square 7 square by 16 plus a n square 7 by 4 plus a n square. So this can be written as, so this will be keep on moving, right? So again, if you calculate n by 8, you can replace this n by 8 with the calculated one, right? So it will be replacing everything. So it will be keep on moving until it reaches to this one. N by 2k reaches to here. So I'm writing the generalized thing. So 7 power k and t of n by 2 power k plus a n square into, so this will be in the form 1 plus 7 by 4 plus 7 by 4 square. Right? And this can be written as t of n is equal to 7 power k t of n by 2k plus a n square and 7 by 4 power k. So this is a generalized thing, and this will be keep on moving until this n by 2 power k reaches to 2. So that becomes k is equal to log n base 2. Log n base 2. So you can replace this n and k values in this one. You can replace k value here. So t of n is equal to 7 power k. K is log n. So 7 power log n base 2 t of n by 2 power k. 2 power k is nothing but n. So avoid the constants. Okay, avoid the constants. Plus a into n square 7 by 4 power log n base 2. So what happens here? 7 power log n base 2, and this becomes 1 plus a n square into 7 power log n base 2 divided by 4 power log n base 2. So which can be written as n power log 7 base 2 plus a n square by using the logarithmic formula. So it becomes n power log 7 base 2, and it will be again n power log 7 base 2 divided by n square. So this becomes 2 square log n base 2, and this 2 becomes here n square, and it becomes n square. So directly I have taken this one, right? So this can be erased, and it will be n power log 7 base 2 plus a into n power log 7 base 2. So you can consider only the highest degree, so you can consider anything. So t power n is equal to order of n power log 7 base 2, okay, so which is nothing but order of n power some 2.81. okay, so log 7 value, once check out what is the log 7 value, that is around 2 point something, which is less than 3. Okay, that's important. So now you can see by using this Strassen matrix multiplication, we are reducing the multiplications, number of multiplications, so that we are also reducing the time complexity. So here it is order of n cube, and by using Strassen it will be order of n power 2.81, so which is less than 3, So automatically some sort of time complexity has been reduced if you use this Strassen matrix multiplication. So now you can check, so consider some 2 by 2 order matrix and use the general method for calculating the matrix multiplication, and also use this Strassen matrix multiplication method, use the formulas to solve and find out the solutions. You need to get the equal solution, the same solution, by using the general method as well as the Strassen. But here the computation time will be less when compared to the general method or the divide and conquer, which is n cube in divide and conquer, which is n power 2.81 or 18, so which is less than 3 in Strassen matrix multiplication method. Right? So this is how we can use this Strassen matrix multiplication, which is, we can also say, the example or application for divide and conquer. Previous sessions we have seen one methodology, that is divide and conquer, where we are going to divide the complete problem into different parts, and recursively we are going to solve each and every problem, and after that integrating all the solutions will give the main solution. And for that we have seen different examples or applications. Right? Now we'll say one more concept of this solving a problem, that is a greedy method. So this is one more methodology in order to solve the problem, right? And this greedy method is mainly used to solve the optimization problems, right? So it's mainly used to solve optimization problems. Now here the question is, what is meant by this optimization? So optimization, that means, so selecting the best solution among multiple alternatives. Okay, so we are having a lot of alternatives, so we need to select the best solution or the worst solution. So for every problem there might be having some constraint or may not be having the constraint. So based upon that constraint we need to select one option from the alternates. So that such type of problems we call it as an optimization. So optimization problem means it is a problem which can have multiple alternates. So usually these multiple solutions will be considered in a subset. Okay, that means a set of solutions. So the procedure or a process which gives a solution, or the procedure which gives the better result, is known as feasible solution. Feasible solution, right? So a normal solution, whether it may be best or worst or minimal or maximum, whatever it may be, the solution for a problem is called as a feasible solution. And the collection of all these feasible solutions will be in a subset. Okay, so there will be a set of feasible solutions. And from these feasible solutions, based upon the constraint, so we can select one solution, and that will be the optimal solution, or we can call it as a best solution. So the best solution among set of feasible solutions is known as optimal solution. Okay, so don't get confused among these two, optimal solution and feasible solution. So any solution can be considered as a feasible solution, and based upon the constraint, selecting one best solution among these feasible solutions is called as an optimal solution. So that's why we call it as an optimization problem. So we need to select the best solution from these feasible solutions, right? So let us take an example, simple example that you can understand, right? So here the real world problem is traveling from city A to city B. Okay, so there is one road, so through streets, okay, through the streets, and there is one more way, which is a bypass. Okay, so there are two solutions. So we can travel from city A to city B among these two paths. Okay, so the feasible solution is through streets and through bypass. So here you can see feasible solutions are, one is a bypass, so using the bypass, and another one is by using streets. For example, if we use a bypass, let us consider some 15 kilometers, and if you use streets, let us assume that 10 kilometers, the distance, okay, 10 kilometers. Now, which path we need to select? So here, constraint, consider a constraint. Okay, based upon the constraints, we are going to select either bypass or street. So if you use a bypass, less traffic will be there, less traffic. And if you use streets, obviously there will be a traffic, and also there will be some signals, traffic signals. So if you use a bypass, it may take a less than 1 hour time, and if you use the traffic signals, it may or may not take. So it may take greater than or equal to 1 hour. So if you want to reach the destination within a short period, within a short time, so without any traffic, you can select this one. And if you had any work in between the city, in between the streets, then you need to use this streets. So that means we are having multiple solutions, okay, multiple alternatives. So based upon the constraints. So if you had some work, okay, if you had some work in between city, so we need to go through streets. If you are not having any work, and if you want to reach quickly without, avoiding the traffic signals, we can choose this bypass. So this type of problems, we can call it as an optimization problem, and these optimization problems can be solved by using this greedy method. Right? So hope you understood the procedure. Now, what are the applications? That means where we are going to use this greedy methods. Few applications. Okay, so few applications. Few applications where we are going to use this greedy method. The first one is a selection sort. So in order to arrange the elements in a sorted order using the selection sort mechanism, we'll use this greedy method. And just now we have seen finding shortest path. Finding shortest path. For example, consider a graph. So we are having A and B, some 5 and 10 and 6 and 5 and 7. Now, see, if you want to reach from A to C, you can see you can reach C through B. So total cost will be 15. So A to C via B, it is 16. A to C directly 6, and A to C via D, it will be 12. So which one will be the shortest? So 6 will be the shortest. So in all these 3 cases, we can reach the destination, but the constraint is minimum shortest path. Okay, so finding the shortest path with the minimum distance. And such type of problems, we are going to use this greedy method. And then fractional knapsack problem, job sequencing. Okay, so finding minimum spanning tree, minimal spanning tree. So there are 2 approaches by using a Kruskal's or Prim's algorithm. So minimum spanning tree. So all these are the few applications where we are going to use this greedy method. So in our further sessions, we'll see one by one. So how we can apply the greedy method and how we can find the solution for all these applications. Right? So let me explain you about one example, and I will wind up about this introduction of greedy method. Right? So example, for understanding, I'll give the example. So I'm taking one example which you frequently listen. So that means I'm having some 25 rupees. Okay, 25 rupees, and I need a change. Okay, need change with minimum number of coins. Minimum number of coins. So coins available. So 5 rupees, 2 rupees, and 1 rupee. So there are 3 possible coins. So we need to get a change for 25 rupees with the minimum number of coins. So the solution 1 is, see, 5 into 5 rupees. Okay, that means it requires 5 coins. Solution 2, we can take 4 into 5 plus 4 5 is 20, 2 into 2 rupees plus 1 into 1 rupee. So how many coins it requires? 4 plus 2, 6 plus 1. So it requires total 7 coins. And simply we can say solution 3, so 25 into 1 rupee, which requires 25 coins. Similarly, solution 4, we can have 2 into 5 rupees, 10, and 10 into 2 rupees, sorry, again 5. 5 into 2 rupees, so 10, 20, 10 plus 10, 20, and 5 into 1 rupee. So total how many coins? 2 plus 5 plus 1, 5, 12 coins. So there are a lot of possibilities. So using 5 coins, we can get a change for 25 rupees. Using 4 5 rupees coins and 2 2 rupees coins and 1 1 rupee coin, still we can get the 25 change for 25 rupees, but it requires 7 coins. And still we can get a 25 1 rupee coins. So to get a 25, so it requires 25 coins. And here, in order to get the 25, we can have a 2 5 rupees coins, 5 2 rupees coins, and 5 1 rupees coins. So obviously we can get the 25 change for 25 with the 12 coins. So that will be keep on moving. These are all the feasible solutions. In all these cases, we are getting the solution, right? But what is the constraint here? Minimum number of coins. This is the constraint. Okay, so this one will be the constraint. So we have to satisfy this constraint. So based upon that constraint, we can select this optimal solution among all the feasible solutions. Among all the feasible solutions, we can select the optimal solution. So this is the procedure of finding the solution for optimization problem. Okay, this procedure we call it as a greedy method. So based upon the constraint, getting the best solution or optimal solution. Okay, so if there is no constraint, so anything can be accepted. We can accept anything. Either it may be the best solution or the worst solution. Whatever it may be, we can accept anything. If there is no constraint for a problem, if there is a constraint for a problem, obviously from the multiple alternatives we have to select the best solution which satisfies the given constraint. Right? So let's stop here. Hope you understood the introduction to this greedy method. So let us move on with the next concepts of applications, explaining the applications using this greedy method from the further sessions. So today we'll discuss about an application of a greedy method. So that is job sequencing with deadlines. So we have seen the introductory part of a greedy method, so which is mainly used to solve the optimization problems. So optimization problem means having more than one solution and selecting the solution based upon the constraint. So that is called as a greedy method, and one application of applying this greedy method is job sequencing with deadlines. So first let us understand the problem and then we'll move on with the solution, the procedure, how we can solve the problem. So the problem is job sequencing with deadlines. So here you can understand with the name, that is a job sequencing with deadlines. So here we'll be having the first one, jobs, the number of jobs. So we can consider them as a process, number of processes we need to execute. And second one is a profit. So profit means so which we can profit after completion of the each and every job. Okay, so or we can say it as a cost. Okay, the cost. And the third one is deadline. So the name itself indicates for every process or for every job there will be a deadline. So that particular job should be completed within that particular deadline. Okay, so these three are most important in this job sequencing problem. So we need to complete the processes or jobs within the given deadline with a maximum of profit. With a maximum of profit. Okay, so that is our problem. That is our problem. And here we need to remember a few points, most important points. See, so before going for the solution for this job sequencing, the first point we need to remember is only one processor. We are going to execute on only one processor. So one processor will have to execute all the jobs. Okay, then no preemption. No preemption. So if you are aware about the scheduling algorithms, you might be knowing about this preemption and non-preemption. So preemption means, so if there is any job with the highest priority, then the executed process will be put on hold and the CPU will be given to the highest priority processor. So that will not be done in this job sequencing. That means once the job is assigned to the processor, it have to complete, and that means the remaining jobs have to wait until the job gets completed by the processor. So no preemption. So once a job is given to the processor, so we have to wait until it completes its execution. So no preemption, no preemption. Okay, so mainly these things, and one more, sorry. So every job takes 1 unit of time, 1 unit of time to complete. Okay, 1 unit for completion. So every job takes only 1 unit for completion. Okay, so don't get confused about this deadline and this 1 unit. So deadline means the complete time, so upon which the job has to be get completed. Okay, so but every job takes only 1 unit. 1 unit. Now, see, these three things are the most important and we have to remember before applying the job sequencing. Only one processor, no preemption, and every job takes 1 unit for completion. Right? Yes. Now, we'll see the procedure, or we can call it as an algorithm. So the first step, let us take an example, then we'll move on with the algorithm. So, first we'll go with the example so that you will be understanding perfectly. Example. So let us take a number of jobs. Let us consider 5 jobs, J2, J3, J4 and J5. So these are jobs. And the second point is a profit. How much profit we'll get after completion of the particular job. Let us take this as 15, 10, 20, 25 and 5. This is a profit. Okay, this is a profit. And the third one is the most important, that is a deadline. Okay, so deadline. Let us take 2, 1, 3, 3, 2. Okay, let us say randomly I have taken this one, right? So this is a deadline. So we have assumed that only one processor, no preemption, and the last point is every job will take 1 unit for its completion. So let us assume that this is a 2 units. This is a 1 unit, 3 units, 3 units, and 2 units. Now, what's the process we have to do? So first we have to find out the maximum deadline, max deadline. So what's the maximum deadline here? So in order to avoid the confusion, let us take it as 3 and let it take it as 1. Okay, right. Maximum deadline among all the deadlines. What's the maximum? So the maximum is 3. So 3. Now we have to draw the Gantt chart. Gantt chart means we need to draw this one. See. So this is Gantt chart 0, 1, 2, and 3. See, this is 1, this is 1, 2, and 3. So 3 units. You can assume that this is a 3 units. And we need to complete the jobs with the highest, more priority, with more number of priority, right? Now, what do we have to do? The next one, sort all the jobs in a descending order with respect to the profit. So sort in descending with respect to profit. Okay, profit. Now rearrange the jobs based upon the deadlines. First, what's the highest? 25. So J4 will be the first with the 25, and the deadline is 3. What's the next one? 20. So J3 21. So J3 21. Next 15. J1 15 2. J1 15 2. Next J2 10 1. J2 10 1. Next J5 5 and 2. So we have arranged the complete jobs in a descending order with respect to the profits. See, for example, let us consider this was not done. Okay, this was not done. So in an order, complete the jobs. So J1 should be completed within a 2 deadline. So let us take here J1 with a profit 15 and J2 with a 1 block, but it doesn't happen here because during the first unit J1 will be completed. So J3 it is also not completed. Next we can go with the J4 with a 25 profit and J5 with a 5 profit. So you can complete the J1, J4, J5, the 3 processes with a profit. So 15 plus 25 plus 5. So which is nothing but 45. Okay, and also we can complete. See, we can complete J1. Next J4. Okay, sorry, already we have done. So we can complete here J2, J3, and J4. Right. So first J2 will be taken here. J3 we can complete. J4 we can complete, and the profit will be 10 plus 20 plus 25. Okay. So here we will be having a lot of solutions, and we can't say that this will be the optimal solution. Okay. So there will be a lot of solutions. So we can execute J1, J4, J5. We can execute J2, J3, and J1. We can execute J2, J3, J5, etc., etc. Right. So what happens here? So we need to select the optimal solution based upon the constraint. So here what is the constraint? We need to get the maximum profit. Maximum profit. Now, in order to find out that maximum profit, we are going to see this process. Sort in a descending with respect to the profit. So this we have done. Now what we are doing? So first J4, the first process with the highest profit. So the constraint is a profit, highest profit. So based upon the profit, we are arranging the jobs in a descending order. So what is the maximum deadline limit? 3. So we can assign J4 in the last one. J4 with a 25. Okay, hope you understood. So the maximum deadline to complete the job 4 is 3. So we are going to select the third one. That is the last option. Okay, the third unit. So the profit will be 25. So this completed. Next, J3 with the highest priority. So because this is a descending order. So 20 is the next priority. And this J3 should be completed with a 1 unit. Okay, deadline is 1. So we can't assign J3 here. Because after 1 we can't assign it. Because 1 is the deadline. So J3 will be assigned here. J3 will be assigned here with a 20 profit. Next, J1, 15. That's the third highest profit. And what we are doing? This is 2 is the deadline. So here we can assign the J1. So what is the highest profit? 15. So 15 is the profit. Now the overall profit of completing the 3 jobs, J3, J1, J4. What's the profit here? So 20 plus 15 plus 25. So what happens here? So 35 and it will be 60. So 60 is the highest profit in order to complete the jobs. Okay, so this is how we have to solve the job sequencing using the greedy method. So greedy method means we'll get the alternate solutions, and from that alternate solution based upon the constraint, we are going to select the best or optimal solution. So here also we can execute J1, J2, J3 or J2, J3, J5 in these 3 slots, or J2, J4 and J5, or J2, J1 and J4. So there are a lot of options. Okay, we can complete. So let us say J2, J4, J5. So this is one solution. Okay, executing all these, completing all these 3 jobs with a particular profit. What's the profit here? J2 10, J4 25, so 35, and it's a 40. And also you can go with the J2, J1, and J4, J2 10, 15, 25, and 25. It will be 50. So in both the cases, we will get the profit. But the constraint is getting the best solution or optimal solution based upon the constraint. Constraint is the highest cost, okay, with a high cost. So for that we have done, so the highest profit, high profit is 60 by executing J3, J1 and J4, 3 jobs. Okay, so this is how we can solve the job sequencing with deadlines problem. Okay, now we'll go with the algorithm. Hope you understood this one. So take a few more jobs, let us take some 10 jobs and try to solve the problem so that you will be understanding more, right? So now I'll write the algorithm and I'll wind up. Okay, so algorithm. So step 1, what is step 1? We need to find out the maximum deadline. Find maximum deadline. And step 2, what is step 2? So after finding the maximum deadline, we need to draw the Gantt chart. Draw Gantt chart with maximum deadline. Maximum deadline. So we have drawn. And step 3, after completion of this Gantt chart, we need to sort the jobs according to profits. Sort all jobs with respect to profits. Step 4, what we have to do? So we have to find out the appropriate slot to fix the job. Search empty slot to fix job. To fix job. Okay, so we having or in a deadline near to its maximum. Near to its maximum. So this is the process we are going to do, right, for solving the job sequencing with deadlines. So here, the time complexity for this one. Time complexity. So first we are going to sort out this one. Okay, only 2 steps. So sorting all the jobs with respect to the profits, which will give the order of n log n. So we can apply any sorting mechanism, quick sort or bubble sort, anything. So I go with the quick sort, okay, because we have seen in our previous sessions by using the divide and conquer. So it will be order of n log n plus what we are doing, searching the empty slot to fix the job in a deadline near to its maximum. Near to its deadline, okay, right? So how many searches we have to do? So if there are n jobs, we have to search for n slots, okay. So obviously it will be order of n square. So n jobs, n slots, okay, m jobs and n slots, or n jobs and n slots, whatever it may be, no problem. So it will be order of n square, order of n square. So the highest degree, what is the highest degree? This one. So the time complexity is order of n square, for this job sequencing with deadlines. And we have followed the greedy method. So that means finding or getting the feasible solutions, and from that feasible solutions we are selecting the optimal or best solution. So first let us see what is this spanning tree, and then we'll go with the construction of this spanning tree. So a spanning tree is a subgraph. So we all know about the graphs. So graphs are nothing but connected nodes with the edges with the cycles, right? So the spanning tree is a subgraph of a graph with the vertices and edges. So a graph will be having the vertices and edges with the cycles, right? But here the tree means it's a subgraph with no cycles. So here, if it is not having any cycles, we call it as a tree, right? Now, so we need to follow a few points or a few rules while constructing this spanning tree. The first one is, so the spanning tree should connect all vertices of a graph, right? So it should contain all the vertices which are available in the graph in the spanning tree. And the second one, if graph is having n vertices, then the spanning tree should have n minus 1 edges, right? So n vertices in the graph, then spanning tree will be having n minus 1 edges. And the third one should not contain any cycles. So we need to follow these rules while constructing the spanning tree, right? So let us take one example, so graph, and we'll see how to construct the spanning trees. So first we'll consider the graph, and then we'll construct the spanning trees from that particular graph. See, so we have to follow all the rules, right? So let us take an example with the 4 nodes. So A, B, C, and D. So these are the 4 nodes, and this is a connection between all these nodes. So this is a graph, okay? So edges, vertices, and cycles, right? So now we should construct the spanning tree. So what is the first rule? First rule is number of vertices should be equal. number of vertices must be equal in both the graph and spanning tree. So we have to connect all the edges. We need to connect all the edges. So I'm writing all the edges here. Next, so these, if there are 4 vertices, we should connect with 4 minus 1 edges. So I will connect this one. So A to B, A to C, and C to D. So this is a construction, right? So you can observe here, we are having a 4 vertices, and the edges are 4 minus 1, that is 3 edges. So this is one spanning tree. And another case, let us see, A, B, C, D. So let us consider this one. So this is also a possible spanning tree from this particular graph, right? So because all the edges, all the vertices has been connected, and the number of edges are n minus 1, that is 4 minus 1, and there is no cycle, right? And one more possibility. So this is one more possibility, right? So here also all the 4 vertices has been connected with n minus 1 edges, and there is one more possibility here. So this is one more possibility. Here also all the 4 edges, 4 vertices has been connected with 3 edges, because we are having 4 vertices, so the number of edges must be 4 minus 1. So this is a cyclic graph, and this is a acyclic graph. Acyclic graph is nothing but our trees, right? So all these are the spanning trees. Okay, all these are the spanning trees, right? So one graph can have a multiple spanning trees. So here we can have the 4 possibilities, right? And if you consider one more example, like a triangle shape. So this is a graph. So we are having 3 vertices and 3 edges, so that it's a graph. So this can be constructed as, so A to B, B to C, A to C, C to B, right? And A to B and C. So these are all the different possibilities of spanning trees can be constructed from this particular graph, right? So hope you got an idea about this spanning tree. What exactly this spanning tree? Spanning tree is a subgraph from the original graph. So with n vertices and n minus 1 edges, right? So we need to follow the 3 points. One is all the vertices should be connected, and if n vertices are there, n minus 1 edges should be there, and there should be no cycles. So this is all about our spanning tree. Now, what is the minimum spanning tree? Now let us see the concept of minimum spanning tree. So minimum cost spanning tree. So it is called as a minimum cost spanning tree. So let us consider the graph A, B, C, and this one. This is a graph, right? This is a graph. So each edge will be having a cost. Each edge will be having a cost. We can also call it as a weight for particular edge. Let us take here some 5, some 2, some 3. So the cost of an edge A to B is 5. The cost of an edge from B to C is 3. The cost of an edge from A to C is 2. Now construct the possible spanning trees. So the possible spanning trees are A to B, B to C, A to B, A to C, A to C, C to B. So these are all the possible spanning trees, right? All the possible spanning trees. Give the edges here. So 5 and 2, sorry 3. And here 5 and 2. 3 and 2. So now you have to, so you can observe here all the vertices has been connected. Okay, all the vertices has been connected, and here also all the vertices has been connected, and here also all the vertices has been connected. Right? So here you can see there is an edge A to B, B to C. There should not be a cycle, right? So here it is A to B, B to C. So if you add one edge from C to A, so what happens? The starting vertices and the end vertices same. That means it forms a cycle. So we should not connect this one. So that's why we are not connecting, and this is a spanning tree, right? Now cost for this spanning tree is 5 plus 3, 8, because there are 2 edges with a weight 5 and 3. The cost of this particular spanning tree is 8, and the cost for this one is 7, 5 plus 2. So the cost for this one is 3 plus 2, it's a 5. So you can observe here, for every spanning tree we are finding the cost. So here the cost is 8, cost is 7, cost is 5. Now we need to select the minimum cost spanning tree. So we will select the minimum cost spanning tree. That means the tree with a minimum cost of edges, right? So minimum weighted edges. So here there are 2 approaches to find the minimum cost spanning tree from a graph. So that is, one is a Prim's algorithm, another one is a Kruskal's algorithm. So in today's session we'll discuss about the Prim's algorithm. So before applying the Prim's algorithm on the graph, make sure that the graph should be weighted, connected, and undirected. So unless the graph is weighted, connected, or undirected, so we can't apply the Prim's algorithm. So make sure the first point before applying the Prim's algorithm. So the graph should be weighted, connected, and undirected. And coming to the steps. So first we need to consider any vertex, because so we know the spanning tree definition. Spanning tree is a subgraph from the graph without any cycles, consisting of all the vertices of a graph, right? So consider any vertex of the graph. And the second step, find all the edges from the selected vertex to all the new vertices. So find all the edges. So among all the edges, you need to select the least weighted edge. So among all the edges, we need to find the least weighted edge and include it in a tree. So we need to construct a tree for that selected vertex and give in the least weighted edge. And if the least weighted edge forms a cycle, so if you include this least weighted edge into a tree, and if it forms a cycle, then simply discard. So if it forms a cycle, then simply discard that one and consider the next least weighted edge. So once you find the least weighted edge, you have to include it in a tree. So after including it in a tree, if it forms a cycle, simply discard that one and consider the next least weighted edge and include it in tree. And the third step, repeat the same step 2 until all the vertices are included in a tree. So once all the vertices are included, automatically that will be the minimum cost spanning tree. Right? So this is how we need to find the minimum cost spanning tree with a Prim's algorithm. So here now we'll see an example and we'll find the minimum cost spanning tree by following all these rules. So let us take an example. So consider one graph. So consider this graph. So let us take some weights. So let's take these weights. Okay, this is a graph. Consider this graph. And we need to find the minimum cost spanning tree for this particular graph. So what we have to do, first consider any vertex, So I'll consider A. I will start with A. So this is a A. So I have included this one in the spanning tree. Now consider all the edges from A. So you can see A to B with a cost of 2 and A to C with a cost of 3. Right? A to B with cost 2, A to C with cost 3. So we need to select the least weighted edge because A is having 2 edges. One is from A to B, one is A to C, A to B, A to C. So consider the least weight. So this is the least among these two. So we need to add this B to the spanning tree. Now the spanning tree will be A followed by B. So with the cost 2. So this is the tree. This is the tree. Now what is the new vertex here? B. So what is the remaining vertex? Consider this one A to C with the 3 and consider the edges from B, right? So from B there is a vertex from B to A which is already covered, right? Because this is a undirected. Okay, this is undirected. So B to A is covered. So we need to consider B to C and B to D. So B to C with a cost of 5 and B to D with a cost of 3, right? B to A, B to C, B to D, right? Now what happens among this one? We are having a 2 edges with a minimum cost of 3, so you can select any edge, no problem. So I will select this one B to D. I will select this one B to D. Now the tree will be A. The tree will be A followed by B, B to D. So the edges are 2, 3. Now the spanning tree becomes this one. So in the first step, the spanning tree is this one. That means only one vertex. In the second step, so first step, second step, and this one is the third step. Now consider the remaining edges. What are the remaining edges? A to C with a cost of 3, B to C with a cost of 5. Right? Now D is added here. Now consider the edges of D. So you can see D to B, which is already done because of undirected, right? So you can simply use this one, bidirectional, right? Right. So B to D is completed. Now D to E. So D to E with a cost of 2 and D to F with a cost of 3. Right. So the edges of D are D to B, D to E, and D to F. So among the D to B is completed, right? Now among these, what is the minimum cost? So this one, least weighted edge. So consider this one. Now the spanning tree will be A, edge to B, edge to D, and from D to E. So the cost is 2, 3, and 2. Cost is 2, 3, and 2. Right? And next, what are the remaining edges? Simply right here, A to C with a cost of 3, B to C with a cost of 5, and D to F with a cost of 2. Now E is added. So what are the edges of E? E to D, E to C, E to F. So E to D is completed now. Just discard that one. E to C. So E to C is not there. So we can write the edge E to C with a cost of 4, and E to F with a cost of 5. E to F with a cost of 5. E to F, right? Now among this one is the least weighted edge. D to F. So see, our graph, our tree will be A, B, D, E, and F, right? So this is 2, weight 3, this is again 2, now again it's a 2, right? You can observe here whether all the vertices have been covered or not, A, B, D. So there is no, C is not there, right? So you can continue the process. So what are the remaining edges? A to C with a cost 3, B to C with a cost 5, E to C, D to F is completed. So E to C with a 4, E to F with a 5, right? Next, F, we have reached to F. So the new vertex is F. So write down the vertices of F. So F to D, F to E, right? F to E is completed. So F to D with a cost of 3. Now you can see among all these things, what's the minimum? A to C or F to D? right? F to D is also completed, right? F to D is also completed, so you need not go with this one. And one more thing is F to E, so that's also completed. F to E, we have written F to E here, right? So now among all these things, what is the minimum cost? A to C. So consider A to C and observe whether it is giving the cycle or not, it forms a cycle or not. So if you apply A to C, it doesn't form the cycle, so consider this one. So A to B, D, F, E, C. Right? Now you can give the weightage 2, 3, 2, 2 and 3. So you can observe here A to B with 2, B to D with 3, D to F with 3, D to F with 3. So D to F 3, okay, D to F is 3. So this is D to F with 3 and then D to E is 2 and A to C is 3. So you can observe here all the vertices have been constructed, that means included in the tree. So A, B, C, D, E, F. So here we are having total 6 vertices. 6 vertices, so all the 6 vertices have been included. And now you can observe here the remaining edges. What are the remaining edges? So consider B to C with a 5 and E to C with a 4 and E to F with a 5. So if you consider B to C, so if you add a B to C, it forms a cycle. So we have to discard this one. Right? E to C4, E to C, if you just connect this edge, again there is a cycle. So A, B, D, E, C, A. So again you need to discard this edge. And E to F, again if you connect this edge, E to F, again a cycle forms. So again we need to discard these edges. So we have to discard these edges so that we can have this one. Okay. So hope you got this one. So I think these things are not clear. So I'll write the edges here. E to C with a 4 and E to F with a 5. Right? So I think now it's clear. So we have to consider from the single vertex, you can consider any vertex and consider the edges, all the edges from that vertex to new vertices and consider the least weighted edge. Okay, and continue the process until all the vertices have been connected. So this is the spanning tree, minimum cost spanning tree for the given graph. What's the cost here? So you can observe the cost, I will write here. Cost is equal to, so what is the cost? 3 plus 2 plus 3 plus 3 plus 2. 3, 2, 3, 3, 2. So what is the total cost here? You can observe. So 5, 8, 10, 13. So 13 is the minimum cost for this particular tree. So the cost is 13. The cost is 13 to construct this particular spanning tree. So this is the procedure we need to follow for Prim's algorithm. Okay. So consider a graph and finally we are getting the minimum cost spanning tree. So we'll get a many spanning trees from this graph. So as we discussed in the previous session, right? So we can get a many spanning trees from this graph. But we need to find out the minimum cost spanning tree. So this is the minimum cost spanning tree obtained from this particular graph. So let us consider this graph and now we are supposed to find out the minimum cost spanning tree for this particular graph. So just recalling the steps, the first step we can consider any vertex and the second step we need to find out all the outgoing edges from that vertex to new vertices and consider the least weighted edge and include it on a tree. And after including the least cost weighted edge on the tree, if it forms a cycle, so we have to discard and we need to go for the next least weighted edge. Right? And we need to repeat the same thing until all the vertices are included in a tree. So let's start with this one. So this is a Prim's algorithm. So by using this Prim's algorithm, we are going to find out the minimum cost spanning tree. So first we need to consider any edge, right? So the first step I will go with here. So consider A. Now what are the edges from this A? So edges are like a to D with a 5 and A to F with a 7. And A to B with a 14 and A to C with a 21. So you can see from A we are having a 4 edges, A to B, A to D, A to F, A to B and A to C. Now the next step we need to select the minimum cost edge, right? Least weighted edge. So among these, this is the least cost edge, right? So consider this one. So our next one will be A to D. A to D with a cost of 5. A to D with a cost of 5. Now, what are the remaining edges? Simply write down all the edges. So, one is A to F with a 7 and A to B with a 14 and A to C with a 21. Now, consider the edges from D, right? Because the new vertex included in our tree, D. So, write down the edges from D. So, 2 edges are there. D to A already done. So, D to F. D to F with 13. D to F with 13 and D to E with 22. D to E with 22, right? So among all these edges, so this is the first step. So among all these edges, what is the minimum cost? So 7, 14, 21, 13, 22. So this is the minimum cost. So consider this one. Okay, consider this one, right? Now the graph, the tree becomes A to D with a cost of 5, and from A to F, so the next cost is A to F. So A to F with a cost of 7. So what are the remaining edges? What are the remaining edges? See, after this one, what are the remaining edges? You simply go with this one. So A to B with a 14. Next, A to C with a 21. A to F. So this already happens, right? Sorry, D to F. Okay, D to F. So D to F with a 13, and D to E with a 22. So now we are having a one more vertex, that is F. So now consider the edges of F. So from F we are having how many edges? So 1, 2, 3, 4 and 5. So among all these things, F to A we have completed. So F to D or D to F. This is a biconnected, so F to D or D to F both are equal. You can simply leave. F to E with a cost of 15. F to G with a cost of 18. F to B with a cost of 2. So these are the edges from F. So among all these things, consider the least cost weighted edge. So among these, this is the least cost weighted edge, right? Now the tree will be A, D, F, B, right? So this is 5, and this is 7, and this is 2. Now our tree is like this. Okay, tree is like this. Now the new vertex added here, and consider all the remaining edges. Okay, consider all the remaining edges. So what are the remaining edges here? So all these are the remaining edges. A to B with a 14. Next A to C with a 21, and D to F with a 13, and D to E with a 22. F to E with a 15. Next F to G with a 18. F to B with a 2. So our tree consists of a new vertex B. Now consider all the edges from B. So from B we are having only 2 edges, B to C and B to G, and B to C, B to G, B to F and B to A. Now B to A, so this is already covered. B to F already covered, right? So we should not consider this one because we are already done, right? So this is already done, so we should not consider. So B to F, there is no edge. So B to G 19. So B to G with 19, and B to C with 15. B to C with 15. Consider the least among all these things. What's the least one? So this one is the least. D to F is 13. So D to F is 13. So if you consider D to F, so it forms a cycle. You can observe here, it forms a cycle. So we should discard this D to F. We should discard this D to F, because if you add this one, we'll get a cycle. So we should not consider this one. Next least. So there are 2 edges which are having the next least costed edge. So F to E or B to C. In such cases, you can consider any edge. Okay, here we are having 2 edges with the minimum cost. You can consider any edge. Okay, so I will consider B to C. Now the tree will be like this: A, D, F, B. Okay, so this is 5, this is 7, and this is 2. Now we need to consider B to C. What's the B to C here? Yes, B to C with 15. B to C with 15. Now consider all the remaining edges here. So A of B with a 14, right? So you can observe here. Okay, let us write down. No problem. Next, A to C with a 21, D to E with a 22, and F to E with a 15. Next, F to G with a 18, and B to G with a 19. Because we should not consider this one, because we have already done the edge from B to C. Now there is a new vertex here included in the tree. Now consider the edges of C. So C to B, there is no edge, right? So C to B, sorry. So already C to B there is an edge, right? So C to A there is an edge here already covered. C to B already we have constructed in the tree. C to G is 3. C to G is 3, and C to E is 4. C to E is 4, right? So among 4 edges from C, C to A is already written. C to B already considered in the tree. C to G and C to E. So this is the next one. So we need to select the least cost from this one. So which is C tends to G with a 3. So from C you can construct a G, so which doesn't form the cycle. So now, I will consider here A with a D with a F, B, C and G, right? So the weightages are 5, 7, 2, 15, and the edge is 3 here. Okay, edge is 3. Now we have taken one edge, that is a new vertex G. So what are the remaining edges? See, you can observe here. So A tends to B with a 14, and A tends to C with a 21, D tends to E with a 22, F tends to E with a 15, and F tends to G with a 18, B tends to G with a 19, and C tends to E with a 4. Now the new vertex is G. Now consider from G. So G, we are having 1, 2, 3, 4, and 1, 2, 3, and 4. So first G to F. So is there any edge? There is no edge. So we have to consider G to F. Okay, so let us consider here, right? So G to F with 18. Next, G to B. G to B, there is considered, we have considered, right? G to C. So we have already constructed the tree. So G to E is 2. G to E is 2. So these are the edges. Among all these things, consider the least. So this one is the least, G to E. Now construct the tree with this one. So A, okay, A to B, F to B, B to C, C to G, and the last one is G to E. G to E. So the cost, let's write down the cost. It's a 5, and it is 7, it is 2, it is 15, it is 3, and again the last one is 2. Right? So this is the tree, and now you can observe all the vertices has been covered. So A, B, C, D, E, F, and G. Right? So all the vertices has been covered here. So we can stop here and consider the remaining vertices. So consider this A to B. So we have considered G to E with 2, and we have included the H. Consider A to B. If you consider A to B, it forms a cycle. So we should discard. A to C. If you consider A to CH, right? Again, it's a cycle. D to E. So D to E, again it forms a cycle. F to E. F to E. Again it forms a cycle. C to G. Sorry, F to G. F to G. Again it forms a cycle. B to G. Again it forms a cycle. So C to E. It forms a cycle. G to F. G to F, again it forms a cycle. So all the edges has been covered and all the vertices has been covered here, and now you need to find the minimum cost of this particular tree. So this is the minimum cost spanning tree. So this is a minimum cost spanning tree. So you can see, so we are having all the vertices. Okay, we are having all the vertices, and if the graph is having n edges, sorry, n vertices, the edges should be n minus 1. So how many vertices are there? 1, 2, 3, 4, 5, 6, and 7. 7 vertices are there. So it should have 7 minus 1, 6 edges. So 1, 2, 3, 4, 5, and 6 edges. So it satisfies the spanning tree, and you can apply. I mean, you can see this is the minimum cost spanning tree for this particular graph. And here the minimum cost. Here the minimum cost. I will write here. I will write down here. So the minimum cost is, so how much? 5 plus 7 plus 2 plus 15 plus 3 plus 2. So how much it is? 12, 14, 29, 34. So minimum cost spanning tree. The cost of this particular spanning tree is 34. Right? So hope you understood. First you need to select any vertex and consider all the outgoing edges of that particular vertex to the new vertices, and select the minimum or least weighted edge from the among all the vertices. And if that edge forms a cycle in a tree, discard that edge and consider the next least cost weighted edge. And repeat the same process until all the vertices are included in the tree. So here you can see all the vertices are included in the tree. So we have stopped the procedure, and we have checked all the edges. So all the edges, if you consider any one of the edge, it forms a cycle here. So that's why we have to remove all the edges. We need to discard all the edges, right? So this is how we can find the minimum cost spanning tree by using the Prim's algorithm. And we'll see one algorithm to find the minimum cost spanning tree. That is a Kruskal's algorithm. So in the previous sessions, we have seen one algorithm to find the minimum cost spanning tree, that is a Prim's algorithm. So before going to that, let me revise the previous concepts. That is, what is a spanning tree? So consider a graph, and a spanning tree is a subgraph derived from that particular graph. So with n vertices and n minus 1 edges, right? And minimum cost spanning tree means the spanning tree with a minimum cost. Okay, every edge will be having a cost. So having a minimum cost to construct the tree is called a minimum cost spanning tree. So in order to find out this minimum cost spanning tree, there are two approaches as we have discussed earlier. That is the Prim's algorithm and Kruskal's algorithm. So in the previous sessions we have seen the Prim's algorithm. Now we'll see the Kruskal's algorithm. So here the step 1, the first step means here arrange all the edges in ascending order based on cost. So every edge will be having their own cost. So we need to first arrange all the edges in ascending order based upon the cost. Right? Ascending order means lower value to the higher value. So we need to find the minimum cost spanning tree. So that's why we are using this ascending order. And then step 2, consider least cost weighted edge and include in the tree. Include it in tree. So consider one by one and just include that in a tree. And if the edge forms a cycle, just ignore and consider next least cost weighted edge. Least cost weighted edge. So every time we consider an edge and we have to include that on a tree. So if by adding that edge, if it forms any cycle, so just we have to ignore that edge and consider the next least cost weighted edge, because a tree should not have the cycles. Right? So graph can have the cycles, but a tree should not have the cycles. So here we are using this Kruskal's algorithm to find the minimum cost spanning tree. Right? And the third step, repeat step 2 until all the vertices are included in a tree. So we know the spanning tree, right? So if the graph is having some n vertices, then the spanning tree should have the n vertices with n minus 1 edges, right? So similarly, we have to repeat the step 2 until all the vertices are included in a tree. So by following these steps, we can find the minimum cost spanning tree by using this Kruskal's algorithm, right? So hope you understood this one, and now we'll see an example and we'll find the minimum cost spanning tree. So let us consider this example, and this is a graph, and we need to find the minimum cost spanning tree. So what's the first step? We have to arrange all the edges in an ascending order based upon their cost. So here the least cost among these things are 2. So first let me write all the edges with a 2. So here you can say A to B. A to B is a 2 with a cost 2. So this is a bidirectional, because this is a bidirectional. We can simply consider A to B or B to A. Next, there is one more thing. There is a 2, D to E. Again it is a 2. Next, 3. So we are having A to C. A to C with a 3, and one more B to D with the cost 3, and D to F with the cost 3. Then what about next one? Is a 4. So 4, B to E with a 4, and C to E with a 4. Next one is a 5. So B to C 5, and E to F is 5. So you can observe these are the edges arranged in an ascending order, because you can observe the cost so from lower to higher. Now what's the first step? Consider each and every least costed edge and include it in tree. So first consider A to B. So I'll construct the tree here. So A, B with a cost 2. Next D to E. So D to E. So D to E. So here it is a D. E. So what is this one? D to E, again 2. Next A to C 3. A to C, there is no C, so we have to add it. A to C 3. Next B to D. B to D, so it doesn't form a cycle, right? B to D, so just include that one. B to D, again it is 3. Next D to F, so there is no cycle, so I will construct here F. D to F, it is 3, right? Next B to E, so if you give the edge here B to E, it forms a cycle, right? It forms a cycle, so we should not consider this one. So this should be rejected. C to E, again if you form an edge, if you give an edge, again it forms a cycle, right? A, B, D, E, C, A. So we have to reject that. B to C, again if you form an edge, so it forms a cycle, so we have to reject. E to F, if you consider the edge here, again it forms a cycle, so you have to reject. So you can see in our graph there are 6 vertices, and our spanning tree consists of 6 vertices, right? And here the edges 1, 2, 3, 4, 5, 6, 7, 8 and 9. Okay, so 3, 6, 7, 8, 9 edges. So there are 9 edges. You can observe here 1, 2, 3, 4 and 5. So 5 edges, which is nothing but vertices minus 1, right? If there are n vertices, there should be n minus 1 edges. So it satisfies. Now you can observe all the vertices are covered, so we can consider this as a minimum cost spanning tree, which can be represented as MST, minimum cost spanning tree. So now what is the cost here? Consider cost here. So cost of this one will be 3 plus 2 plus 3 plus 3 plus 2. So the cost will be 5, 8, 11 and 13. So cost is 13. So the minimum cost we can create or construct the spanning tree is with 13. So you just remember, this is the same example we have taken in the Prim's algorithm also. So there also we have constructed the minimum cost spanning tree with a cost of 13. So once just observe the session, so I will post the link in the description so you can follow that one. So that is the procedure of Prim's, and this is the procedure we need to follow for the Kruskal's. So this procedure is Kruskal's algorithm, right? So first we have to arrange all the edges in an ascending order based upon their cost, and then consider each and every edge and construct a tree. And if by adding the edge to the tree, if it forms a cycle, just ignore that and consider the next least cost edge, right? So we have to repeat that one until all the vertices are covered. So here there are 6 vertices, all the 6 vertices have been covered with a cost of 13, right? So hope you understood this one. So this is a Kruskal's algorithm to find the minimum cost spanning tree. Yeah, one more application of greedy method, that is Dijkstra algorithm. So someone will call it as a Dijkstra or Dijkstra. Okay, so today's topic is Dijkstra algorithm. So using greedy method. So we have seen the greedy method. What is a greedy method? So selecting the best or optimal solution from a solution set is called the greedy method. And here the Dijkstra algorithm means finding the shortest path from the source vertex to all the remaining vertex in a graph. So we know that a graph is a connected edges for all the vertices. So for that particular graph, so finding the shortest path from the source node or source vertex to all the remaining vertices. So this is also called as single source shortest path. Single source shortest path. So the main aim is to find shortest path from source vertex to all remaining vertices in a graph. So this graph can be directed or undirected graph, right? So this can be directed graph or undirected. So this algorithm will be suitable for either a directed or undirected. So before going to this one, let's have a small introduction about the graphs. So graphs will be having vertices or vertex and edges. So vertices are represented as a circle and edges are represented with a arrow marks. So this is a directed and this is a undirected. So if you are directing towards some particular vertex, that will be represented with this arrow, and if you are not directing, it will be like this arrow. And widths. So for every edge, so this is a numerical, right? For every edge which connects two vertices will be having some sort of cost, or we call it as a width. Example, a graph A, B, C. So here we are not using this directed, right? This is an undirected graph, and it becomes directed if the graph is in this way. And here the weight of this particular edge which connects the vertex A and vertex B is represented with a numerical. So this is a numerical. So this is called as a weight. So 5 and 4. So this will be calling as a weights, and this will be calling as a edge, and this will be calling as a vertex, and we can also call it as a nodes, or we can also call it as a hops. Okay, depends upon the subject course. So vertex, node, or hops. So this is a small introduction about this graph. Now the single source shortest path will find, first we have to find out the source node. Let it be, this is a source node. For example, this is a source node. Okay, don't get confused here. I write source, right? Source is A. So from A, what is the shortest path for all other vertices? So A to B, A to C. Okay, so that we have to find using this single source shortest path. So where it will be used? So it will be used in order to find the shortest distance in between one place to another place. And also the same thing will be applied in a networking concept for routing a packet. So it will find the shortest path, and through that shortest path the packets will be transferred. So in many applications we use this Dijkstra algorithm. So Dijkstra or Dijkstra algorithm, right? Whatever it may be. Now we'll see what exactly happens in this single source shortest path using this Dijkstra algorithm. I'll explain with a small example so that you'll be understanding, right? So I'll take it A, B, C, D. So this is an undirected. So this Dijkstra algorithm can be applicable for both the directed and undirected. I'm giving the undirected. So I'll give the values 4, 10, and 15. Right. So 5 is the weight given for this edge which connects vertex A and B. 15 weighted edge between B and C. 10 weighted edge between D, C and D. 4 weighted edge between A and D. So this is a vertex, this is an edge, this is a weight. Now we need to find, so this is a source. Let us assume this as a source. So we need to find the shortest path from A to B, A to C, and A to D. Okay. See, usually A to B there is only one edge, that is a 5, and A to D there is only one edge, it's 4. What about A to C? So A to C can be done through D or through B. If A to C from B, the cost will be 5 plus 15, total 20. And if you use this path, that means through D, it will be 14. So which will be the minimal shortest path? So in order to reach C, A can travel through D, which gives the minimal cost. So here you can see we are having a multiple solutions. From these multiple solutions, we are selecting the optimal solution, right? So that's why we call this as an application for a greedy method, right? Now we'll see the procedure. What happens first? Okay, so step one, find out the source node. Find the source node. So in this example, let us assume source is A. And step two, initialize the weight of, or the cost of A, that means the source is 0, and all other nodes cost is infinite. So initialize cost of source is 0 and cost of other nodes or vertices is infinite. So I'll give the weights here itself. Okay, I'll give the weights here. So I'll represent with black, small difference. So 0, and here it will be infinite, and infinite. So this is a cost. Okay, don't confuse. This is a weight and this is a cost. So from source, how much cost it takes to reach the destination. So here A is the source, and if A is the destination, the cost is 0. And if B is a destination, let it be, assume it as infinity. Right? So next, step 3. Okay, so find cost of neighbor vertices from source. So what are the neighbor vertices? So B and D. So how we can say that B and D are the neighbors and why not the C? Because there is a connectivity between A and B and A and D. Okay, so if it is a directed graph, consider the outgoing arrow marks, not the incoming arrow marks. Outgoing arrow marks. So if it is a directed, right? Now the neighbor edge or neighbor vertex will be D, not B, because B is connected to A, but not A is not connected to B, because it's a direction, right? So in the absence of this arrow, that means this is a undirected graph. So we can say A to B and A to D, both are the neighbors. So A is having a neighbors of A to B and A to D. So find out the cost. So there is direct connection. So obviously A to B, the cost is a 5, and A to D, the cost is a 4. Right? Now change the cost. Initially, so next, step 4, change the cost on vertices, or you can see update the cost on vertices. Now you can see initially, so how we can check means the minimum of, see what happens here, the cost plus weight of that particular edge, comma, existing cost. So we need to consider any one, minimum of cost plus weight and existing cost. See what happens here, A to B is a 5 and A to D is a 4. So there is a direct connectivity. So we have to go with either 5 or infinity. Okay, so here in this example you can see A to B means 0 plus 5. So here the cost is 0 plus weight is 5, comma, infinity. So among this we have to find out the minimum. This is for A to B. And similarly A to D, the minimum of 0 is the cost plus weight, 0 plus 4. What is that initial cost? Infinite. So in both arguments we need to consider the minimum. So obviously it will be 5 and obviously it will be 4. Hope you understood now. Okay, now we need to update the cost on vertices. So simply remove this one. So remove this one and update it with D, 4, right? And update this one with 5. Okay. So this is a 4 and this is a 5. Okay, 4 and 5. Now what happens? Right. Next, step 5. What we have to do now? Place the visited node in a set. Visited set. For example, I mean here we will write a visited set. So write down the set. So what will be the visited node? A, because we have considered A with the shortest cost, and then okay. So and then we are updating the neighbors. So this node has been visited. So once the node is visited, we need not revisit that node. Okay. So that's why we are placing the visited node here. Now, step 6. Consider vertex with minimum cost. Now the cost, this is already visited, so we need not consider this one. Consider the cost of B, which is 5, C infinity, D 4. So these 3 are unvisited links, okay, unvisited vertices. So here we can have B with a 5 cost, D with a 4 cost, and C with a infinite. So among these we have to find out the minimum cost as a source. Now we can change. We can select that one. So among this we can simply say D with a cost 4, which is a minimum. Now consider this one as a visited. Okay, because this is the shortest cost among these 3. So now add it here, A and D. Okay, Then step 7, update the cost on neighboring vertices. Neighboring vertices. So what are the neighbors? So this has been completed. We are selecting the source as node D. Now we have selected A, and now we are selecting D. What are the neighbors for D? So one is A. There is a direct link to A, right? But A is already visited, so we need not bother about this one. We are having only one node, that is C. So D to C. D to C. So what we have to do? Update the cost based upon this one. Minimum of cost plus weight, comma existing cost. So here you can see existing cost is infinity. So what we have to do? So minimum of cost. What is the cost of D? 4 plus weight 10, comma infinity. So which one is the minimum? So obviously it will be 14. 14 is the minimum. So update this one with 14. Update this one with 14. Okay. Next, what we have to do? Repeat the same process from step 5. Okay, sorry, step 6 and 7. Repeat the same process. Step 8. Repeat step 5 and 6. Sorry, 6 and 7. Step 6 and step 7 until all nodes becomes visited. So we have to repeat the same steps. What is the step 6 after step 7? Consider vertex with the minimum cost as a source. Now consider the source. So these are the visited, right? We need not bother about that. So these are unvisited. Now consider the same 14, C14 and B5. So C14 and B5. Which one is the smaller? So obviously this is the smallest node. Consider this as a visited. And update the, what happens? Update the cost on neighboring vertices. And one point is important, that is no need to go with the visited nodes. So what are the neighbors of B, A and C? A is already visited, so we need not bother about that one. Go with the C. So what is the thing we have to do? A minimum of cost 5 plus 15, comma 14. So the cost, existing cost is 14, right? So minimum of 5 plus 15, comma 14. So what happens? This is a 20 and 14. So this is a minimum. Already the cost is minimum. So you need not change the cost. And then repeat the same thing. So add here B, right? And repeat the same thing. Consider a vertex with the minimum cost as source. Only one node is there, that with the 14. So consider the same thing and go with the this one, right? So what is the order we have done? Simply go with the order. First we have seen A as a source. From that we have visited the D. From that we have visited the B. From that we have visited the C. Okay, D to C, right? D to C. And this is the minimum cost tree. Minimum cost tree. So this we call it as a tree because this is not closed. Okay, this is a open. So this we call it as a tree. So like this we have to apply the single source shortest path. Okay, so first I'll repeat once and I'll close. So in our next session we'll see one more example, right? So first consider any graph, any directed or undirected graph. So I am taking the undirected graph. So first select the source. So that will be the single source, and our aim is to find shortest path from the same source to all the remaining vertices. So here I am taking A. So we need to find out the shortest path from A to B, A to D and A to C. Now first initialize the cost of source as 0 and other vertices as infinity. So first 0 and other cost is infinity. So find out the minimum cost vertex from all the vertices. So we are having A is a minimum because it is a 0, so consider this one. And now find out the cost for all the neighbors. That are also unvisited neighbors. Okay, so find the cost of, here I write unvisited neighbors. Unvisited neighbors. Okay, so A neighbors are B and D. So B with a cost 5 and D with a cost 4. And so A is completed because already the neighbors have been got a cost. So A will be considered as a visited. So we need not bother about A. Now we have to update the cost for each and every vertex. Now again the same process repeated. So we need to find the vertex with a minimum cost. So here 4, some here it will be 5 and it is infinity. So 4 is the minimum cost. So we have to select the D and again repeat the same process. Find out all the unvisited neighbors and find out the cost and repeat the same until all the nodes or all the vertices have been visited. Right? So one thing. So here we are having a 2 paths in order to reach the C from A. AB, BC, AD, DC. That means we can have multiple solutions, and from that multiple solutions we are taking a constraint as a shortest path based upon the cost of the edges. So that's why we can say this Dijkstra algorithm is an application of a greedy method. So which gives the optimal result among the several solutions. Right? Example for single source shortest path. So we can also call it as Dijkstra algorithm. And example for this Dijkstra algorithm. Example, right? So before going to the example, let us recall the algorithm. Okay, so first we have to select the source node or a source vertex, and we have to give the cost of that particular vertex as 0 and cost of all other vertices with an infinity. That's the first step. Second step, among all the cost or the cost of all vertices, select the minimum cost vertex. Okay, so that will be a visited vertex, right? And from that we have to change or update the cost of neighboring nodes, unvisited neighboring vertices, and we have to repeat the same process until all the vertices becomes visited vertices. So the main aim of this particular algorithm is to find the shortest path from source to all other vertices, not from source to destination, source to all other vertices, right? Now we'll see an example. So let us take an example: A, B, C, so again I'm taking undirected graph. Okay, so I'll give you some weights, random weights. I'm giving some random weights. So let us take it as 8. Okay, so this is a graph. Okay, so finally we'll get some tree. Okay, so from source, so I consider this one as a source. That means A is a source. So first what we have to do, we have to give the cost for every vertex. Okay, so I'll update the cost for A as 0 and all other vertices with infinity. Okay, the cost of all other vertices as infinity. Right, now we have to find out the minimum. Okay, so the first step, cost of source 0, cost of other vertices infinity. Second step, minimum of all cost. Okay, the vertex, select the vertex with minimum cost. I'll write completely. Select vertex with minimum cost. So what is the minimum cost? A, right? A. So select this one. Okay, and now we have to update the cost of adjacent. So let us select A. Okay, so let us select A. So what are the adjacents? B and F. So update the cost of B and F. So this is a direct edge. Okay, so we can update with a 5, and here it is 7. Okay, 5 and 7. All remaining are infinity. And mark this one as a visited node. So A is visited now because from A we have find out all the cost of adjacent vertices. Okay, so we only two neighbors. So we found the cost of these two neighbors, B and F. Now we need to find the cost of, so the second step, we have to repeat the second step. What's the second step? Select the vertex with minimum cost. So I'll update here visited. So A is visited, and next upon all these things, 5, 7, infinity, infinity, infinity. So among this one, which one is the highest? Sorry, minimum 5. So select B. Select B. Now find out the neighbors. Okay, what are the neighbors? One is A, another one is F, another one is C. And you can observe A is already visited. You can see A is already visited, so you need not bother about A. So we need to find the cost of neighbors, unvisited neighbors, F and C. Okay, F and C. So what is the C? Update. So 5 is the cost. Here source is A, right? So the name itself indicates it's a single source shortest path. So we need to find out the shortest path from the same source. From A to B it is 5, and from B to C 5 plus 6 it will be 11. So the path from A to C via B will be the 11, and we have updated it. Now we need to find out the F. Okay, F. So from B to F it will be 5 plus 8. Okay, so don't forget to count the actual cost plus a weight, because here the source is a fixed. That means we are finding the path from A itself. So here B to F means A to B and F. So this implies A to B, B to F, A to C, sorry, A to B, B to C. Okay, so A is visited and we are finding the next minimum path. So B to C it was 11, and B to F, what happens? 5 plus 8. Okay, so for this one it will be 5 plus 8, which gives 13. So we need to find the existing cost and the calculated cost, and we need to select the minimum among that one. So here already F is visited with a 7. Okay, there's the shortest path from A, it is 7, and now through B it will be 13. See, A to F is 7, and A to B and to F it will be 13. So among this one, which will be the shortest path? Obviously this will be the shortest path. So we need to select the minimum. Okay, minimum. So we need not update this one. We need not update this one. So we have already done with the neighbors of B. We have already done the neighbors of B. So we can add this B to the visited set. So this node is visited. This node is visited. Now, repeat the same process. Select the vertex with the minimum cost. Select the vertex with the minimum cost. So here where the vertex means unvisited. So here unvisited are F, C, D, E. Among all these one, which is the shortest, I mean minimum cost. Here 7 it is 11, infinity, infinity. So F is the shortest one, I mean minimum cost. So we can select F now. And now find out the adjacent neighbors of F. F, A, B, E. And you can see A and B are in the visited. So simply you can ignore. Okay, we need not revisit that particular vertexes. Okay, only there is a path from F to E. So the cost is 3. But here this implies, what is this one? A to F and F to E. So what is the A to F? It is 7. The cost plus 3, 10. In order to reach from A to E, the cost will be 10. So this is a 7 and this is 3, which gives 10. Right? So update this cost 10. Okay. So any other neighboring edges? No. So obviously we can add this to F. Okay. And this is a visited. F is visited now. Now repeat the same process again from the unvisited nodes or unvisited vertices. Select the minimum. So which one is having the minimum? E with 10, C with 11, and D with infinity. Obviously E is the minimum. So E, and find out all the adjacent or the edges, neighboring edges. So E to F, E to C, E to D. Okay, E to F, E to C, E to D. Now this implies A to F, F to E. So we can write it here. A to F, F to E, and now E to F or E to C or E to D. So here any vertex in the visited? Yes, F is already visited. So you need not worry about this one, F. So we have to find out the cost for E to C and E to D. So E to C, see, E to C. E to C means, see, A to F, F to E, E to C. Similarly, A to F, F to E, E to D. So what is the cost here? So A to F is 7, 7 plus 3, 10. So here we got a 10. So simply we can say 10 plus C, 10. See, E to C it is 10. So total 20. Already the cost of C from A is 11. That means the path or the distance required for A to reach C is 11 through B. And the path from A to C through F and E becomes 20. So which one will be the lowest? So obviously 11 will be the lowest. So we can discard. So we have to select the minimum. Okay. Now coming to this one, E to D. E to D. So already 10 is the cost to reach up to E, and to D it will be 12. So update this with 12. 12. So this will be 10 plus 2. It will be 12. And 12 and existing is infinity. So 12 and infinity, the minimum will be 12. So we are updating here. And what happens? Any other edges? No. So obviously we can select E as a visited. E as a visited. And here it will be E. Again, we are having two more unvisited vertices. That is C and D. Select the minimum cost vertex. So among the C and D, C is the minimum. C is the minimum. So what we have to do? So we need to select C. In order to get C, we are using A to B, B to C. So what are the adjacent? C to B, C to E, C to D. And this comes from B and it comes from E. This implies. So we are just having the path from C to B, C to E and C to D. Select, verify whether any vertex are in the visited. So B is visited, so you need not worry about this. E is also visited, you need not worry about this. So we are having only one edge, that is from C to D. So that implies A to B, B to C, C to D. So up to C it is 11 plus C to D it is 4. So which is 15. So from A to reach D, the cost is 15 through C. But through E, it becomes 12. So among these 12 and 15, which is the lowest? 12. So we can discard. So any other edges? No. So simply you can add it to visited. So you can add it to the visited. And now repeat the same process. Consider all the unvisited vertex, and from that unvisited vertex, find out the vertex with the minimum cost. So we are having only one unvisited, right? Only one unvisited. So only one, and the rest of all are visited. So obviously this will be visited with a 12. So this will also be added in the visited set. So this is the procedure to find out the minimum cost for each and every vertex from the source vertex. So first source is A. So B, C, D, E, F are the different vertices. So we are finding the shortest path to reach all other vertices from the source vertex. Okay. So what is the shortest path? Let us take A to B. That is directly it is a 5, and A to F it is directly a 7. So what about C? So A to B, B to C it is 11. Next E, A to F, F to E it becomes 10. Next A to F, F to E, E to D it is 12. So this is the cost from A to B, A to F, A to C, A to E, and A to D. So you can apply here. First step A, so it is a visited, and after that B. next it becomes a B, next it is F, next visited is E, next visited is C, next visited is D through E. So this becomes a tree. This is not a graph because we know that graph is a connected, right? So closed graph, closed loop. So here it is not connected, right? This is a tree, minimum cost tree from the single source. So this is the source. This one will be the source. Okay, so hope you understood this one. So the problem is finding the source node and finding the shortest path from source to all other vertex. Okay, so here I'm not talking about the destination. So we are not considering the destination as D and finding the cost to reach the destination. So here the question is finding the shortest path from source to all other nodes. Okay, right? So this is the procedure, and what is the time complexity of this one? What is the time complexity? So one point is finding all the vertices. Okay, so considering all the vertices from A, all the edges. So what we are doing here is, so we are selecting A and all vertices, edges B and F. Next, we are getting B and all vertices A, C and F, and we are finding the C with B, E, D and E, and D with C and E, and E is having some C, F and D, and similarly F is having A, B, E. So we are selecting each and every vertex and finding the edges, the cost of all incoming or outgoing edges. Okay, so that implies in order to iterate each and every vertex, it will be n minus 1. And again, we have to repeat all the edges. So the maximum edges we can get is n minus 1, right? If n vertices are there, we can have n minus 1, right? So n minus 1 edges. So it will be n square. So the time complexity is order of n square. For this particular Dijkstra. And this is an example application of greedy method, which is used to solve the optimization problems. So here you can observe, in order to reach C, it can go with A, B and C, also A, F, E and C. And in order to reach F, it can directly go with a direct edge, or it can reach till A, B and F through B, right? So for this kind of problem, we are having a multiple solutions. So here, in order to reach F, what we are doing? In order to reach F, A to F is one path, A to B to F is another path. So we are having a multiple paths, and again we can have a multiple A to B, B to C, C to E and E to F. So that's also one path. So that means for finding the cost or reaching this one, so we are getting a lot of paths, multiple paths. But what we are selecting the path with minimum cost. So that means the shortest path. So that kind of problems we call it as a greedy method, and this particular algorithm is implemented or solved by using this greedy method. So today we'll see one more concept in algorithms, that is knapsack problem using greedy method. So how can we solve the knapsack problem using greedy method? So knapsack problem. So in our previous sessions, we have seen the 0-1 knapsack. So what is the 0-1 knapsack and what the 0 and 1 represents in the knapsack, right? So in that we have seen there will be some weights and corresponding profits, and there will be one container or a sack, okay? So with a capacity, so that we have to carry the products, okay, the weights, inserting into this particular sack, so that we have to get the more profit. So here, the status of the weight is represented with xi, and that can be either 0 or 1. So 0 implements, so not considering the weight. That means not inserting the weight into the sack. And 1 represent considering. So this is called as a 0-1 knapsack. So the only constraint is we have to get a more profits. Okay, by moving the weights into this sack, we must get the more profit. And the result, the status of these weights will be either 0 or 1, either considered or not considered. And this 0-1 knapsack will be used for mainly non-divisible products. Non-divisible products. So non-divisible products means either we have to consider the weight or we may not consider the weight. So some portion of that weight can't be inserted into sack. So example, let's take some mobiles. So we can insert the complete mobile into the sack, but we can't insert a portion of mobile into sack. So that is not divisible, non-divisible. So we cannot divide the complete weight. So we have to consider either complete weight or we should not consider it. And similarly, some television. So we can't divide the television, right? We can't insert some portion of television into the sack, right? So these are all non-divisible products, and for that non-divisible products, we are using this 0-1 knapsack. But coming to this one, knapsack problem. So this is mainly used for divisible products. Divisible products means the products which we can divide. That means we can consider some portion of the weight to be inserted into the sack. Example, So vegetables. So you can consider the vegetables so that you can give some portion of vegetables into the sack. For example, let it be some 3 kgs of onions over there. So we can accommodate 1 kg of onion into the sack, or 2 kg onion into the sack. That means we can accommodate the portion, not the full, the portion of the weights into the sack. Those products we call it as a divisible products, and this knapsack problem using greedy method will be useful for these kind of divisible products. So here the status xi. So previously the xi gives the status of weight, whether it can be considered or not considered. That is completely. So this can be in between 0 and 1. So 0 means completely not accepting, 1 means full weight means accepted, and in between 0 and 1, that is some portion of the weight is also accepted. Okay, so here the xi will be in between 0 and 1. 0 not accepting, 1 completely accepting. Some portion of the if some portion of the weight is accepted, then it will be in between 0 and 1. So that is our knapsack problem. So there is a slight difference between 0-1 knapsack and knapsack. If you are saying 0-1 knapsack, there will be no fractional weights. Okay, so if you are talking about the knapsack, it allows the fractional weights. It allows the part of weights. Right? Now, let us check with an example how we can solve this one. Right? So whatever the thing we have learned in 0-1 knapsacks is completely different, and now this is mainly for divisible products. Divisible products. Now we'll take an example. So here let us consider this example. So it is having some 4 weights. Okay, so let us assume this one as x1, x2, x3, and x4. So there are 4 weights and the corresponding profits. So by moving the 3 weights capacity, we are getting a profit of 15. So by moving 4 weights of capacity, 4 kgs of weight, we are getting some 24 as a profit. Consider this weights in a kgs and profits as a rupees, right? So 6 kg weight, if you move the 6 kg weight, you will be getting the profit as 12 rupees. If you are moving 2 kg weight, you will be getting the profit as 17 rupees. Now we need to carry the weights into the sack from one place to another place. So without beyond going the capacity with a more number of profits. Now the capacity of sack is 11. Let us assume it. Okay. Now as I have said that these are the suitable for divisible products. Divisible products. So for example, let us take 3 kg. If you are moving the 3 kg weight, we are getting a profit of 15. Now, if you want to move 1 kg weight, what will be the profit? Because in this particular knapsack using greedy, we can accommodate some portion of the weights into the sack. So it is not needed to give complete 3 kg weight into the sack, right? So we can also accommodate some portion of the weights. So first we need to calculate the profit per weight. Okay. So first we need to calculate the profit by weight. So the profit by weight, 15 by 3, it's 5. 24 by 4, 6. 12 by 6, 2. 17 by 2, 8.5. Okay, so this is a profit per weight. Profit per weight. Imagine this is the 5 rupees per kg, 6 rupees per kg, 2 rupees per kg, 8.5 rupees per kg. Now the next step, arrange weights and profits in descending order. In descending order with respect to Pi by Wi. So with respect to Pi by Wi, we have to arrange them in descending order. So you can check what is the highest one. So I once again I'll write the x values, weights, profits. Okay. Now among these, which one is the highest profit? 8.5. So 8.5 means 2 and 17. So weight is 2, 17 is the profit. The x value is x4. The next one, 6, 4, 24. So 4, 24. The x value is x2. Next. 15, 3, 15. 3 and 15, the x value is x1. Next, 6, 12. 6, 12, the x value is x3. So, after calculating the Pi by Wi, the profit per weight, we need to arrange the weight and profit in descending order with respect to Pi by Wi. So, with respect to Pi by Wi, the highest profit is 8.5. So, that means weight 2 and profit 17. That should be written first. So, we are saying it as a descending order, right? Next, 6, 4 and 24. So, I am also writing the corresponding x value. Corresponding x value. Now, so initially, the weight of capacity, weight of the sack is 11, right? So first insert 2, so that the balance capacity will be 9. Okay, so 2 is completely inserted in the sack, because if you push this 2 into the sack, we are getting more profit. So we can push the complete weight into the sack. So what is x value? X4. So what is x4 value? We are completely pushing it into the sack, right? So x4 will be 1. So we are saying that if x value is 1, that indicates that weight is completely pushed into the sack. And if it is 0, not considered, right? And if it is in between 0 and 1, that implies some portion of weight is added. So we are giving the x4. In the next step, what we are doing? So already 2 is there, and m is equal to 9, right? Now insert 4. 4. You can check. So 4 can be accommodated in 9 capacity. So what is the remaining? 5. The remaining capacity is 5. So what about the status? x2. So here you can see x2. x2, 1, because we are completely inserting the weight into the sack. Then, so 2 is inserted, 4 is inserted, and n value is 5 now. Okay, now 3. Yes, 3 can be accounted in a 5 capacity. So 3 can be included, and the remaining stack weight is 2. And what about this value, x value, x1? So we are inserting the complete weight, so x1 is equal to 1. And then, so 2 is there, 4 is there, 3 is there, and again, still the capacity is 2. Okay, but if you observe, here we are having the weight 6. So 6 can't be accommodated in 2 capacity. So what we have to do, we have to divide that 6, and from 6 we are inserting 2 weights, 2 kg weight into the sack. So here it will be 0, and I am inserting 2. So x3 value will be not 1, because we are not inserting the complete weight. Okay, and it's also not 0 because we are considering some portion. So what is the portion? We are considering 2 out of 6. 2 kgs out of 6. So x3 will be 2 by 6. x3 will be 2 by 6. Now you can check with the formula sigma xi into wi, which will give the complete capacity of the sack. You can observe x1, what is x1? 1 into what's the weight? x1 weight 3 plus x2 1 into what's x2 weight? 4. Okay, plus x3 1 by 3 or 2 by 6. You can write it as a 2 by 6, right? So 2 by 6 into x3 6 plus x4 1 into x4 value is 2. Now if you observe, so this will be 3 plus 4 plus 2 plus what is this one again? 2. So the complete result is 11. So which is the capacity of sack? Which is the capacity of sack. Now what will be the profit? What is the profit? So profit, how much profit we are getting means simply you can calculate sigma xi into PI. Okay, so this will give the profit, how much profit we are getting. So here you can observe x1. x1 means, see x1 here 1 into what's the profit of x1? 15 plus x2 1 into x2 profit 24 plus x3 2 by 6 means 1 by 3 into what's the x3 profit is 12 plus x4 1 into x4 value profit is 17. Now you can check, this is 15 plus this is 24 plus this will be 4 plus it will be 17. So total 39 plus 4 43 plus 17 60. So 60 will be the profit if you insert the values. You can see the result x1, x2, x3, x4. So the result is x1 1, consider x1, consider x2, consider 2 by 3 of x3 and consider x4. So this will be the result. So by considering the first weight, second weight, fourth weight, and some portion of, sorry, this is 1 by 3, I think. Yeah, 2 by 6 means 1 by 3. Right? So 1/3, right? So by considering this portion, right, the complete weight of x1, complete weight of x2, complete weight of x4, and 1/3 weight of x3 will give you the profit of 60. So this is how we can solve the knapsack problem using greedy method. So here first we have to find out the profit by weight. So per weight, how much profit we are getting, and based upon the PI by WI value, we have to rearrange all the weights and profits in a descending order. That means highest should become first, and then slowly keep on inserting each and every weight into the sack based upon this changed order, right? So finally, if you go with this formula, sigma xi pi, so you'll be getting the highest profit. Right? So this is how we can solve the knapsack problem, and once again I'm repeating, knapsack problem is completely different with a 0-1 knapsack. So 0-1 means it doesn't accept the fractional values, it doesn't accept the portion of weights to be inserted into the sack. But coming to the knapsack, the status of x value, the weight, some portion of the weight can also be accommodated in the sack based upon the capacity remaining in the sack.
Dynamic programming. So this is one algorithmic approach in order to solve the programs or problems. So in our previous sessions we have seen the greedy method and divide and conquer, and now we're moving on with the next concept, that is a dynamic programming. So this is similar to our divide and conquer method. So usually the divide and conquer method is represented as DAC, divide and conquer, and this is represented as DP, so which is abbreviated as a dynamic programming. And the main goal is this dynamic programming approach is used to solve optimization problems. I think we have seen this in the greedy method. So greedy method is also used to solve the optimization problems, and here also it is used to solve the optimization problems.
So we know that optimization problems are the problems which are having a multiple solutions, and we are selecting the optimal solution based upon the constraints, right? So that is an optimization problem. And so working is similar, not equal, right? It is a similar to divide and conquer. Divide and conquer. That means here also the complete problem will be divided into subproblems, similar to our divide and conquer. But only one thing difference is, so the division should be with overlapping subproblems. Okay, with the overlapping subproblems. So overlapping subproblems. But in case of divide and conquer, okay, in case of divide and conquer, so the subproblems will be divided without any overlapping solutions. Right? So let me explain what is exactly the overlapping subproblems and the not overlapping subproblems. For example, so in both the cases, I'll write the steps and then I'll differentiate these two things. Okay, so the first step, step 1, the first step, the complex problem will be divided into subproblems. The complex problem is divided into subproblems. So either it can be a complex problems or a large problems. Okay, and step 2. So this is common with the divide and conquer. Next, so next we have to find out the solution for these subproblems. Here also find solutions. That's also optimal solutions. So here that is important. Find optimal solutions for all subproblems. Okay, here this is also common. And step 3 is the most important and a unique among the remaining algorithmic approaches. So store the solution of subproblem in the memory. Okay, so stores or save solution of subproblem, so that if it requires to get a solution for the same subproblem some other time, so in order to avoid that one, so we can get the solution from the memory. So we have to find out the optimal solutions for all the subproblems, and we have to save the complete solution in the memory. And before solving the subproblem, first we need to check in the memory whether there is a solution for the subproblem. If it is there, then automatically we can retrieve the value. Otherwise, we have to solve the optimal, solve the problem and get the optimal solution, and again save the same thing in the memory. So this is a unique thing. Okay. For example, consider the Fibonacci series. Okay. See. So I read the step 4 also, the last step. So what's the last step? So finding the complete solution for overall problem. So based upon the optimal solution. So from all optimal solutions, from all optimal solutions of subproblems, find out overall solution. Find out overall solution. Find out overall solution. So these are the main steps that will be followed in this particular algorithmic approach. The first one, complex problem, will be divided into subproblems. And second, find the optimal solutions for all the subproblems. And the third, stores or saves each sub-solution of the subproblem and for the future reference. And step 4, from all optimal solutions of the subproblems, find out the overall solution. See, now I'll tell you the example of overlapping subproblems and non-overlapping subproblems. Example, let us consider the Fibonacci sequence. Fibonacci sequence. Alright? So, we know that Fibonacci sequence means the element is nothing but the addition of previous 2 elements. The element is addition of previous 2 elements. For example, so if the first element is 0 and the next element is 1, the next element will be 1 plus 0, it will be 1. Next element will be 1 plus 1, 2. Next element will be 2 plus 1, 3. Next element will be 3 plus 2, 5. Next element will be 8. Next 13, 21, etc. So how we got a 21? So 21 we got with the addition of 13 and 8. How we got a 13? 13 addition of 8 and 5. How we got a 8? Addition of 5 and 3. So n is equal to n minus 1 plus n minus 2. So if you want to get n minus 1, n, so we need to add n minus 1 and n minus 2. So we can solve this one by using the recursion. Okay, simply we can use the recursion, Fibonacci of n minus 1 and n minus 2. So if you solve the same thing using the recursion, what happens? Let us see. See, if you want to solve, for example, Fibonacci of n, how we can solve? So this can be done with the help of Fibonacci of n minus 1 and Fibonacci of n minus 2. Okay, then how we got n minus 1? Again, Fibonacci of n minus 2, Fibonacci of n minus 3. Correct? And what about this one? Fibonacci of n minus 3, Fibonacci of n minus 4. And the process will be repeated similarly. So here you can observe, so Fibonacci of n minus 2, here we are solving, and the same thing we are solving here also. Fibonacci of n minus 3, here we are solving, and also we are solving here. Similarly, a Fibonacci of n minus 4 is solved here, and somewhere else definitely we will solve the same thing. So that means that repeatedly we are solving the same thing multiple times, even though it is a recursion, right? So instead of that one, if you solve the solution, if you get the solution for this problem, that will be stored in a table. Okay, so simply here I'll write Fibonacci of n minus 2. So whenever it is required here, I need not execute the same thing, I need not implement the same thing. So I'll get the value from the memory because it was already solved and it was already stored. The solution is already stored in the memory. Right? So consider these are all the subproblems. These are all the subproblems. So once you solve the subproblem, the solution will be stored in the memory. Right? And this process is called a top-down approach. Top-down approach. And this process is called as memorization. 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 So here, the same problem can be solved in two different approaches. One is a top-down and the bottom-up. Okay. So bottom-up approach. One more thing we can write a bottom-up approach. So that means the solution will be getting from the base case itself, right? So this process we call it as a tabulation. Tabulation. Okay, tabulation. Right? So hope you understood. So these type of subproblems we call it as a overlapping subproblems. So here we are having a Fibonacci of n minus 2, and here also we are having Fibonacci of n minus 2. The same problem repeated twice here. So this process, these two subproblems, we can call it as a overlapping subproblems. Overlapping subproblems. So this is the one characteristic of dynamic programming is overlapping structure. Overlapping structure. Okay, so I'll write down here characteristics. So one is overlapping structure. So actually in the dynamic programming we are also dividing the problem into subproblems but without overlapping subproblems. And the second characteristic is an optimal solution. Optimal subproblems. Optimal subproblems. That means here also, as we discussed just now, so consider each and every subproblem and we have to find out the optimal solution for each and every subproblem. Right? So that we call it as an optimal subproblem. And these two we can say as a characteristics of dynamic programming. Dynamic programming. See, as I here, consider this approaches. Approaches. So we can say this as a top-down approach and two approaches. Another one is a bottom-up approach. So in this top-down approach, we call the process as memorization, and here it is called as tabulation. And here we'll use a recursive function. Recursive, right? So every subproblem will be solved by using a recursive, and here this recursion will be avoided, and here it will be iterative. Iterative, right? So these are the different approaches to use this dynamic programming to solve any problem using this dynamic programming approach. And now let us see the applications. So what are the applications or what kind of problems can be solved by using this dynamic programming? So as we just discussed it just now, that is Fibonacci sequence, multi-stage graph, matrix multiplications, 0-1 knapsack, Traversals of Hanai. So a lot of applications are there. So these type of problems can be solved by using this dynamic programming in order to get the optimal solution, right? So hope you understood the top-down approach and bottom-up approach and overlapping subproblems and not overlapping subproblems. So that's the main difference between the dynamic programming and the divide and conquer. Divide and conquer, the division will be done without any overlapping subproblems, and but here dynamic programming will be divided with the overlapping subproblems, right? The characteristics, overlapping structure, and the optimal subproblems. So hope you understood. So let's stop here, and in our further sessions we'll move on with the applications. We'll take some problems and we'll see how we can solve the problem using this particular algorithmic approach, dynamic programming, right? 0-1 knapsack problem. So before going to this problem, first let us understand what is meant by a knapsack and what is meant by 0-1 knapsack. So we know that a sack means it's nothing but a bag. So here the problem is we are supposed to fill some objects into the bag with a highest profit. So let us consider 4 objects, right? Some x1, x2, x3 and x4, and the weight of the bag is W. Okay, so these are 4 objects, and for each object there will be a different weights. So W1, W2, W3, W4. Okay, in order to avoid the confusion, let us take the capacity of bag. Capacity is represented as m, sub m. Okay, so there is one bag or one container with a capacity m, and here in order to move these weights into the bag and carry towards somewhere, it requires some profits. So P1, P2, P3, P4. So with this particular X1, we get a profit P1. With object X2, we get a profit P2, X3, P3 and X4, P4. Here the problem is we have to arrange the weights into this particular bag that should not exceed the maximum size, and we need to get the maximum profit. That is the problem. And why we are calling it as 0 and 1 means here 0 indicates no move or no insertion. That means we are not supposed to move the weight into this particular bag, or we are not inserting the particular weight into this bag. And 1 implies move or insertion. Move or insertion. So that means if 1 represents moving the weight into the bag or inserting the weight into the bag. Hope you understood the problem. And why 0, 1? So there will be only 2 solutions, either 0 or 1 for every weight. Okay. So this will be 0 or 1, and this will be 0 or 1, and this object will be 0 or 1, and this object will be 0 or 1. So this is a solution, 0 or 1. These are objects, these are weights, and these are profits. Okay. So we need to fill the objects into this bag so that we need to get a highest profit. And for that, moving or not moving is represented with 0 or 1. So that's why we call it as a knapsack problem. Knapsack problem. Right? So in order to solve this knapsack problem, we are supposed to have the 4 things. One is number of objects. Second one, profits, weights, capacity of sack. Capacity of sack or bag. Right? So these 4 things we require. Right? So if you are having these 4 things, we can easily find out which objects should be moved from outside to the inside, and by representing with 0 and 1. So now we'll see an example, right? One example so that you will be understanding exactly how to solve this knapsack problem. Right? Now let us take an example. See. Example, let us take objects n as a 4 and capacity as 10. Okay, the sack capacity is 10, and then profits is equal to, so 10, 40, 30 and 50. And weights capacity, sorry, weights, what are the weights? So 5, 4, 6 and 3. Okay, so we need to find out which objects should be inserted into the sack so that the capacity should not reach the capacity, go beyond the capacity, right? So for example here, the sack capacity is 10. Right? So we can move 4, 5 and 4, the combination 5 and 4, and similarly 6 and 4, and similarly 6 and 3. Okay, similarly 3 and 4. For example, if you go 3, 4, 5, what happens? The total weight becomes 7 plus 5, 12, so which is beyond 10. So we can't insert the weight, 12 kg weight objects into 10 kg bag. That's the only logic, right? So we need to insert the objects that should not be on the weight. So 10 here, the weight is 10. And here you can get the profit, right? If you move the 5 and 4, the total is 9, so it can be accepted. So 5 and 4 is 50 profit. In order to carry the weights 5 and 4, the profit is 50. What about the 6 and 4? 6 and 4, it's a 70. And 6 and 3, it's a 80. And 3 and 4, it's a 90. So there are different solutions, okay? So we are having a multiple solutions. So from this we have to find out the optimal solution. So here the optimal solution is based upon the constraint of highest profits. So we need to get the highest profit. Now, we'll see the procedure, how we have to move it. Okay, see, this is a problem, and now we'll go with the solution. So let us take first one, the solution. Okay, the stack, S of 0. So we are having 4 elements. So we need to find out 0, 1, 2, 3, 4. That means initially S0 is empty. That means without any weights. S1 means insertion of one weight, of weight 1. S2, insertion of weight 1, weight 2. Already weight 1 is there, so we are moving another weight. S3, insertion of weight 1, weight 2, weight 3. S4, insertion of weight 1, weight 2, weight 3 and weight 4. That means here we can say S0, W1, and here we can say S1, W2, and here we can say S2, W3. Here you can say S4, W4. Because S1 is empty. So empty, we are adding W1. And here W1 and W2. W1 means nothing but S1. So S1, S2. Here W1, W2 and W3. S1 is having W1 and W2. So adding third one, right? Now we have to find out all these things, right? So first S0, that means empty sack. So we are not moving anything, right? 0, 0. So here we are representing as PI and WI pair, a profit and weight, corresponding weight. PI and WI, profit and weight. So 10, 5, 40, 4, 30, 6 and 50, 3. So if you want to move 5, you will get a profit of 10. If you move 4, you will get a profit of 40. If you move 6, you will get a profit of 30. If you move 3, you will get a profit of 50. So we are representing this profit and weight as a pair, PI and WI. So initially, so everything will represent in terms of set. Set means nothing but a collection of pairs here. Okay. So initially S0, that's a empty sack. Initial sack, it is an empty. Now what happens? We have to insert 1 into 0th sack. Okay. So we are inserting this one. So obviously, insertion means what we are doing? We are moving 5 to the sack with a profit 10. So 0 plus 10, 0 plus 5, 5. Okay, we have inserted. Now, what is the S1? S1 will be, what is S1? S0 and W1. So S1 means, S0 means 0, 0. S W1 means after insertion of one thing. So we are getting 10 and 5. So this is a S1. Remember this one. And this is S0. This is S0. Again, after that, what we have to do? We have to insert one more element, right? Now, S1 and insert one element. So just remember the prefix. Okay, the upper script will be the 1 and lower script will be the insertion of one element. So what we have to do? We have to add one more element. So one more element means 4 with a 40. What happens here? If you add 4, okay, if you add a 4 and it is 40, what happens? So complete it is 9 and complete it is 50. Okay, the same thing apply to the S1. So S1 insert to S1. So what happens? 40 and 4. 40, 4. Because we are adding to this particular S1. 0 plus 40 and 0 plus 4, then combination 40 plus 10, 50, 4 plus 5, 9. So you got it. So empty, initially we have moved it and then we are getting the next one. Now what is the S2? S2 is equal to, so what is the S2 here? So complete S1 and new thing. So S1 is here 0, 0, 10, 5, 40, 4, 50, 9. Right? Yes. Okay. Now you observe what it means: 0 weight, 0 profit. Okay, 0 profit with a 0 weight. And if the weight 5, here we are having weight 5. How much profit we are getting? 10. Good. Second case, adding weight 4, and profit is 40. So you are getting less profit with 1 weight, because you can see with the weight 5 we are getting only 10 profit. With the weight 4 we are getting more profit. So imagine it as a kgs. For 5 kgs the profit is 10. For 4 kgs itself the profit is 40. So which one is better? Obviously this one is better. So we can avoid this particular case. Okay, this rule we call it as a dominance rule. Okay, dominance rule. Dominance rule. That means if Pi is greater than Pj and Wi is less than Wj, less than or equal to, okay, or simply you can write it less than. Okay, then we need to remove the pair with less profit. So this process we call it as a dominance rule. Dominance rule. Here the same thing happens. Consider Pi and Wi, Pj and Wj. See, Pi, Wi, Pj, Wj. What happens? Pi is greater than, sorry, I have written small, right? Pj and I, and here also j and I, right? So increasing of weight should increase the profit. So Pj is greater than Pi, Pj is greater than Pi, perfect. And Wj is less than Wi, Wj is less than Wi. So we need to remove the pair with less profit, which is having the less profit. 10 is the less profit, because the pair is profit and weight, not weight and profit. Don't get confused. Okay, profit and weight. The first term will be the profit, the second term is the weight. So if we need to remove the pair with the less profit, that is a 10. So this is also called as a purging rule. Purging means removing, also known as a purging. Okay, so what we have to do in this case? We have to avoid this one. Okay, so now we can write the final S2, 0, 0, 40, 4, 50, 9. Okay, only 3 terms we are getting. So 0, 0, 10, 5, 44, 59. So 10, 5 we are removing. So only 3 terms are there for S2. Now find out the next term, that is S3. So in order to find out S3, we need to add 1 to S2. 1 to S2. So the next term is 30, 60. So 30 comma 60, sorry 30 comma 6, and add 30 comma 6 here. How much? 70 comma 10, and here 80 comma 15. Okay. Now you observe the profit is 80 if the weight is 15. That's good, but the maximum weight here is only 10. So in the 10 capacity bag we can't insert the 15 weight. So this is also invalid. So we need to remove that one. Now S3 will be the combination of S2 and the insertion. So consider 0 comma 0, 40 comma 4. So before 44 we can get a 30 comma 6, 40 comma 4, 50 comma 9, and 70 comma 10. So these are the elements. And now again you can see the same thing. So here 6 and here 4. So we are getting a profit for 6 weight 30, and we are getting a more profit for weight 4. So we can remove the less profit. And see 0, 4, 4 to 9, and 9 to 10, 0 to 40, 40 to 50, 50 to 70. Everything is okay. Now S3, the final S3, 0 comma 0, 40 comma 4, 50 comma 9, 70 comma 10. This is the S3. This is the S3. Now insert the last one. Already we have inserted the 3 things. We need to go with the 4th one. So S1 into 3. So we have to add the 4th one. So 50 comma 3. So 50 comma 3. 53. So 90 comma 7. 53. 53. 100 comma 12. 50. 120 comma 13. Right? Okay. Now you can observe this is a beyond the weight 12. So we can't process this one. And this is also beyond weight because 13 and the maximum capacity was only 10. So you can avoid this one. Okay. Now write on the S4. What is S4? Combine both the things. S3. So 0 comma 0, 40 comma 4, and you can go with the 50 comma 3, 50 comma 9, 70 comma 10, 90 comma 7. See, these are the S4. And again you can observe, yes, so we are getting 3 with the 50 and 9 with the 50. Weight 3 with the profit 50, weight 9 with the profit 50. So you can avoid this one. Okay, with only weight 3 we can get a 50, right? So we can avoid this one. So finally write the S4, 0, 0, 44, 50 and 3, 70 and 10, 90 and 7. And again observe, so with 4 we are getting 40 and with 3 we are getting 50. Okay, again there is a violation, the same dominance rule, right? So avoid the less profit. So you can avoid this one. Again write on the final thing. So hope you are understanding. 50 comma 3, 70 comma 10, 90 comma 7. And again you can see, so with 10 weight we are getting 70, with 7 weight we are getting 90. So again there is a problem. So you can avoid this one also. So S4, 0, 0, 53, 97. So this is finally the S4. Okay, so now we found that S1, S2, S3 and S4. So we have inserted all the 4 elements, right? Now we'll see which one is the best. Which one is the best among all these things? So here the highest is this one. So just consider the same thing. So 90 comma 7. Check the conditions belongs to S4 and 90 comma 7 belongs to S3. Check both the condition. Okay, which one is true? So 90 comma 7 it is available in S4. Right. 90 comma 7 is available in S3. It doesn't belong in S3. Okay. So here you can see it is in S4, not in S3. That means you can simply say that X4 is equal to 1. That means we can move the element into bag, into the sack. Okay. If both are equal, we need not move it. Okay, both are equal. That means if 90 comma 7 belongs to S4 and 90 comma 7 belongs to S3, then we need not move the weight to the sack. So here one condition is true, another condition is false. So move the 4th element, last element or last weight into the sack. Now remove the 4th element from this particular weight. So 90 minus 50 comma 7 minus 3. So this is the 4th one, 50 comma 3. So remove the things from the pair. So obviously it will be 40 and 4. Check out. So 40 and 4. Check the same conditions. Now already S4 completed, belongs to S3 and 40 comma 4 belongs to S2. Check out whether 40 comma 4 belongs to S3. 40 comma 4 it is available, right? 40 comma 4 in S2. Where is S2? 40 comma 4 in S2. Yes. So obviously we can say the third object need not be moved because both the conditions are true. So in both the cases, in both the sets, 40,4 is available, so need not change. So in our first discussions, we say that 1 represents moving the sack into the, moving the weight into the sack. And coming to the 0 representation, we should not move the weight into the sack. Then, so we need not remove the third element from this here. Okay, so simply continue with the same thing. So 4,4 belongs to S2, 40,4 belongs to S1. Check out, in S2, 40,4, it is available. 40,4 in S1, no, not available. So that implies X2 should be moved. X2 should be moved into the sack. Hope you understood. If both the conditions are true, that means if the pair is available in S of I and S of I plus 1, or sorry, S of I minus 1, then no need to move the weight into the sack. So we need to compare each and every set. Okay, so here 40,4 is available in S2 and 40,4 is not available in S1. So that's why we have to move the second weight because we are checking with the second one, right? Now, what happens? So here we need to remove the second element from this pair. So what's the second element? 40,4. So 40,40 and 4,4. So what happens? 0, 0. So it is 0, 0. So we have to check and again with 1 and 0, 0 with S0. So 1, 0, 0, yes, and S0, 0, 0, yes. So obviously X1 will be 0 because the pair is available in both the set S1 and S0. So the solution is 0, 1, 0, 1. So the solution will be either 0 or 1, right? So 0 means we should not move the first weight. 1 means we have to move the second weight. 0 means we should not move the third weight, okay? And 1 means again we have to move the fourth weight. Just observe, moving off, see this is a weight, this is a weight. Moving off, second weight is 4 with a profit of 40. Next, fourth means this one. Third weight, okay, with a profit of 50. How much total profit we got? 90 profit. So by moving a 3 and 4, okay, by moving a weights 3 and 4, we got a 90 profit. That's the maximum profit. You can check. So 5, 4 is 50. 4, 6 is 70. 6, 3 is 80. 3, 4 is 90. Just now we got it. 5, 3, 60. In every combination you can check. So only we'll get a maximum profit if you move the third weight and the fourth weight. Sorry, the weight 4 and weight 3. That means the second and fourth one. So X2 and X4. If you move the X2 and X4 weights into the sack, then only we'll get the maximum profit. Okay, so this is how we can solve the knapsack problem. So first we have discussed about what is a knapsack, right? And then we have discussed how to solve it. This is by using the set method. By using the sets, we are using all the combinations, and then we are getting the result with the zeros or ones, which are to be moved and which are not to be moved. So once again, I am repeating. So initially insert one element, and then initially the sack will be 0, and insert one element and combine both the things, and insert the second element and combine both the things. And just remember, so make it a mark of S0, S1, S2, S3, and S4. And one thing we have to remember, the dominance rule, if the Pj greater than Pi and Wj less than Wi, then immediately remove the pair with a less profit. Simple example, we are inserting weight 5 and we are getting a profit of 10, and we are inserting weight 4 and we are getting a profit of 40. So here the remaining weight we can insert into a bag is only 5, and in this case we can insert the weight of 6 into the bag, right? So that means with the highest weight we are getting the lowest profit. So such cases we can remove the pair with low profit, and that we call it as a dominance rule, or the technique called a purging mechanism. And one more thing, so if the weight exceeds the maximum size, then also we can remove the pair. Here you can see 80, 15. So 15 is a weight which is beyond the maximum. So we have avoided it, we have ignored. So here in this case at 12 and 30 we have ignored, right? And all these are the purging. Okay, so dominance rule, applying the dominance rule. Afterwards we need to check the highest weight or highest profit pair with the S4 and S3, so that if it belongs to in both the cases, simply we can say we should not move it, because already in either cases, in some other case it may be available. So automatically we should not accept it if the pair is available in Si and Si minus 1. And if not, then immediately we can move that particular weight, and we have to remove that particular weight and profit from this particular weight, profit and weight pair. Right? So like that, finally we will get the solution in either only zeros or ones. So this represents we are moving. So by moving the second object and a fourth object, we will get the highest profit. By moving the second object 4 and fourth object 3, we are getting the maximum profit of 90 rupees. So 90, profit as 90. Okay, so this is how we can solve the 0-1 knapsack problem. So today we'll see one more example for knapsack problem. So in our previous session we have seen what is a knapsack problem, and then we have solved one problem. Right? Now we'll see one more problem. So we need to take a number of objects and corresponding weights and corresponding profits, and also the weight, the maximum weight of a sack. Right? So let us take 3 objects. So x1, x2, x3. and the profits. So some 35, 40 and 30, and the corresponding weights, let it be 10, 25 and 20, and the maximum sack weight is 40. Maximum sack weight is 40. Now we need to find which objects should be inserted into a sack so that we will get the maximum profit. Okay, now let us assume the sack is empty. So S of 0, it will be 0 comma 0. And after considering the empty sack, just insert the first object. So I am inserting one object to the empty sack. So we need to add the first profit and weight to this one, right? So these are nothing but profit and weight pairs. The pair is profit and weight. So why I am writing like this means the first element is a profit and the second element is a corresponding weight. So 35 plus 0, it's a 35, and 10 plus 0, it's 10. Now with one element, that means with one object, the sack with one object is the empty sack and after insertion of one object. So this is a S1. So we need to note down these things. This is S1 and this is S0, which is an empty sack. Now I'm inserting one more object to sack with one object, right? So add the second one, 40 and 25 to 0, 0. It is 40, 25. And 40, 25 to this one, right? 40 means 75. Next, 25 plus 10, it is a 35. So you can see it is in an increasing order, right? There is no dominance. There is no dominance. So with a weight of 25, we are getting 45, and with a weight of 35, we are getting some 75. So there is an increase. There is no problem. And S2 is, so combine both these things, 0 comma 0. So 35 comma 10, and after insertion, so 45 comma 25, and 75 comma 35. Right? Now this is a S2. So we have taken three elements or three objects. So we need to calculate the S0, S1, S2 and S3 because already two elements or two objects have been inserted into a sack. Now the third one. So after insertion of 1 in sack 2. So what is the third one? 30, 20. So 30 plus 0, 20 plus 0. So 30 comma 20. 30, 20. So 65, 20 means 30. 30, 20. So 75, 20 means 45. 30. So 105 profit, 20. It's a 55. It's a 55. Right. Now you can eliminate these two things because the maximum weight is a 40. The sack can accept up to 40, right? But here we are having some 45 and 55 which is beyond the maximum weight, so we can avoid these things. And now we can consider only these terms, that is S3, so 0 comma 0 and 30 20. 30 20, next 35 and 10, 45 25, 65 30, 75 35. And here you can see with the 20 weight we are getting some 30 profit, and here with 10 weight we are getting 35 profit. So which is a dominance, right? Which is a dominance. So with a less weight we are getting more profit. So what we have to do? So we can simply avoid the pay with less profit. So among these two, the less profit is 30. So we can simply avoid this set or this element, right? Now we'll write the pay. S3 is equal to, what are the pay? So 0 comma 0, 35. So you can observe 35, any other deviations, dominance here. So 35, 10, 45, 20. So both are maximum and here also maximum. 45, 65, 25, 30 maximum. 65, 75, 30, 35 maximum. So there is no dominance, right? So 0 comma 0, 35 comma 10, 45 comma 25, 65 comma 30, 75 comma 35. So among these one, so we can see this is the maximum profit. We can get a maximum profit. Now we'll go with this one. So checking out 75 comma 35, which belongs to S3, and 75 comma 35 belongs to S2. So let us check. S3, 75 35 belongs to S3, true, and 75 35 belongs to S2. So whether there is a 75 35 S2, yes, it is there, right? So there is no change. We need not change. And the third element cannot be inserted into a sack. Third element cannot be inserted into sack. After that, we have to remove. So we need not remove it, okay? Because in both the things we are having the same thing. So 35 belongs to S2 and 75 comma 35 belongs to S1. Let us check. S2, yes, it is available. S1, there is no. So there is no. So there is a deviation. Obviously, we can say S2 should be inserted. X2 must be inserted because in S2 it is there, in S1 it's not there. Now what happens? We have to remove the second object, second object profit and weight with this one. So 40, that means a 35, comma 10. Check it out, S1 and 35, comma 10 belongs to S0. So we need to check only in two sets. One is S power I and the next one is S power I minus 1. Okay, so 35, comma 10, it's available in S1, right? Yeah, 35, comma 10 is not available in S0. So obviously we can move the first object into set. First object into set. So you can say the solution S is equal to 1, comma 1, comma 0. That means inside the sack we are supposed to move the first object and second object so that we'll get the highest profit. So what is the first object and second object? 10 weight and 25 weight. 10 plus 25. So what is the profit here? We are getting 35 plus 40, which is 75. Okay, so let us take a more. Okay, so if you move 25 and 20, that means second object and third object, we can't move because the weight goes beyond the maximum size, right? So we can go with x1 plus x3. So 10 plus 20, the profit will be 65. Okay, so there is no chance. So obviously with this move we can get a more profit. That means moving the objects x1 and x2 into the sack, we'll get a maximum profit. Well, so today we'll see one more concept in a dynamic programming in algorithms, that is a traveling salesman problem. So this problem we'll solve by using the dynamic programming method. So in our previous session we have already seen what is the dynamic programming, right? So a complex problem will be divided into subproblems and each subproblem will be solved and the solution of each subproblem will be saved in the memory so that in future, in order to avoid the recalculation, so we'll make use of the existing solutions. And this is also mainly used to solve the optimization problems where there will be a lot of solutions. Among them, we have to select the optimal solution based upon the given constraint. So this is about the dynamic programming. So about all this dynamic programming we have seen in our previous sessions. So I'll post the link in the description. So just go through. And now we'll see what is the traveling salesman problem. So here, first let us see what is this problem. So there will be a graph. So here we are supposed to take a graph. Okay. So consider different vertices and edges. We know that a graph will be having vertices and edges. So how this graph is related to our salesman problem? So consider the edges as a distance and vertices as a places in the city. So how the salesperson travels from one place to another place, covering all the places in the city with a minimum distance. Okay, so assume each vertex as a place in the city. So that from the source, the salesperson should start traveling and have to visit all the places only once. Okay, all the places only once and have to come back to the source. So this is the salesman problem. That's also with a low cost. That means distance, least distance. So for that relation, we are taking the complete places as a vertices and the distance as a edges so that we can have a graph and we can solve it. So one thing, we have to select a source. So selection of source. That's the first important point. And the second one, so starting from source, traverse through all vertices in a graph exactly by one time and come back to source with minimum distance or cost. Minimum distance or cost. So we have to select the source node and from that source node we have to traverse all the vertices exactly one time and come back to the source with a minimum distance or cost. So for this we have to consider a weighted graph. So every edge should have a weight which represents the distance or cost, whatever it may be. Okay, so we have to consider weighted graph. Weighted graph, and one more important, so we can have the directed graph or undirected graph. So graph can be directed or undirected. So I think you know the difference between this directed and undirected. Okay, for example, if A, B, C and this is a graph. Okay, this is a graph. So there is no directions on the edges. So this comes under undirected. Undirected. For example, A, B, C. Okay, so there is a directions. So there is a direction. That means this edge is between A and B. This edge is between B and C. This edge is between C and A. Right. So there is a directions. So this is a directed graph. So we can work this problem, traveling salesman problem, either on both directed or undirected, but it should be a weighted graph. So for every edge, there should be a weight, okay, which represents the distance or cost. And one more important point is the graph, either directed or undirected, the graph should be complete graph. Complete graph. So what do you mean by complete graph? So every vertex should have the edge to all other vertices. Okay, for example, consider A, B, and C. So this is an undirected graph. So we can say this is an edge between A and B, and also B and A. For example, let us take the distance. So this implies the distance between A and B is 10. Similarly, the distance between B and A is also 10. Distance between A and C is 20. Similarly, C and A also 20 because undirected. So if it is like this, A to B, B to C, C to A. So this is also an directed graph, but not a complete graph, because A is having an edge from A to B. There is no edge for A to C. And B is having an edge for B to C. There is no edge for A. C is having an edge for A. There is no edge for B. So the complete graph means every vertex should have the edges towards all other vertices. For example, so A is here. I'll write one more edge here. So A is having edges to B and C. Now B is having only for C. I'll write here. So B is also having an edge from A and C towards A and C. So C is having only for A. So C is also having an edge to A and B. So A is having an edge to B and C. B is having an edge to A and C. C is having an edge to B and A. So this is a complete graph. This is a complete graph. Complete directed weighted graph. Okay. So this is a complete weighted, the complete directed weighted graph. Okay. So in such type of graphs, we can apply this traveling salesman problem. Okay. So these points are most important before starting the problem, right? So selection of a source, we can select any vertex as a source, but from that particular vertex, we have to traverse all other vertices exactly once and come back to the same vertex. And consider a weighted graph. So that should be a weighted graph, can be a directed and undirected. Graph should be a complete graph. So these points are most important. Right. Now, so before going to this one, let us have a formula. So just remember the formula, so that while solving the problem, you can understand the formula exactly, right? So here we'll write a formula. The function I comma set, S stands for set, which contains a number of elements, or we can say vertex, right, is equal to cost of I comma j. So j, so here, okay, I'll write here itself, I'll erase this one, I'll write here. So g of I comma set, which contains all other vertices, is equal to minimum of j belongs to set cost of I j plus again a function j comma set minus j. So this is a formula which we have to remember while solving the problem. And one more formula, g of I comma pi is equal to cost of I comma source. I comma source. Okay, right. And one more thing, remember one more thing, cost of I comma j will becomes 0 if I equal to j, and becomes cost of ij if ij edge belongs to graph. Ij belongs to graph. That means if there is an edge between I and j. Okay, so just remember the cost, if I and j both are equal, then the cost will be 0. Right? Yes. Otherwise, we can write down the direct. So remember this formula. Remember this formula. So we need to calculate the shortest path from source, visiting all vertices, and come back to the source. Right. So I is a source. Okay, I is a source, and S is a set of all vertices. Set of all vertices other than I. Okay. From that we have to find out the minimum. Okay. So we'll write down the example. So let us take this example. Okay. So this is a undirected graph. Okay, first let us check. It is an undirected graph. This is a weighted graph because for every edge there is a weight. And let us check whether it is a complete graph or not. So here we are having a 4 nodes, that means 4 vertices. So every vertex should have the 3 outgoing edges. So A is having an edge from A to B, D and C, right? From B to A, B to D, B to C, okay? C to B, C to D and C to A, okay? D to A, D to B, D to C, yes. So this graph is a complete weighted undirected graph. Now we have to solve the problem. First let us write down the table. Okay, let us write the adjacency matrix. So I am writing here, so A, B, C and D, and here also A, B, C and D. So we'll write the cost. Okay, so this is I and this is j. So there will be no edge from A to J or B to B or C to C or D to D. So that's why I have mentioned. So cost of I comma j will be 0 if I is equal to j. So if I is equal to j, then the cost will be 0. And it will be Cij if the edge ij belongs to graph. Okay, see A to A. So I is equal to A, j is equal to A. Obviously it will be 0. Next, A to B. Then if there is an edge, A to B, yes, there is an edge. So belongs to graph. Okay, A comma B belongs to graph. So that implies the cost is 10. Next, A to C, 15. A to D, 20. Similarly, B to A is 10. B to C, sorry, B to B there is 0. B to C is 35. B to D is 25. Similarly, C to C again is 0. C to B is 35. C to C 0. C to D is 30. Similarly, D to A is 20. D to B is 25. D to C is 30 and it is 0. Okay, sorry, C to A 15, it's not 0. C to A is 15. Right. So this is an adjacency matrix. Okay, so this represents a cost from one edge to another edges. It's clear. Now, so just start with the set 0. Okay, if the set contains 0, what are the different possibilities? If set contains one element, what are the different possibilities, different edges? Now we'll select the source. So I'll write source as A. A is a source. Okay, A is a source vertex. Now first, if set is equal to 0, okay, the set contains different elements. Okay, so 0th element, first 1 element, 2 element, 3 elements, because the source is A. So if set is equal to 0, if set is equal to 0, apply the formula G of I means B. So from B comma set is 0, there is no element, so that can be represented as pi. If set is equal to 0, then we can represent it as pi. Now what happens? See, if I 0, then I comma source. So this will be G of, what is I here? B comma, what is the source? A. So what is the cost here? B to A, it is a 10. Similarly, there is a possibility of C to pi. C with no element. So G of C comma source, which is nothing but C to A is a 15. Similarly, G of D comma pi, G of D comma A, which is DA, is a 20. So which means if the last vertex is B, if the last vertex is B, obviously our statement says that we have to visit all the vertices and come back to source. So that's what happens. So if the last vertex is B, then what is the edge from B to source? And if the last vertex is C to A, that means, for example I'm saying A is here, the next edge can be B, C and D. From this, if B, the next edge can be C and D. Next edge can be B, D. Next edge can be B, C. And A, B, C, obviously it will be D. A, B, D, obviously it will be C. If A, C, B, it's D. A, C, D, it's D. A, D, B, it's C. A, D, C, it's B. So only one vertex. So all the vertices have been visited, right? So this is a possibility, maximum possibilities, all possibilities. So after coming to D, what's the next move? So visited all vertices here. So it should go back to A. Similarly, if it is C, it should go back to A. If it is D, again it should go back to A. B, go back to A. C, it should go back to A. B, it should go back to A. So that's what here we have written. If B with a null set, if B with a null set, that means no other vertices are remaining to visit, then obviously the next move will be from B to A. And that means at this position, if there are no unvisited vertices, if set is 0, no unvisited vertices, obviously the edge should be towards the source. So that's why we have written this formula, I comma pi, then I comma source, right? So hope you understood this one. And the next possibility, so only 3 possibilities, because we are having 4 edges, 4 vertices A, B, C, D, and here we have taken source as A, so we need to check the possibilities of all the remaining 3, B, C, D, right? Now if set is equal to 1, that means if there is only one unvisited edge, unvisited vertex, if the set contains unvisited vertex, only one unvisited vertex, then possibilities G of B, and the unvisited from B, where it can go, either it can go to D or B, it can go to C. Only 2 possibilities. Okay, only 2 possibilities. So if there are one more vertex, for example, if there is one more vertex, then we can write it here, G, B comma E. That means there can be edge between B and D, B and C, P and E, so anything, right? So the set contains 1 means having one unvisited edge, vertex. So always I'm getting edge, right? So that's a vertex. Okay. So write down the formula here, B, D. So what is the minimum of J belongs to S. Here J means D. D belongs to set S. So Cij, that means C, B, D plus G of J comma set minus J. J here D, D minus, sorry, D comma set minus D. So here set is nothing but D. See, here set is nothing but D. So D minus D, obviously it will be empty, right? So empty means we can simply write it here, 5. Okay, so there is no other edge, only one edge is here. So only one unvisited vertex. So we are just getting the cost of that particular unvisited vertex. So if there are multiple, obviously we can have to select the minimum edge. So here we are having only one thing, so we can simply remove it and we can write it C HBD plus G of D comma 5. Okay, so you can see what we have done in the dynamic programming. So we are dividing the complex problem into subproblems and we are calculating each subproblem and we are storing in the memory. So that's what we are doing. So here G of D comma 5 we need not recompute it. So already we have recomputed. So D comma 5 is this one. So obviously we can get the value from here. So CBD plus G of D comma 5, which means cost of B and D is a 25 plus 20 D comma 5. So which is 45. Now again, G of another possibility. So there can be an edge from B to C. So this can also be written as BC plus G of, so what is the J here? C comma set minus C. Obviously it will be pi. So the edge between B and C, BC 35 plus G of C5 is a 15. So which will be 50. So here we have taken B as a source and we are computing the cost between B and all unvisited edges. See here, next change it. C to B. We can check the possibility. If C is a node and we have to check from C to all possible unvisited vertices. So C to B and similar here, CB plus G of B comma set B minus B. So obviously it is pi. So it will be CB 35 plus G of B5 10, which is 45. And similarly from C that might be having an edge to D. Okay, C to B. Okay, now C to D. Cost of CD plus G of D comma pi. So cost of C comma D, C to D is 30 plus D pi 20. So which is 50. Hope you understood. If set is equal to 1, we need to, set is 1 means 1 unvisited vertex. There is a 1 unvisited vertex. Okay, so we need to check all the possibilities towards that unvisited vertex, right? So if you consider B to D and B to C. If you consider C to B and C to D, because we are having only 4 vertices. So if our graph is having the 5th vertex, so here we'll get one more thing, G of B comma E. Okay, that's also one possibility. The same thing, right? Now, consider set is equal to 2. That means 2 unvisited vertices. Here also we have to go with the different possibilities. Check it. G of B, consider B as a source. From source, 2 unvisited vertices will be either C comma D. Okay, C comma D, unvisited vertices. So how we can write it here? Here we can write minimum of, okay, first cost of BC and cost of BD plus G of, what happens here? C comma, okay, set C comma D minus J C plus G of D comma C comma D minus D. So among these two we have to find out the minimum from this formula only, right? J belongs to S, Cij. So C, D are the 2 elements in the set. So BC and BD. So in this case, J value is C. So G of J value C comma set C comma D minus J minus C. And in this case, J value is D. So plus G of D comma C comma D set minus D. So obviously you can see set C comma D minus C means it will be D. Okay, and here C minus D means it will be C. Hope you understood. So among these two, we have to select the minimum. So that's the formula. And in the previous case, we are having a set with only one element. Okay, only one unvisited node. So we are having only an edge between B and D, B and C, C and B and C and D. Now we are having 2 unvisited vertices. So there can be a chance of having an edge between B to C and B to D. B to C and B to D. So among those, we have to select the minimum cost. So that's why minimum BC plus this one. And here, and this will be BC 35 plus G of C comma D. Already this was calculated here. C comma D, which is 50. So which is 50, 85. And coming to this one, C of BD, BD 25 plus DC. Already we have calculated here. Oh, we have missed it. Yes, we missed it. I'll write here G of D comma C. So we have missed it. We have calculated till CD. So for D also we have to calculate. And DC. So C of DC plus G of C comma 5. So which is DC 30 plus C 5 15 is equal to 45. There is one more possibility. From D there can be a chance of edge to B. So this is one more chance, right? So C of DB, that means the cost of DB plus G of B comma 5. Similar to this one, right? Similar to this one. So what's the cost here? DB. So D to B 25 plus G of B 5. G of B comma 5. Okay. So G of B 5 10, which is 35. Which is 35. Right? I'm sorry, the board is very small, so I'm forcibly adjusting everything in the single board, right? Okay, just right. Now here you can get cost. G of D comma C. D comma C cost is 45. So which is equal to 70. So which one is the minimum? 70 is the minimum. So you have to consider this one. Okay. Now again G of, if C is a source, what are the remaining elements? B and D. So minimum of CB, CD plus G of B comma, okay, from set we have to minus B, so obviously it will be D plus G of B comma B. So which is cost of CB is a 35 plus G of B comma D, G of B comma D, which is 45. It's a 80. Okay, and this one CD, C to D 30 plus DB. Here we have written DB 35. So which is equal to 65. So among these two, which is minimum? 65 is the minimum. So this we have to consider. And the next one, G of, what is the next? D. If the possible source is D, from D there can be edge between B and C. So here we can write B and C is equal to minimum of C DB C DC plus G of B comma, from set we have, if you minus B, the set will be containing only C, plus G of, if C is the source and remain minus C from the set, so it will be B. So what's the amount here? Cost of DB is 25 plus BC cost is 50, 75. And here what's the cost here? DC, D to C 30 plus CB, which is a 45. Again it is a 75. So both the edges will be having the same cost. So we can select any one edge, no problem. Okay. So only possibilities, 3 possibilities we have chosen, right? If the source is B, there can be edge from B to C or B to D. If the source is C, there can be edge between C to B or C to D. If the source is D, from D there can be a source to B or C. Now, if set contains 3 elements, that means 3 unvisited nodes. So G of, here 3 unvisited means the source A, B, C and D. Because here we are having only 4. Right? Among 4, the 3 are unvisited, and obviously the next one will be the source. So I write here, so which will be a minimum of C of AB, C of AC, C of AD plus G of B comma, if you subtract B from set, it will be C comma D plus G of C comma BD plus G of D comma BC. Okay, hope you understood this formula. So J comma, from set we have to subtract the J value. Okay, so here J value is B, we are taking B from set, so CD. Here J value is C, we are taking C from set, so it will be BD. Here D is a J value, so we are taking D from set, so it will be BC. Okay, so calculate the cost. CAB, so AB cost is 10 plus B of CD. So here we have calculated, and here we are having a 2 values. Among these we have to select the minimum, so 70. So which is 80, and the next one AC, A to C is 15 plus CBD. Here also we have calculated 2 values, 80 and 65. So among these we have to select the minimum 65. So it is also 65, and the result is 80. And the third one AD, cost of AD is 20. D of BC, which is both are same value, so we can select any value. So it is 75, which is a 95. So among these 3 we have to select the minimum, and C we have to stop the process because we are having a maximum of 4 nodes or 4 vertices, and among these the 3 are unvisited. So already we have fixed that one as a source, and only the possible are 3 more vertices, and we have repeated from 0 unvisited to 3 unvisited. So we have to stop here, right? Now among these we can select the minimum, but here you can see we are having the 2 possibilities because 2 values are same, 80, 80, and we can't select this one because it's the highest. So we have to select either this node and this node. So the path, the possible solutions are A to B or A to C. So A to B or A to C. Okay, then first if it is A to B, the next one is B, C, D. Go to here, B, C, D here. So among these we have selected this one, right? So this one we have selected B to D. Now B to D, and coming to this one, A to C. If A to C is 1H, then next to CBD, CBD. Among these we have selected the minimum, that is CD. So the next vertex we visit is D. Now if D, okay, this one we have selected. Next D comma C. Go to that thing, D comma C. This one, D comma C. So the cost is DC. The next one will be C. And similarly here also go to CD, DB. So DB means here. So after that the next node will be B. And after that, in both the cases, the next vertex will be A. So that implies there are 2 possible paths where starting from A, visiting first vertex as B, next D, followed by C, and come back to A. This is one possible path with a distance of 80. So you can calculate A to B, which is 10, B to D, which is 25, D to C, which is 30, and again C to A, which is 15. Total will get 80. And similarly here, starting from source A, visiting first vertex as C, next vertex as D, followed by B, and come back to A. So in both the cases, the distance is 80. So there are 2 possible paths. So if we are having only one among these 3 are minimum, so that will be the single path where the person can travel from source to visiting all vertices and come back to the source. So here we are just calculating and we are saving the result, and we are making using this result in further procedure. Well, so today we will see one more problem in traveling salesman problem. So in our previous session we have seen what is a traveling salesman problem, and we have solved one example which is an undirected complete weighted graph. Now in this session we will see one more example which is weighted directed complete graph. So we have seen the difference between a complete graph and a normal graph, and also weighted graph and unweighted graph, directed and undirected, right? So now we will solve this example, right, by using the dynamic programming. First let us write the adjacency matrix, and we'll erase this one because the board is very short. So I'll write the adjacency matrix and I'll erase the complete thing, right? I'll write the adjacency matrix here. So A, B, C and D. So 4 vertices. So we'll write the cost from one vertices with another one. So A to A, so which is always 0, and A to B. So A to B it is 10, A to C it is 15, A to D it is 8, B to A 5, B to B 0, B to C 13, B to D is 10, C to A is 6, C to B it's 9, C to C 0, C to D is again 9, and D to A is 20, D to B is 8, D to C 12, and D to D is 0. So this is the adjacency matrix, right? So I'll erase this one. So which is a weighted directed complete graph. Now first we'll write the formula. So we need to remember 2 formula before starting the solution, right? So G of I comma set of S is equal to minimum of J belongs to set cost of Ij plus G of J comma set minus J. This is one formula. And another formula, so cost of or G of I comma I is equal to G of I comma cost of I comma source. So we need to remember these 2 formulas so before starting the solution. Now we need to find the minimum distance from source vertex visiting all other vertices at least once, exactly once, and come back to the source vertex. So we'll see the source vertex as A. So we can consider any vertex as source vertex. So the first step we have seen in our previous session, that is we need to select the source vertex. So here I will select the source vertex as A. Now we need to start from A, visiting all nodes and come back to A with a minimum distance. So we'll write the next possible source, unvisited. So first one, let us take if set is equal to 0, that means no unvisited vertices. If there are no unvisited vertices, then the recent vertex will be the last vertex. So the possibility is G of B comma 5, because itself is the last vertex. So what is the formula of this one? G of I comma 5 is a cost of B comma source. Here the source is A, cost of A. B of A, cost of B comma A. So we can write simply it as G of B comma A, which is B to A, it's a 5. Similarly, if the last vertex is C, then obviously if the last vertex is C and there are no unvisited vertices, then immediately we need to reach the source. So that's what the problem. So we need to start from source, visiting all the vertices exactly once and come back to the source. So if the last vertex is C and there are no unvisited vertex, so obviously we need to go to the source. So G of C comma source. So CA, which is a 6. And the next possibility D comma pi is equal to G of D comma source. So it is 20. Okay, so the only possibilities are this one. The only possibilities are this one. Now let us assume if set contains 1. 1 means unvisited vertex is 1. So I write here 1 unvisited vertices. 1 unvisited vertex. Okay, so for example, if we are at B and there is only one vertex, so what are the remaining vertex? For example, if we are at B, what is the remaining vertex, unvisited vertex? It may be C or it may be D. For example, if our graph is having one more vertex like this one, B, C, D, E, right? So if our graph is having one more E, then there is one more possibility E. So we need to check the cost for each and every edge. If B, B to C, B to B, B to E. That means the set contains only one unvisited. So if we are at B, the unvisited can be C, and similarly if we are at B, the unvisited is D. So two possibilities. So we are at B, so unvisited vertex, it may be C or D. So we need to find out this one. So what's the formula? Minimum. So here our set is having only one element, so we need not write this minimum because we will get only one formula. So C of BC plus function of, what is this one? Consider it as a J. So J, that means C comma G of J comma C comma set of C minus C. Set of C minus C. So this can be written as a pi. So obviously, so we can replace this one. So we are having the set as C. We have to subtract the C itself from the set. So the remaining is pi. Okay. So what is the amount here? What's the cost here? C BC. What's the BC cost? B to C 13 plus G of C comma. Sorry. Yes, this is the thing I have written wrong. So G of C comma pi. Okay, C comma pi. So what is the value of this GC pi? Already we have calculated here. So that's what we are saying in the dynamic programming. So the complex problem will be divided into subproblems, and we are solving the subproblem and we are storing the result so that in future, if it is required, so we can make use of the value from the memory. So here already we have calculated, so we need not calculate once again. So we can simply use this value 6. So here 13 plus 6, which is 19. 13 plus 6 is 19. And now let us calculate the second thing. So the next possibility, B comma D. If the unvisited vertex only one is D, then C B D plus G of D comma pi. Because the set is having only D and we need to subtract the same vertex from the set. So which is nothing but pi. And here what's the value? BD, HBD, B and D. It's a 10 plus G of D pi, which is 20. So what's the value here? 30. So we need not select the minimum because only one calculation. This is 1 edge and this is 1 edge. Okay. So this is 19 and this is 30. So now change the vertex. If we are at C, the possibilities are B. Okay. So cost of CB plus G of B comma pi. So which is the cost of CB? CB it's 9 plus GB pi. It's a 5, which is 14, which is nothing but 14. And the next possibility, G of C comma D. If the unvisited vertex is D, so cost of CD plus G of D comma pi. So cost of CD, edge C D is 9 plus G of D pi 20, 29. Okay, so we have completed the two vertices. Now, if the vertex we are at D, if we are at D, so G of D comma, the possibilities are C, so which is cost of DC plus G of only one element, so C comma pi. So DC is a 12 plus C pi, which is 6, is equal to 18. And there is one more possibility. If we are at D, the next unvisited can be B. So C dB plus G of B comma pi. B comma pi. Then see dB. So dB means 8 plus G of D pi, which is a 5. So which is 13. So we have completed all the possibilities if unvisited is one vertex. If unvisited, so just listen carefully. So if the set is having only one unvisited and we are at B, then the possible unvisited vertex will be C and D. And the next possibility, if we are at C, the next unvisited will be either B or D. And if we are at D, the next unvisited will be either C or B. So we are calculating for all the possibilities. Now, so we have calculated all the possibilities if set is equal to 1. Now calculate with set is equal to 2. That means if set is having two unvisited vertices. Two unvisited vertices, right? Now calculate G of B, okay, comma, if the set is, if we are at B, the next two unvisited can be C comma D. Okay, C comma D. So how we can write this one? So G of, we have to write down this formula. So we are having a two possibilities, two edges. One is BC, another one is BD. So among that we have to select the minimum. Okay, so previously in the set we are having only one unvisited vertex. So we need to calculate the minimum because we are having only one edge. There is the possibility of having one edge. But here we are having in the set two unvisited vertices. So that means there will be a two possible edges. So among those two possible edges, we need to select the minimum one. So how we can write? So G of, I'll write here, okay. So minimum of cost of BC, cost of BD. So these two are the possibilities. Plus G of, okay, what's the formula? G of J. Here J is C, comma, set minus J. So set minus, here the set is having two elements. So set minus C, obviously it will be D. And here also G of, here J is D. So D, comma, set minus D, it will be C. So we need to select the minimum cost among these two. So what's the cost of this one? So BC, okay, BC, B to C is 13 plus G of C comma D. Already we have computed this one. G of C comma D. So G of C comma D, which is 29. So this will be 29. So 13 plus 39, right? So that will be 42. Okay, and what about this cost? C of BD. BD is a 10 plus G of DC, already calculated. DC, which is 18. So the cost will be 28. So among these two, which one is the minimum? So this is the minimum value. Okay, we need to select that one. And next, so this is the possibility. If we are at B, the next possible edges will be either C and D. Now, G of, if we are at C, the next possible unvisited are B and D. What we have to do? So minimum of cost of CB and cost of CD. And here the J value is B, so B comma, from the set we are removing the B, so the remaining is D. And here it is D, and in the set, from the set we are removing the D, so it will be B. So what's the cost? Cost of CB, what is the CBH? 9, so this is a 9 plus G of B comma D, already we have computed, so BD, so this one, 30, which is 39. And what about this one? CD, C to D, it is 9 plus DB, here DB, which is 13, which is 22. Right? So among these two, which is the minimum? This one is the minimum. This one is the minimum. Okay. So among these two, this is the minimum. Among these two, this is the minimum. So if we want to consider the edge, we have to consider this edge. That means C to D. And if you want to consider here the edge is B to D. Okay. Now, so what happens here? Again, check one more possibility. So there is one more possibility. G of, if we are at D, the next possible edges will be B comma C. So how we can write it? So minimum of cost of DB and cost of DC plus G of, here B is a J, and from set remove B, so C. And here also G, the J is C, from set remove the C, so it will be B. Now calculate the cost. DB, so DB which is 8 plus G of B comma C. G of B comma C, which is 19, which is 27. And what about this cost? DC, D to C, 12 plus G of C comma B. G of C comma B, which is 14. So which is 26. So among this one, this is the minimum. Sorry, this is the minimum. Okay, this is the minimum. So if you want to consider the edge, we need to consider D to C. Okay, so here we have completed the set 2. That means set of 2 unvisited vertices. Now we will see set of 3 unvisited vertices. So if S is equal to 3, so 3 unvisited. So what are the possibilities? So G of, so 3 unvisited vertices means B, C, D. Because in our graph we are having 4 vertices. Among these 4 vertices, 1 vertex we are considering it as a source, and remaining 3 are the unvisited vertices. So simply here we can write it as source, and in the set B, C, D. All the 3 are unvisited. All the 3 are unvisited. Now what we can do here? So we can write it as minimum of cost of AB, cost of AC, cost of AD plus G of here J is B, so G of B minus set minus J, set minus B. Here the set is having BCD, and among that we have to remove this B, so it will be set of C comma D. And here also G of C comma, and here the J value is C, from set we have to remove C, so it will be B comma D. And here also G of J value is D, and we have to remove D from set, so it will be B comma C. Now calculate here, right? So we need to consider the minimum among these three. So CAB, that means HAB, A to B is 10 plus G of B comma CD. Already we have computed this one. G of B comma CD. Okay, what's the value? So we are having two values and we have to consider the minimum. So among these two, 28 is the minimum. So we have to consider 28. So the result is 38. And coming to this one, A to C. So A to C, it is a 15. 15 plus C comma BD. Already computed, C comma BD. Here also we got two values. Among these two, we have to consider the minimum. What's the minimum value? 22. So here we need to do 22, which gives 37. And coming to this one, A to D, which is 8 plus G of D comma BC. D comma BC, among these two, the minimum cost is 26. Consider 26, which is 34. Okay, so among these three values, which one is the least? 34 is the least. Right. So we have completed this one. There are no other possibilities because the source, from source, let us consider all the remaining three vertices are unvisited. So that also we have computed. So we need to stop here. Right. Now we need to find out the path with the minimum distance. So what is the minimum distance among these three? So only 34. We are getting 34, right? So all the remaining values, that means remaining 37 and 38, both are greater than 34. So here we are having only one path with a minimum cost, that is 34. Now we have to write out the path. So what is the edge of this 34? A comma D. So from source, the next visited vertex is D. Okay, next visited vertex is D, and then we need to find out the next edge from this function GDBC. Go to here, GDBC. Which one we have considered? This one. So from D, next vertex is C. So we have to consider this DC. The next vertex is C. Right? And again, go to this function for finding the next edge. So from C, next edge, C to B. So go to here, C to B. So edge is C to B. That means B. Okay, B. Because here we are having only one value, right? So go to the B to 5. B to 5. The next edge is A. So obviously it will return back to A. So here the cost is 34. So this is the shortest path. Okay, the shortest path means, so minimum distance visiting all the vertex exactly once from the source and coming back to the source. Now we'll see A to D, it is 8. D to C, it is 12. C to B, it's 9. And B to A, it is 5. So you can consider 8 plus 12, 20, 29, 29 plus 5, 34. So which is this one. So we need to consider this edge. And from this, we have to consider this one. From this, we have to consider, so C comma B, this one. And from this, we have to consider this one. So these are the edges. So this is the order we have to, the salesperson or the salesman traverse the vertex with a minimum distance. Right? So if you are having 5 vertices, the one more calculation will be there. So this is one more calculation, and after that we'll get the final calculation. So once practice with any random graph considering more number of vertices, so that you will be getting understandable. So you will be understanding very easily. So today we'll see one more problem in dynamic programming in algorithms concept, that is longest common subsequence among two strings. Longest common subsequence. Right? So we'll see what is exactly about this longest common subsequence, and then we'll solve a problem. Okay, so the first and important point we have to know is there is a difference between a substring and a subsequence. Okay, so subsequence is different from substring. Okay, so most of the people will confuse about this substring and subsequence. For example, let's take AB, CB as string 1 and some random numbers, string 2. So let us take these two strings. Okay, two strings. So here, first, what is a subsequence and what is a substring? You can see, let us take some AB. Right? So we are having in both the strings we are having the A and B, right? So AB we can call it as a substring. Okay, AB we can call it as a substring, common substring in both the strings. And if you observe here, then how it differs from subsequence? So sequence means order in which we are arranging the alphabets or characters or numbers or anything, right? Elements. In general, we can call it as elements. So arranging the elements in an order, right? So sequence. So we need to find whether there is a sequence or not. Okay. First, let us take A. Okay. So A, B. In this, we can see the particular sequence. That means A should appear first and next B should appear. Okay. So in between, there can be any number of elements. No problem. Okay, that means there should not be a consecutive. There may not be a consecutive. Okay, so in between the alphabets or in between the elements, there can be anything. But only one thing we have to check: the first A should appear and then B should appear. That means before B, A should appear. So here A we are having, and then B, AB, okay, AB is one subsequence. And what about C? A, B, C, A, B, C, and here we are having A, B, and after that we are not having C. In the second string we are having a C, and after that we are getting A and B. So we can't tell that A, B, C as a subsequence, okay. And see, let us start with the B. Let us start with the B. So B afterwards C. You can observe here B afterwards C. Yes. So that will be a subsequence. And B, C, and again we are having a B. So here also you can observe B, C. Again we are having B. Okay. B, C. Again we are having B. So there is a sequence. So even though in between B, C, B we are having some more elements, right? That doesn't bother about that, right? Subsequence means you have to follow the sequence whether the elements are following the sequence in the second string or not. So B, C, B. Yes. And if you start with the C. So C followed by B, you can observe C is here and followed by B. Okay, B appears after C. Yes, correct. So CB, CB is one more sequence. Next, CB, and there are no other elements, right? Next, last one is a B. So here the last one is a B. You need not write that. So these are the common subsequences. Common subsequences. You can see. So first one A B. So B should appear after A. So here also B is appearing after A. Here also B is appearing after A. B C C before B, right? C before B, right? B C B, B C B, yes. Next C B. If you take it randomly, take this one A B C B. So A should appear, yes, we got it. Next B should appear, yes, we got it. Next C. So there is no string, right? So in the second string, C is appearing before A and B. So A B C B is not a subsequence, only this one. And among this one, the longest common subsequence. So this is the longest common subsequence because it is having some 3 elements. So I am generally writing it as elements. You can consider it as a characters or numbers. Okay, right. So how to find all these things? How to find all these things? So just we have to remember 2 formulas. And first of all, we need to draw a matrix. Matrix means rows and columns. So towards the rows, we have to write down one string. Towards the columns, we have to write down another string. So that we'll get some matrix, 2 by 2 matrix. Okay. See. First, what's the length of this string? You can consider the same string. So length is 4, and here the length of this one will be 1, 2, 3, 4, 5. Now the matrix, we have to draw the matrix with 4 by 5. So you can draw either 4 by 5 or 5 by 4. So you can go with the 4 by 5 or 5 by 4. So if you go with the 4 by 5, so number of rows will be string 1, number of columns will be string 2, and here also number of rows will be string 2, number of columns will be string 1. Okay, so like this we have to first draw the matrix. Okay, right. First we'll draw the matrix. Right. See, I write here. So A, B, C, and B. And here I write B, D, C, A, and B. So first, design a matrix, a table, and then we'll start the procedure. We'll see your formulas, and then we'll start the procedure. How we can find out the longest common subsequence. Right. So you can observe here. So extra, we have written 1 column and 1 row. You can observe here, right? So this is again separate column and separate row. Right. So initially fill all these first row and first columns with zeros. First rows and first column with zeros. And towards this one it is string 1, and towards this one it is string 2. Right. Now let us see, the index is I, and here the index is J. Okay, how can we represent this particular box? So corresponding rows and corresponding columns. Okay, so this particular portion we can represent with corresponding rows and corresponding columns. So for everything we'll get some I value and J value. Consider it as an index. Okay, simply you can consider it as an index. So I, J can represent the corresponding column. Now, what are the 2 formulas we have to remember? So I'll write the formulas here. If, okay, so consider S as a string. Okay, so S of I is equal to S of J. Consider any string. So this is a string or a character, whatever it may be. So S means this one, A. Here S means this one. So S of I is equal to S of J. Then what we have to do? So we have to add with LCS. So this is usually called it as a LCS. So longest common subsequence, LCS. LCS of string of I minus 1, J minus 1. So we need to find out, or we need to add one number to this particular box. So this particular column. Okay. this particular cell. So 1 plus LCS of S of I minus 1, J minus 1. Similarly, the next part, if S of I not equal to S of J, what we have to do? So we have to select a maximum value among LCS of S of I minus 1 J or S of I J minus 1. Okay, I J minus 1. For example, let us consider 0, 0, 0, 1, 0, 2, 0, 3, 0, 4. And here 1, 0, 1, 1, 1, 2, 1, 3, 1, 4. 2, 0, 2, 1, 2, 2, 2, 3, 2, 4. For example, consider. So if you want to fill this particular position, so here just remember two things means 0, 0 means ith row, jth column. 1, 0, first row, 0th column. Okay, and this one 2, 2, second row, second column. Okay, second row, second column. So we are starting from 0 and initial first row and first column, just avoid it. Okay, starting from this one. So 0, 1, 2, so second row, 0, 1, 2, so second column, right? So let us assume that. And we will see this formula. 1 plus LCS of S of, for example, if you consider 11, here S of I is equal to S of J. Okay, so S of I is equal to S of J, S of 1 is equal to S of 1. What we have to do? If both are equal, we need to add 1 plus LCS of S of I minus 1. I minus 1 means S of 0, J minus 1, 0. So if you want to, if the elements are equal, S of I and J, both the elements are equal, that means these characters, okay, these characters are equal, then we have to add 1 to this particular element. So S of 0, 0, 0, 0 means this one. So diagonal. Okay, we have to add to the diagonal. For example, if it is not equal, then what we have to do? So we have to go with this one. So LCS of, maximum of, if both are not equal, for example, let us take S of 2 and S of 2. Consider this one. Okay, now what happens? We need to take maximum of LCS of I minus 1, 2 minus 1, 1, J, 2, or LCS of I, 2, J minus 1, 1. So we need to consider 1, 2 and 2, 1. So 1, 2 and 2, 1. So we are checking about this particular cell, and if both the elements are not equal, okay, if both the elements are not equal, so for example, consider this one, S1 is equal to S2, okay. So if both the elements are not equal, then we have to check the maximum of either previous row or previous column. So the same thing, see, 1, 2, 2, 1. So 1, 2 means this one, 2, 1 means this one. So we need to remember these two formula, and we have to fill out all the table. So just for reference, I have written the indexes. Okay, so usually we should not write the indexes. We have to fix the values. So all positions initially 0. So that's why we have added a first row and first column with zeros. Okay, now we have to traverse. So how? See, A and B. Okay, A and B. Here I'll write the strings 1 so that we can erase the portion. So string 2 is B, D, C, A and B. So I'll erase this one so that there will be no confusion, and we can simply use the word, right? So string 2. See, this one is string 2 and we are representing it as J. Okay, so now we can observe A and B. Okay, we are comparing the elements A and B. So that is nothing but S of I comma is equal to S of J. So A, B, both are equal or unequal? Obviously, these two are unequal. So if these two are unequal, what we have to do? So we have to add if both are not equal, then we have to do maximum of LCS of I minus 1 J, I and J minus 1. So obviously we have to select either portions. Okay, either portions. So either portions means we have to select the maximum of either this portion or this portion. So diagonal. So both are equal. Okay, both are equal. What we have to do? So we can take any of these things. So let us take this one, and let us assume we have taken from this particular cell. Okay, we have taken this particular cell. So give an arrow mark through which direction, through which cell we have taken. And next, A and D. Compare A and D. Here also not equal. Then we have to apply the second formula so that these two positions will get. So among these two, which is the maximum? Both are equal. So you can select either. So I'll select from this cell itself. Again, I'm selecting only this one. So I'm writing this arrow mark. Else, if you consider here, from here, you have to write the arrow mark in this way, because we are considering this 0 from this particular cell. Okay, so anything we can do, no problem. So I select from here, and A and C, again both are not equal. So then again compare and select the either. So again I'll take 0 and both are equal from this cell. Now A and J, both are equal. So if both are equal, we have to add to S of I minus 1 J minus 1. So what we have to add from here, diagonally we have added. So here 0, it becomes 1, and the arrow mark should be in a diagonal position. Okay. So 1, and in this way we have taken 1. Now A and B, both are not equal. So we have to compare and we have to take the maximum of diagonal. So here we are having 1, here we are having 0. So a maximum of 1 comma 0. So obviously we have to consider 1. So I consider 1 and that is from this cell. Okay, so hope you understood. Very simple. So just applying these two formulas. Now coming to this one, B and B both are equal. So in the diagonal, so we have to add 1 to I minus 1, j minus 1. So this one. So this becomes 1 and we have taken this from diagonally. And next B and D both are unequal. So if it is unequal, we have to consider a maximum among these two cells. I minus 1 j, I j minus 1. So these two cells. So it is 1 and I have taken from this cell. Okay, coming to B and C both are unequal. Again, in the diagonal 0 and 1, we have to consider 1 and I have taken from this cell. And again B and J both are unequal. So diagonally here we are having 1 and here we are having a 1. So both are equal, we can consider anything, right? So I'll consider here 1 and I'll consider from this cell itself. You can also consider, you just try at home by considering this one. Okay, no problem. Now B and B, so both are equal. Then we have to add 1 to the I minus 1 and j minus 1. So here 1 it is there, now it becomes 2 and I have taken from this particular diagonal position. Next, C, B both are not equal, so I have to consider either from 0 or 1. So diagonal, we have to consider the maximum, and 1 is the maximum. I take 1 and from this cell, so arrow mark will be towards upward. So C and D both are unequal, both are 1s, so same thing, and we can consider any value, right? Any cell. Next, C and C both are equal. Now we have to update, that means we have to increment by 1 of this particular diagonal element. So it becomes 2, and here we have considered like this. Okay, next, C and A both are unequal. So 1 and 2 are there diagonally, so we can consider the maximum. So I'll consider 2, and this is from this cell. And C and B both are unequal. So here in the diagonal, both are having the same value. So you can consider anything and use an arrow mark. Now B and B both are equal. So increment the diagonal element 0. So 0 will become 1, and arrow mark will be like this. And B and D both are unequal, right? B and D both are unequal. So among these diagonal, we have to consider 1, and I am considering from this cell. And B and C both are unequal. So 1 and 2 are the diagonal elements. So 2 will be the maximum. I am considering this way. And B and A both are unequal. So both are unequal means again we have to consider the maximum among the diagonal 2 and 2. So both are equal. So I'll consider the same thing. So I'll consider from this one. Okay. So B and B both are equal. So increment the diagonal element. So 2 and it will be 3 and in the diagonal. So now we have filled the complete table based upon with the help of these two formulas. Okay. Both the elements are equal. Then increment the diagonal element with 1. And if both the elements are not equal, so select the maximum value among the just previous row or a previous column. So now what is the maximum value? 3. And starting from 3, follow the arrow marks. If there is a diagonal, write down the element there. If it is a diagonal, write down the element. So important, right? Point. If there is only a diagonal, then only we have to write down the element. And that element should be written from right to left. So here we are having a diagonal, right? So this 3 we got from this particular cell. Okay, this 3 we got from this particular cell. So what we have to do? We have to select the element B. Okay, now we are at 2. There is no diagonal, so we should not consider it. So from 2, the arrow mark is this one. That means we got 2 from this particular cell. So consider now this cell. Okay, this cell. So here we are having a diagonal. So we got this 2 from this particular diagonal element. So what is the value? C. So write down here C. Now we are at this position. Here the arrow mark is not diagonal. So we got this value from this particular cell. So moving towards this one. Right? So here again we are having some diagonal. That means we got this with this one. Okay, B. So write down here B. Now we are at this position, and here the weight is 0. So the longest common sequence is BCB. Just now we have seen the longest common subsequence. So just following the same way. Okay, right? So in this way we can solve the longest common subsequence. So just we have to iterate both the I value and j value. Right? So this is also a recursive function. From the previous cell we are using the value. So we are updating 2 from this particular cell. That means the result of this cell is already been saved. And from here we are updating here. And from this cell we are updating into 3. Right? So hope you understood this one. So the longest common subsequence among these two strings. Longest common subsequence is BCB. Among these two substrings. It is BCB. Okay. So you can consider any two substrings and try out this particular method, so that definitely you will get the longest common subsequence. And we can get a multiple long common subsequences also. Okay, if it is having a multiple paths, automatically we can get multiple common subsequences. So today we'll see one more example on longest common subsequence problem using dynamic programming. So we usually call it as LCS problem. So which is the longest common subsequence. Right? So first we need to take two different strings and we need to find what are the common subsequences Okay, so in our previous session we have discussed about this one. So the difference between subsequence and the substring. So coming to the subsequence, the order of elements can be any. I mean, we have to follow the order of the elements, not the consecutive elements. Okay, so that we have seen in our previous session. I'll post the link in the description box. Please follow that, and then you can listen. So we have taken two different formulas in order to fill the 2 by 2 matrix. Okay, see, let us take the strings. Consider str1, a string as AB, C, D, D, and AB. And coming to the string 2, BD, CA, BA. Okay, so these are the two different strings. Now we have to find out the longest subsequence among these two strings. First, we have to draw the horizontal and the vertical lines. I write here A, B, C, B, D, A, and B. And here I write. So initially take it as zeros. Consider initial values as zeros. Okay. So in the vertical, we can write it as B, D, C, A, B, and A. Consider the boxes. We need to fill all these columns, and these columns should be filled with the help of two formula. So here also initially we are taking it as zeros initially. Okay. So we have taken the complete cells, and now we need to fill all the cells by using two formula. The first one, if xi is equal to xj, if both are equal, then the cell value will be, okay, we can write it as cell of I j will be 1 plus cell of I minus 1 and j minus 1. So we need to add one element, I mean 1 to the cost of I minus 1 and j minus 1. And the second one, if I not equal to j and both the elements are not equal, then the cell cost of ij will be a maximum of cost of I minus 1, j, or c of I and j minus 1. Among these two, we have to select the maximum. Okay, select this one. B and A, right? So let us consider this as x and this one as y. So xi, xj, sorry, I think is y, and here also, right? A and B both are compared, and we know that both are not equal. So we need to consider the maximum of I minus 1 j and j minus 1. So we have to consider I minus 1 j. So let it be I and let it be j. I minus 1 means this one. J minus j means this one. And I minus 1 j or I j minus 1. So both the cells are this one, diagonal cells. So here we are having the same number. So what we have to do? We can take any value. So I will consider this one and just place the array from which cell we are taking this. I am taking this from this array, from this cell. Now B is compared with B. Both are equal. Then we have to add 1 to the cost of I minus 1 j minus 1. I minus 1 j minus 1 means this one. Okay, this diagonal. So we need to add 1 to this particular diagonal. So 0. So now it will be 1, and we have taken it from diagonal position. Okay. Now B and C both are not equal. Among these two, which one is the max? 1. So I will take 1, and we have taken this from this particular cell. And again, B and B both are equal. So we need to add this one. 1, and we got this from the diagonal. And B and D both are unequal. So we need to consider a maximum from either this cell or this cell. So 1 is a maximum, and we have taken this from this cell. And B and A both are not equal. So we have to select maximum among these two cells. I consider this one because 1 is a maximum among 0 and 1, and we have taken from this cell. Now again B and B. So we have to add 1 to I minus 1 j minus 1. So this one is I minus 1 j minus 1. So obviously it will be 1, and we have taken from diagonal position. Now coming to the second one, D, A both are not equal. So what we have to do? So we have to consider the maximum among this one and this one. So both are equal. I am taking here, and I am taking from this cell. D and B both are unequal. So from these two diagonal positions, we have to consider a maximum. 1 is a maximum. I am taking 1, and we have taken it from top cell. Okay. So put the arrow mark towards the upward. Next, D and C both are unequal. We need to consider a maximum among these two diagonals. So both are 1s. So obviously the result will be 1, and we can consider it from any cell. You can write a leftward arrow or upward arrow. Next, D and B both are unequal. Again we got 1, so I'll take 1 from this particular cell. D and D equal. So we have to add 1 to Ci minus 1 J minus 1, which is this one. So 1 plus 1 it becomes 2, and we got 2 from this here. So D and A both are unequal. Among these 1 and 2, we have to consider the maximum. I consider the maximum as 2. We got this from this cell. D and B both are unequal. Again 1 and 2 are there. Diagonally we need to take maximum. I take a maximum, and I am taking from this particular cell. Now C and A both are unequal. So if both are unequal, we have to consider a maximum among diagonal. Both are zeros. Again I will consider 0. I consider from this cell. Or okay, you can also consider from this particular cell. No problem. C and B both are unequal. 0 and 1. Diagonally we are having two values. Among these two we have to select the maximum. So I am considering 1, and we have considered from this particular cell. C and C both are equal. So we need to add 1 to I minus 1 J minus 1, which is this cell. So 1 plus 1 it becomes 2. We got 2 from this particular cell. And C and B both are unequal, and 1 and 2 we need to choose a maximum among this 1 and 2. So 2 is a maximum, and we got this from this particular cell. And C and D both are unequal. Among the diagonal we have to select the maximum. So both are equal. So we can select 2 either from this side or this side. I consider this side. No problem. Anything. And C and A. So C and A both are unequal. We are having a diagonally 2 and 2. So we can consider 2, and we can select either. C and B both are unequal. 2 and 2. I consider 2, and let us consider upwards. No problem. And A and A both are equal. So we need to add 1 to Ci minus 1 J minus 1, which is this cell. Here it is 0. Now it becomes 1, and we got 1 from this cell. And A and B both are unequal. So we need to select a maximum among diagonal 1 and 1. So both are equal. So we can consider any cell. So A and C both are unequal. 1 and 2 are diagonals. We need to select a maximum among these 1 and 2. So I'll select 2, and this comes from upward cell. And next A and B both are unequal. Again we are having a 2 and 2. We can select any. Both are equal. We can select any number. Okay, I mean the number from any cell. So I consider from this one. Next A and D both are unequal. Again diagonally we are having 2 and 2. So from this we got a 2, and I consider from this cell. A and A both are equal. So we need to add 1 to the I minus 1 J minus 1. That is a diagonal here. So 2. So 2 becomes here 3. We got 3 from this particular cell. And next A and B both are unequal. Among these diagonal 2 and 3, we have to consider the maximum. So I am considering 3, and that we got from left side cell. And B and A both are unequal. So 0 and 1 we have to consider maximum. I consider maximum, and we got this one from upward cell. B and B both are equal. We need to add 1 to diagonal. So here it is 1. So after adding 1 it becomes 2. So we got 2 from this particular cell. And B and C both are equal, and diagonally we are having a 2 and 2. So both are same. We can consider it as a 2, and we can consider any cell. And B and B both are equal. So obviously this diagonal position we need to add 1. So 2 becomes 3, and here from this cell we have considered the 2. Next B and D both are unequal. So here diagonally 2 and 3 are there. Among 2 and 3 we got only 3. So we have to consider a 3, which is selected from left cell. B and D both are unequal. Sorry, B and A both are unequal. Here diagonally we are having the same number 3 and 3. So we can select any number from any cell. I consider this one. And B and B both are equal. Diagonally it was 4. So we have to write it as a 4, and we got it from diagonal. Next A and A both are equal. Diagonally 0. It becomes 1. So from here we got it 1. Next A and B both are unequal. So among 1 and 2 we need to take the maximum. So 2 is a maximum. I am considering 2 with this particular element. So A and C both are unequal. Diagonally we are having the same element. So we can take the same element from either cell, either left cell or up cell. And A to B both are unequal. Again we are having 2 and 3. Among 2 and 3, 3 is the maximum selected from up cell. A and D both are unequal. We are having a diagonally both are equal 3 and 3. So obviously we can consider 3, and we can select any cell. A and A both are equal. So if both are equal, what happens? Diagonally 1 should be added to I minus 1 J minus 1. This is I minus 1 J minus 1. 1 should be added to 3. So it becomes 4, which is a diagonal position. And again A and B both are unequal. So we need to select a maximum among these two diagonals. So same value, which we are taking from 4. See here we need to select the last one. A and B both are not equal. Okay, A and B both are not equal. So we need to select either this cell or this cell, because here we are having both 4, right? So we need to select the maximum, and here we are having the same number. So we can select the 4, and either from left cell or up cell, you can select anything. So if you consider the left cell, so in such a situation, you can get a more than one longest common subsequence. Okay, we are having two paths. Either we can go with the left cell, or you can go with the up cell. So first case, if you are selecting this particular cell, that means the left cell, what is the longest subsequence you can see? So left cell. If you consider a left cell, okay, so what happens? So from here we need to start traveling. So this one and this 4 comes from this cell. So here we got a change. So which is A. Okay, now we are at 3. This cell comes from here 3, and again diagonal. So this cell comes from C. So here there is a change. So B, and writing everything from right to left. Okay, so we are at 2. Now we have considered it as 2. Okay, and here this cell we got from this particular cell. So there is a change. So that is C. 1. So this we have considered 1. So here this cell we have got from A. It was updated. That means a change. So we have to consider this a B. Okay, the left cell. This is the longest common subsequence among these two strings. You can see B, C, B, A. So the same order it was following from string 1 and string 2 in both the strings, the same order. So B followed by C followed by B followed by A. Here also B followed by C followed by B followed by A. So we are not considering the substring, we are considering the subsequence. So whether it is following the same sequence or not. Right? Next, so if you consider it as an upcell, so if you consider it as an upward cell, if the last cell was taken from upward, so if the arrow mark is from this side, we can check. So this cell we got from this one, and here it is changed from the A. So what is this one? B. Now we are at A, so the direction, just follow the direction. And we got a 3 updated from D, so here we have to select A. Okay, next, this one we got from this cell, so which was not updated. Again, this was appeared from this particular cell, which was updated, right? So now it is C. Now we move to 1, and this cell we got from above cell, right? Here we got. Here there is a change, it was updated from A to B, right? So we need to consider B. Now we are at A, which is 0. So this is also the longest common subsequence. How we can check? We can check. So check the same thing in the strings. First B, yes, followed by C, yes, followed by A, yes, followed by B, yes. So the order is same here also. Here also the order is same. So B followed by C, C followed by A followed by B. So both are the longest common subsequences. So this is an example where we can get multiple subsequences. Okay, it's not limited to only one subsequence. So we can get maximum subsequences with a number of elements. So if it is a longest subsequence, 4 element subsequence, we are getting a 2 answers, so 2 solutions. Okay, so hope you understood. So first we need to draw the table and initialize it with the zeros for first row and first column, and then use these 2 formulae to fill each and every cell and use the arrow marks in order to travel from bottom to top. Here also we need to write the solution from right to left. Write down the elements from right to left. So BCBA is one solution, BCAB is another solution for these 2 strings. So there will be a more number of subsequences, but this is the longest common subsequence. We'll see one more problem in algorithms concept, that is multi-stage graphs problem. Multi-stage graphs. So here the name itself indicates the multi-stage graph, means here this is a graph problem. It is a graph problem. And what is this problem? And here we need to find the shortest path from source to destination. So already we have solved the similar problem by using a different methodology, by using the greedy methods. But here we are supposed to solve this one by using the dynamic programming, right? So finding shortest path from source to destination. So here we are having a few constraints. In order to find the shortest path, we are supposed to have some constraints. So that is, we need to use the weighted and directed graph. So only we have to take the weighted and directed graph. And here the vertices will be divided into different stages. Okay, so some sort of partitions. Right? So vertices were divided into partitions called stages. So each stage will be having a subset of vertices, and so the direction should be only one word, right? So if the direction is from current vertex to the next vertex, so there should not be an edge between next vertex to the current vertex. So I'll show you the example so that you can understand. So if the graph is like this, so if A, B, and let us take this C, D, okay. So these are different vertices, okay. If there is an edges like this, okay. So this is one partition, this is another partition. So here we can say K1 is a stage, K2 is another stage, and K3 is another stage. So in this stage K1 we are having one vertex, in K2 we are having two vertices, in K3 we are having one vertex. And there should not be direction in this way. So in this example you can see the direction is towards the destination, right? A to B or A to C, and B to D or C to D. And the direction should not be like this. So one is towards destination and another one is towards the source. So this type of graph is not applicable, right? So the direction should be towards the destination only. For example, let us take this as a source, right? And this as a destination. Then the direction should be towards the only destination, not towards the source. And also every edge should have a weight. For example, the weight is 5, 2, 3, and 6. So you can call them as a weight or a cost or a distance, anything, right? Weight, cost, or a distance. So there should be this one. So such type of graph we can call it as a weighted directed graph. So here we are having the directions and also weight for each and every edge. So this will be the weighted and directed graph. So in order to solve this graph problem, multi-stage graph problem, so the graph should be weighted and directed, and the partitions, the complete vertex should be in partitions called stages, and the direction should always to be towards the destination, right? Then we can solve this by using the dynamic programming, and such type of problems can be solved by using two approaches. One is forward approach, another one is backward approach. So if you are using this forward approach, we are supposed to select the destination first and we need to solve the problem. So that we call it as a forward approach. Don't get confused. In the forward approach, we are supposed to start our process from the destination itself. And if it is a backward, we have to start from the source itself. Okay, now in this session, we'll see the forward approach of solving this multi-stage graph problem. So let us take an example and we'll solve this multi-stage graph problem using dynamic programming using this forward approach. So come up with an example. See, let us solve this example. So this is a weighted and directed graph. You can see the directions, and also for every edge we are having some weight or cost or distance, right? And also all the directions are towards the destination. For example, consider this as a source and this one as a destination. Right? Now we need to find the shortest path from source to destination, right? So based upon the edges. So we can start from source and we can reach the destination in different paths. We can go with A to B, B to F, F to H, or A to B, B to E, E to H. See, A to B, B to E, and E to H. A to C, C to F, F to H. A to D, D to G, G to H. Similarly, A to C, C to E, E to H. So like this, we will be having a lot of solutions, lot of possible paths, right? But we are supposed to select the path with an optimized route. That means the weight, the cost should be a minimum. That means that we call it as a shortest path. So such type of problems, we can say them as a optimization problems. So where the problem is having a lot of solutions and we have to select a solution based upon the constraint. So here also the constraint is shortest distance, shortest path, right? Now let us check here how many stages we are having. Let us assume this is a stage 1 and this is stage 2, this is a stage 3 and this one is a stage 4. Right? Let us assume K as a stages. So there are 4 stages. So K1 is having only 1 vertex, K2 is having a 3 vertices, K3 is having a 3 vertices, and K4 is having only 1 vertex. So we need to start from the destination if you are going with the forward approach. So let us go with the K4, right? So we can call it as a cost of K4, comma, what is the H, I mean vertex H. We need to find out the cost for K4 to H. So where the formula will be the distance of H to H. So which we can call it as a cost. Okay, cost of H and H. So the destination and source of both are equal, then obviously the weight is 0, right? If the source and destination both are equal, then we can say the weight is 0. So it will be 0. Now, any other vertex available in K4? No. Now we can move with the K3. So K3, the cost of K3, comma, let us find out for E. Okay, then what is this one? So cost of E to destination, right? So E to destination, what's the cost of E to destination here? The distance from E, comma H plus cost of H, comma H. So here we are having the destination, so E to H and H to H. For example, if it is B, we need to find out the B to E plus the cost of E and H. Okay, hope you understood. So we need to find out the distance from B to H. Then obviously we can say the distance of B to E and from E to H. So similarly, if we are finding out the cost E, comma H, then the distance of E to H and the cost of H and H. If we are having a multiple paths, we need to find out the minimum. So what's the value here? So DE, comma H, 18 plus, we need not find out the value once again because already we have calculated here. So that's an advantage of dynamic programming. So we are supposed to solve the problems and save the solution in order to avoid the calculation. Once again, calculating the same problem. So here cost of H is 0, which is 18. So is there any vertex in K3? Yes, F is there. So once again, cost of K3, comma F. So which means cost of F to destination is equal to the distance from F to H plus a cost of H to H. So what is the distance of F to H? 13 plus cost of H to H. It's 0, which is 13. Next, again we need to find out the cost of K3, comma, there is one more vertex G. So cost of G to H, which we can say the distance of G, comma H plus cost of H to H. So what's the value of this one? The distance of G to H. It is 2 plus 0, which is equal to 2. So we have completed the K3. Now we need to move with K2. K2. So K2 edges are B, C, B. Now let us find out the cost of K2 comma B. Right? Now we need to find out the cost of B to H. So we need to find out the B to H, the cost of B to H. Now you can see, now you can understand why we are writing here this one. So B to H means, so there are different possibilities. So B to E, E to H, B to F, F to H, right? B to E, E to H, B to F, F to H. So there are multiple possibilities. Here we need to find out the minimum. So minimum of distance of BE, distance of B comma E plus, now we are at E, so we need to find out the cost of E comma H. So cost of E comma H, which was already found here, see, right? Similarly, I'll write here D of C comma E, sorry, B comma F, because from B we can reach H through E or through F, okay, two paths. So we need to find out the minimum plus the cost of F comma H. That also we have found F comma H, right? Now calculate DBE. DBE means 4 plus cost of EH, we have to find out 18. So which gives it 22. And next possibility BF, B to F, it is 11 plus cost of F comma H, it is at 13. So which is 24. So we need to consider the lowest, so the minimum. Next, there is one more edge, one more vertex in K2. Now we need to find the cost of K2 comma C. That means cost of C to H. What is the cost from edge, vertex C to vertex H? So that we can also have a minimum because we are having multiple paths, C to E, C to F, C to G. 3 possible paths are there, right? So minimum of D of C to E plus cost of E to H. Similarly, D of C to F plus cost of F to H. Similarly, D of C to G plus cost of G to H. See, there are 3 outgoing edges. So we can reach H from C via E or F or G. So 3 possibilities. So now we need to find out the distance of C to E and cost of E and H. Distance of D to C and F and cost of F and H. Distance of C and G and cost of G and H. So what's the value here? What's the value? D of CE. CE is 9 plus E and H. So what's the E and H? Cost of E and H already we have to find out, right? So here 18. We have calculated, so 18 which is 27. And here C and F, it's a 5 plus cost of FH, already calculated, cost of FH, which is 13. Next, D of CG, it's 16 plus cost of GH, cost of the GH, it's 2. So how much? This is 27, 9 plus 18, which is 27, 5 plus 13, which is 18, 16 plus 2, which is again 18. So we can consider 2 possibilities. One is reaching H through F or reaching H through G. Both are equal cost. Right, leave it. Now, is there any vertex in K2, stage 2? Yes, there is a H, there is a vertex of D. So again, find out the cost of K2 comma D, which is nothing but cost of D to H. So here, whether it is required to find the minimum value. Whether it is required to find the minimum value? No, because only one path is there from D to H. There is no outgoing edge, only one edge is there. So we can write it as D of D to G plus cost of G to H, which gives D to G, which is 2 plus cost of G to H, again it's 2. So 2 plus 2, which is a 4, right? So is there any vertex in stage 2? B, C, D, we have calculated B, C, D, all possibilities. So there is no vertex in stage 2. Now go with the stage 1, which is a source. Then K1, the cost of K1 comma A, which is cost of A to H. How many edges are there? 3 edges are there. So we have to find out the minimum among these 3. So minimum of distance of A to B plus cost of B to H. So we did not find again B to E and E to H. Already we have calculated everything. So A to B and cost of B to H. And see again D of A to C plus cost of C to H. Again D of A to D plus cost of D to H. So among these things we have to find out the minimum. Now find out D of A comma B. What's the distance of AB? 1 plus cost of BH. Already we have calculated somewhere. BH, cost of BH. See, cost of BH, this one. So among these 2 we have considered minimum. So 22, we need to consider the 22, which is the 23 cost. Now D of AC is 2 plus cost of CH. So here we have calculated cost of CH. So 18, we can consider anything, right? In either, because both are equal. So I am considering 18, which is 20. Next, D of A to D, it is 5 plus cost of DH. What's a DH? Once again here, B to H, C to H, and D to H is 4. So it is 4, which is a 9, right? So among these three, what's the minimum? This is the minimum. This is the minimum. So we can consider 9, and this is the first stage. So that means a source. So in order to find the path from source to destination, the minimum path is a 9, right? So we have to find out the path. So 9 means A to D. Okay, so first A to D, then cost of DH. Go to the cost of DH. Where's the DH? This one. So here DH, it is G, D to G. So after D, we have to visit a G, and then cost of GH. What's a GH here? GH. So from G, we can go with the H. From G, we can go with the H. So among all the different paths, this one is the shortest path. You can observe A to D, D to G, G to H, which is 5 plus 2 plus 2, which is 9. So if you go with the A to C, C to F, F to H, 2 plus 5, 7, 7 plus 13, 20 it will take. And if you go with A to B, B to E, E to H, 1 plus 4, 5 plus 18, 23 it will take, right? So this is the only path which is having the shortest distance. So in order to reach from source to destination, the shortest path is A to D, D to G, and G to H. Right? So here what we have to do is we have to start with the destination, and from the destination try to find out the cost from each and every stage towards the destination. So here the cost of fourth stage, which is a destination to destination, the cost will be 0. So only one node is there, right? So once again, one more constraint is here in this problem, the graph should contain only one source and one destination. And coming to the third stage, from the third stage we are having the 3 nodes, and from the 3 nodes we have to find out the cost from each node to the destination, so E to H. If there are multiple paths, we need to find out the minimum. We need to consider the minimum. So how we can use? We have to find out the distance from E to H and a cost from H to H. So here you can find out, here you can understand, if you are finding the distance for cost of B to H, what we are doing, we are finding the distance of B to E plus the cost from E to H. So obviously we have calculated the cost of E and H, the same value we are using here. So in the dynamic programming, the complete problem will be solved into, divided into subproblems. Those are the overlapping subproblems, and each subproblem will be solved and the solution will be stored in the memory, so that in further we can make use of that particular solution in order to get the final solution, optimal solution. So the same thing happens here. For every situation we are saving the solution. So the same solution we are using in our next recursions. So today we'll see one more example in multi-stage graph problem. So in our previous session, we have seen this multi-stage graph problem. So where we have to consider the weighted directed graph. So all the vertices will be arranged in stages, in terms of stages, and the problem is to find the shortest path from source to destination. So using this dynamic programming. So in our previous session, we have seen one example following the forward approach, and here also we will see the same forward approach. And here we are having a different stages. So this is 1, this is 2, this is 3, this one is a 4, and this one is a 5. So total 5 stages. So in our previous session, we have seen about the 4 stages. Now we'll see the 5 stages. So first we have to start with the destination, right? We have to start with the destination, and we need to find the minimum path in each and every stage. So here you can see every stage is having a different number of vertices. For example, in the first stage, we are having only one vertex, that is a source. And in K5, that means the 5th stage, one vertex, it is a destination. And similarly, in the stage 2, we are having 2 different vertices. Stage 3, 3 vertices. Stage 4, again, we are having 2 vertices, right? And you can see B, we are having 2 possible paths. C, we are having 3 possible paths. So among these, we have to find out the minimum, right? So first we need to start with last vertex, that means a destination, right? So now I will go with the K is equal to 5. K is equal to 5. How many vertices are there? We are having only one vertex, that is I. Okay, we need to find out the cost of I. So cost of I, comma, destination I, which is nothing but distance of I and I. So which is equal to 0. So the distance from the same vertex, if the source and destination are the same vertex, obviously it will be 0. Now, any other vertex in stage 5? No, right? Now we have to find out the vertices, the cost in the stage 4. So stage 4 we are having 2 vertices. How many vertices? 2 vertices, G and H. So we need to find the cost of G to I. G to I. Okay, cost of G to I, which gives the distance of G comma I plus cost of I and I. Okay, so which is equal to distance of G and I. It is 7 plus 0, which is equal to 7. Similarly, we need to find out the cost. Any other outgoing from G? No. So cost of H and I. So which gives the distance of H comma I plus cost of I comma I. That means the next vertex to destination. Okay, here the same vertex will be the destination, so we are getting 0. So H and I, which is 3 plus 0, which is equal to 3. So any other vertex in stage 4? No, we have covered both J and H. Now go with the next stage. K is equal to 3, which is having 3 vertices, D, E, F. So D, E, F. So we need to find the distance from the cost from D to I, E to I, F to I. So first, the cost of D to I, which will be from D of distance of D comma the next vertex, that is G, plus cost of G to I. Okay. So this portion we have already calculated in our previous stage, G to I, right? So directly we can use it instead of recalculating, right? That's what the advantage of dynamic programming. So the problem will be divided into subproblems where each and every subproblem will be calculated or solved, and the result will be stored in the memory, and it can be returned whenever it requires. So the same thing happens here. So here the cost of D to C. First let us check whether there are any other edges from D to G. How many possibilities from D to G? Sorry, D to I, right? So there are two possibilities from D to I, right? D to I. How many possibilities? We can go with the D to G, G to I, D to H, and H to I. So two possibilities. Among these two, we have to find out the minimum. So the same thing happens. So I am finding the minimum value here. So D of distance of D comma H plus cost of H comma I. So we need to find out the minimum value of these two. So distance from D to G, which is 1, plus cost of GI, already calculated, 7. So which will be 8. So here you can see the distance from the cost from D to I, the cost from D to I via G is 1 plus 7, it is 8. And here D to H plus cost of. So D to H is 4 plus cost of HI, already we have computed here, right? So 3, which is 7. Which one we have to consider? Obviously 7, because among these two we are having a minimum. So this part we are getting 8 and this part we are getting 7. So our solution is to find the shortest path from source to destination. So that's why we need to always find the minimum value, right? So next, E, we need to find the E. So cost of E to I, that means E to destination, E to destination. So how many parts are there? Let's check here. E to destination, that means I. So one possibility, E to G, G to I, E to H, H to I. So two possibilities, right? So let us check minimum. We need to find out the minimum. So D of E comma G plus cost of G comma I. Similarly, D of E comma H plus cost of H comma I. So we need to find out the minimum among these two. Distance of E and G. E to G, it is 6 plus cost of GI, already it was pre-computed. So GI, it is 7. So which gives a 13 as a distance. The distance of EH, E to H, it is 2 plus cost of HI. Cost of HI, it is 3. So it's equal to 5. So we got the path, this path, through this path we got a distance 13. Through this path we got a distance of 5. So which one we have to select it? So 5 should be selected, right? Among these two. Among these two. So still any other vertex in this particular stage? Yes, F. So we need to find the F also. Cost F to I. Let us check how many edges are there from F. So F to I, how many paths? You can check. F to G, G to I. Similarly, F to H, H to I. Two paths are there. You can observe. F to G, F to H. So same D of F to G plus cost of G to destination. Similarly, D of F to H, F to H plus cost of H to destination. So we need to find out the minimum among these two. What's the distance of F and G? F and G is 6 plus cost of G and I, which is 7. Again we got 13 as a result. Okay, then D of F H, F to H, it is 2 plus cost of H I. So here we have computed it is 3. So which gives a 5 as a result. So among these two, here we got a 13 and here we got a 5. Again we have to select this 5, right? Yes. So any other vertex in stage 3? You can observe in the stage 3, D, E, F. Already we have computed D to destination, E to destination, F to destination. Now we need to find out the cost from stage 2 vertices. So K is equal to 2, which is having the vertices B and C. B and C, right? Now, what we have to find? We have to find from B to I, so which is the cost of B to I. So let us check the possibilities from B to I. That is how many outgoing edges. So B to I, how many outgoing edges? So B to D, and similarly B to F. Two edges are there. And D towards I, F towards I. Two possible paths. So here also we have to consider a minimum. So D of B to D plus cost of D to I. Similarly, D of B to F plus cost of F to I. So you can see already, so B to D, what's the distance from B to D? Oh, B to D, I think it was 2. Let us assume it as 2. So B to D, let us take it as 2 plus cost of D to I. So what is the cost of D to I? Already we have computed. So here we got 8 and 7, and we need to consider the minimum. So 7 is the final value. So it is 9. D of B to F, B to F, it is 3 plus cost of F to I. Here F to I. So 13 and 15 among these two we have to select the minimum. So it is a 5. So which is 8. So we need to consider the minimum value 8. And any other vertex in the stage 2? Yes, C. Now find out the cost from C to I. Okay, C to I. So D of, so C to I. Any other possibilities you can check. So C to D and D to I. C to E and E to I, C to F and F to I. So there are three possibilities here. So we need to check all those things. So C to D plus cost of D to I. Similarly, D of C to E plus cost of E to I. Similarly, D of C to F plus cost of F to I. So among these things, we have to consider the minimum. Let us check the distance or the cost. So D of CD, D of CD, C to D, it is 6 plus DI. What is a DI? So here 7, which is a 13. D of CE, C to E, it is a 5 plus EI, which is again 5, which gives a 10. And D of CF, C to F, it is 8 plus cost of FI, again it is 5, so which is a 13. So among these three, which one is the minimum? Obviously 10 is the minimum. So we got 13, here it is 10 and here it is 13, so 10 is the minimum. So we are considering the 10 as a value. Now, any other vertex in the stage 2, we have computed the distance or the cost from B to destination and C to destination, which are the two vertices available in the stage 2. So completed. Now come with the stage 1. So stage 1, we are having only one vertex, that is A, which is a source. We need to find the cost of A to I, so which gives the distance. So here you can see A to I. What are the outgoing edges from A to B and A to C? So we can go with A to B and followed by AI, A to C and followed by I. So two possible paths are there. That's it. So cost of, so here the distance of A to B plus cost of B to I. And similarly, D of A to C plus cost of C to I. So among these two, we have to select the minimum. So I am writing here minimum. So we need to select only the minimum value. So here also it is a minimum value. Now D of AB is 5 plus cost of BI. So here we have computed BI, right? So here 8, we got a minimum value 8, 5 plus 8, which is 13. And D of AC is 2 plus cost of CI. So among these two, we got 10. So which is 12. Among these two, which one is the minimum? 12 is the minimum. So here A is the source and I is the destination. So in order to travel from source to destination, the minimum distance or the minimum cost is 12. So now we have to backtrack to find out the path. Okay, find out the path. So this is the last stage. A is the source, last stage. So we need to stop the calculation. And here we are considering that the AC plus cost of CI. So we need to consider the edge from A to C first. A to C. And then cost of CI. Go to the cost of CI. So in that we are having a three possible paths. Among these three possible paths, which one we are selecting the minimum? That is this one, C to E. So the next vertex is E. And cost of EI. So cost of EI, again go with this one, cost of EI. Here we are having a two possible paths. Among these two, we are selecting this one because of minimum cost. E to H. So E to H. And cost of HI. Cost of HI goes here. So it is HI, which is the destination, this one. So this gives the optimal result. That means the shortest path from source to destination. Find out the values or weights here. A to C, which is a 2. C to E, which is a 5. E to H, which is again 2. And H to I, which is again 3. Which gives the total cost of 2 plus 5, 7 plus 2, 9 plus 3, 12. This is the minimum cost to find a path from source to destination. So here A is the source, I is the destination. So this is the forward approach where we are considering from the destination itself. So first we need to consider the destination. From that we have to go with the source, towards the source, right? So we need to compute all possible paths in all different stages. So here stage 5, only one vertex, that is the destination. In stage 4 we are having a 2 vertices D and H. In stage 3 we are having a 3 vertices D, E, F. And in the stage 2 we are having 2 vertices B and C. And in the stage 1 only one vertex, which is a source, right? So here we are computing and we are making use of the same result in our next problems. So coming to the stage 3, we are not computing about cost between G and I. So we are considering the value of G and I from the previous result. From here we are considering. So here we are not computing the cost of D and I because we have already computed this cost of D and I in the previous result. So the problem is solved and divided into subproblems, and again the subproblems have been solved and the results have been saved in the memory, and we can retrieve that results whenever it is required in order to avoid the recomputing the values. So this is called the dynamic programming. So this is the multi-stage graph using dynamic programming. So today we'll see one more approach to solve the multi-stage graph problem. So the multi-stage graph problem means finding the shortest path from source to destination, right? So in our previous session we have seen one approach, that is a forward approach. Now we'll see the backward approach in order to solve this multi-stage graph problem. Multi-stage graph. And this is a backward approach. So in our forward approach, we have started from the destination and we have traveled through the source. And now, quite opposite, we have to start from the source and we need to travel through the destination. Right. So here there are a lot of stages. We can see it is 1, second stage, third stage, and fourth stage. So usually we are representing a stage with a K. So K1 is the first stage where we are having only one vertex A, and K2 is a stage which is having 3 vertices B, C and D. K3 is another stage which is having 3 more vertices E, F and G. Now H is the 4th stage, only one vertex, that is a destination. Starting from 1, so in our forward approach we have started from the destination itself. Now we have to start with the source, and the formula is same. We need to find the cost of source to destination. So here K is equal to 1, which is having only one vertex, so we need to find out cost of A to A, source to destination. So here source and destination both are equal. Obviously that will be the distance between A to A, which is equal to 0, because we are at source and we are at destination. So the distance between source and destination is 0, because both are same, right? Now there are only one vertex in stage 1 because it is a source, so completed. Now go to the second stage where we are having 3 vertices B, C and D. So we need to find out cost of source to B, cost of source to C and cost of source to D. So one thing we have to remember, how many incoming edges for B, C and D, because we are traveling from source to B. So if B is having 2 edges, that means there are 2 possible paths from source A to B. So then we have to find out the minimum among those 2. So here we are having only one incoming edge for B, C and D, you can see. So we need not go with the minimum. So only one calculation will be there. So that will be cost of A comma A plus distance of A comma B, that means edge. And here also cost of A comma A plus distance of A comma C. Here also cost of A comma A plus distance of A comma D. So here we are at source, so that's why you need not write this one directly, we can go with the H's, right? So if you are at E, then how to reach to E? So you can reach A to B, B to E, similarly A to C, C to E. So this we are computing here, right? So this will be the cost of A to B plus distance of B to E. That means whatever the vertex is, so just before E, that is already computed. So in the same way, now we are at A, so the cost of A to A plus A to B, cost of A to A plus A to C, cost of A to A plus A to D. So we can compute here, cost of A to A is 0, which is already computed in our previous stage. So that is a dynamic programming. So complete problem will be divided into different solutions, different subproblems, and each subproblem will be solved and the solution will be saved in the memory, so that in order to avoid the recalculation, right? So cost of A comma A is already computed, which is 0, 0 plus distance of A and B, which is 1, so finally 1. And here cost of A to A is 0 plus distance of A to C is 2, so totally it is 2. And here again cost of A to A is 0 plus A to D, it is 5, so it will be 5. So in order to reach from A to B, the distance is 1, A to C it is 2, A to D it is 5. Now, so any other vertices in the stage 2? No, B, C, D. So we have found already the distance from source to B, source to C, source to D. Now go with the 3, stage 3. So what are the vertex available in D3? E, F and G. Now we need to find out cost of A to E. A to E. So how many ways we can go to E, right? So how many incoming edges? So find out the incoming edges of E. So incoming edges of E are 2. One is from B, another one is from C. So we need to find out the cost of A to B, A to C, and then the distance of B to E. So, and we have to use a minimum value, so which is the cost of A to B plus distance of B to E. Similarly, cost of A to C plus distance of B to C. So we need to find out the minimum among these two, because in order to reach E, vertex E, there are 2 possible paths from the source. One is through B, one is through C. So cost of A comma B already we have computed in our previous stage. Cost of A to B is 1 plus D of B, distance of B and E, it's a 4. So which is totally 5. And coming to the cost of A to C, already computed in our previous stage, it is 2. Distance of B and C. Sorry, this is not B and C. C and E, right? C to E, which is, this is 11, right? Okay. B, okay. So C to E it is 9, so it is 9, which is 11. So among these two, which is a minimum? This one. We need to consider this one. Okay. Now, any other edge? A to F. Cost of A to F. So in order to reach F, you can see in order to reach F, what are the incoming edges to F? 2 edges. 2 edges. So what are those 2 edges? One is from C. Okay. Another one is from B. So we need to reach A to C, A to B, and then only we need to go with the C to F. So we need to find out the minimum of, so cost of A to B plus distance of B to F. Similarly, cost of A to C plus distance from C to F. We need to find out the minimum cost of AB, already computed here, 1 plus distance of B and F. B and F distance is 11. So total it is 12. Then cost of A and C. Cost of A and C already computed, so which gives a 2 result, plus distance of C and F. C and F is 5. So it will be 7. So we need to consider 7 itself. Okay. Now cost of, there's one more vertex G. So source to G. So how many edges, incoming edges for G? You can see 2 edges. two edges. One is from C, another one is from D. So we can travel from A to C and A to D. So which one we have to pass? Okay, which one we have to select? Minimum path. So here also we need to find out the minimum value among the cost of A to C plus distance from C to G. Similarly, cost of A to D plus distance of D to G. So cost of AC already computed, which is 2 plus distance of CG. C and G 16, total 18. So cost of A and D is 5. Distance of D and G is 2. So which is 7. So we need to select this one. Okay. So any other vertex, we have find out the distance from A to E, A to F, and A to G. So both E, F, G all are from stage 3. Okay. So this is stage 2, and this is stage 1. This is stage 1. Right. Now going to the stage 4. So which is a destination. So here we are having only one vertex, that is stage. So one constraint in multi-stage graph is there should be only one source and one destination. So if any stage is having only one vertex, that will be the destination. Now we need to find out the cost of source to destination. Source to destination. So in order to go with H, what are the incoming edges? You can see one is from E, another one is from F, another one is from G. So through E, what is the cost between A to E, A to F, and A to G? Because source is A itself, right? So already these we have computed in our previous one. These we have computed in our previous stage because E, F, G all are in stage 3. So here we have computed the cost from A to E, A to F, and A to G. So we have to use the already computed solution. See, so this can be a minimum of so cost of A to E plus distance of E to H. Similarly, cost of A to F plus distance of F to H. Similarly, cost of A to G plus D of G to H. So find out. We have to find out the minimum. Cost of A to E. So already we have computed cost of A to E, which is 5. We got two paths, 5 and 11. Among that we have to select the minimum path. I am selecting this one. So 5 will be the cost of A to E plus D of EH. EH is 18. So which is 23. And cost of AF already computed here. AF again we got two values, two possible paths. One is with the 12, one is with 7. So we need to find out we need to consider the lowest path. So that means 7. So 7 plus distance from F to H. So F to H the distance is 13. So which is 20. And similarly cost of AG. So again we are having two possible paths. Among that we have to select the least possible path, which is 7. So 7 plus D of GH, which is 2. So it will be 9. So among these two, 23, 29, which one is the lowest? So this one is the lowest. So we need to consider the 9, right? So this is the only one vertex in this stage 4. So that implies this is the destination. Okay. So now what is the solution for this one? What is the path? Now what is the last one? Distance of G to H. So distance of G to H, and which is added with A to G. So go to the cost A to G. So in this A to G we have considered this one, right? So A to G, that means the distance of D and G. So D and G, which is computed with A and D. Cost of A and D. Go back. Cost of A and D. So which is distance from A and D. So which is distance from A and D, right? And then cost of A comma A. So source and destination. So this is the shortest path for this particular multi-stage graph. You can see A to D, which is a 5, D to G, which is a 2, G to H, again it is 2. So totally 9 is the distance to travel from A to H. That means source to destination. It is shortest path. So you can cross check multiple ways. So A to B, B to E, E to H. So it will be 5 plus 18, 23. A to C, C to F, F to H. 7 plus 13 is 20. So A to C, C to E, E to H. 2 plus 9, 11 plus 18, 29. So all other possible paths will give more than 9 distance. More than 9 distance. So only this particular path, that means A followed to B, sorry D followed to G followed to H, will give the shortest path to travel from source to destination. Right? So hope you understood. Here we have taken the 4 stages. So you can remember that the same diagram we have taken for the forward approach also, and we have solved it, and we got the same path. Okay, for the shortest distance. Right? So you can cross check. So the complete subject link will be posted in the description. So you can go through the forward approach, and now you can analyze the backward approach. So already in the forward approach we have taken one more example with 5 stages. So try to solve the 5 stages by using the same problem, same procedure. So you need to get the same path which gives the shortest distance.
We will see one more concept in algorithms, that is optimal binary search tree. Optimal binary search tree. So which can also be called as OBST, and this by using the dynamic programming. Okay, so we have to implement this one using dynamic programming. So we know that the dynamic programming means the working of dynamic programming will be similar to the divide and conquer method. So where the complete problem will be divided into subproblems, and that will be solved, and the solutions of each subproblem will be stored in a memory.
right? So that we can implement by using a top-down approach and the bottom-up approach, and the process we call it as a memorization and the tabulation. So the same concept we are going to use in this particular OBST, Optimal Binary Search Tree, which is an application of dynamic programming. Now we will recall about the tree. So a tree is nothing but nodes and vertices, okay? And coming to the binary search tree, so we have seen about the binary search, right? So the constraint of binary search is to maintain the sorted elements. That means we have to first the elements to be get sorted, and then only we have to apply the binary search tree. And here we'll be having the root node in this binary search tree, and on the left hand side of this root node, all the elements should be less than the root element, and on the right hand side of the root should be greater than the root elements. So if the tree satisfies this one, we can say it as a binary search tree. Okay, so for example, let us take some 10, 20 and 30. So you can consider 20 as a root, and left hand side the less than element, and right hand side it is a one more element, that is a greater than root. For example, the same thing, if you consider 30 as a root, left side you can have a 10, and on the right hand side of 10 it will be a 20. And you can see on the right part, right hand side of this root, we are having all the elements of which are less than root. And if you consider 10 as a root element and 20 is on the left hand side, sorry, right hand side because greater than 20, and 30 is the right hand side of 20. And similarly, you can also go with a 30, with a 20, with a 10. See, all these are the different cases. So we can draw the binary search tree for these three elements in these multiple ways, right? Now, the question is optimal. How we can say it as an optimal binary search tree? So the mainly binary search tree, the name itself indicates it is used to search the element in a tree. For example, if you want to search for 30, so it will be here, and it will be here, and it will be here, and it will be here. So for searching the element, we'll be using this binary search tree. Now, what about this optimal binary search tree? Optimal binary search tree. For example, if you want to search 30, how many comparisons you require here? So 1 and 2. So 2 comparisons are required. But here it is only one comparison is required because it's a root element. But here 1, 2, 3. 3 comparisons are required for searching of 30. And here it requires only one comparison, right? So if you want to search the 30, we are having a different possibilities. Among that, these two comes under the optimal. These two comes under the optimal because it requires a minimum number of comparisons. So with one comparison, we can get the success. And here also we can, with one comparison, we can get the success. For example, if you want to search for 20. So it is one comparison, it requires a 3 comparisons, it requires a 2 comparisons, it requires a 2 comparisons. So you can check. So these 3 will be the optimal. Okay, any one we can draw. Okay, so like that. So optimal means with the minimum number of comparisons, we are supposed to get the success. Okay, so less number of comparisons, the search operation should be done. Right? So that you can see, in order to search all these elements. See, I'll draw here and I'll explain you. If you consider the same 3 elements, some 10, 20 and 30. So I'll give you a few examples. So 20 and 10. This is the first case. If I go with the 20, I can get a 10 and I'll get a 30 here. And if I get a 10 here, I'll get a 20 here and I'll get a 30 here. So let us take only the 3 possibilities. We'll be having a more number of possibilities to draw the 3. So here, how many comparisons we require? For 30 it will be 1, for 20 it will be 2, for 10 it will be 3. And here for 20 it will be 1, for 10 it will be 2, for 30 it will be 2, for 10 it will be 1, 2 and 3. So what is the average cost for search? Average cost, 1 comparison, 2 comparison, 3 comparison by 3. And here 1 plus 2 plus 2 by 3. Here 1 plus 2 plus 3 by 3. So which is nothing but, here it is a 6 by 3, it is a 5 by 3 and it is again 6 by 3. So obviously this is the optimal binary search tree for these elements among these 3. Okay, there are many possibilities. We can go with one more possibility. So let us take a 20 here, and here we can give a 30 here, and here it can be 10 here. So this is also one more possibility. And we can compare all the things. But among these 3, we can say that it is a 5 by 3. The cost will be 5 by 3. That means it requires a minimum cost to search all the 3 elements. So this will be called as an optimal binary search tree. So which will have a minimum comparisons. So if there is no comparisons, if there is no search, obviously this will be the binary tree. No doubt at all. All the 3 comes under the binary trees. Now we will see how can we find out the optimal binary search tree among a different binary search trees, different combinations. Okay, so if we take some 4 elements, there will be a lot of combinations of, we can draw a lot of combinations of binary trees, binary search trees. But among that, we have to find out the optimal binary tree. So that is the problem here. How to find the optimal binary tree? That means with a minimum cost. So for this, first we have to find out the root element. So which root element will give the minimum cost of the complete tree? So here we'll be having 2 options. One is the keys, which are nothing but elements, and another one is probabilities. Or sometimes we can also call it as a frequencies. The frequency for a successful search of an element. Okay, so we'll be having these 2 things. Okay, and there will be also the third thing, probability of success and the probability of unsuccess or not success. So there will be two types. So we can implement this OBST with the two types. One is with the keys and probabilities of success, and another one is the keys and the probability of success and probability of unsuccess. Right? So two ways we can find out the optimal binary search tree. So now we'll go with this process. That means with the keys and the corresponding frequencies or the probabilities of success. Right? Yes. Now we'll see. We'll take a problem and we'll solve it. So we required keys and the probabilities or frequencies. So here my keys are 10, 20, 30 and 40. I have only 4 elements. Okay, 4 elements. So the corresponding keys 4, 1, 3, 2. These are the probabilities. Now we have to find out the optimal binary search tree. That means the binary search tree with a minimum number of comparisons. So we can construct a lot of binary trees. For example, I will take a 10 here, so 20 here, and 30 here, and 40 here. So this is also binary search tree. And if you consider 30 as a root, I can go with a 20 here, and a 40 here, and here again a 10. This is also one binary search tree. And if you go with the 20 as a root, I can get 10 here, 30 here, and 40 here. This is one more binary search tree. If you go with the 40, and you can go with the 30 here, 20 here, 10 here. So this is the one more. So I think there will be a lot of combinations of binary search trees. Among these, we have to find out the optimal binary search tree. Now, let us consider. See, this will be using some table. We are supposed to fill the table. So first, I will draw the table here. So 0, 1, 2, 3, 4. Because we are having a 4 nodes. So similarly, on the rows also, I will go with a 1, 2, 3, 4. So 4 rows and 4 columns. So I am constructing the table with 4 by 4 size. And now we have to fill out the cost of each and every node to other nodes. So this is the use of this table. So what is the main purpose of dynamic programming is memorization or tabulation. That means storing the results for the future purpose. So now here, let us consider this as I, rows as I and columns as j. So I'll tell you what is that I and j. Now we have to consider what is the root. Okay, which should be used as a root. For example, for the first case, if there are no nodes, so we can have 0 nodes in a binary search tree, 1 node in a binary search tree, 2 nodes in a binary search tree, 3 nodes in a binary search tree, and 4 nodes in a binary search tree. Okay, yeah. So this is nothing but I minus j is equal to 0. This is, sorry, j minus I is equal to 0. Always j should be greater than I. Okay, so j minus I is equal to 1, j minus I is equal to 2, j minus I is equal to 3, j minus I is equal to 4. So that implies a tree with 0 nodes, tree with 1 node, tree with 2 nodes, tree with 3 nodes, and tree with 4 nodes. Now what we have to find? We have to find out the root. So which we have to consider it as a root. So if it is 0, 0 nodes, that means there will be no roots. So there will be no cost. So when happens in this one? So obviously whenever I becomes j, then this becomes 0. That means let it be c as a cost 1 1, cost 2 2, cost 3 3, cost 4 4. Okay. So always this becomes zeros. Okay, so I fill this one 0 0, 1 1, 2 2, 3 3, 4 4. All the costs are 0. Now let us consider the second one. That means j minus I is equal to 1. J minus I is equal to 1. That means if it is having only one root node, so that means I and j, you can check 0 1, C of 0 1, C of 1 2, C of 2 3, C of 3 4. So you can check I and j. So let us consider C of I, j. 1 minus 0 is 1, 2 minus 1 is 1, 3 minus 2 is 1, 4 minus 3 is 1. You can check it. So 0 1, okay, 1 2, this one, 2 3, this one, 3 4, this one. So that means this is a next diagonal position. So that you have to find out. So what we are saying 0 1, 0 1. So if it is there only one element. So always remember, you don't consider this I value. Start with I plus 1. Okay, don't consider the I value, start with the I plus 1. Now 0, so you should not consider 0. So I plus 1, 0 plus 1, 1, and the end is j, that means 1. So only one node. What's the first node? 10. So if there is 10, see the formula I am writing here, C of I, j is equal to minimum of C of I, k minus 1 plus C of k, j plus W of I, j. W is nothing but a cost, complete cost. So I'll write somewhere else this one. Okay, no problem. As of now, leave it. So C of 0 1, that means C of 0, and here minimum this is I less than k and less than or equal to j. That means k value will be in between greater than I and equal to j. So that means So 0 less than k less than or equal to j. So in this case ij. So what is the value of k here? So j greater than 0. So we should not consider 0, right? Greater than 0 and 1. So here it is 1. J value is 1. So obviously the value will be k is equal to only 1. So only 1. If k value is only 1, you can see. So hope you understood this one. Now we'll consider one by one. So we are now in this position and erasing all the remaining. Okay, for calculation purpose. So we need to calculate C of 0, 1. So C of 0, 1 is equal to a minimum of, okay, so that means only one element is there. One element means only 10, the node 10. So what's the frequency for search of 10? It's a 4. So simply you can write it here 4. Okay, so if here it is a 4, 1, 2. So you should not consider 1, only 2. So that means second element 20. Frequency is 1. You can represent here 1. And 2, 3. 2, 3. So 2, 3 means don't consider 2, the third one. So third one is the 30. 30 frequency is 3. You can simply use here 3. And the next one is 2. Here it is 2. Okay, don't confuse. I'll explain you this one. So see, if it is a 2 nodes, what we have to get? J minus I is equal to 2. For example, consider 10, 20, 30, 40. So what we are doing? First, this one completed. So either 10 or 20 or 30 or 40. These are all individual nodes. So that's in this diagonal. Now we have to suppose to find what is the 2 nodes. J minus I is equal to 2. So for that we can write it as C of 0, 2, C of 1, 3, C of 2, 4. So we can't go with the 3. If it is 3, then it will be 5. So there are only 4 nodes are there. So 1, 2, 2, 3 and 3, 4. So that we can go with this one. Okay, see. Now we are replacing this one. So we have to find out C of 0, 2, the cost of 1, 3 and the cost of 2, 4. For example, let us go with the 0 and 2. 0 and 2. 0 to 2. Right? So only 2 elements are there. That is 10 and 20. Only 2 elements are there, 10 and 20. So you can check the possible binary trees are 10 on the right hand side, 20, and if it is 20, right left hand side it is 10. Only 2 possibilities. So what's the this one frequency of 10? It is a 4. Frequency of 20? It is 1. Frequency of 20? It is 1. Frequency of 10? It is 4. So how many comparisons required? 1 comparison, and here it is 2 comparisons. Here it is 1 comparison. Here it is 2 comparisons. Now find out the cost here. So 1 comparison into 4 plus 2 comparisons into 1. So which is nothing but 4 plus 2 is a 6. And here you can see the cost is equal to 1 into 1 comparison plus 4 into 2 comparisons is equal to 1 plus 8, which is 9. So among that, which will be the optimal? Obviously, if 10 is a root node, then it will be an optimal. If 10 is a root node, it will be an optimal, right? So with this, because we need only 6 comparisons, that means a 6 cost. Cost is 6. Here cost is 9, which is greater than 6. So this will be the optimal. So the same thing we'll be getting by using this formula. I'll write this formula here once again. So C of I, j is equal to minimum of I less than k less than or equal to j, C of I k minus 1 plus C of k, j plus W of I, j, where W of I, j is nothing but a weight or cost. Okay, cost. Now you can consider the same thing here. Okay, we'll do the same thing by using formula. We have to do this thing for each and every possibility. But here it is only 2 elements, we are having only 2 combinations. If that is a 3, we'll be having a lot of combinations. If it is a 4 nodes, we'll be having more combinations. So this is a generalized formula to find out this particular cost. For example, consider the same thing, 0, 2. So C of 0, 2 is equal to minimum of 0 less than k less than or equal to 2. Okay, so 0 less than k less than or equal to 2. That means k will be either 1 or 2. So we have to write down 1 or 2 and we have to take out the minimum. So this is the minimum. So I write here C of I is 0, k minus 1. If k is 1, k minus 1 will be 0. Plus C of k is 1. J is 2. So this is the I value, this is the j value. Okay, this is one possibility. Now if k is equal to 2, then it will be 0, k minus 1, 1 plus C of, what is here? K is 2, 2 plus W of 0, 2. So that is the 0 of 2 means only we have to consider other than I plus 1 to j. That means I plus 1 means 1 to 2. So 1 to 2, here it is a 1, 2, 3 and 4. 1 to 2, that means 4 plus 1, it will be 5. The frequency 4 plus 1, it will be 5. So this will becomes 5. Okay, so what we have to do? Check out. Cost of 0, 2 is equal to minimum of, okay, first C of 0, 0. You can go with the table. 0, 0, cost 0 plus cost of 1, 2. Cost of 1 and 2 is 1. And this one, C of cost of 0 and 1. 0 and 1 is 4. Cost of 2, 2. 2 and 2 is a 0. Plus, what's about 5. So how much you will be getting? 1 plus 5, either 6, 4 plus 5, either 9. So what we got in this way. So these are the two different ways. Actually, based upon the frequency, if you are able to draw the tree, then it will be simple to find the cost. But if there are more number of nodes, so we have to find out for all the combinations. So that will be somewhat difficult. So that's why we can use this particular formula to find out the cost. Okay. So now, which one we have to consider? 6. 6 we are considering, right? So if you consider 6, what is the root node here? So here we can apply 0 to 2. It is 6. And what is the root here? So whenever the k becomes, so this is the solution, right? Whenever the k becomes 1, we are considering it as the optimal, right? See, the first 10. K is equal to 1. So this is the k value. And this is the elements. And this is a probability, right? So whenever the k becomes 1, this first case, if you consider first case and second case, first case only we are getting the optimal solution. So first case k is equal to 1, right? So you can represent it here as a 1 as a root node. So similarly, here also you can see 4 is a 1. 1 is a 2 as a root node, 3 as a root node, 4 as a root node. Okay, now consider the same, apply the same formula to find out the cost of 1, 3. So now I am not drawing the trees anymore. I am directly using this formula to find the cost, okay, for remaining process. So I use this place to find out the cost of everything. And see, we are just storing the information in the table so that we can retrieve the data whenever it is required in order to avoid the recalculation. Now, C of 1, 3. So is equal to a minimum of 1 less than k less than or equal to 3. And what we have to do, C of I 1, k minus 1. So here k will be becomes 2, 3 because 1 less than k less than or equal to 3. That means k will be in between greater than 1 and less than or equal to 3. So k of 1, 2 minus 1, 1 plus C of k, 2 and 3. This is one possibility. And one more possibility, whenever k becomes 3. So 1, 3 minus 1, 2 plus C of k. That means a 3, 3. Sorry. Plus W of 1, 3. So this we have to find out. Now you can find the minimum of C11. 1 cost it is 0 plus 2, 3. 2 and 3 cost is 3. So simply remember this 4, 1, 3, 2 are cost. And 1, 2, 3, 4 are the root nodes. So 1 represents this 10, 2 root node means a 20 as a root node, 3 means a 30 as a root node, 2 means a 40 as a root node. So next, if there are 2 items, we have to consider 1 as a root node so that we will be getting the optimal solution. So 0 plus 3 and C 1, 2. 1 and 2, it's a 1 plus 3 and 3. 3 and 3 is 0. Yes. Plus W of 1, 3. So you should not consider 1 here, right? So we are considering from only 2 and 3. So 2 and 3. What is the profit of 2 and 3? That is the cost of 2 and 3. 1 plus 3 is a 4. Now, what is the minimum value here? It will be 7 and it will be 5. So obviously 5 will be minimum. 5 will be minimum, right? We have to consider 5 values. So what is the value of k? That means a root node. So the second case we are considering. In the second case, what is the k value? 3. So 3. So in these two things, that means from 20 and 30, in between 20 and 30, 3 should be the root node. That means the 30 should be the root node. Then only we will be getting the optimal solution. So just represent that there. So the cost is 5 and 3 is a root node. Okay, 3 is a root node. Now, see here it is a 5. Now again we have to consider C of 2, 4. One more possibility, 2 and 4. So the same thing apply here. So we have to fill all the table, right? So here always the j should be greater than I. So we will be getting only the upper triangle. Okay, we can ignore the lower triangle. So next C of the next one is a 2, 4, and you can see a minimum of 2 less than k less than or equal to 4, and see the k values will be 3 and 4, which is minimum value 2. That is greater than 2 we should consider. So C of what we have to do? I k minus 1. I is 2, k minus 1 3 plus C of 3 and no, k is 3, no, k is 3 means here 2, 3 and 4, and similarly C of I came 4 minus 1 3 plus C of 4, 4. So what we are getting? Plus W of 2, 4. So we have to consider the frequencies of 3 and 4, right? So 3 and 4 means these two things, which is a 5. So this will be 5. This will be 5. So we have to consider the values, the minimum of, so C2, 2, cost of 2, which is 0, 3, 4, cost of 3 and 4, cost of 3 and 4, it is a 2. Next, cost of 2 and 3, 2 and 3, it is a 3. And 4 and 4, it is a 0. Plus 2, 4, means it's a 5. So among these minimum values, this will be 7 and this will be 8. So 7 will be the cost of 2 and 4. So when we are getting the cost 7, what is the root node? So first case we are considering so that we are getting the optimal, right? In the first case, what is the k value? It is a 3. Okay, so 3. Now update here. So the cost of 2, 4, 2, 4 will be 7 and the root should be 3. the root should be 3. That's most important, because after that, after completion of this table, so we are supposed to draw the tree, construct the tree. That will be based upon these root nodes, because these are the root nodes we are using to get this particular minimum cost. Okay, yes. So there are all possibilities has been completed for 2 nodes. Now gradually increase. That means 3 nodes. So what happened to get the 3 nodes? So you need to find out the root if there are 3 nodes. Okay, so 3 nodes. What is the root? If the tree is having 3 nodes, that means j minus I should be 3. J minus I should be 3. So starting from 0, if you can consider 0, 3 and C of 1, 4. So you'll be getting only 2 possibilities. If you go with the 2, then it will be automatically 5. So there are no 5 nodes, only 4 nodes. So there are only 2 possibilities here. So first let us consider C of 0, 3. We'll find out. So a minimum of 0 less than k less than or equal to 3. What we have to do? C of 0, so here k will be, becomes 1, 2, 3. 3 possibilities are there here. 3 possibilities. So among these 3, which one should be the root node to get the optimal solution? So k value 1, 0 plus C of 1, 3. And similarly the second one, if k value is 2, 0, 1 plus C of 2, 3. And if it is k value is 3, 0, 2 plus C of 3, 3. So just go with this formula. What we have to add? W of 0, 3. So W of 0, 3. So that will be minimum of, you can calculate 0, 0 plus 1, 3. 1 among 3, so 5. Next 0, 1. 0, 1, it is 4. And 2, 3. Yeah, 2, 3. 2, 3, it is a 3. And then 0, 2. 0 with a 2, it is a 6. Plus 3, 3, it is a 0. Plus, what's the weight here? So we have to consider the weight from I plus 1. That means 1 to 3. So 1, 2, 3. So 4 plus 1, 5, 5 plus 1, 5 plus 3, 8. So it will be 8. So the cost will be a minimum of, so what's the minimum value here? So 5, 7, 6. Okay, 5, 7, 6. So 5 is the minimum value, 5 plus 8, it will be 13. So we have got the cost of 0 to 3 is 13. When we got this 13? By considering the first case. What's the k value in the first case? K value in the first case is 1. So it is 13 with a 1 as a root node. 13 with a k value is 1 as a root node. Okay, now, hope you understood, right? So this is the case where we'll be getting the optimal solution. So whenever the k value becomes 1, we are considering the optimal solution. So that means if in these 3, 10 will be the root node, then only we'll be getting the optimal solution. Now, there's a one more possibility. To find the root node. So which is C of 1, 4. So which becomes minimum of 1 less than k less than or equal to 4. And C of, whenever here k becomes 1, 2, 3 and 4. Whenever k becomes 2, 1, 1 plus C of 2, 4. Similarly, C of 1, whenever k becomes 3, 1, 2 plus C of 3, 4. So because it is a k, I, k minus 1, kj. And see here it is also C of 1, 4 is a k, so k minus 1, 3 plus C of 4, 4. And we have to add the frequencies from 1 to 4. That means 2 to 4. So what's the values? The minimum of, what's the values here? C of 1, 1, which is a 0, plus C of 2, 4, 2, 4, it's a 7. And again 1, 2, C of 1, 2, it's a 1, plus C of 3, 4, 3 and 4, it is a 2. C of 1, 3, 1 and 3 is a 5, plus C of 4, 4, it's a 0, plus this one. So now we have to consider these 3, 2 to 4, 1, 3, 2. That means total 6. So among these 3, which one is the minimum? This one. That means we are considering the second case. So 3 plus 6 it is a 9. Okay, 3 plus 6 it is a 9. So now what is the root node here? So second case. In the second case, what is the k value? 3. So 3 will be the root node. So 9 will be the cost, and here also I am going to be the 9, and the root node is 3. And there is one more possibility. So now we are considering all the 4 nodes, right? We are considering all the 4 nodes because we are having only 4 nodes. If you are having 5 nodes, then there might be 2 more possibilities. Okay. So 4 nodes. We are having only 4 nodes. We are having 4 nodes. So that means j minus I is equal to 4. That is, we'll be having only one case among that. That is 0, 4. So C of 0, 4 is equal to a minimum of 0 less than k less than or equal to 4. And you can now apply C of, whenever k, here the k becomes values of 1, 2, 3 and 4. K values are 4, right? So whenever k becomes 1, then 0, 0 plus C of 1, 4. When k becomes 2, 0, 1 plus C of 2, 4. So here I k minus 1 kj. C of 0, when k is equal to 3, 2 plus C of 3, 4. And whenever k becomes 4, 0, 3 plus C of 4, 4. Plus W of 0, 4. So here what we have to do, we have to consider from I plus 1. So all these things we should be considered. Now let us calculate a minimum of, so 0, 0, its cost is 0. plus 1 4, 1 and 4 is 9. Next 0 1, 0 1 it is a 4, 2 4, 2 with 4 it is 7. Okay, next 0 2, 0 to 2 is a 6, plus 3 4, 3 with a 4 it's a 2, 0 3, 0 with a 3 it's a 13, plus 4 4, 4 4 it's a 0. Plus, wait, 4 plus 1 plus 3 plus 2, that means total 10. Now what among these things, what's the minimum value? It's a 9, it's 11, it's 8, it's 13. So this is the minimum. So 8 plus 10, which is 18. 8 plus 10, which is 18. So when we are considering this 18, the third case. In the third case, what's the key value? What's the key value in the third case? 3. So 3. So the cost is 18 and 18 and it is 3. Now you can see the root node is the third element, which is 30. Third element, which is 30. Now we have completed the construction of a table, right? Now we have to construct the tree. We have to construct the tree. How we have to construct the tree? So only one formula is there. So which is R, that is a root node. So of 0, 4, of 0, 4, or you simply can write it as I, j, which is a k. So obviously left node will be R of I, k minus 1, and here it is I R of k, j. So the same thing we have to apply here. Now, what is the node? 0 to 4. So we have to consider all the 4 elements, right? So when we are considering all the 4 elements, what is the root node in which we are getting the optimal solution? So our problem is having 4 elements. Okay, our problem is having 4 elements. So this will be the root node. Which will be the root node? 3. So third element is 30. So here the k value is 3. So I am writing the element, okay, k value. So after that, I have to write it as here R of, what is this one? 0, k minus 1, 3 minus 1. Okay, 3 is a k. This is a k value. Okay, so 3 minus 1, 2. 0 2, 0 2. What is the root node? 1. So first element. Okay, just remember here these are the k values. K value means the order of elements. Okay, not the one. 3 is not an element. 3 means third element. 1 means first element. 2 means second element. Okay, now what is this one? R of k. What's the k value here? 3. See, this is a k value. 3, j means 4. What's the 3 4? 3 and 4. Okay, so what's the k value? 4. So this should be written here. That means the fourth element. Fourth element in this order, right? Now expand this one. We have to expand until we get the 0 0. Okay, until 0 0. Now again R of, see, I value is 0, k value. So here it is a k. 1 minus 1, 0. So R of 0 0, 0. So you can remove this one. And what about this one? R of k. See, R of k. K means 1. 1, j. J means 2. 1, 2. 1, 2. It's a second. That means a second element. Second element. Now expand this one. What is this one? R of I means 3, k minus 1. Here it is a k. 3. So which is 0. So this is not possible. Okay. And expand this one. R of, what is the k value? K value is 4. When j value is a 4, which is again 0. Cross. Now you can construct this tree. So third root, first element, second element, and a fourth element. Now you can consider this one. See, I'll erase this one and I'll draw. What is the third element? 30. First element on the left, 10. Second element on its right, 20. Fourth element on its right, 40. And you can check about this binary search tree. So 30 is the root. So left side we are having the less than 30, and right side we are having the greater than 30. If you consider 10, left side there are no elements, right side we are having the greater element. Right? So this is the optimal binary search tree we can construct from these elements with the probability of success. So this is only having the probability of success in the search. Okay, so there is one more possibility there. We can have one more chance. That means the probability is for unsuccessful search. Okay, that will go with the next session. So hope you understood. Just by observing this formula, we are supposed to use this table. We have to fill this table. So you can observe we have calculated 0 0 0 1 0 2 0 3, then 1 1 1 2 1 3, and 2 2 2 3 2 4, and all these things we have calculated to find the root element. That means this is a bottom-up approach. So this process we can call it as a tabulation. Okay, not a memorization. It's a tabulation. It's a bottom-up approach. So we'll call it as OBST, optimal binary search tree. So in our previous session, we have discussed about this complete information about OBST. So what is a tree, what is a binary search tree, and how it differs from the optimal binary search tree. So if you have not seen that video, I'll post the link of that particular video in the description. First, go through that video so that you will be getting a clarity about the differentiation of tree, binary search tree, and optimal binary search tree. And in our previous class, we have seen one example that takes the frequencies of successful searches. And now today's session, we'll see one more example which takes the frequencies of both successful and unsuccessful searches. Right? So let us take an example. Let us take some elements. So those are 10, 20, 30, and 40. So I'm taking only 4 elements, right? So in order to reduce the calculations, okay. So we need to construct the optimal binary search tree. That means we have to construct the binary search tree with a minimum number of comparisons for a successful search of each and every element of that particular tree. So obviously here the question is which we have to select it as a root. Then we can get the optimal binary search tree. So with this, we can have a multiple binary search trees. We can construct a multiple binary search trees. Among that, we have to decide which will be the optimal binary search tree. That means minimum number of comparisons. With the help of minimum number of comparisons, how efficiently we can get the search, right? Now, let us take some P of I. Let us indicate P as a successful search, successful searches, which is from 1 to 4. Let us take the frequencies as 3, 3, 1, 1. That means the frequency of first element, to search for the first element is 3, and the second element is 3, the fourth element is 1, and fifth element is 1. And similarly, let us consider a Q as unsuccessful. So obviously, that will be from 0 to 4, because so if we are having 4 elements, in our tree, so we have to compare all these 4 elements, and in the fifth element we will be getting the fifth comparison, we will be getting the unsuccessful, right? So fifth element will be getting the fifth comparison, will be getting the unsuccessful. So the unsuccessful nodes will be 5, and successful nodes will be the number of elements. If n elements are there, the successful frequencies will be n, and unsuccessful frequencies will be n plus 1. So let it be some 2, 3, 1, 1, and 1. So that's why we have given it as 0 to 4, P as 1 to 4. Right? Now we have to start executing. So let us write the formula first. So whichever the formula we have done, the same thing we have to apply here. So what's the formula we have done? C of I comma j is equal to minimum of I less than k less than j, and from here we have to apply C of I comma k minus 1 plus C of k comma j plus W of I comma j. So this is the formula where we have to find the cost of the element, to search the element cost. And the next one, similarly, R of I comma j is equal to k. That means for which k value we got the minimum cost. So we need to consider the element as a root. So this is particularly for the root element, to select the root element. So for which k value, this particular expression we are getting a minimum value, that will be the k value, and that will be considered as a root. So that will be considered as a root of ij. Now W of I comma j is nothing but W of I comma j minus 1 plus P of j plus Q of j. So this is the formula. This is the formula we have to calculate the W of ij. So this is a somewhat different, which we have not calculated in our first example. That means when we have taken only the successful frequencies. But here in this example, we are taking the 2 different frequencies, successful and also unsuccessful. So based upon these 2, we have to find out the optimal binary search tree. Now, the initial conditions. Initial conditions. So what is the initial conditions? Whenever it is I comma I, that means whenever j becomes I, whenever the j becomes I, then that will be a Q of I. So it will be Q of I. And similarly, cost will be 0, and obviously root will be 0. See, simple. This is nothing but when the tree structure doesn't have any elements. If tree structure doesn't have any elements, obviously in the first thing only we will be getting the unsuccessful. Yes or no? So for example, we are searching for element 10, and initially there is no tree. There is no tree. Then obviously what happens? For the first frequency itself, we will be getting the unsuccessful. So obviously, so Q of j will be the weight. And what about the C of ij, cost to search? So if there is no element, there will be no cost. If there is no tree, there will be no root. So that's why these 2 becomes 0, and this becomes the unsuccessful. This becomes the unsuccessful. So now we have to draw the table for searching of the root element. So which one should be a root, right? So the root should be for elements 0. So this is this thing. And what is the root for element 1? If there is only one element, then what will be the root? Itself will be the root, right? And if there are 2 elements, for example, we are having here 4 elements. That means 4 nodes. 4 nodes. So we can consider 0 nodes. What is the root? So obviously 0. Okay. Then if there is only 1 node, what is the root? If there are 2 nodes, what is the root? So we have to find out the minimum root, right? So what is 3? If the tree is having some 3 nodes, what is the root? And if it is having some 4 nodes, what is the root? We have to calculate that root value. Okay. And this happens when j minus I is equal to 0. That means j and I is equal to 0. Both are the same, right? If this becomes j minus I is equal to 1, and this becomes j minus I is equal to 2, this becomes j minus I is equal to 3, this becomes j minus I is equal to 4. So we need to calculate the cost, weight, and root for all these cases. So whenever j minus I is equal to 0, whenever j minus I is equal to 1, whenever j minus I is equal to 2, whenever j minus I is equal to 3, whenever j minus I is equal to 4. That implies here 0 means 0 nodes in the tree. If it is 1 node. if it is 2, there are 2 nodes in a tree. Among that, we have to select the optimal. That means the minimum cost. And here, j minus I is equal to 3 means if the tree is having 3 elements, what is the root we need to calculate? So in order to get the optimal binary search tree. And j minus I is equal to 4 means if the tree is having 4 elements, which one should be considered, right? Now, see. Now, let us draw the tabular form. So I'll draw the tabular form here. So I'll take 0, 1, 2, 3, and 4. 0, 1, 2, 3, and 4. So we need to fill the table and find out the root and apply the backward process so that we will be getting the complete tree structure, right? So let's check out. So for every case, we are supposed to find the weight, cost, and also root. Weight, cost, and root by using these formulas. Now, so this is a I value and this is a j value. I value, j value. Now, initial conditions that we have seen, and every time, see, by using this formula, I'll calculate each and everything and here, and we'll update the table here. Now, initial conditions, whenever I minus j, I is equal to I, that means first one, j minus I is equal to 0. J minus I is equal to 0 means, so there are no nodes in a tree. If there are no nodes in a tree, obviously the cost will be 0, the root will be 0. But the weight, that means the frequency, it will be 2 or 3 or 1 or 1 or 1. Okay, let us check. So this implies I is equal to, sorry, j is equal to I. J is equal to I. So we'll get W11 is equal to, okay, W of 1, 1. W of 1, comma 1. I is equal to j. Okay, so what is the value? Q of I. Q of I. So that means Q of 1. Q of 1. So what is the Q of 1? See, 0 and 1. Q of 1 is 3. So 3 will be the weight. What about the cost here? I'll write the cost here. So C of 1, comma 1 is equal to, so if both are equal, then it will be 0. So 0. And root of 1, comma 1. So what is the root of 1, comma 1? That's also will be 0. Right? So update here. 1, 1. Okay. So if it is 1, 1, it will be 3 and so on. Right? So 1, 1. So W of 1, 1 is equal to 3. C of 1, 1 is equal to 0. R of 1, 1 is equal to 0. Okay. Now, let us also consider W of 0, comma 0. So then it will be Q of 0. Okay. Then Q of 0 means it will be 2. C of 0, comma 0, which is 0. R of 0, comma 0, which is 0. So, yeah, this is 1, 0, no? So we need to update here, not here. So this is the place. W of 1, 1 is equal to 3. Yes. C of 1, 1 is equal to 0. R of 1, 1 is equal to 0. And here, W of 0, 0 is equal to 2. C of 0, 0 is equal to 0. R of 0, 0 is equal to 0. Right? Now, 2, comma 2. Then also it will be 0, right? So Q of 2. So what's the value of 2? Q of 2. It is a 0, 1, 2. It's a 1. And C of 2, comma 2, which is 0. And R of 0, comma 0, it is again 0. So 2, 2. So W of 2, 2 is equal to 1. C of 2, 2 is equal to 0. R of 2, 2 is equal to 0. Okay, we'll extend this one. Right. Now, again W of 3, comma 3. So again it will be Q of 3. So Q of 3, which is again 1. C of 3, comma 3 is equal to 0. R of, yeah, here it is 2, comma 2. 3, comma 3 is equal to 0. So this position. So W of 3, 3 is equal to 1. C of 3, 3 is equal to 0. And R of 3, 3 is equal to 0. Okay, so same thing. Now, W of 4, comma 4. So we need to consider each and every condition, right? Every case, each and every case we have to calculate. So W of 4, comma 4 is Q of 4. So which is again it is 1. And C of 4, comma 4, it will be 0. And R of 4, comma 4. If there are no elements, then automatically root will be also 0. So W of 4, 4 is equal to 1. C of 4, 4 is equal to 0. R of 4, 4 is equal to 0. Okay. So same thing. We have calculated all the roots. Okay, all the roots, a K value or weightage and a cost for 0 elements of a tree. If the tree is having 0 elements. Now, if the tree is having only 1 element, if tree is having only 1 element, that is j greater than I. Now, what are the weight, cost, and root? If tree is having only 1 element, okay, consider tree is having only 1 element. So obviously W of 0, comma 1, which is 1 minus 0, it is 1, right? Now, what we have to calculate? W0 of 1 is equal to W of I value 0, comma. Next, what's the formula here? J minus 1. Y minus 1, 0, plus P of j, j is 1, plus Q of j, 1. So, which is nothing but W of 0, 0. W of 0, 0 is 2. So, 2 plus P of 1. P of 1, 3. Q of 1. Q of 1 is this one. So, this starts with 0, right?
So this is 0, 1, 2, 3, 4. So that's why I have written a key here 0 to 4. And here 1 to 4, 1, 2, 3, 4. So Q of 1 means this one, 3. So which is nothing but 8. Okay. Now calculate the cost from 0, 1, which is a minimum of 0 less than k less than or equal to 1 C of, so here k holds only one value. That means the k is in between greater than 0 and less than or equal to 1. Greater than 0 and less than or equal to 1. So that means it will take only one value. So now C of, what's the formula here? I means 0, comma, k minus 1. Here k is 1. 1 minus 1, 0, plus C of k. K means 1, comma, j. J means 1. Plus W of 0, comma 1. So W of 0, comma 1 already we have calculated here based upon the successful and unsuccessful searches. So what's the value here? So here we are taking only one value, so that will be the minimum value. So if there are multiple k values, so that way they will be getting a multiple value. So from that we have to select the minimum value. So but here we are having only one value. So C of 0, 0, C of 0, 0, it is 0, plus C of 1, 1, 1, 1 again it is 0, plus W of 0, 1. W of 0, 1 here we have calculated. So 8. So which is nothing but 8. And obviously the root of 0, comma 1 is equal to k. See, k. So here what's the k value? 1. So 1. So what's the values? 8, 8 and 1. So whenever j minus 1, I is equal to 1, W of 0, 1, C of 0, 1 and R of 0, 1. So we need to fill this one. So 0, 1. 0, 1 means this one. So W of 0, 1 is 8. C of 0, 1 is again 8. R of 0, 1 is 1. Okay. Now what we have to do? Again, we need to calculate a few more things. So which is W of 1, 2. So in this case also the j minus I value is 1, right? So is equal to W of 1, comma 1 plus P of j, that means 2, plus Q of j, which is 2. So W of 1, 1, 1, 1 W is 3, plus P of 2. P of 2 is 3, Q of 2, 0, 1, 2, it is 1. So which is 7. And C of 1, comma 2, which is nothing but a minimum of 1 less than k less than or equal to 2. And C of I, k minus 1, that is 1, plus C of j, k is 2, k value is only 2. So 2, comma j, that means 2, plus W of ij, 1, comma 2. So here the k value will be only one value, right? So because k value will be greater than 1 and less than or equal to 2. So k is equal to 2. C of 1, 1. C of 1, 1, it is 0. C of 2, 2. C of 2, 2 again it is 0. Plus W of 1, 2, which is 7. So that is 7. So the root of 1, comma 2. So only one value k is there, so that will be a 2. So what we have to do? So we have to fill the three things here. So 1, 2. So this one. So W of 1, 2 is equal to 7. And C of 1, 2 is equal to 7. And R of 1, 2 is equal to 2. Right? Now, one more thing. That is 2, 3. This place. This will also be 3 minus 2, 1. Right? So C of 2, comma 3. So we need to calculate C of 2, comma 3. So C of 2, comma W of, first we need to find out the weight because we have to add this weight in the C cost, right? So W of I, comma j minus 1, 2, comma 2 plus P of j, that is 3, plus Q of j, which is again 3. So W of 2, 2 it's 1 plus P of 3. So 1, 2, 3 it's 1. Q of 3, 0, 1, 2, 3 it's again 1, which is 3. And cost of 2, comma 3 is equal to a minimum of 2 less than k less than or equal to 3. And C of, so here the k value will be only one element, that is a 3. One value is a 3. So C of I, that means 2, k minus 1, again it is 2, plus C of k, which is 3, comma j, j is again 3, plus W of ij, that means 2, comma 3. So what happens here? C of 2, 2. C of 2, 2 is 0, plus C of 3, 3. It's again 0. So yeah, so this is 1, comma 2. 1, comma 2. Okay. So W of 2, 3, it's a 3. Okay. And here R of 2, comma 3 will be k. K is here only one value, that's a 3. So 3, 3, 3. So 2, comma 3, this place. 2, comma 3. W of 2, 3 is 3. C of 2, 3 is 3. R of 2, 3, it is, again it's 3. Again it is 3. Now, one more case, that is 3, 4. This also, the difference is 1, right? So W of 3, comma 4. So which is W of I, j minus 1 plus P of j plus Q of j. So which is W of 3, 3, which is 1 plus P of 4, it's 1 plus Q of 4, it's 1, which is 3. And cost of 3, comma 4, it will be a minimum of 3 less than k less than or equal to 4. So the k value holds only 4, right? Now C of I, comma k minus 1, it is 3 plus C of k, comma j, right? Plus W of ij, so 3, 4. So which is nothing but a 0 plus 0, 3, 3, 4, 4. C of 3, 3, C 4, 4 plus W of 3, 4 is 3. So which is nothing but 3.
and R of 3 comma 4, which is nothing but a 4. Okay, k value is 4. So fill here W of 3 4 is 3, W of C of after weight cost, C of 3 4 is again 3, R of 3 4 is 4. Okay, now see, this is completed. This diagonal is completed, right? That means if the tree is having only one element, right? Now let us consider the second one. If tree is having a 2 elements, that is j minus I is equal to 2. So j is greater than I. We need to find out W of 0 2, W of 1 3, and W of 3 4, 2 4. See, 0 2, 1 3, and 2 4. So this diagonal. Right? Now W of 0 comma 2, which is nothing but W of I comma j minus 1. So 0 comma 1 plus P of j 2 plus Q of j. Again it is 2. So W of 0 1. What is it? 0 1. W of 0 1. We say 8. 8 plus P of 2. P of j. P of 2 means 1 2. This is 3. Q of 2 0 1 2. It is 1. So which is nothing but 12. And the cost of 0 2. So which will be minimum of 0 less than k less than or equal to 2. So here you will be getting k value as 1 comma 2. So 2 values we are getting. So we need to consider only one thing which is having the lowest value. So minimum value, right? So C of whenever k is equal to 1, then it will be 0 comma 0 plus C of 1 comma 2. Similarly, C of whenever k is equal to 2, 0 comma 1 plus C of 2 comma 2. So we need to consider minimum from these two, and we have to add it to W of 0 comma 2. So what's the values here? The minimum of, let's take the value C of 0 0. C of 0 0 is 0 plus C of 1 2, 1 and 2. C of 1 2 is 7. And here C of 0 1, 0 and 1. C of 0 1 is 8 plus C of 2 2. C of 2 2 is 0 plus W of 0 2. 0 2 is 12. So among these, so what is the minimum value? 7. 7 plus 12 it will be 19. 7 plus 12 it will be 19. Now root of 0 comma 2 will be k. So in which k value we have got the minimum value? Obviously in the first case. In the first case, what's the k value? 1. So R of 0 2 will be 1. R of 0 2 will be 1. So we need to update the same thing here. So 0 2 0 2. So W of 0 2 is equal to 12. C of 0 2 is equal to 19, and R of 0 2 is equal to 1. So here you can see we are having a 2 k values. Among those 2 k values, for which k value we are getting the minimum value, that should be considered as a k. So in these two, the first case we are getting the minimum value as 7. So for the first case, the k value will be 1, so that will be stored in R02. Now what happened? Now we have to calculate W of 1 3. Now we have to calculate W of 1 3. So W of 1 comma 3 is equal to W of I means 1, j minus 1 2 plus P of 3, that means j, plus P of j, it's again 3. So what is the value of W1 2? 1 and 2, it is a 7, plus P of 3, 1 2 3, it's a 1, plus Q of 3, 0 1 2 3, it's again 1. So which is nothing but a 9, value of 9. So cost of 1 comma 3, C of 1 3 is a minimum of 1 less than k less than or equal to 3, which holds the k values as 2 comma 3. So we need to find out the cost. C of I 1 and k minus 1. Let us consider k as 2. 2 minus 1, 1 plus cost of k means 2 and j 3. And the second case, C of I 1 k minus 1. Now k, let us take k as 3. 3 minus 1 2 plus C of 3 comma 3 plus a weight of 1 comma 3. Now you can consider here minimum of C11. C11 is 0 plus C23. C23 is 3 and C12 is 7 plus C33. C33 is 0 plus W of 13, which is 9. So that implies among these two cases 3 is minimum. So 3 plus 9 is 12. Now R of 1 comma 3. So we got a 12. Okay, and among these two cases, we are taking the first case as a existence, because the first case we are getting the minimum value. In the first case, what is the k value? 2. So now R13 will be 2. So update here. So what is that one? 13, right? This one. So W13 is equal to 9. C13 is equal to C13 is equal to 12. R13 is equal to 2. R13 is equal to 2. So 3 3 is again 0, right? So we should be very careful about these values, right? Now there's one more case, which is 2 4. We need to calculate the weight, cost, and root for 2 4. 2 4. Okay, the nodes of 2 and 4. So W of 2 comma 4. So that means we are calculating for every combination, right? So C of W of 2 comma 4. So 2 comma 4, you can see W of 2 comma 3 j minus 1 plus P of j 4 and Q of j 4. So W of 2 3, 2 and 3. It's a 3 plus P of 4, which is 1, and Q of 4, which is again 1, which is nothing but a 5. And C of 2 comma 4 is equal to a minimum of 2 less than k less than or equal to 4. So which k holds the values 3 comma 4. And C of I, it's 2, k minus 1. First case k is 3, 3 minus 1, 2 plus C of k, 3 comma j, 4. And the second case again, now k, consider k as a 4, 4 minus 1 it is 3 plus C of k is a 4 comma j is 4 plus a weight of 2 comma 4. So now consider the minimum among these two, C22, C22 is 0 plus 3, 4, 3 and 4, it's a 3, 2, 3, 2, 3, it is 3, see, 2, 3, it is 3, yeah, plus 4, 4, it is 0. So you can consider any value, k can be either 3 or 4, right, plus 5, so which is nothing but 8, so R of 2 comma 4 will be either 3 or 4, anything you can consider, I consider it as 3, okay, because both are same. Now, update here, W of 2, 4 is equal to, W of 2, 4 is equal to 5, and C of 2, 4 is equal to 8, and R of 2, 4 is equal to 3 or 4, whatever you can consider anything, right? So here R is 4, 4 is equal to 0. So now we have calculated the root. We have find out the root if the tree consists of 2 elements. That means the difference between I and j should be 1. Sorry, 2. Now we have to consider this one. J minus I is equal to 3. Now that means if the tree is having 3 nodes, okay, if tree is having 3 nodes, which one should be considered as a root? So for this we have to calculate the things like W of 0, 3 and W of 1, 4. So 0, 3 and 1, 4, right? Now W of 0 comma 3 is equal to W of I j minus 1, 2 plus P of j 3 plus Q of j 3. So I am applying only these formulas. So is equal to, I write here itself, okay. W of 0, 2, W of 0, 2, it's a 12 plus P of 3, 1, 2, 3 is 1 and Q of 3, 0, 1, 2, 3 is 1. So which is nothing but 14. W of 0, 3 is 14. And similarly C of 0 comma 3, and here we are getting minimum of 0 less than k less than or equal to 3, where k will be holding the values of 1, 2 and 3. So we are getting 3 values. Now first case, consider k as 1. So C of I, k minus 1, 0 plus C of k, 1 and j, 3. Second case, C of I, 0, k minus 1, 2 minus 1, 1 plus C of k, 2 and j, 3. And third case, 0, C of I, 0, k is 3, k minus 1 it is 2 plus C of k, 3 and j, 3. And then add W of 0 comma 3. Now you can consider here a minimum among these 3 values. C00 it will be 0 plus C13 1 3, C13 it is 12 and C01 01 it is 8 plus C23 2 3 it is 3 and C of 02 02 it is 19 plus C of 33 it will be 0 plus W of 03 which is 14. So among these, which one is the lowest? The second one, 12, 11, 19, so 11. 11 plus 14, so this is the minimum value, 8 plus 3. So 11 plus 14 is a 25, 25. Now what is the root of 03? Then the k value becomes the minimum. So second case k value is 2. So R of 03 is 2. Now you can see 14, 25 and 2, update here. So W of 03 is equal to 14, C of 03 is equal to 25 and R of 03 is equal to 2. Okay, and we have to check with the one more case, that is 1, 4. 1, 4, calculate the same, apply the same formula for this to calculate the weight, cost and root. So W of 1 comma 4, so which is equal to W of I 1 j minus 1 3 plus P of j 4 and Q of j 4. So W of 1 3, W of 1 3 it is 9 plus P of 4 it is 1 plus Q of 4 it is again 1, so which is 11, which is 11. Now we need to find out the cost. So cost of 1 comma 4, it will be a minimum of 1 less than k less than or equal to 4. So k value will be 2 comma 3 comma 4. So first case C of I 1 k minus 1 here, k first case 2 minus 1 1 plus C of k which is 2 j which is 4. In the second case k will be 3, so 1 comma 2 k minus 1 2 plus C of k 3 and j 4. In the third case k value will be 4, C of I 1 k minus 1 it is a 3 plus C of k 4 and j 4. So which should be added with a weight of 1 comma 4. So here we have to find out the minimum among all these 3. C of 1 1 it will be 0 plus 2 4 2 and 4, C of 2 4 it is 8 and C of 1 2 it is 7 plus C of 3 4 it is 3 and again C of 1 3 it is 12 plus 4 4 it is 0. So among these 3 the first case is having the minimum value, so W of 1 4 is 11, so which will become 19. So root of 1 comma 4 will be obviously the first case, that means a 2. Update this in the table, right? So here we have to update W of 1 4 is equal to 11, C of 1 4 is equal to 19 and R of 1 4 is equal to 2. So first case it's a 2. Okay, so this we have done. Now in the last case we need to find out the root whenever the difference is 4, that means element is having some 4 elements. Okay, the tree is having 4 elements. So our element is also 4 elements, right? The number of nodes we have taken is 4. So this will be the last case. So it will be 0 4, this part. So we need to calculate the same formula, we have to apply the same formula and calculate the weight, cost and root. So weight of 0 comma 4 is equal to W of I 0, J minus 1 3 plus P of J 4 plus Q of J 4. So W of 0 3, W of 0 3, which is a 14, and plus P of 4, it is 1, Q of 4, it is 1, so which is 16. And similarly C of 0 comma 4, which is a minimum value of 0 less than K less than or equal to 4, K holds the values 1, 2, 3, 4. So 4 values. So when the first case K value will be 1, second case K value will be 2, third case K value will be 3, fourth case K value will be 4. So C of I means 0, K is 1, 1 minus 1, 0, plus C of K, 1, J 4. This is the first case. Second case, C of I 0. Now I value, K value is 2, 2 minus 1, 1, plus C of 2, 4. Third case, K value will be 3. So C of 0, 2, 3 minus 1, plus C of 3, 4, K, J. And the fourth case, K value will be 4, C of 0, K minus 1, 3, plus C of K value is 4, J, 4. J value is 4. So plus weight of 1, 0, 4. So we need to calculate the minimum among these 4 cases. So what is the first one? So 0 plus C14. C14, it is a 19. C01, C01 is 8 plus C24, 24, it's again 8. And C02, 02 is 19. C34, it's a 3. C03, 03 is 25. And C of 44, it is 0. So among these, the second case, we are getting the minimum 16, right? So plus it is 16. So which will be 16 plus 16, 32. So R of 0, 4, in which K value we got a minimum value, second case K value is 2. So 16, 32 and 2, update here. So W of 04 is 16. C of 04 is 32. R of 04 is 2, here 2. Right? So here we have completed the root nodes, finding of root nodes for each and every case. So the same thing we have applied in the first case also, that means first example in our previous session. But there we have considered only the successful frequencies. But here we are also considering the unsuccessful frequencies. So the calculation of this particular W weight will be different. Okay, that's only different. The formula of C is same and also root is same. Now we have completed this one and we know the root. What is the root? Okay, if the tree is having 2 elements, 3 elements, 4 elements, 1 element and 0 element. Now we need to construct the tree. Yes. Let us consider this one. Let us consider and let us draw the tree. So only the thing is we have to consider it from R of 0, 4. Okay, so R of I, J. Sorry, this is J, which is a K value. So the left tree will be R of I, K minus 1, and right side element will be R of K, J. Okay, again it will be the K values. Whatever the result we are getting, that will be the K values. Consider this one. So R is having some 4 elements. That means the tree is having some 4 elements. We need to start from R of 0, 4. What's the R of 0, 4? 0, 4, it is 2. 2. So here 2 means the second element. So the elements, these are the elements, right? So 1, 2, 3 and 4. Second element. Now the left is R of I, K minus 1. 0, K minus 1. It's a 1. R of 0, 1. What's the R of 0, 1? R of 0, 1 is 1. So here it is 1. And now here it will be R of, so this is a K value, right? K, J, 2, 4. So what's the R of 2, 4? R of 2, 4, it is a 3. 3. And this is a K value, and here this is a K value. Again, the left of this one will be R of 0, K minus 1, which is 0. What's the R of 0, 0? It's a 0. So there is no element. If there is 0, that means it is a no element. Okay. So here on the left hand side, R of, what's the K value? 1, J value 1. R of 1, 1, again it is 0. So we need to stop here. This is no element. Now consider this one. So R of 2, K minus 1, 2. 2, 2. It is again 0. We need to consider. Next, R of 3, 4. R of 3, 4. It is a 4. Right? And here we need to consider R of 3, 4 minus 1, 3. It is 0. Should not consider. Here this one, R of K. K means 4. So here it is a K. Okay. So 4, 4. Which is 0. So that's not. Now this is the optimal binary search tree. Now replace these K values with the corresponding elements. So here 2 means second element. So 20. Okay. On the left hand side, 1 first element. It is 10. On the right hand side, third element, that is 30. And see, again on the left hand side, it is 40. You can see the third element, fourth element. So this is the optimal binary search tree for the given example. You can observe here the root element will be one thing, and all the left subtree will be the less than root elements, and the right subtree will be the greater than root element. You can consider the 20. So left subtree 10, which is less than 20. Right subtree is 30, which is greater than 20. And again 30 is having 40 on the right hand side. So 40 will be the greater than 30. So this is the optimal binary search tree we can construct from the given elements for both the successful searches and unsuccessful searches. Okay, so just remember this formula to construct the tree. R of ij which is left hand side it will be I comma k minus 1, right hand side it will be r comma k comma j. So here the k means nothing but corresponding element numbers. Okay, root elements, right? So first we have to consider, or first we have to calculate what is the weight, cost, and root. Based upon the weight, we are calculating the cost, and based upon the cost, we are selecting the root element. So for which, for when the k value we are taking, we are getting the minimum cost, we are considering that element as a root element. So from this table, we are constructing this particular tree. So this is the optimal binary search tree. So with a less number of comparisons. Today we'll see one more concept in dynamic programming, that is all pairs shortest path. So we can consider any graph, and we are supposed to find the shortest path between all the vertices, right? So for example, if the graph is in this format, right? So this is a directed graph. Then we have to find out the shortest. If you select the vertex 1, we have to find out the shortest path from 1 to 2, 1 to 3, and 1 to 4. So the shortest, there might be a direct edge between the 1 and 2. If not, we have to find the shortest path from 1 to 2 using some intermediate node. For example, so here you can see there is no connection between 1 and 3, right? So there is no connection. So there is an edge between 1 and 2 and 1 and 4, but there is no edge between 1 and 3. So this can be computed that 1 to 2, 2 to 3, right? So like that, we have to find out the shortest path for all the vertices to all different vertices. So we have to consider first vertex, and we have to find out the shortest path from this vertex to all the remaining vertex. And second, we have to consider the second vertex, and we have to consider the shortest path from 2 to 1, 2 to 3, and 2 to 4, either direct or indirect. Direct means direct edge will be there, indirect means through intermediate node, right? And consider the third vertex, and we have to find out shortest path from 1, 2, and 4. And consider the fourth vertex and find out the shortest path from 4 to 1, 2, and 3. So like that, we have to find out the shortest path from one vertex to all the remaining vertices. So for this, we are supposed to find the adjacency matrix, and from that adjacency matrix, we are supposed to calculate all these things. So here we are using a one formula. Okay, so I'll write that formula first, and then we'll apply that one, right? So I write the formula here. Example, A of 1 or k, A of k, that means the adjacency node k, right, is equal to, we have to consider a minimum of in between two terms. What's the first term? The first term will be A of k minus 1 I comma j, or A of k minus 1 I k plus A of k minus 1 k j, right? So we need to select either this one or this one. Simple logic. So this is a direct edge. Okay. So this will be the indirect. That means whatever the intermediate node we are taking. So if we are selecting 1 as a first vertex, so the k will be 1 itself, right? So by using the intermediate node, we are supposed to find the cost from I to j. Okay. So this is the thing. So I to j using intermediate via intermediate node k. Right? Note. So this is ak of ij. So this is the main formula we need to do. So first step, we need to find the adjacency matrix. So find adjacency matrix. So we need to give the cost from one vertex to another vertex. So by finding the adjacency matrix, if there is no edge, okay, if there is no edge from one vertex to another vertex, so fill it with infinity. If there is no direct edge, we have to fill it with infinity. And see, all self loops. Self loop means if you consider the vertex 1, so what is the cost or what is the distance from vertex 1 to vertex 1? Similarly, vertex 2 to vertex 2, vertex 3 to vertex 3, right? So all the self loops should be filled with 0. So we have to remember these three things. First, we have to find the adjacency matrix. While finding the adjacency matrix, if there is no edge, so if there is an edge, directly we can give the distance there, right? So if there is no edge, fill the particular rows and columns with an infinity. So take the distance as an infinity. And for all the self loops, so from same vertex to the same vertex, right? So all self loops should be filled with a 0. So that will be A of 0. Okay, that's an initial adjacency matrix. And then we have to find out A1. That means considering the first vertex. So in that adjacency matrix of A1, okay, so we are finding the shortest path from 1 to remaining vertices. So A1 means, so this is an initial adjacency matrix. A of 1 means shortest path from vertex 1 to remaining vertices. Vertex 1 to remaining vertices. Similarly, from this one we have to calculate A2. So from this one we have to calculate A1. Okay, from this one A1 we have to calculate A2. So A2 means the shortest path from vertex 2 to remaining vertices. Right? And this will be keeps on moving until it goes with the last vertex. A of n means the shortest path. So all these are adjacency matrix, right? So the shortest path from vertex n to remaining vertices. Right? So this should be happens, keep on moving until you find the adjacency matrix for all the vertices. Right? So just remember this one, and we are going to use this formula. You can see A of k. So initially that will be 0, right? Initial adjacency matrix will be 0, A of 0. And from A of 0, we are supposed to find A1. So here k is 1, and k minus 1 is 0. K minus 1 is 0. K minus 1 is 0. So with the help of initial adjacency matrix, we are finding out the A1. And with the help of A1, we are finding A2. With the help of A2, we are finding A3. So that should be keep on moving until it reaches to the all vertices. So finding of shortest path for all vertices. Right? Now let us take an example. So I'll explain you. So let us calculate all these things. Right? So let us take this example. So this is a small graph, directed graph. So the edges, the distance can also be a negative, right? The distance can also be the negative. So first let us write the initial adjacency matrix. So that is A0. So I'll write here. So 0, 1, 2, sorry. We'll write the vertices, right? So 1, 2, 3, and 4. 1, 2, 3, and 4. Fill out all those things, right? So 1 to 1, which is a self loop. Okay. So we have seen all the self loops should be filled with the zeros. So 1, 1, 0. 1 to 2, there is no edge from 1 to 2. There is an edge between 2 and 1, 2 to 1. There is no edge between 1 to 2. So if there is no edge, we have to fill with infinity. So 1 to 2, it is infinity. 1 to 3, yes, there is an edge between 1 to 3, it is 1, but distance is 1. 1 to 4, no edge. So simply use infinity. 2 to 1, 2 to 1, there is an edge, the distance is 3. 2 to 2, it's a self loop, so fill with 0. 2 to 3, there is no edge, fill with infinity. 2 to 4, there is no edge, fill with infinity. 3 to 1, 3 to 1, there is no edge, infinity. 3 to 2, 3 to 2, yes, there is an edge, so 2. 3 to 3 is a self loop, so 0. 3 to 4, no edge. 4 to 1, it is 5. 4 to 2, infinity. 4 to 3, 9. 4 to 4 self loop is 0. So this is the initial adjacency matrix. So we are calling it as A0, adjacency matrix, initial adjacency matrix. Now what we have to do, we have to find out the A1. So with the help of A0. So A1 should be calculated. So A1 means we have to find the shortest path from vertex 1 to all remaining vertices. So for that we have to do, so we have to keep the first row and first column as it is in the adjacency matrix. Okay, so where A1 is used to find the shortest path from first vertex to all the remaining vertices, so we have to keep the first row and first column as a same, right? So A1 will be having the values, so 1, 2, 3, and 4, 1, 2, 3, and 4. So keep the first row and first column. So the first row is 0, infinity, 1, infinity, column 3, infinity, 5. And see, these are the self loops, we have to go with a 0. So we need to find all the remaining items, okay, remaining places. So what is this place? 2, 3. So A1 of 2, 3 is equal to, so minimum of AK minus 1, A1 minus G1, 0 of 2, 3, and comma A0 of 2, 1 plus A0 of 1, 3. So we need to find the minimum from these two things. Okay, so we have to find the distance from 2 to 3 from A0, and here we need to find the distance from 2 to 1 in adjacency, initial adjacency matrix plus 1 to 3. So that means we are finding the edge of 2 to 3 with 1 as an intermediate node. With 1 as an intermediate node. So you can find out here. So minimum of, so from A0, say A2 to 3, A0 2 to 3, this is the A0, 2 to 3, it's a infinity. And coming to this one, A0 2, 1, 2, 1, 2 to 1, it is a 3 plus 1, 3, 1, 3, it's a 1. So you can see we have to consider minimum of infinity and 4. So what will be the final thing? So it will be 4. That means the distance from 2 to 3 is infinity initially. So by using the first node, first vertex, so visiting from first vertex, right? So 2 to 3 with 1 as an intermediate node, it can travel from 2 to 1 and 1 to 3 with a distance of 4. So there is, among these two, this one is a minimum, right? 4 is a minimum. So fill that one here. So this will be 4. This will be 4. Now coming to the 2, 4, we need to find out the 2 and 4. So what we have to do, again the same procedure, A0 of 2, 4 is equal to minimum of, so A0, A1, right? A0 of 2, 4, direct this one, and A0 of 2, 1 plus A0 of 1, 4. So we are taking 1 as an intermediate node between 2 and 4. So from this one, you can find out minimum of, so from A0, what is a 2, 4? 2, 4, which is an infinity. And here 2, 1, 2, 1, it is a 3, plus 1, 4, 1, 4, it is an infinity. So simply you can say both are infinities. Both are infinities. So we can consider the infinity here. So I'll consider infinity only. Okay, I'll consider infinity only. So you can see from 2, 4, using 1, there is no path. You can see the graph. So from 2 to 1, there is an edge, but 1 to 4, there is no edge. So that's why we got infinity here. Okay, then next, this one, 3, 2. So A1 of 3, 2 is equal to a minimum of A0, 3, 2 and A0, 3, 1 plus A0, 1, 2. 1 has intermediate node between 3 and 2. So you can consider here minimum of, what is the 3, 2 distance? 3, 2, it's a 2. And A0, 3, 1, 3, 1, it's an infinity plus 1, 2, 1, 2, it's an infinity. So among these, which is the minimum? 2 is the minimum. So just to keep the same here, 2. Okay, now you have to find out this one, 3, 4. 3, 4, right? So A dash of 3, 4, which gives a minimum value of A0, 3, 4 and A0, 3 to 1 plus A0, 1 to 4. So you can consider minimum in adjacency matrix 0, 3, 4, 3, 4, which is an infinity, and 3, 1, 3, 1, which is an infinity, plus 1, 4, which is again infinity. Again, we got infinity only. So that means there is no edge between 3 and 4 also, by using in 1, right? So we got infinity here. Next, this one, 4, 2. Hope you understood. Just we are applying the same in this formula. So A1 of 4, 2. So minimum of A0, 4, 2. Similarly, A0, 4, 1 plus A0, 1, 2. So a minimum of, what is the 4, 2 distance? 4, 2 is an infinity. Next, 4, 1 distance, 4, 1, it is a 5 plus 1, 2, it's an infinity. Right? So 4, 1 is there, but 1 to 2 there is no distance. So again, we got an infinity plus the infinity here. And next one, 3. 3. So A1 of 4, 3. We need to find the distance for 4, 3. So we can consider here minimum of A0, 4, 3, and also consider 1 as an intermediate node and find out the path A0 of 1, 3. So a minimum of, you can find the distance from 4, 3 in A0. 4, 3 is a 9, and 4, 1, 4, 1 it is 5, plus 1, 3, 1, 3 it is 1. So 9 and 6 it is 6. Right? So by using 1, okay, from 4, by using 1 you can go with the 6 distance, you can reach 3. So 4 to 1, 5, 1 to 3, 1, 6. So minimum distance is 6, you can simply place here 6. So this adjacency matrix gives that from vertex 1, the shortest path to all remaining vertices. Okay, now what we have to do? We have completed A1. Now we have to find out A2. Okay, A2. So what is this A2? Finding the shortest path from vertex 2 to all the remaining vertices. All the remaining vertices. For this also what we have to do? So we have to make use of A1 and we have to fix both the second row and second column. So what's the second row? Second row is 0, 3, 0, 4, infinity. Second column, infinity, 0, 2, infinity. And all the diagonals, the self loops will be 0. We know that. And we need to find the remaining. So what's this one? A2 of 1, 3. 1, 3 is equal to a minimum of, what we have to do? We have to take the A1 because AK minus 1. So 2 minus 1 means 1. A1 of, what is this? 1, 3 or A1 of 1, 2 plus A1 of 2, 3. So we need to find the shortest distance, whether it is having 1, 2, 3 or by using the intermediate node 2. So here we are finding the shortest path from the second vertex. So the intermediate node will be 2. So we can find out here a minimum of, what's the value of A1, 3 from A1. This from here, 1, 3, it is 1. 1 to 3, it is 1. A1, 2, 1 to 2, it is infinity, plus 2 to 3, it's a 4. So obviously this will be infinity, so this will be the minimum. So fill that one here, 1. Right? Next, A of 1, 4. Okay, we need to find A2 of 1, 4. So that will be a minimum of A1 of 1, 4 or A1 of 1, 2 using intermediate node plus A1 of 2, 4. So we need to select the minimum among these two. So from A1, what is the 1, 4 distance? 1 to 4 distance is an infinity. From A1, 1 to 2, 1 to 2 again it is an infinity, plus 2 to 4 again it's an infinity. So obviously what happens? Infinity. So place the infinity here. Okay, the next one. We need to find A2 of 3, 1. 3, 1. So what we have to find? So minimum of either direct edge from adjacency matrix 1 or by using the intermediate node 2, 3, 2 plus A1 of 2, 1. So what, is there any edge? 3, 1 from A1. 3, 1. It's an infinity. A1, 3, 2. 3, 2 is a 2 plus 2, 1. 2, 1. It's a 3. You have to find out the minimum among these two. Obviously it will be 5. So you can see the distance from 3 to 1. So distance from 3 to 1. Okay, there is no edge. So by using intermediate node 2, there is a distance 5. So that's what we are finding out. So fill it with here 5, and next find out the value of 4, 3, 4. So A2 of 3, 4, which is a minimum of what we have to do, A1 of 3, 4, and A1 of 3, 2 plus A1 of 2, 4. So we need to find out the minimum among these two. So minimum of 3, 4 from A1, 3, 4 from A1, it is a infinity. 3, 2 from A1, 3, 2 from A1, it is 2 plus 2, 4, it's infinity. So which is infinity. So from 3 to 4, there is no cost. 3 to 4. By using intermediate node, there is no edge from 2 to 4 also. Therefore, otherwise we will be having infinity. And next, we need to find two more values, that is a 4, 1 and 4, 3. So A2 of 4, 1, which will be a minimum of A1, 4, 1 and A1, 4, 2 plus A1, 2, 1. So what we have to do, minimum of 4, 1. What's the cost between 4 and 1? So 4 and 1, it's a 5. And 4, 2, with intermediate node, 4, 2, it's an infinity plus 2, 1. 2, 1, it's a 3. So obviously this will be infinity and this will be the minimum, so 5. So you can simply take it as a 5. And now the next one, 4, 3. Find out the 4, 3. So A2 of 4, 3. So which gives a minimum value from the direct edge or using intermediate node. So A1, 4, 3 or A1, 4, 2 plus A1, 2, 3. So from A1, what is that 4, 3? So 4, 3 distance is 6 and 4, 2. 4, 2 distance is infinity plus 2, 3. 2, 3 distance is 4. So obviously this will be infinity and this is a minimum, right? So 6 will be the result and that will be stored here. So this adjacency matrix indicates the shortest path from 2 to all the remaining vertices. Now what we have to do, again we have to calculate the A3. A3. That means we have to find out the shortest path from third vertex to all the remaining vertices. For this we have to use A2. So 1, 2, 3, 4. 1, 2, 3, 4. So what we have to do, we have to keep the third row and third column in the same from A2. So from A2, what is the third column? So 5, a third row, 5 to 0, infinity. Third column, so 1, 4, 0, 6. And we know that the self loop, we are having zeros. And we need to find out all these elements. So A3 of this one, 1, 2, 1, 2, we have to find out a minimum of A2 from the matrix 2, 1, 2, or A2 of, take the 3 as an intermediate node and find out the distance, A2 of 3, 2. So a minimum of, consider 1, 2 distance from 2, 1, 2 is an infinity. And what about the next one, A2, 1, 3. A2, 1, 3, it is 1 plus A2, 3, 2. A2, 3, 2, it's a 2. So which gives a 3. So we need to fill the value. 3 is a minimum among infinity and 3. So 3 should be here. So you can check from 1 to 2 with the index 3. Okay, with the intermediate node 3. So there is no direct edge from 1 to 2. So in order to reach 2, what is the minimum cost? 1 to 3, 3 to 2. So 1 to 3 is 1, 3 to 2 is 2. So total 3, distance 3. Okay. Next, we need to find out the distance of 1, 4. So A3, 1, 4, which is nothing but minimum of, okay. So A2, 1, 4, and similarly A2, 1, 3 plus A2, 3, 4. So from A2, 1, 4, what's the 1, 4? It's an infinity. Coming to this one, A2, 1, 3. A2, 1, 3, it is 1 plus 3, 4. 3 and 4, it's again infinity, right? So obviously, the result will be infinity, so you can just fill with the infinity only. Okay, so there is no path by taking 3 as an intermediate node, right? From 1 to 4. So 1 to 4, you can go from 1 to 3, but there is no edge between 3 and 4. So obviously, it will come infinity. The next one, 2, 1. A3 of 2, 1. So which gives a minimum A2, 2, 1 or A2, 2, 3 plus A2, 3, 1. So taking 3 as an intermediate node. So from adjacency matrix 2, 2, 1, 2, 1, it is a 3. And A2, 2, 3, 2, 3 is a 4 plus 3, 1, it's a 5. So you can see we have to consider the minimum, right? Minimum. So obviously 3 will be the minimum. So we can have a path from 2 to 1. From 2 to 1, there is a direct edge or with the help of 2 to 3 and 3 to 1. Okay, 2 to 3 and 3 to 1. So 2 to 3 means 2 to 3, it's a 4, right? How we are getting 4? So from adjacency matrix 1. So obviously from here we are not having 2 to 3, right? So if you want to reach 3, we can go with the 2 to 1 and 1 to 3. So for that we are having 4. So with that cost also we cannot reach 1 from 2, right? With the 3 as an intermediate node. So 3 and 9. So obviously the 3 will be the minimum value. So fill the 3 here. Okay, hope you understood. So here the edge from 2 to 1. There is 2 to 1, there is a direct edge, and we are also checking whether there is an edge with a minimum cost if you consider 3 as an intermediate node. So we are not having that one. Next. So A3 to 4 is equal to minimum of A2 to 4 or A2 2, 3 plus A2 3, 4. So you can check minimum of A2, 4, sorry, this one, 2, 4, it is an infinity. Similarly, 2, 3, it's a 4 plus 3, 4, again it's an infinity.
So obviously there is no edge, right? Next, 4 1. We have to find out 4 1. So A3 4 1, which will select a minimum from A2 4 1 or A2 4 3 plus A2 3 1. So what we are doing, A2 4 1 4 1, it is a 5, and A2 4 3, it's a 6 plus 3 1, it's a 5. So you can see there is a direct edge with a minimum cost, and if you are taking 3 as an intermediate node, the distance will be more. That means 11. It becomes 11. So we should consider only 5. So fill 5. And again 4 2, we have to consider 4 2. So A3 is equal to, sorry, A3 of 4 2, which should be considered minimum value from A2 4 2 or adjacency matrix 2 with an intermediate node 3 4 3 plus A2 3 2. So minimum of, you can select A2 4 2. In A2 4 2, it is an infinity. A2 4 3, it is a 6 plus A2 3 2, 2 8. So 2. So obviously it will be 8. So fill here 8. Okay. So hope you understood this one, right? Next, find out the A4 adjacency matrix 4, so that we have to consider, right? So we have to make the fourth vertex and then fourth row and fourth column as a constant, right? 5 8 6 0. Similarly, infinity infinity infinity. So you can check 1 to 4. There is a no path. Okay, so there is no path. If you go with the 2 also, there is no path. If you go with the 3 also, there is no path to 4. So that's why we got an infinity. And 2 infinity. From 2 also, there is a 2. And if you go with the intermediate node 1, so 2 to 1, there is no edge from 1 to 4. Here also, there is no edge from 2 to 3. Right? So obviously that will be infinity. Similarly, 3 infinity. So 3 to 4, there is no edge. If you consider 2 as an intermediate node, 3 2, yes. From 2, if you take 1 as an intermediate node, yes. From 1, there is no edge to 4. So there is no connectivity from 3 to 4. That's why we got an infinity. So infinity means there is no path. There is no path. And see, coming to here, what we have to do? So the self loops, it will be zeros. And here we have to find these things, right? So A4 of 1 2 is equal to minimum of, what we have to do? So A3 of 1 comma 2 or A3 of 1 comma 3 plus A3 of 3 comma 2. So making 3 as an intermediate node. Okay, sorry, it's a 4, right? So we are taking 4 as an intermediate node. So 1 4 and 4 2, right? So what we have to do? So minimum of, you can consider from A3 1 2. 1 2 means it's a 3. And A3 1 4. 1 4 is infinity. Plus 4 2. 4 2 is 8. So obviously 3 and infinity, 3 is a minimum, so you can fill it with 3. Okay. Next, find out the A4 of 1 3. 1 3 is equal to minimum of A3 of 1 3 or A3 of 1 4 plus A3 of 4 3. So taking 4 as an intermediate node. So minimum of A3 1 3. So in A3 1 3, it is a 1. And coming to 1 4, 1 4, it is an infinity. Plus 4 3, 4 3, it is a 6. So 1 will be the result. So here we can take it as a 1. Okay. Now coming to the next one, 2 1. So A4 2 comma 1. So it will be a minimum from A3 2 comma 1 or A3 2 comma 4 plus A3 4 comma 1. So which will be taken as minimum of A3 to 1. 2 1 is a 3. A3 to 4. 2 4 is an infinity. Plus 4 1 is a 5. So obviously this is a minimum. So simply consider 3 here. And similarly A4 to 3 is equal to minimum of A3 to 3 or A3 2 comma 4 plus A3 4 comma 3. And you can see the cost from 2 3 in adjacency matrix 3. 2 3 it is a 4 and 2 4 it's an infinity plus 4 3 it's a 6. So obviously this will be infinity and 4 should be taken. So 4 will be filled here. Okay. Next 3 1. So A4 of 3 comma 1, which will be taken from minimum A3 3 comma 1 or A3 3 comma 4 plus A3 4 comma 1. So from this we can see minimum of A3 3 1. 3 1 is a 5 and A3 3 4. 3 4 is an infinity plus 4 1. It's a 5. So 5 will be the minimum because infinity plus something will be infinity. So 5. We can go with the 5. And next and the last one, A4 of 3 2 is equal to the minimum of A3 3 comma 2 or A3 3 comma 4 plus A3 4 comma 2. So what will be the value? Minimum of A3 2. So in the adjacency matrix 3 3 2 it's a 2. 3 4 see infinity plus 4 2 which is a 8. So obviously 2 will be the minimum. So you can write it as 2.
right? So this is the final adjacency matrix where all the vertices can be visited with the shortest path from one vertex with the all other vertices. So you can see 1 to 1 0, so 1 to 2. If there is no direct edge between, okay, there is no direct edge between 1 and 2, but the shortest distance is 1 to 3 and 3 to 2. The cost is 3. Okay, initially it is infinity. Now with the minimum cost 3, the person can visit from 1 to 2. Similarly, 1 to 3 there is a direct, 1 to 4 there is no edge, 2 to 1, 2 to 3. Coming to 2 to 3. So if 2 to 3, we can reach 3 with the minimum cost with using 1 as an intermediate node, 2 to 1 and 1 to 3. So 3 plus 1, it's a 4. So this is the final adjacency matrix which gives the shortest path from one vertex to all other vertices. Right? So hope you understood. So infinity, here infinity means there is no way to reach from 1 to 4 by using intermediate nodes also. So you can see 1 to 4. So 1 to 4. So there is no outgoing edge from 1 to 2 or 1 to 4. There is an outgoing edge from 1 to 3. So you can consider 1 to 3 and you have to check whether there is an edge between 3 to 4. So from 3 there is no outgoing edge, you can observe. There is no outgoing edge. So it is impossible to reach 4 from 1. So in such cases we are filling with an infinity. The same case comes with a 2 to 4. So it is impossible to reach from 2 to vertex 4. Okay, in this example, in this particular example. So based upon the given graph, you have to draw all these things. So you have to find out all these things. So find out the initial adjacency matrix. With the help of initial adjacency matrix, you have to find out the A1, considering the first vertex as a constant, as an intermediate node, and finding all the shortest paths from 1 to all the remaining vertices. And from this A1, we have to find out the A2, which means taking 2 as an intermediate node and finding all the shortest distance from vertex 2 to all the remaining vertices. And after calculating A2, with the help of A2, we have to find out the A3, which means 3 is an intermediate node. Vertex 3 will be an intermediate node, and we are finding the shortest path from vertex 3 to all the remaining vertices. And after calculating A3, we have to find out A4, which means 4th vertex is the intermediate node, and we are finding the shortest path from vertex 4 to all the remaining vertices. So here we are having only 4 vertices, so we have calculated from A1 to A4. A0 is the initial adjacency matrix. Right? So final A4 gives the shortest distance from one vertex to all other vertices. Today we will see the difference between the divide and conquer methodology and the dynamic program methodology. So first I'll write divide and conquer, and here we'll write dynamic programming. Dynamic programming. So already we have seen the methodology, how these works in our previous sessions. I'll post the link in the description so you can follow that one. And also we have seen different applications which follows this divide and conquer and which follows the dynamic programming. Right? So now we'll see what is the difference. The first is a common thing. So both are the algorithmic methodologies to find the solution for a problem. So the working or the working process is similar in both of these. So what is the first one? So here the problem is divided into subproblems. Divided into subproblems. That's the main thing. To find the solution, the complete problem will be divided into subproblems. The same thing will be applied here also. Okay, the same thing will be applied here. So here also a problem is divided into subproblems. Okay, but what is the difference? So here the solution for these subproblems are independent. So one subproblem will not depend upon the another. But that doesn't happen in this dynamic programming. The solution of one subproblem will be used in another subproblem. Okay, so here there is no overlapping. We are calling it as an overlapping if the subproblems are independent. Okay, based upon the dependency, we are calling it as an overlapping, right? So subproblems are independent. So which will not be dependent on other. That means here we can say no overlapping, or we can call it as a non-overlapping subproblems. Okay, but here what happens? The one subproblem will depend on other. Okay, the solution of one subproblem may be used for other. So here subproblems are dependent. That means one subproblem will depend on other. So we can call it as a overlapping subproblems. We call it as a overlapping subproblems. Here there is no overlapping. There will be having an overlapping. Now here the combination, or after getting the solution for each subproblem, combining of these solutions will form the final solution. Okay, sometimes the solution of the individual subproblems may also lead to the solution. Okay, so solutions of subproblems. So we are saying every problem is divided into subproblems. So we need to find the solutions for subproblems. So solutions of subproblem combines to produce overall solution. That's the final solution. And sometimes the solution of only single subproblem may also lead to the overall solution. But here this is also same thing. Solutions of subproblem combines to produce the overall solution. So the same thing here. So solutions, and see here we should call it as an optimal solutions. Optimal solutions of subproblems. Optimal solutions of subproblems combines to produce optimal solution. Optimal solution. So that's the most important. So here in the divide and conquer, we can't say that solution is an optimal. Okay, there will be only one solution. So we can't say that is an optimal solution, and that will be obviously the optimal solution, right? So whenever we are saying it as an optimal solution means, so whenever we are having a multiple solutions, among those multiple solutions, if we want to get the best solution, then we are calling it as an optimal solution. But divide and conquer is not like that. If you see an example, let us take some quick sort or a merge sort. Merge sort is a best example for the divide and conquer, right? So whatever the process we are using, we'll be getting only one solution, which is the sorting of elements. So there are no multiple solutions there. For if you consider binary search, so we are dividing the complete solution into two halves, and we are processing only one category. That means only one half. And finally, we are getting the result. So there also we are not having a multiple solution. There will be only one solution, whether the element is present or not. So here we will be having only one solution. There will be no feasible solutions. But in dynamic programming, we'll be having the feasible solutions. So we need to select the optimal solution, and this optimal solution will be getting only combining of optimal solutions of subproblem. So we are saying that problem is divided into subproblems, and we need to find the solutions for this subproblem, and thus solutions are also should be optimal here, right? So the next one, solutions of subproblems will not be stored in memory. Solutions of subproblem, these solutions of subproblems will not be stored in a memory. But here the solutions, the optimal solutions of subproblems will be stored in memory, because so here we are supposed to retrieve the data whenever it is required, because each subproblem is dependent on another subproblem. So we need to combine all the solutions of all subproblems to get the optimal solution. So here the solutions of subproblems will be stored in a memory, but here the solutions of subproblems will not be stored anywhere else. Okay, and here, and this divide and conquer uses top-down approach. Okay, top-down approach. But here the dynamic programming mainly uses a bottom-up approach. Bottom-up approach. So here this process we are calling it as a memorization. Okay, and the applications of divide and conquer, and before going to the application, the time complexity. So the complexity will be more in divide and conquer when compared to the dynamic programming, because it requires a more number of computations, because all the subproblems are independent. So the recursive calls should be more in order to solve each and every subproblem, right? So it is less efficient than dynamic programming, and as it requires more computations. Okay, so because of independent nature, we need to calculate a more number of computations. But here that doesn't happen, because we are calculating, or we are solving the subproblem, and we are storing the solution in the memory. So whenever it is required, just instead of reconstruct or recalculate, we can automatically retrieve the data from the memory itself. So for that purpose, the efficiency will be high when compared to the divide and conquer. So here only comparing dynamic programming and divide and conquer, right? So more efficient than divide and conquer, as it avoids redundant computations. That means once you've done that, so that will be stored in a memory. So once again, we need not calculate the same thing, right? So we can make use of the existing. We can retrieve the data from the memory itself, right? So here the last one, the applications. So what are the applications that uses this divide and conquer? We know that quicksort, binary search, merge sort, etc. Okay, a lot of applications. And here the applications which use these dynamic programming is optimal binary search tree, OBST. Okay, optimal binary search tree. So that's the one thing we can use by using this dynamic programming. Okay, and etc. There are more number of applications which uses the dynamic programming, but among these two, the dynamic programming is efficient than the divide and conquer because of the overlapping subproblems. So it will be having a feasible solutions. So among the feasible solutions, we are selecting the optimal solution. Okay, so hope you understood the difference among divide and conquer and dynamic programming. We'll see the difference between two problem solving methodologies in algorithm, that is dynamic programming and greedy method. So the first one is dynamic programming, and the second one is greedy method. So we'll see the differences. So the first difference is which kind of problems we have to use this dynamic programming and this greedy method. So both are same. So that means both the cases, I mean both the approaches can be used to solve the optimization problems. So where the problem should have the optimal solution, in such cases we are going to use this dynamic programming or the greedy method. So in order to solve the optimization problems, these two approaches will be used. So it solves optimization problem. And here also the same thing, solves optimization problem. So optimization problem means getting the best solution, optimal solution. So there will be a lot of solutions. So among that lot of solutions, we have to select the best solution. That is called the optimization problem. And the second difference is also same. So that means the complex problem will be divided into subproblems. So the second difference, problem is divided into subproblems. Coming to this one, here also divided into subproblems. And see which kind of subproblems these are. In dynamic programming, these subproblems depends on one to other. So there will be a dependency upon the subproblems. So that usually we are calling it as overlapping subproblems. So there will be overlapping nature. So these subproblems are overlapping subproblems. Whereas greedy method, no overlapping will be there. No overlapping. So that means here one subproblem will be depending upon other. That means if you want to solve one subproblem, it will take the result of another subproblem. And here there will be no overlapping. That means here the problem solving approach, is finding feasible solutions and selecting optimal solution. Finally, we'll be getting the optimal solution. But here, at each and every stage, it will be selecting the optimal solution. Each and every stage. So, each stage, it selects optimal choice. Optimal choice. Rather finding all the feasible solutions and selecting the optimal solution, it will be selecting the optimal choice at each and every stage. And here, so memorization will be there. That means the results will be stored in the memory. So the results of subproblems will be stored in memory, because as we are saying that this is a overlapping subproblems. If you want to solve one problem, it may require the result of another subproblem. So that's why in order to avoid the recomputation, so it will store all the results of subproblems in a memory. We usually call it as a memorization. And here there is no option of backtracking. No option of backtracking. So results will not be stored because there is no overlapping, right? So results will not be stored in a memory. And one more difference. So in order to apply this dynamic programming, we'll be using bottom-up approach. So it follows the bottom-up approach. And here, so it will be using the top-down approach. Top-down approach. And obviously, when compared to the dynamic programming, greedy method works fast. So it is slow when compared to greedy. When compared to greedy method, this will be slow. And when compared to dynamic programming, works fast. It works fast. Okay. And the next very important thing is the next important thing is guaranteed of finding optimal solution. So if you are using this dynamic programming approach, it is guaranteed that we'll be getting the optimal solution. But here, no guarantee of getting optimal solution. There's no guarantee, right? Because here each and every stage we are getting this optimal choice. So there will be no guarantee of getting the optimal solution in greedy method. But dynamic programming definitely will be getting the optimal solution. Okay, but time taking. It's a time taking process because we are storing the complete results in the memory. So some memory will be required to store and retrieve the data. But here results are not stored in the memory, right? So there is no concept of memorization. So that's why it will be very fast, but it will work with very slow. And some applications here we can say it is 0-1 knapsack. One such kind of application which will be using dynamic programming is 0-1 knapsack problem. So that means 0, 1 knapsack problem means this problem will be having to solve the non-divisible products. So we can't divide them, right? So this can be worked with fractional knapsack. So fractional knapsack means for all the divisible products. So these are the major differences among dynamic programming and greedy method. So only one thing, here it goes with the memorization, here there will be no memory. So that's why this works slow, this works fast, and it follows the bottom-up approach, it follows the top-down approach. And one major thing is there will be a guarantee of getting the optimal solution in dynamic programming. There will be no guarantee of getting the optimal solution in greedy method. Right? So hope you understood. So both will be working for solving the optimization problems. That's the first and most important thing.
So graphs in a data structure is also similar to a trace, but here we can have a closed loop, right? So whereas in a tree we can't go with a closed loop, but here graph can have a closed loop, and here a graph is defined as a set of V comma E phase, where V is a set of vertices, E is a set of edges. So a graph can be defined as a set of vertices and a set of edges. So every graph will be having a vertices and edges. So vertices can be represented as circles, and these are also known as nodes. Edge is represented as lines, and also so lines which are connecting two vertices or nodes. So a graph can be defined as vertices and edges. So vertices are represented as circles and the edge is represented in the lines. So let us take an example for this graph. This is a simple graph. This can be called as a graph. So here B and C are vertices or nodes, and the connectivity between the vertices AB and AC are, so AB, A comma B, A comma C. These are called edges. So edges means the connecting two nodes, right? So this can be considered as a graph. And if you have a line between this B and C, so BC, it also forms a page. That means it is also an edge. So this is also a graph but not a tree. So in the absence of this one, in the absence of this edge, this can be either a graph or a tree, right? So if you have an edge between B and C, it is a closed loop. It's a closed surface, right? It forms a cycle. So if it forms a cycle, it cannot be called as a tree. It is a graph. That's the only difference between the tree and a graph, right? So here the nodes and edges. So let us see. First, let us see the terminology of a graph, and then we'll go with the types of graphs, different kinds of graphs. Graph terminology. The first one is node. First one is a node, which is nothing but vertices represented as a circle, and then edge, which is a line, it's a connection between two different nodes, right? The third one is adjacent nodes. So if you consider any edge, that means there will be, so let us take an example, A, B, and similarly A, C, similarly B, C. So there are three edges, right? Three edges. So for this edge, the node A and B are the starting and ending points. For this edge, the node B is the starting point, C is the ending point. For this edge, A and C are the end points for this particular edge. So that's why the adjacent nodes means which connects an edge, those nodes we call it as adjacent nodes. In this example, A and B are adjacent nodes. Similarly, A and C are adjacent nodes. Similarly, B and C are adjacent nodes. So this is how we can have the edge. So degree of a node. So how to calculate the degree of a node? So it represents the number of edges corresponding to the particular node can be considered as a degree of node. Number of edges connected to that node. For example, let us take this one, A, B and C. Right? Now degree of A. What is the degree of A? So A is having two nodes, so degree of A is 2. So degree of B is also having two nodes, so degree of B is 2. Similarly, degree of C is also having two nodes, 2. So in the absence of this one,
So degree of A is 2, degree of B is 1, degree of C is 1, because B is having only one node towards A, C is also having one node towards A. So that's why we call this degree as the number of edges connected to that node. Size of a graph. Size of a graph. So size of a graph represents the total number of edges. The total number of edges in graph can be considered as the size of a graph. So let us take this example. So there are 3 edges in this graph. So size of this graph is 3. So size is 3. What about this example? Only 2 edges are there. So the size for this graph is 2. So the total number of edges in the graph represents the size of a graph. Path. Path means the sequence of vertices. So from starting node to ending node. So sequence of vertices from source node to destination node. Source node to the destination node, right? So let us take an example here. So if you take this one, A, B, C, D. So if you want the path from A to C, right? A to C. So this is the source, this is the destination. The path will be A to B to C, or A to D to C. So whatever the edges or the sequence of vertices from source node to destination node. So here the source is A and the destination is C. So we can have that the path can be A to B, B to C, or A to D, D to C. Right? So this is called a path. Okay. Then, so these are the basic terminologies we need to know before starting the graphs concept. So hope you understood the definition of the graph. So graph is a set of vertices and edges. Right? Now we'll go with the different kinds of graphs, different types of graphs. Types of graphs. So the first one, directed graph and undirected graph. Right. Directed and undirected. See, coming to this undirected, so there will be no directions specified on the edges. So let us take an example. So A, B, C, D, and A. Let us take one more thing. So this one. Right. So this is also a graph. It contains vertices and edges. Right. So in this example, there is no directions specified on the edges. So we can travel from A to B or B to A. So here, A comma B is equal to B comma A. Right. Similarly, B comma C is equal to C comma A. So that means there is no direction specified in this graph. So we can consider that A and B, A to B is one traversal and B to A is another traversal. So in both the directions we can travel. Right. In both the directions we can travel. So coming to the directed graph, as the name indicates, so every edge will be having a specific direction. That means, so this we can call as a bidirectional, right? This we can call as a unidirectional. So in only one direction we can travel through the edges, right? See, let us take an example here. A, B, C, D, A. So this is called a directed graph because so here every edge is specified some direction. So only one direction we can travel. So there is a node between A and B. So A and B is not equal to B comma A because here we have specified the direction from A to B, not from B to A. So here B to C. So direction is only from B to C. So B is the starting point and C is the ending point, but not the vice versa. Right? So this is the only difference between the directed graph and undirected graph. Right? So hope you understood. It's a bidirectional, it's a unidirectional. It's a bidirectional, it's a unidirectional. So only one way we can travel. So this is the difference between directed graph and undirected graph. Now we'll go with another kind, right? Weighted graph and unweighted graph, weighted and unweighted. So here we have to specify some weight or a cost for the edge. See, let it be either it may be a directed graph or an undirected graph. So there is no any cost specified for that edge. So here we can specify some cost. for every edge. So in order to travel from A to B, the cost is 2. That means here we are specifying some weightage for every edge. So if you specify some weightage for every edge, that is called a weighted graph. So here weight is specified for every edge. No weight is specified. So either it may be a directed or undirected, whatever it may be. So in the directed also we can have the weighted, and in the undirected also we can have the unweighted, right? So whatever it may be, if the edge is having any weight or a cost, then the graph is called as a weighted graph. And if the graph doesn't have any cost or weight specified for the edge, that is called an unweighted graph. So this is the difference between weighted graph and unweighted graph, right? Now we'll go with the third one. We'll go with the third one. Cyclic graph and acyclic graph. Cyclic and acyclic. So cyclic means it should perform the loops. Loop means, so if you find the path from source to destination, the starting point and the ending point should be the same vertices. I will show you example. So if you consider this one, find the path here. So here you can form, so A to B, B to C, C to D, and again D to A. So the starting vertex and the end vertex both are same. So that means it forms a cycle. It forms a cycle, right? So hope you understood this one. So if the starting vertex and the ending vertex are same, then that forms a cycle. And if our graph consists of the cycles, then it is called a cyclic graph. If our graph doesn't have a cycle, then that is called a cyclic graph. See, so here it doesn't form any cycle. It doesn't form any cycle. So this is called a cyclic graph. So similarly, we can say this one. So if any graph doesn't have the loops, that we can call as a acyclic. So in the acyclic also, this graph can be either directed or undirected. It can be weighted or unweighted. So whatever it may be, if our graph consists of the cycles, then we call it as a cyclic. If it doesn't have any cycles, it is called as a cyclic graph. Right? So hope you understood this one. So weighted, unweighted, directed, undirected, cyclic, and acyclic. So these are the different kinds of graphs available in our data structure. Right? And also we have seen a few terminologies. So what is meant by an edge, what is meant by a graph, and what is meant by node, what is meant by path, and degree, how to find the degree, how to find the size, and everything we have seen in this session. So if you are having any doubts regarding this terminology and different kinds of graphs, so feel free to post your doubts in the comment section, so that definitely I will try to clarify all your doubts. And if you really understood my session, like my sessions, share my sessions with your friends, and don't forget to subscribe to our channel. Thanks for watching. Thank you very much. So our topic is graph traversals. So what is meant by this traversals? So traversal means visiting all the nodes. That means traveling around all the nodes in the graph. So here we will not have any root node. So we can assume any node as a starting node. Any node as a starting node. And from that starting node, we have to visit all the nodes without any repetition. That means every node of a graph should be visited only once. Right? Now, we are having two types of techniques in this traversal, graph traversals. So the first one is depth first search traversal. It is called as DFS. And the second one is breadth first search, which is called a BFS. Right? So based upon the depth, we will travel all the nodes of a graph, that is called a DFS. Based upon the breadth, that means level. So we have to visit all the nodes of the same level, then only we will shift to the next level. So that in such a way, we will go with the BFS. We will implement this BFS. So in order to implement this DFS and BFS, we will use the stack data structure for implementing the DFS. We will use queue data structure for implementing the BFS. Right? So now let us take an example and we will see the procedure, how the DFS will work and how the BFS will work. It's a very simple topic. Right? Now, coming to this DFS. See, let us take an example here. A, B, C. Yes. So you can go with this one. Okay. So you can go with this one. This is a graph. So graph is also similar to a tree, but a graph can contain cycles. That means loops. So this is a graph, of course. Right? So now, first, let us assume this one is a start. So we can assume anything. Any node can be a start. Okay. I will assume that a start for simple understanding. Right? So I will visit one by one. Okay. So after visiting this one, so I will place a weight as 1. I have visited A, I have placed it as 1. Now I am coming to C. Right? So you can go with the B or C, anything else. Okay, both are same. You can visit either B or C. So we can get a different outputs. Okay. So I will visit C. So the C weight is 1. Now from the C again there are 2 adjacent nodes. So we can visit any one node. Okay. So I will go with the G, and the weight of G is 1. Now it is a leaf node. There are no nodes. Okay. There are no adjacent nodes. We should not say it is a leaf node. We are not having any adjacent nodes. So backtrack C and go with another adjacent node, right? And mark it as 1. So here also there is no adjacent nodes. Again backtrack. So again the node is visited. So go with the adjacent node. So B will be 1. Now again B is having 2 adjacent nodes. We can go with the D or E. Anything. Okay. So I will go with the D. Mark as D1. Again there are no adjacent nodes. Backtrack. Right. Again go with the E and go with the 1. So there are no nodes. Okay. There are no adjacent nodes. Backtrack and again backtrack. Again we came to the start node and there are no adjacent nodes. So this is how we can use this DFS. So first we have visited A, then C, then G, again backtrack C. So already C is visited, so we should not write C. Next F, right? Next no adjacent nodes. Again C is visited. Again A is visited. B, and then we have visited D. No adjacent nodes. Backtrack B, already there. No E. So E, there are no adjacent nodes. Again backtrack to B. B is there. Backtrack to A is there. So there are no adjacent nodes. Any other adjacent nodes. So this is the DFS of a given tree. So right here. Okay. So this is the DFS for the given graph. Right? Now we'll go with the implementation part. So for implementing this one, we will use the stack. So for the step one, consider a stack and consider the DFS expression. Right? So starting node, push the starting node into a stack. So A will be present in here. So A is pushed here. Now pop the A and place it in the DFS expression. Right? So this is the DFS expression. So step 2. In the step 2, so popping the A and placing A here. Now place the adjacent nodes. Here. So we'll go with adjacent nodes B, C. Push the adjacent nodes of A. So what are the adjacent nodes of A, B and C? So we can write B, first we can push the B and then C, or we can push C and B. So if you push C and B, the output will be different. So both are same. So here both are the adjacent nodes, we can visit any node. Right. So next step we have to pop the, so already C is visited, so we have to pop the C and push the adjacent nodes of C onto the stack. So step 3, B, A and C. Now what are the adjacents of C? F and G. So F and G. Right? B, F and G. So we can write first, we can push first F and then G, or we can push first G and then F. Anything is correct. Okay. So I am pushing the F first and G in the next. Now remove the element and push the adjacent nodes of that node. So here G is a leaf node, right? So it doesn't have any adjacent nodes. So just pop that node and place in the DFS. So step 4, A, C, G. So B and F are there. A, C, G. Okay. Then step 5. Same. So here G is not having any adjacent nodes. Leave it. Now F. Remove the F and push all the adjacent nodes of F. So already the DFS expression is having A, C, G, and now we are placing F here. So F is also having no adjacent nodes. Leave it. Now B. Step 6. Stack is empty. A, C, G, F and B. So just pop the element and push the adjacent nodes of that element. So what are the adjacent nodes of B? That are D and E. So first I will push E and then D. So anything we can do. First D and then E, or first E and D, because both are the adjacent nodes. Right. So after that, step 6. Now step 7. What we have to do? Again, pop the element and push the adjacent nodes into the stack. So here D is having no adjacent nodes. Just pop the element. So step 7, E, and in the DFS, A, C, G, F, B, and D. Right? Now, only one element in the stack. The same thing. Apply the same thing. Pop the element from the stack and place the adjacent nodes of that node into the stack. Here E is also having no adjacent nodes. So just after step 8, the stack is empty, and the DFS traversal is B, D, and E. right? So stack is empty. Stack is empty, right? So don't get confused. Just I have written empty. Okay, okay. This is empty stack. Empty. Right? So if you observe this one, we got the same thing. A, C, G, F, B, D, E. So by using the stack, we can implement this DFS approach. Right? So this is one way we can implement this one. So one more thing I just want to say here, both are the adjacent nodes. Need not worry to push the order of pushing the order of nodes into the stack. So we can follow any order. So you can push B first and then C next. We can push first C and then B, so that we'll get a multiple number of outputs. So if you push first to C, so here we have applied, push operation first on B, then C. So we got this one. If you apply first to C, then B, we'll get the next one, another one, another output. So don't get confused, right? So hope you understood this session. A simple DFS approach, depth first search. For implementing this depth first search, we'll go with the stack. So which is called a BFS. So in order to implement this BFS, we'll use the queue data structure, which is a first in, first out queue. So let us take the same example, and then the same procedure is followed. So here also we have to visit all the nodes only once. So we can assume the start from any node, and then we have to start traveling, and we have to visit all the nodes only once. The same thing, we'll take that A, B. So the same example I am taking, D, E, F, G. Right. So first travel from A. So mark it as 1. So then visit the adjacent nodes, all the adjacent nodes. So first 1, and there is one more adjacent node. 1. Right. Then coming to the next level, visit the adjacent node of B, and then visit the adjacent node of E. Backtrack. Right, because there are no adjacent nodes here. So backtrack to A, again backtrack, come to C, so visit F and backtrack to C, visit G, backtrack to C, backtrack to A. So that all the adjacent nodes have been visited. So here we have to visit the nodes in level wise. So first complete the level, top level, level 0, and then level 1, level 2, level 3. So top level we have to complete all the visiting all the nodes, then go with the second level, go with the third level. Now we'll go with the implementation. So here after visiting all these things, we'll get the same order A, B, C. So A, level 0, level 1, level 2. So level 0 visit the node, level 1 visit all the nodes, B, C, level 2 visit all the nodes, D, E, F and G. So we have to visit all the nodes level by level. So that's why we call it as a breadth first search. Okay, so in the previous session we have seen depth first search, we have to go in a depth. Right. Now we'll see how we will get this one with the implementation of queue. So step 1. So this is a queue, and this is a BFS. Queue and BFS. So first, so let us assume this one is a start node. Okay, the same thing. Start node is A. So A, right? Insert A into the queue. So this is a queue. Okay. Step 2. Remove the element from the queue and place in DFS. BFS. So as it is a queue where we have to remove the element, so both the insertion and deletion will be applied on same end. Okay. So sorry. So deletion will be from front end, insertion will be from back end, rear end. Okay. So A is removed and placed in BFS. Now insert all the adjacent nodes of A in queue. What are the adjacent nodes in A? B, C. B and C. So this is a BFS, and this is a queue. So in the step 3, and remove the element from the queue. So here we have to remove the element from the front end. We have to insert the element at the rear end. Okay. So we have to remove the element. So the C will be in the top and place here A, B. Now what we have to do? We have to insert all the adjacent nodes of B into the queue. What are the adjacent nodes of B? D and E. So D, E. So the insertion will take place at the rear end. So this is a front. At the rear I have inserted D, and next at the rear I have inserted the E. So at the rear end I am inserting the nodes, adjacent nodes of B, because we are removing B here. Next, in the step 4, remove the element from the queue. Remove the element from the queue. So C is removed because the element is deleted from the front end. So D, E, A, B, C. Now what is the element we have removed? C. Now place the adjacent nodes of C into the queue. Place or insert the adjacent nodes of C into the queue, because we are removing C from the queue. So what are the adjacent nodes of C? F and G. So insert them into the queue, F and G. So apply the same procedure. Step 5. right? So already A, B, C are there. Now remove the element. So deletion will be done from the front end. So D is deleted and placed here. Now there are only 3 elements, E, F and G, and we have removed D. So we have to add the adjacent nodes of D into the queue. So here D is a leaf node. So here D doesn't have any adjacent nodes. So just ignore. Next, follow the same procedure. Step 6. So A, B, C, D, and remove the element. So element is removed from the front end. So E will be removed, and we have to insert all the adjacent nodes of E into the queue. So what are the adjacent nodes of E? There are no adjacent nodes. Ignore. So there are only 2 elements in the queue. Step 7. Remove the element from the queue and place it in the BFS. So what is the element? F is removed here and placed in BFS. And we have to insert all the adjacent nodes of F into the queue. So there are no adjacent nodes for F. So remove, just remove. Next, step 8. Step 8. So A, B, C, D, E, F. So G is removed. So G is placed here, and we have to insert all the adjacent nodes of G into the queue. So there are no adjacent nodes for G. So here queue is empty. So this is the queue, and this is the BFS. So the same thing we got here: A, B, C, D, E, F, G. A, B, C, D, E, F, G. So this is how we can implement the BFS, breadth first search, using queue. So hope you understood. So here we are visiting all the nodes level by level. So we have to visit all the nodes in level 0. Then only we have to go with the level 1. Then only we have to go to the level 2. Right? So here A is in level 0. So we have visited A in level 0. In the level 2, level 1, there are 2 nodes which are adjacent to A. So A, B, C. So we have visited B and C. And then we'll go with the level 2 because only 2 nodes are there in level 1. In the level 2 there are 4 nodes, and we have to visit all these 4 nodes before entering into the next level. So visit all these nodes because all these nodes are adjacent to B and C, all the nodes of level 1. So D, E, F, G. So we are visiting D, E, F, G, and go with the next level. So there are no other levels, right? Because level 2 is the last level. So this will be the answer. And this will be implemented by using the queue. Just insert the node into the queue, and then first insert the node into the queue if the queue is empty. If not, remove the element or remove the node from the queue and enter into the BFS. Place it in the BFS and insert all the adjacent nodes of that particular node into the queue and follow the same procedure. So first we have inserted A, and we have removed the A and placed it in the BFS, and we have to insert the elements of adjacent nodes of A into the queue. There are 2 adjacent nodes, B and C. So B and C. Right? In the next step, we have to remove the element from the queue. So where we have to remove the first element from the front end. So from the front end, we will remove the node from the queue, and we will insert all the adjacent nodes of that particular node into at the rear end. Right? Because here we are using the queue, all the insertions will be done on front end, all the deletions will be done from the rear end. Right? So we have to delete the element and we have to place it in the BFS. So this is a very simple traversal technique, BFS, breadth first search.
So this is also one problem solving technique which is used to solve the problems based upon the brute force approach. So it's a problem solving technique. Which follows the brute force approach. So what is meant by this brute force approach? So brute force approach means checking all the possibilities to get the solution. So brute force, checking all possibilities. Checking all possibilities. For example, so imagine you are having one lock and you are having some 5 keys. So you don't know the exact key which opens the lock. So what we'll do usually, so we'll try with each and every key. So at some point of time, so the lock will be opened with only 1 key among those 5 keys. That approach, that means without having any knowledge, just applying all possibilities is called the brute force. And here the backtracking will work with the help of a brute force, with some sort of additional technology will be used for this brute force to calculate, to solve the problem using the backtracking. So here the name itself indicates the backtracking means if the current position is not, if the current solution is not viable or is not proper, then immediately we can undo. That means we can backtrack to the previous point and we can go with the alternate path. Okay, so if the current solution, that means whatever the solution we have solved, right? If the solution is not suitable, then backtrack and choose alternate path. Okay, you can choose an alternate path. So mainly this algorithm is suitable whenever there is no time limit to find the solution for a problem. So this works well when there is no time limit. there is no time limit to find solution to a problem. Right? There is no time limit. Then only this particular backtracking will be possible. And here we'll be getting all feasible solutions. Here we'll find all feasible solutions. Feasible solutions. So we have studied about these feasible solutions, right? So one problem can have a lot of solutions, but based upon the constraints, we are supposed to select the optimal solution. So all possible solutions, we call them as feasible solutions. So here we are supposed to find these feasible solutions. And the solution for a problem will be obtained step by step and incrementally using recursive calls. This is also most important. So here the solutions will be obtained by using recursive calls. So step by step solution will be taken as well as in the incremental fashion, so using the recursive calls, right? So the three possible categories where we are going to use this backtracking, right? So three categories where we use backtracking. So the first one, decision problems, and these are the problems so which will be worked with the help of a decisions, right? So all feasible solutions, a feasible solution can be considered as a decision problem. Okay, so this is a feasible solution. And the second one, optimization problems. Optimization problem. So we have studied about these optimization problems. That means we can have a lot of feasible solutions, but based upon the constraints given, we have to select the optimal, that means a best solution. So that is an optimization problem. So best or better solution. So the first one is a feasible solution, and that may not be an optimal. And coming to the second one, it is a best or a better solution, optimal solution. And the third one is enumeration problems. This is nothing but all feasible solutions, all possible solutions. So if you want to find all possible solutions for a particular problem, then also we are going to use this enumeration problems. That's such type of problems, we call it as enumeration problems. And if you want to solve a problem and get the optimal solution, that is called as an optimization problems. And if you want to solve a problem to get a normal solution that may be optimal or not be optimal, that is called as a decision problems. So this backtracking problem solving technique will be used to solve these kind of problems: decision problems, optimization problems, and enumeration problems. And in order to find this feasibility, feasible solutions, here we are going to find out the state space tree. This is most important. So what is a state space tree? So this is a tree with all possibilities. So we need to construct the tree. Tree means nothing but a path. Okay, a path with all possibilities. Either it may be a solution or a non-solution, right? So path with all possibilities. A solution which gives a solution or non-solution. So everything will be constructed in this state space tree. So with the help of this one, we are going to find out the solutions. So initially the backtracking will start with an empty set. Okay, initially the backtracking will start with an empty set. And after finding one solution, that solution will be added here. So this is nothing but the solution plus solution 1. So if it is feasible, then it will be inserted into this set. So it will be getting it as a S1. And afterwards, again the second solution. So if second solution is added here, so if it is feasible, second solution is feasible, then S2 will be added into this particular set. Otherwise, it will be just discarded, right? So these are nothing but possibilities, possible solutions: S1, S2, S3, and so on, Sn. Let it be. All are different solutions for a single problem. So initial set is empty set. So if S1 is a feasible solution, so based upon our constraints, right, S1 will be inserted into a set. And if coming to the second solution, if it is not feasible, it doesn't meet our constraints, then S2 can't be inserted here, so we can simply avoid this S2. Then S3, the next solution. If this solution is feasible, which obeys all the constraints given by the user, then S3 will also be added to the initial set, that means this set, right? So in such a way, only the feasible solutions will be added into this initial set, and the solutions which are not viable or not suitable, they will be discarded. Okay, now let us see the algorithm, a simple algorithm, how the backtracking will be applied. Okay, simple algorithm. So step 1, only the 3 steps will be there. Step 1, if the current position is the desired output, if it is a desired output, then success. Okay. Step 2, and if it fails, so else, and again if current position is not further explored or generated, then it is failed. That means if the path is not extended, okay, if the path is stopped, that means a dead end, then obviously we can say it as a failed. And step 3, else, that means this condition is also failed. If the current position is not dead end, then backtrack with alternate path, explore and repeat steps 1, 2, 3. So again we have to repeat the same process. So one is if the current path or current position is the solution, that means the desired output, then we can stop, it is success. And if the current position is not further explored, right? So we are talking about the state space tree, right? So initial state, for example, it is A, B, C. Okay. Now, if it is a dead end, so we can say it is failed. If it is not dead end and it is again C, it is further explored, then we can backtrack and we can choose another path. Okay. So this is a way, and we can backtrack and we can go with the other path. And if it is here, then it is a dead end. It is not been explored further, right? But here there is an alternate way. If not C, we can move with the E. So that in such cases we need to backtrack and explore with another alternate path. So this is a simple algorithm. So that means if we reach to the dead end, okay, and if there is no further exploration, automatically we can stop. If there is an exploration, we can just backtrack and move with the alternate path. Now, what are the applications of this backtracking? So we'll see the applications. What are the different applications? Applications of backtracking. So by using this backtracking, we can solve the n-queens problem. So in our further sessions, we are supposed to solve this one, right? So sum of subsets problem. Hamiltonian cycles or Hamiltonian paths. Finding Hamiltonian paths in a graph coloring problem. So etc. All these are the different applications where we are going to use this backtracking. Okay, so hope you understood the general method of this backtracking introduction. So what is exactly the backtracking? So it is similar to our dynamic programming, right? It is similar to our dynamic programming. In the dynamic programming also we are supposed to find the optimization problems, right? Solve the optimization problems. And here also we are trying to find the optimization problems. But if our current path is not suitable, then again we can backtrack and we can choose the alternate path. So that is only one thing which is different from this backtracking and the dynamic programming. N-queens problem. So first let us discuss about what is the problem exactly, and then we can see how to solve it by using the backtracking methodology. So in our previous session we have discussed about the introduction to backtracking, so how we can proceed for the backtracking. So that means getting all possible solutions by using the brute force approach, and if one solution is not viable or not suitable, then automatically we'll backtrack and we'll choose the alternate path. And by means of a state space tree, we are going to solve the problems by using the backtracking. So state space tree is a tree which gives all the possible paths, including the solutions and non-soluted paths. So now let us see what is meant by this n-queens problem. So arranging the queens in a checkboard or chessboard, right? So we know that in chess game we'll be having a queen. So usually we call it as a mantri. So we know the steps that can be done by the queen. So the queen can move towards a row, a number of steps, towards a column, number of steps, and towards a diagonal way, number of steps, right? So here the problem is how we can arrange the number of queens in one chessboard so that there will be no attacking mode. That means no two queens should be in a same row, no two queens should be in the same column, and no two queens should be in the same diagonal path. So there should be no attacking mode, right? So n queens means arranging queens on a chessboard or a checkerboard, right? Chessboard without attacking mode. So that means without attacking mode means no two queens should be in single row or same row. Similarly, no two queens should be in a single column, and no two queens should be in diagonal path. Diagonal path. So if we arrange the queens, number of queens, let it be 4, 6 or 8, whatever it may be. So we have to arrange the queens on a board so that no two queens should be in a single row, no two queens should be in a single column, and no two queens should be in a diagonal path. So for this we have to consider the n by n boxes, a table with n by n columns or cells, we can say, right? For example, if you consider 4 queens, so we need to consider 4 rows and 4 columns, right? See, so we need to arrange the 4 queens in this board so that no two queens should be in the same row. For example, 4 queens are Q1, Q2, Q3, Q4. For example, if I arrange a Q1 here, I can't arrange Q2 here or here or here, because the steps that can follow the queen is towards the rows, towards the columns, towards the diagonal. So number of steps, n number of steps, this queen can move this side or this side or this side. So where we can keep the queen 2, so you can arrange a queen 2 here. Okay. So here also this queen can move this side, this way, and this way. Right? So in such a way, we have to arrange all the queens so that no two queens should be in a single row or column or diagonal path. For example, if queen 1 is here and if queen 2 is here, so that will be a diagonal path. So this is an attacking mode. Okay. So if Q2 is placed here, that is also attacking mode. And if Q2 is placed here, this will also be attacking mode, right? So we have to avoid all these things and we need to solve the problem. That means we have to arrange the queens, the number of queens on the board. For example, here we have considered 4, so we need to arrange the queens in 4 by 4 checkerboard. And if we consider 8 queens, so that should be arranged in 8 by 8 checkerboard or a chessboard. Similarly, if you consider 16 queens, so that should be arranged in 16 by 16 table. So without the attacking mode. So in general, we are saying that it has a n queens problem, right? So now we'll see the 4 by 4, right? In order to easy understanding and in order to solve the problem very easily. So let us consider 4, and by following the same procedure, you can practice with 8 by 8 so that you will be getting it. Okay, now, so for solving this one, we are going to use the methodology called a backtracking. So here we can have a multiple solutions. So here now I'm not talking about the optimal solution. So solution, it's a feasible solution. That means whatever it may be, the source will be, the element will be reaching to the destination. Okay, so it is not an optimal. I'm not talking about the optimal solution, best solution, right? So all the feasible solutions are the answers for this n queens by using the backtracking. So there will be a number of possibilities. So in order to, while solving that one, if it may not lead to the solution, it will backtrack and go with the another procedure, another path. So like that, we have to solve the n queens problem, and so I'll show you what 4 queens problem. Right. So let us take the 4 queens problem and let us solve it. So I'll draw here. So I'm taking 4 by 4 table. Okay, just now we have seen that we have to consider n by n table. So I'm taking a 4 by 4 table. So 1, 2, 3, 4. Similarly 1, 2, 3, and 4. So these are the rows and these are the columns. And 4 queens, Q1, Q2, Q3, Q4. Right? And now the problem becomes not n queens, it is 4 queens problem. Okay, now consider, so starting with the root, let us consider it as a root. So from root, we can travel first. Here I will go with the, so there are 4 columns, let it be 4 columns. If Q1 falls at first, okay, so that means place here Q1. Then where the Q2 should be placed, should be placed. So then let it be, if Q2 placed in 2, okay, because Q2 can't be placed in the first column. Okay, so just here you can see no 2 queens in row, column, diagonal. Right? Now, if you place a Q2, now we have placed a Q1 at the first position, right? So starting with the first column. Next, where we have to insert the Q2. So if Q2 is placed here, okay, what is the problem here? You can see both the queens will be in the same column, while this one, right? So we should not place here. And if you place here, so here, and then also the Q1 and Q2, for example, I write here, okay? Now see, Q1 and Q2 both placed in the same row, so we should not place here. Q1, we should not place here. Q1. What happens here? Here also we can't place because diagonal. What about here? Yes, there is no problem. So here you can see both Q1 and Q2 are not in the same row, not in the same column, and not in the diagonal position. Yes. So here we are placing Q2. So Q1, Q2. Q1 in the first column, Q2 in the second column. Okay. Next. What about the Q3? Q3. So what about here? Q3. If you place Q3 here, what happens? Q2 and Q3 are diagonal, so we should not place here. What about the Q3 here? Again, it's a diagonal, so we should not place here. What about the Q3 here? Yes. So we can't place Q3 here also because both in the same column, right? So this is a safe. So sorry, here also we can't place here, right? Q3 cannot also be placed here because Q1 and Q2 both equal, right? So see, there is no option for Q3 to place Q3. Hope you understood. So if you place Q3, it violates the same column. So if you place Q3 here, what happens? Diagonal. If you place Q3, again both are in the same column. And if you place Q3, diagonal. So there is no position to place Q3. So this path doesn't suit or doesn't give the proper solution. So backtrack. So here we can't place the Q3. Now go back. Go back. This is a backtracking. Go back and change the position of Q2. Change the position of Q2 because so if you place Q2 here, we can't place Q3 in the next one, right? Next step. So we need to backtrack and we need to change the Q2. So I'll change the Q2 here. So if I place Q2 here, diagonal, this is not possible. And if you place Q2, this is also not possible. So if I place Q2 here, yes, there will be no problem. Now the second path. Q2 in fourth position. So Q1 in first column, Q2 in fourth column. Yes. Now, so this is a backtrack. Okay, this is a backtrack. And now, what's the next step? Q3. Where we have to place the Q3? So I'll write the boxes. Right? If you place Q3, again, both fall in the same column, so we should not place here. And if you place Q3, is there any problem here? No problem. So Q1, Q3 both are in a different rows and columns, and Q2, Q3 both are in different columns. There is no diagonal path, there is no column, there is no row. So Q3 can be placed in Q2, second one, right? So Q3 in the second one. Now, what about the Q4? Where we have to place the Q4? Again, I'll draw the same thing. So now we need to place the Q4, the last queen. Let us start with here. We can't place here, right? Because both fall in the same column. Here also both fall in the same column. There's only one position, Q4. There's only one position, that is the third position, right? So where we can place the Q4. But what happens? Again, Q3 and Q4 falls in the diagonal path. So this is also wrong place. And here we can't give the Q4 because again two queens will be in the same column. So this, if you place Q3 here, we can't place Q4 anywhere else. So it stops here. Again, backtrack. So we need to change the position of Q3. We need to change the position of Q3. So this is a backtracking, right? So it will be removed here. It should be removed here. Where we can place, there is no position here. So if you place a Q3 here, diagonal, in this position, there is no possible position to place the Q4. So this is also not cut position. And here also we can't do this. So again, go to backtrack. Right. So here we got the backtrack here. Again, there is no position. So backtrack to Q2. We have to change the position of Q2. So there is no possibility. If you place here, there is no possibility here. If you place here, already we have taken here. See, if you change the position of Q2 here, there is a diagonal. So we can't place here. If you place here, there is also violation of rule. So the only position is Q2, third position. Already we have done, but we are not getting the solution if you place Q2 in the third position. So again, backtrack. We need to change the position of Q1. So let us change the position of Q1 now. So move to the second one. Right? Then, what about the position of Q2? So here we can't place diagonal, and in this position we can't place because both falls in the same column. Here also we can't place, and here we can place it. So Q2. Q2. Then, what about a Q3? Okay, Q3. So there's only two possibilities, Q3 in this place and in this place. So Q3, Q3. What happens? See, so this is a diagonal, so we can place here. What about here? Yes, we can place a Q3 here. There is no violation of rules because no other queen is available in the same row, same column, and diagonal. So Q3 can be placed in first position. And from this, we can go with the Q4. Now Q4. So only one option. If you place Q4, is there any problem here? So there is no problem. So you can observe no two queens fall in the same row or same column, either in the diagonal. So there is no attacking mode here. So Q4 can be placed in 3 with a safe, without any attacking mode. So you got a solution here. So placing the Q1 in 2, placing the Q2 in 4, placing the Q3 in 1, and placing the Q4 in 3. So this becomes one possible solution. This becomes the one possible solution in order to place or arrange the 4 queens without any attacking mode. Right? So what happens here? So we have started from the first position We have started from the first position and we have gone through, but there is no place of Q3 without any attacking mode. So we have taken the backtracking. We have taken the backtracking and we have changed the position of Q2. Sorry. So here we have backtracked this one. Okay, we have changed the backtrack here, right? So the backtrack will be this one, right? Backtrack. And similarly, we change the Q2 position from third column to fourth column. And again, we have started the procedure, but here we got a problem for Q4, arranging of Q4. So we have backtracked to Q3, and even we can change the position. We didn't get the location where we have to place the Q4. So again, backtracked, and again we have changed the position of Q1. So what happens for finding the solution? If we are not getting the perfect solution, just we are backtracking and we are keep moving on to the next alternate path, alternate solution. Okay, so this is how we can solve the n queens problem. Okay, the same thing you can apply by using the state space tree. So this is not only the solution, there might be multiple solutions. Okay, there might be multiple solutions. For example, if you draw the state space tree for this one, see, what is the root? From this root, there are four possibilities. Q1, the first level is a Q1, placing of Q1. Okay, so if the Q1 is placed in a first column, second column, third column, and fourth column, four possibilities. Okay, after that, from Q1 we can get three more paths, Q2, and from here also we can get three more paths, Q2. From here also we can get three more paths, Q2, and from here also we can get four more paths, three paths. That means, see, possibility. So if Q1 is at position 1, in the second column, if you place Q2, third column, fourth column, second, here the first column, second, third column, and fourth column. Here first column, second column, fourth column. First column, second column, third column. So all the possibilities. So 1 in Q1, 2 in Q2, 1 in Q1, 3 in Q2. So like that. And similarly, from here again, we can have a Q3, and here also two possible things, Q3. See, this is a state space tree for a 4 page. That means these are the lot of, all the possible paths. So some may have the possibility solutions, feasible solutions, and some may not have the feasible solutions, right? So previously we have gone through the directly backtracking method, and we found one solution, that is placing of Q1 in second column and placing of Q2 in fourth column, placing of Q3 in first column, and placing of Q4 in third column will give the arrangement of queens without the attacking mode. But here you can see all the possible paths. So 1 in Q1, 2 in Q2, and 3 in Q3 and 4 in Q4. So we can check all the possibilities here, right? So let us take these possibilities. For example, consider this one by using the state space tree. How we can find out? See, first possible paths 1, 2, 3, 4. So placing Q1 at 1, placing 2 in a Q2, Q3, Q4. So this completely violates the rule because we have said that no two queens should be in the same row. But here all the 4 queens will be in the same row. But that is one possible path. So this is not valid, right? So this path is not a valid path. So we may not consider this one. Right? Now, second possibility. What is the second possibility? So let us check the second possibility here also. So place the Q1 and 3 in Q2. See, 2 in Q2. Sorry, Q3. Okay, and 4 in Q4. So again, it violates the rule, right? Diagonal. So this possibility is not possible, right? So this possibility is also not. This path is also not possible, right? So like that, we can check each and every path here, and we can find out the solution. So one solution. Let us check one solution. So we found that 2. So Q1 in 2, right? So whatever the solution we found, just we will see Q1 in 2 and Q2 in 4, Q2 in 4, and then Q3 in 1. So Q3. So Q3 in 1, and similarly Q4 in 3. So this is a possible path. So we will see one more possible path. So just a reflection. 3, 1, 4, 2, right? So let us check the reflection, mirroring, right? So placing Q1 in 3, Q1, Q2 in 1, Q2, Q3 in 4, Q3 in 4, next Q4 in 2. So this is also one possible solution. So here also we didn't get any attacking mode, right? So we have placed the queens so that there is no attacking mode for all the queens, right? So like that, this is the complete, this graph is somewhat clumsy, please excuse me. So these are all the possible paths. Okay, how many ways we can arrange the 4 queens in this particular checkbox. And from this, so some may have the possible solutions, feasible solutions, and some may not lead the solutions. So like this, we can find the possible solutions in a solution set. So here we are not talking about the feasible, optimal solution. So we are talking about just the feasible solutions. What are the feasible solutions? Right? So this is a small example for solving the 4 queens problem. So just try the method for 8 queens problem to solve the 8 queens problem. So that we will see one more concept in backtracking, that is a sum of subsets problem. Sum of subset. So we know that a subset, right? So we'll take a set of elements, some x1, x2, x3, and so on, xn, and from this particular set we are supposed to find out the subsets, right? So all the combination of subsets, right? Let it be x1 comma x2 is one subset, x1 comma x3 is another subset, x1, x2, x3 are one subset, and similarly so on. There will be a lot of combinations, right? So here what we have to do is we need to consider a sum, right, which is denoted as m, and we need to form the subsets whose sum is equal to this m, right? For example, let us take 3, 4, 5, 2. So these are the elements in the set. Okay, these are the elements in the set. Now the total sum is 9. So we need to form the subsets where the sum of elements of that particular subset should be equal to 9. So here you can see 3, 4, and 2. So this is a subset of this main set whose sum is equal to 9. Similarly, 4 comma 5. 4 comes before, no? So 4 comma 5. This is another subset whose sum is equal to given 9. If m is equal to 8, m is equal to 8, we need to form the subsets where sum of all the elements of subset must be equal to 8. So it will be 3 comma 5. Any other possibilities? Any other solutions? No, there is no solution. So to find these subsets where sum is equal to given total is the problem of this sum of subset problem, and this will be implemented with the help of backtracking. So we have studied about the introduction of backtracking, and also we have seen one example of one application of backtracking, and here we are supposed to find the sum of subsets using backtracking. So in this backtracking we are supposed to use the brute force. Brute force means checking all possibilities, right? And we need to find out the state space tree. So in this state space tree we will get all the combinations. So some paths may lead to the solution, some paths may not lead to the solution. So all the possible paths which may lead to solution and not solutions will be there in this state space tree. From there we will be getting the solutions. And here we are not finding the optimal solution, but we are finding all the feasible solutions. So here we can see this is not an optimal solution, because optimal solution is only one solution, best solution. So in this backtracking we are not finding the optimal solution, but we are finding all possible solutions. So in this one we can get the 2 possible solutions, right? Now we'll see the state space tree first, and then we'll write the step by step procedure, right? So we'll take the same example, and I'll draw the state space tree so that you will be getting the solutions, right? So let us consider it as W. So by observing this, you may having an idea about the 0-1 knapsack problem. So there also we are taking weights and a profit. So we need to consider the optimal solution by considering less number of weights with a more profit, right? So the same way here we are calling them as elements, and we are simply finding the sum of subsets. So the elements are 3, 4, 5, and 2. And m means a total which must be equal to 9. Yes. Now we are supposed to find the solution. State space tree, right? For example, consider them as x1, x2. So if x is equal to 0, that implies not consider. If x equal to 0, that implies not consider. If x equal to 1, it implies consider. So we need to check each and every possibility for all the elements with inclusion and without the inclusion. That means with consideration and without consideration, we need to find out the state space tree, right? See, first let us take the sum as 0, okay, right? 0 subset, and weight is 9. Sum is 9. So this is the root. That means subset with 0 elements. Now let us consider if you add one element, the first element. For example, let us consider only first element. What's the first element here? I'll write here x1, x2, x3, x4. 4 elements are there. Consider x1. x1 is equal to 1. So if x is equal to 1, we are considering, right? So what's the first element? 3. So 3 will be added into this one, and from the weight we need to reduce the, from the sum we need to reduce the weight. What's the weight? 3. So 9 minus 3, it is 6. So we are considering 2 arguments. One is a subset, other one is a weight. Now check whether the sum of subset is equal to 9. No, right? So we can again further consider. See, x2 is equal to 1. Always this backtracking will be following the depth first search. Okay, this is most important. always we need to find in a way that depth first search. So this element we need to find out this element. Now x2 is equal to 1, that means second element should be considered. So now the subset will be having 3, 4, and 4 will be reduced from 6, so it will be 2. Consider 3 plus 4 7, which is not equal to 9, so it can be further down, right? Again depth first search. x3 is equal to 1, we can consider x3 also because the sum is less than 9, right? So x3 is 5, so here 3, 4, 5. 5 minus 2 minus 3. You can check the weight goes to the negative. So that implies the sum of subset is greater than the target value. So let it be, this is a target. Sum of subset is greater than the target. So we should not consider this one. So this is not a feasible, right? So not feasible. So what we have to do, we need to backtrack and move with the another direction. So backtrack towards this one and let us consider x3 is equal to 0. That means without considering x3. Without considering x3, so we are moving with 3, 4, 2. The same thing will be appear here. Again, depth first search. Again, you have to go with the depth first search. Now, x4 is equal to 1. Okay, x4 is 2. Consider 3, 4. Sorry, we have to consider 2 also. 2. And 2 minus 2 is 0. You can say that sum of subset 3 plus 4 plus 2 is 9. And also the target, the total value is 0. That means 9, right? So this is one solution. We got a solution, so we can stop here. And we need to find another possible solutions, right? So we need to find all the possibilities. So backtrack and consider if x4 is equal to 0, then it will be 3, 4, 2. What is the sum of subset? It is 7. So it can be further executed, right? Further evaluated, but it reaches to the last element. So not feasible. Not feasible. So what we have to do if it is not feasible? We need to backtrack. So move to the backtrack, and here again there is no position. So again backtrack, and again backtrack, and here you can consider x2 is equal to 0. So previously this path is considering x1, x2 0. Now the path, the elements are 3 and 6. From this again we need to find the depth first search. Consider x3 is equal to 1. Okay, depth first search means left side root. So x3, what is the third element? It is 5. Now 3, 5, 1. So we need to reduce the weight from the target sum. So 3 plus 5 it is 8. Again still it is less than the target. It can again furtherly divide it, right? x4 is equal to 1. So consider x4, 3, 5, x4 is 2, it is minus 1. You can check the total value becomes 10, which is greater than 9. So this is not feasible. This is not feasible. Backtrack, and possible position. x4 is equal to 0. Without considering x4, it will be 3, 5, 1. And this cannot be further divided because x4 is the last element. So this is also not feasible. Again backtrack, this was completed. Again backtrack, and here we can consider x3 is equal to 0. x3 equal to 0. x3 is equal to 0 means again we'll get 3, 6. So sum of subset 3, which is less than 9, further divided. So again x4 is equal to 1. So 3, 2. Comma 4. What happens here? Sum of subset is 5. It can't be further divided because this is the last one. So this is not feasible. Similarly backtrack. So without considering x4 is equal to 0, this becomes again 3, 6. This is also not feasible. It can't be further divided because this is the last element. Now again backtrack. Check all the possibilities. No, here also there is no possibility. Backtrack, and again it moves to backtrack, and now we are supposed to consider x1 is equal to 0. So this complete path, these are all the possibilities when we consider x1 is equal to 1, and we need to consider the second one, that is x1 is equal to 0. Right? So if x1 is equal to 0, the set will be again empty set with a 9, empty set with a 9, and we need to follow all the same things. So again consider x2 is equal to 1. What is x2? 4. 9 minus 4 is 5. Sum of subset is less than 9. So further divided. x3 is equal to 1. It will be 4, x3 is 5. Okay, and it will be 0. Right? What happens? 9. 9 becomes 9. So this is one solution. This is one solution. So I'll mark with a double circle, right? This is one more solution, and we need not move further. So backtrack for alternatives. Again, x3 is equal to 0, not considering. So it will be 4, 5. Again, further can be divided. So x4 is equal to 1, 4, 2, 3. It can't further divide it because x4 is the last element. So 4 plus 2, it says 6, not equal to 9. So this is not feasible. So backtrack and check with the alternative. X4 is equal to 0 and it will be 4 comma 5, which is also not feasible. Now again move with the towards the backward and here, and consider now x2 is equal to 0. X2 is equal to 0. Right? Now what happens? Again empty set with 9. X3 is equal to 1. X3 is 5. 4. So 5, sum of subset is 5, which is less than 9. Further it can be divided. Consider x4 is equal to 1, 2. So then it will be 5 comma 2. So which is not further divided. So it is not feasible. It's not a feasible. So move towards backtrack and consider x4 is equal to 0, and it will be again 5, 4, which is also not feasible. Right? Again backtrack, and now I'll write here. Right? So consider x3 is equal to 0. X3 is equal to 0 means again it will becomes 9. So again it can be further divided. So x4 is equal to 1. So it becomes 2 comma 7. It's not feasible. Backtrack again. X4 is equal to 0. It will be blank and 9, which is not feasible. Right? So we are having only two possible solutions. One is 3, 4, 2 and 4 comma 5. Okay, manually we have seen all these things. Right? Now the solutions will be. What are the solutions? How we can write down the solutions? So one is 3, 4, 2. 3, 4, 2, right? So this can be represented 3 comma 4 comma 2. This can be represented as 1, 1, 0, 1. 4 elements. We are considering the first element, second element, and we are not considering the third element, and again we are considering the fourth element. So 3, 4, 7 plus fourth element 2, total becomes 9. Similarly, the second one, it is a 4 comma 5. So this can be represented as 0, 1, 1, 0. So this is not a binary. Okay, don't get confused. This is not a binary representation. So this represents which element should be considered and which element is not to be considered. Right? So again, this becomes 9. So these two are the solutions of sum of subset problem for a given example. Right? So what we are doing? So first we are starting with an empty set. We are inserting or adding one element to the empty set, and we are checking whether the sum of subset is equal to the target sum. And if it is not, or if it is less than, it can be further evaluated. That means again we can add one more element and we can check the total sum with the target sum. And if it is also not equal, then we can stop and we can consider that as a solution. And if it is not equal and it goes beyond the target, then obviously we have to stop and we have to backtrack and we have to select the alternate path. So in this state space tree, you can see we have considered all the possibilities. So some paths are not feasible. So you can check this path is not feasible and this path is not feasible. This path is not feasible. So this state space tree will be having all the paths which leads to the feasible solutions and not feasible solutions. And backtracking is mainly to identify the multiple feasible solutions, not to the best or optimal solution. Right? So hope you understood this one, and practice with a more number of examples so that you can understand and you can get a complete clear-cut idea about this sum of subset problem using backtracking. And then, so today we'll see one more application in backtracking, that is finding Hamiltonian cycles in a graph. Hamiltonian cycles. So this is also one of the applications of backtracking. So backtracking main motto is to find all the feasible solutions, not the best solution, using backtracking. Okay, so we'll check all the possibilities, and if one possibility doesn't suitable, the solution doesn't suitable and it does not lead to the feasible solution, we are supposed to backtrack and we'll start with the alternate solution. Right, now coming to this particular Hamiltonian cycles, let us consider a graph. Okay, see, let us consider this graph. Let us consider this graph. So this graph means a combination of vertices and edges. Okay, so this is a graph, and this graph forms a cycle, right? So forms a cycle, and this graph will be having a lot of cycles. But here, our main problem is finding of Hamiltonian cycles. So what is meant by Hamiltonian cycle? So consider a starting vertex, visit all other vertex at least once, exactly once, and come back to the original vertex from the source vertex. So this is called as a Hamiltonian cycle. So I'll write what is a Hamiltonian cycle. Start from source vertex, visit all vertices exactly once, and come back to source vertex. This is called a Hamiltonian cycle. So we need to find out how many Hamiltonian cycles were there in this particular graph. by using backtracking. Okay, so the same thing we have learned somewhere else, right? Yes. So the same problem, that means starting from source vertex, visiting all vertices exactly once and coming back to the source vertex, is a solution of the traveling salesperson problem. But there we have to solve this with a minimum cost. That means the traveling salesperson have to start from the source vertex, visit all other vertices in the graph and come back to the source vertex with a minimum cost. So there also will be getting a lot of cycles, a lot of paths, but we are going to select only the optimal solution, right? But here we are finding all the possible paths. Okay, so this is a Hamiltonian cycles. So how we can find out these Hamiltonian cycles? See, let us start with the source. Let us consider this source. Don't change the source. So if you change the source, the cycle may be equal, right? So we should not consider that one. Fix the source vertex and find out all possible paths, feasible solutions. So let it be. So first I'll write the outgoing edges, okay, of every vertex. For example, consider A. So A is having outgoing vertices to B and C. B is having the outgoing vertices A, C, D. A, C and D. And C is having outgoing vertex A, B and E. A, B and E. So it will be very easy. Okay. So D is having the outgoing vertices B, E, F. B, E, F. And E is having the outgoing vertex C, D, F. C, D, F. And F is having the outgoing vertices D and E. So with the help of this one, so usually we call it as an adjacency matrix. Okay, adjacency matrix. So instead of writing the adjacency matrix, I have written the complete nodes, adjacency nodes, right? Now, start with the vertex, source vertex. So let it be my source vertex is A, right? A. So here we are starting from source vertex A and we have to visit all other vertices exactly once. So from A, what are the outgoing edges? B and C. Let it be. This is B and this is C. And we know that the backtracking will work on depth first search. So first we need to find out the depth. So yes, A and C. Now B, what are the outgoing edges? A, C and D. See, A, C and D. A is already visited because we are at B from A itself. So A is visited. So you need not consider A. So what are the outgoing edges? C and D. So C, D. Okay, C and D. Now we need to find out the depth. So C is A, B, E. So A, B are already visited. So if you are at C, we are from B. If you are in B, we are from A. So A, B are already visited. So only one vertex is not unvisited, that is E. So C is having E. Now check this E. E is having outgoing edges C, D, F. Among that, C is already visited. So there are only two possibilities, D and F. So D and F. Coming to D, B, E, F. So E is there, B is there. There is no F. So here we can have F. So F, D, E already visited, right? Now you can observe in this path A, B, C, E, D, F. So how many nodes are there? 1, 2, 3, 4, 5, 6 nodes are there. So you can see 1, 2, 3, 4, 5, 6. All nodes have been visited. So here the last step is F is the last node visited. So we need to check whether there is an edge between F and A. Then only it forms an Hamiltonian cycle. So start with the source vertex, visit all other nodes exactly once and come back to the source vertex. So start from the source vertex, visited all vertex exactly once, and now it have to visit back to source vertex. So F having edges D and E. So there is no direct connection from F to A. So this path is not feasible. This path is not feasible. So backtrack. So there is an alternate way. Okay, here from F there is D and E. In this path, check whether D and E have been visited or not. E is already visited, but D is not visited. So there is a path from F to D. Again check. So here you can see 1, 2, 3, 4, 5 and 6. So all nodes have been visited. And now it should go back to source vertex. So check whether D is having an edge to A. So D is having no edge to A. So this is also not feasible. So again, backtrack. So here also one possibility, backtrack. And there is another possibility. So A, B and D. So from D, check B, E, F. B is already visited. So E and F. E and F. Now E. So depth first search, right? E. C, D, F. D is visited. So C and F. So here it will be C and it will be F. Coming to C. Edges are A, B, E. Check out. A is there, B is there, E is there. So how many nodes we have visited here? 1, 2, 3, 4, 5. So this is not feasible because there is no edge from C. Okay, because C is having an edges towards A, B, E which are already visited. A, B, E in this path. So backtrack and follow this one. Okay. F. So from F there is an edge between D and E. So in this path A, B, D, E, F, check whether D and E are visited. Yes, D and E are visited. Now count the nodes. 1, 2, 3, 4, 5. So total nodes are 6. but only 5 are visited, and there is no other edge which is used to visit the unvisited node. So this is also not feasible. Backtrack, and go with the another possibility. So in order to reach F, we have to travel from A, B, D, F. So from F there is a D and E. So in this path, D is already visited. We have to visit E. So there is one path. It is E. Now from E there is a C, D, F. Check. D, F are already visited. There is no edge to C here. So the next one is C. And you can check C, A, B, E. So A, B, E. All the three have been visited in this path. Now we have to check whether the 6 nodes have been visited. So 1, 2, 3, 4, 5, 6. Yes, all the nodes have been visited. So there might be a chance of having the Hamiltonian cycle. So there should be an edge from C to A. Then only we can say that is an Hamiltonian cycle. So check out C, A, B, E. So there is an edge towards A. So this is the one possible solution. So it forms a Hamiltonian cycle. And now go with the backtrack and move with the alternative. Next alternative, C, A, C. So C is having an edges from A, B, E. A is already visited. So there will be edges from B and E. Now B, depth for search, B is having edges towards A, C, D. A, C has already visited. So D, B, E, F. B is already visited. So E and F. E, C, D, F. C, D is already visited. F. F, D, E. D is already there. Now check the total number of nodes. 1, 2, 3, 4, 5, 6. So all nodes have been visited. So there is having a chance of getting the Hamiltonian cycle. So check out the edge from F to A. If there is an edge from F to A, then we can say this is a Hamiltonian cycle. So F didn't have the edge from F to A, right? So this is not feasible. Backtrack, go with the alternate solution F. So coming to F, D and E. So D is visited in this path, but E is not visited. So you can write it here, E. Now check E with C, D, F. C is there, D is there, F is there. So all nodes have been visited. So count the nodes. A, C, B, D, F, E. Total 6 nodes were there. So that implies there is a chance of getting Hamiltonian cycle. So we can say this is a Hamiltonian cycle if there is an edge between E and A. So E doesn't have an edge towards A. So this is also not feasible. This is not feasible. Now backtrack. And here we are having an alternative. So E, A, C, E. E is having edges C, D, F. C is already visited. So we can have an edges towards D and F. Depth for search. So we need to find out the depth. D. D is having B, E, F. B, E, F. So in this path A, C, E, D, we are having only E. There is no path from B and F. So give the B here and F here. Coming to B. A, C, D. A is there, C is there, D is there. So not possible. So there is no new edge to unvisited nodes. So there is no, it's not a possible solution or a feasible solution. Move on to the backtrack towards this one and go with the alternative. F. F is having again D and E. So in this path A, C, E, D, F, we are having already D and E have been visited. See, E and D have been visited. So there is no edge towards the unvisited. So this is not a feasible solution. So backtrack and move with the alternative F. So F is having the edges D and E. So F is in this path A, C, E, F. There is no D. Okay, F is visited to D. Now you can check a D. B, E, F. In this path A, C, E, F, D. E, F are visited. D is not visited. So you can have B here. Now B. A, C, D. A is there, C is there, D is there. So all nodes visited, right? Now check the total number of nodes. 1, 2, 3, 4, 5, 6. So total nodes, all nodes have been visited exactly once. So it may lead to the Hamiltonian cycle. Now check the edge from B to A. Whether B is having an edge to A. Yes, it is having. So this forms the Hamiltonian cycle. This is one solution, right? So all the possibilities we have compared and we got 2 Hamiltonian cycles for this particular graph. I'll write here the solutions. See, solutions, Hamiltonian solutions. The first solution is, see, A to B, towards D, towards F, towards E, and C and A. So this is the one Hamiltonian cycle. So starting from the source vertex, I am considering the source vertex as A. So starting from A, visiting B, D, F, E, C. That means all the remaining vertices exactly once, and coming back to the A. So you can check here A to B. So this is one solution. A to B, B to D, D to F, F to E, E to C, C to A. So this is a solution 1. I'm just for representation, I'm representing it as 1, just for understanding, right? This is the first solution. And the second solution, let us take this one. A to C, C to E, E to F, F to D, D to B, and B to A. So this is a one more solution. That is a one more Hamiltonian cycle. So let us draw this here. A to C, A to C, C to E, E to F, F to D, D to B, and B to A. So this is a second solution. Second solution, right? So in this particular graph, we are having 2 possible solutions. That means 2 Hamiltonian cycles. So starting from source vertex, visiting all vertices exactly once, and reaching the source vertex is known as a Hamiltonian cycle, right? So here once again I'm saying in this backtracking we are not finding the optimal solution. We are finding all the feasible solutions with the help of brute force approach. That means taking all possibilities. So for that we are drawing the state space tree where we can get all the feasible and non-feasible solutions. So this is a state space tree. Okay, from here we are able to find out all the feasible solutions. So here we got the feasible solutions, 2 solutions, right? So let's stop here. Hope you understood these Hamiltonian cycles, finding the Hamiltonian cycles in a graph. And we'll solve this graph coloring problem using a backtracking methodology. So imagine if you want to represent a map with different colors, so we need to take care that no 2 adjacent regions should be colored with the same color. So if that happens, so 2 different regions will be considered as a single region. So that we have to color a graph or color a map which is having a different regions with different colors without any overlapping, right? So similarly, let us take here a graph and we need to color each and every node or vertex such that no 2 adjacent nodes or vertices should be colored with a similar color. See, let us take an example. There are 4 regions or 4 nodes. So these are the 4 nodes. And we need to color these 4 nodes with some 3 colors. So red, green, and blue. Usually we call it as a RGB, right? Let us take the 3 colors. First, if we color the region A or node A with red, the adjacent node B should not be colored with red. So you can color it with green. And coming to the C, the 3rd region, it should not be colored with green because it is adjacent. So it can be colored by using red or blue. Red or blue. And here, this should not be colored with a red because the adjacent region is filled with a red color. So it can be colored with green. Green, right? For example, let us take here, it has a red, okay? And here we can fill with the blue, right? So you can observe we have filled this one such that no adjacent nodes are colored with a similar color. See, A is colored with a red. What are the adjacents? So D and B. So both are with the different colors. And see, B is green. What are the adjacent? A and C. So A and C were not colored with the green. And C is red. What are the adjacents? D and B. Both are not colored with the red. And D, which is colored with the blue. So adjacent are A and C. A and C are not colored with the red. So this is one option. For example, if you consider here blue, if you color this region with the blue, then what happens here? D should not be colored with the blue or red because D is having adjacents A and C. A and C are colored with red and blue. So we should not color D with red and blue. It can be colored with the green. So this is another solution. So like that, we have to color all the regions with the different colors so that the adjacent, no 2 adjacent nodes should be colored with a similar color. So for this, we are supposed to use the state space tree where we are having all possibilities, and from that we are finding the feasible solutions. And if one solution or one path may not lead to the feasible solution, there we are going to backtrack and select the alternate path. So like that, we have to solve the problem and we need to find multiple paths, that means the feasible solutions, right? Yes. Let us take the same example. Let us take the same example. I'll draw the example here. A, B, C, D. So these are the 4 regions. 4 regions or 4 nodes. So let us represent it as a 1. Okay, 1. In order to avoid the confusion, because we are also representing the colors with RGB. So in order to avoid the confusion, we can name it as 1, 2, 3, 4. Okay, 1, 2, 3, 4 are 4 nodes or 4 regions, and we need to color with red, green, and blue. Red, green, and blue. So root node, state space tree, first root node. From this root node, first we have to fill the node 1. So 1, 1, 1, right? And this one we are filling with red and green and blue. So 3. So we can fill the first region with either red, green, or blue. So we need to write down all the possibilities, right? So I'll tell only this possibility, so you will be practicing with the remaining 2 possibilities, right? So first consider this one. If that, see, always the backtracking will work with a depth first search. So we need to solve it using depth first search, right? So 1, and from here there are 3 possibilities for filling the second node. See, these are the different nodes, or simply depth first search. So go with the x2 is equal to red. Okay, x2 is equal to red. If 1 is filled with red and R2, and node 2 is also filled with R, that means the 2 adjacent nodes comes with a similar color. So this is not a feasible solution. So we should not fill the second node with red. So backtrack, move with the alternatives. So there is one more alternative, that x2 can be green, red and green. Is it possible? Yes. So 2 is an adjacent of 1 and 1 is filled with R. So 2 is not filled with R, 2 is filled with green. So this is possible way. Again, what is the next possibility? x3. That means the third region. Third region is red. Third region is red. Is it possible? Yes. So third region having a 2 adjacents, 4 and 2. 4 is not filled so far, 2 is filled with green. So 3 can fill with red. This is also possible. And again, fourth, x4 is equal to R. So x4 is equal to R. That means fourth region is filled with R. So is it proper? No, because 4 is having the adjacent nodes 1 and 3, and 1 and 3 nodes are filled with R. So we should not fill the 4 with R. So this fails. This is not a feasible solution. So backtrack and move with the next alternate path. That is, if x4 is filled with green, so x4 is filled with green. Is it possible? Yes. So 4 is having the adjacent nodes 1 and 3. So fourth region having the adjacent regions 1 and 3, both are filled with R. So 4 is filled with green. Yes, it's possible. So this will be one solution. So next possibility. If x4 is filled with blue, if x4 is filled with blue, that means the fourth region filled with blue. So this is also possible because adjacent nodes 1 and 3 filled with R, so 4 can be filled with blue. Yes, so this is second solution. Backtrack, move with the alternate. So 2 is filled with red and we have proceeded. Now, sorry, 3 is filled with red. Okay, now 3 is filled with green. Let us take 3 is filled with green, the next possibility. Right? So is it feasible? No, because 3 is having the adjacent regions 4 and 2. 4 is not filled so far, and 2 is filled with green. So 3 can't be filled with green. So this is not feasible. Similarly, move on with the next possibility. The third region filled with blue. We have to check. So third region is filled with blue. Okay. So is this may lead to the feasible solution? Let us check. 3 is having the 2 adjacent regions 4 and 2, and 4 not visited. 2 if is filled with green. So obviously 3 can be filled with blue. So this may lead to the feasible solution. Yes. So further depth for search. So we need to fill the fourth region. So let it be filled with red R. So it may lead to feasible. So 4 is having adjacent regions 1 and 3. So 1 is filled with R. So 4 should not be filled with R. So this is not a feasible. Next possibility. Sorry, this is 4, right? So 4 is filled with green. Let us take 4 is filled with green and check whether it is a feasible. So 4 is having the adjacent regions 1 and 3, and 1 is filled with R, 3 is filled with blue. So obviously 4 can be filled with green. There is no overlapping. Yes, this is a third solution. And the next possibility, if the 4 is filled with blue, see, 4 is having the 2 adjacent nodes 1 and 3, 1 is filled with R, 3 is filled with blue. So 4 can't be filled with blue. So this is not possible. This is not possible, right? So again backtrack, and there is one more possibility for 1. If x2 is filled with blue, see, the second node is filled with R, no solution. Second node filled with green, we got some 2 solutions, and now we are moving with second node filled with blue. So the next alternate is second is filled with blue. Okay. So x2 is equal to blue, and here x3 is equal to R. X3 is equal to R. Is it possible? So 3 is having, third region is having 2 adjacent nodes 4 and 2. 2 is filled with blue, and 4 was not visited. So 3 can be filled with red. Yes, it is possible. Again, 4 x4 is equal to red. X4 is equal to red. So this is not possible because 4 is having adjacent nodes 3 and 1. Both are filled with red. So 4 can't be filled with red. So this is not possible. So backtrack and go with the alternate. X4 is equal to green. Now let us take green. Is it possible? See, 4 is having adjacent nodes 1 and 3. 1 and 3 both filled with R. So the fourth region can be filled with green. Yes. So this is one more solution. And what is the next alternative? If x4 is filled with blue, what happens? It may lead to feasible or not. So it is filled with blue. You can check for the adjacent nodes for 4 are 1 and 3. Both are filled with red. So 4 can be filled with blue. Yes. So this is one more solution. And we have completed all the 3 possibilities from region 3. Backtrack and move with the next possibility. If x3, that means the third region is filled with green. The third region filled with green. Is it possible? Yes, because 3 is having adjacent nodes 4 and 2. 4 is not visited. 2 is filled with blue. So 3 can be filled with green. Yes. Now, x4 is equal to red. Is it possible? No, because 4 is having adjacent node 1 which is filled with R. So it can't be possible. So it is false. Again, G, that means a green. So if it is green, this is also not possible because 3 is adjacent to 4 which is filled with green. So 4 can't be filled with green. Next, blue. If this one is filled with blue, is it possible? Yes, because 4 is having adjacent nodes 1 and 3 which are filled with red and green. So it can be filled with blue. So this is one more solution. So here we have checked all the possibilities. Coming to the second node, only 2 possibilities we have checked. So again we have to go with the next possibility. That means if x3 is blue. So if it is blue, is it possible? See, 2 is an adjacent of 3 which is filled with blue. So this can't be happened. This can't be happened, right? So here we have checked with all possibilities, right? x3 is equal to blue, which is not possible. So we have checked all the possibilities here. Okay, these all possibilities have been fixed when the first node is fixed with R. First node is filled with R. So we have to repeat the same process and find out all the solutions if the first node is filled with green. And similarly, the next possibility if the first node is filled with blue. So there are three possibilities. The first node can be filled with either red or green or blue. So all these things we have done so far is if the first node is filled with red. Right? So here the solutions 1, 2, 3, 4. So what is the first solution we got? This one. That means R, G, R, G. So R, G, R, G. This is the first solution. And the second solution, R, G, R, B. R, G, R, B. Third solution, R, G, B, G. R, G, B, G. The next solution, R, B, R, G. R, B, R, G. Next solution, R, B, R, B. R, B, R, B. The next solution, R, B, G, P. R, B, G, B. So these are all the different solutions. Okay, these are all the different solutions. You can see. So without any overlapping, that means without filling the adjacent nodes with a similar color, so we can fill all the regions by using these combinations. If the first node is fixed with R, that means if it is filled with R. Similarly, we have to find out if the first node is filled with green, what are the possible solutions? And if the first node is filled with blue, what are the possible solutions? So I'm just stopping here. You just practice with these two nodes, right? And solve this and comment all the possible solutions for this particular graph and all the possible solutions for all these possibilities. Branch and bound. So we'll see what exactly this branch and bound and which type of problems can be solved by using this branch and bound, and what are the characteristics of branch and bound, and what are the applications, that means which type of problems can be solved, right? So first let us see what is this branch and bound. Usually this can be represented as BB. It's a branch and bound, or BNB. N stands for N, branch and bound, or B and B, right? So we can represent in any one of these forms. Okay, and mainly this branch and bound is used to solve the optimization problems. So it is used to solve optimization problems. Optimization problems. So we have seen different category of problems. Among that we have seen the decision problems and the optimization problems. So decision problems are nothing but all the feasible solutions, right? The problem which gives all the feasible solutions. So backtracking is mainly used to find or solve the decision problems. So in apart from this optimal solution, backtracking will find all the feasible solution with the help of state space tree. And coming to this branch and bound, so it is mainly used to solve these optimization problems. Already we have seen what is meant by this optimization problem. That means a complex problem can be divided, complex problem can be divided into small subproblems, and each subproblem can be solved, and we are going to find out the optimal solution. So these solutions for subproblems can be solved by using a backtracking in this branch and bound. Okay, this can be done by using a backtracking. So we know that backtracking, what is meant by backtracking? So backtracking means checking all the possibilities by using the state space tree. So this depends on state space tree. So what is meant by state space tree? So state space tree is a tree structure which gives all possible paths. So those paths may have a feasible solution, or those possible may not have the feasible solution. Right? So that is the state space tree. So this branch and bound will use all these things, but there is only one difference. Among these subproblems, the solutions for these subproblems, based upon the boundary levels, that means lower boundary and the upper boundary, we are supposed to eliminate or ignore the subproblem. And we have to find only the optimal solution. That means, so we need to find optimal solution. So use it to find optimal solution. That means the best solution. So one problem can have multiple solutions. Among that, we are supposed to select the optimal solution, which is the best solution. In order to find out that optimal solution, we are going to draw the state space tree where we are having all possibility paths, right? And we are also using the backtracking. So we are just expanding the nodes in the tree, and if it doesn't lead to the feasible solution, backtrack and go with the alternate path. So that is called the backtracking. So in this branch and bound, we are going to use all these things. So you can see branch and bound. That means we are just drawing the state space tree. That means a branching levels in terms of levels, and then we are applying the bound. That means a boundary levels. Excuse me, boundary levels, lower boundary and upper boundary. So based upon the lower and upper boundaries, we are going to ignore some sort of solutions which are not being executed or which are not useful to get the optimal solutions. Right? So we are going to apply all these things. So now, what are the characteristics? What are the characteristics of branch and bound? The first one just now we have seen there is a backtracking. So we are starting with one node, just we are expanding that node, okay, and while expanding, if it doesn't lead to the feasible solution, we are just backtracking to the previous node and we are going with the alternate path. So this is one characteristics of branch and bound. So we are going to use this backtracking process. And the next one, pruning. Pruning is nothing but ignoring, right? So just now we have said, so while creating the path, so if there are any not feasible solutions, we are going to ignore. Pruning means ignoring. And the next one, lower bound and upper bound. So we'll use some boundaries, lower bound values and upper bound values, in order to select or in order to get the optimal solution. So if by applying this lower boundary and upper boundary, if the solution, the current solution or current path is not viable to the feasible solution, so obviously we'll prune it and we'll backtrack. And the last one is optimal solution. So finally, the result should be optimal solution. So finding the optimal solution. So finding the optimal solution with the help of lower boundary and upper boundary, which are not feasible, then just ignore it and backtrack with the alternate. So these are the characteristics of branch and bound. Now we'll see the application. That means which kind of problems, what are the problems we are supposed to solve by using the branch and bound. So applications. So the first one is a knapsack problem. So already we have solved it, and the same kind of problem we can solve using the branch and bound in order to get an efficient, that means optimal solution. And the next one, a traveling salesperson problem. So the same thing we have already solved this one, but the same problem can also be solved by using this branch and bound to get the optimal solution. Similarly, there are a few more like game playing. Game playing is one more problem. Okay, next uncleans problem. So whatever the applications we have done in this backtracking, everything can be solved by using this branch and bound. Then what are the advantages? What are the advantages of using this branch and bound? First one is performance, because it leads to the optimal solution. The next one, reducing search tree, that means a state space tree. So it is not required to create the complete state space tree. Okay, and the disadvantage, only one disadvantage, the complexity is an exponential complexity. So this branch and bound gives the exponential complexity, the time complexity. So this is a one drawback of using this branch and bound. And one more thing, this backtracking will be using, or the backtracking methodology uses the depth first search. So in all our previous applications we have seen, while solving the problem, we are just going with the depth first search. Okay, depth first search. But here in this branch and bound, these problems can be solved with the help of breadth first search, not the depth first search. So completion of one level, then only it will move with the next level. Right? So this is all about our branch and bound methodology. So this is one more important problem solving methodology you have to learn in algorithms concept. So in our further sessions, we'll see the knapsack problem and the traveling salesperson problem, how we can solve by using this branch and bound methodology. Channel. So today we'll see one of the application of branch and bound, that is traveling salesperson problem using least cost branch and bound. So traveling salesperson problem. So already in our previous sessions we have seen this traveling salesperson problem, which has been solved in different methodology. In this session we'll see how can we solve this traveling salesperson problem by using branch and bound. So once again recalling the problem, so traveling salesperson means starting from one vertex or one city, so traveling or visiting all other cities or nodes exactly once and coming back to the origin. That means wherever the person starts, so the final destination will be the source. So that means, for example, A, B, C and D. So traveling salesperson is starting from the source. Let us take A as a source, visiting all other vertices exactly once. So A, then B, then C, then D, and finally come to the source. So from D to A. So this is one possible path. Okay. Similarly, A, D, C, B, A. This is one more path, another path, right? But here the optimal solution means with a least cost, minimum distance, or we can say minimum distance. Right? So the traveling salesperson have to visit all the cities and come back to the source with shortest distance. So that we call it as a traveling salesperson. And now we are going to solve this problem using branch and bound. So in this branch and bound, we are supposed to go with a state space tree, but we need not construct the complete state space tree. So we are supposed to expand the nodes which are having the least cost. So that's why we are calling this as a least cost branch and bound. So let us move on to the problem. So I have taken the cost adjacency matrix, this one. So I have taken the cost or the distance from one node to another node, right? So I have represented an infinity where the node doesn't exist. So here vertex A to A, there will be no edge. Okay, so this we call it as a infinity. Similarly, there will be no edge between B and B, so this will be represented as infinity. C and C, this will be represented as infinity, and D, it is infinity. There might be have a chance of getting the distance from other nodes, A to B, A to C, A to D, similarly B to A, B to B, B to C, etc., etc. Now we'll see how we can find the optimal solution. So for this, we have to construct the state space tree. State space tree in a breadth first search approach. Okay, usually in our previous sessions we have seen the state space tree expanding along with the depth first search, but here we are going to use breadth first search. And first one, we have to find the reduction cost. Okay, reduction matrix. So we will call it as a reduction matrix. What is this reduction matrix? So here two things should be identified. So one is every row should have 0. Every column should have 0. Right? If not, what we have to do? Find the minimum in row and subtract with every element. Similarly, find the minimum in each column and subtract with every element in the particular column, right? So after applying this, we will be getting the reduction matrix, and from this reduction matrix we are supposed to calculate the reduction cost. So this is the first one, and the second one, calculate reduction cost. That means how much value we have subtracted from the rows and from the columns. We have to add both the things so that we'll get the reduction cost, and this will be the initial reduction cost for source vertex, and from that vertex we are supposed to expand the nodes based upon breadth first search. So first we have to do this one. So let it be, this is the adjacency matrix. Okay, so every row should have 0. Observe, this doesn't have 0, this doesn't have 0, this doesn't have 0, this doesn't have 0. What we have to do? We have to find the minimum in row and subtract with each element. So what we have to do? So what is the minimum element? 10. In this row 5, in this row 6, in this row 8. So what we have to do? We have to subtract with every element in that particular row. So we have to subtract 10 from infinity, 10 from 10, 10 from 15, 10 from 20. Similarly, second row, third row, and fourth row. After that, again we have to check every column should have a 0, whether every column is having a 0. If not, again find the minimum in the column and subtract with every element in that particular column, so that finally we'll get the adjacency matrix. Now, I'm erasing this one. Let us move on to the problem. See. Yes. So first we have to eliminate the rows. So 10, 5, 6, 8. I'll write here. So infinity minus 10, obviously it will be infinity. 10 minus 10 is 0. 15 minus 10 is 5. 20 minus 10 is 10. Similarly, 5 minus 5 is 0. Infinity minus 5, infinity. 9 minus 5, 4. 10 minus 5 is 5. 6 minus 6 is 0. 13 minus 6 is 7. Infinity minus 6, infinity. 9 minus 6 is 3. And 8 minus 8, 0. 8 minus 8 again 0. 12 minus 8 is 4. And again infinity. So this is the matrix we got with the row reduction. Okay, we have to do the column reduction and row reduction. So this we got after a row reduction. Now from this we have to calculate the column reduction. Okay, so from this we are calculating the column reduction. So this is a row reduction. Right? So let us check whether every row is having a 0 or not. Every row is having a 0 or not. So sorry, every column reduction. So this one, yes, 0. This one, yes, 0. This one, there is no 0. So find out the minimum value. What's the minimum value? 4. And here, no, the minimum value is 3. Now we have to subtract the value from each and every element of the column. So write down the column wise. So first column, infinity, 0, 0, 0. And next second column, 0, infinity, 7 and 0. Third one, 4 is the minimum. 5 minus 4 is 1, 0, infinity and 0. 3 is the minimum. So 7, 2, 0 and infinity. So this one is a matrix we got after row reduction and a column reduction. So this is called as a reduction matrix. Reduction matrix. So first step, we have to find out this reduction matrix after performing row reduction and column reduction. Right, hope you understood. Now, what is the cost reduction? Cost reduction is equal to whatever the values we have subtracted from each row. So that is 10 plus 5 plus 6 plus 8 plus from row or columns 4 plus 3. So you can calculate 15, 21, 29. Yes, yes. 14, 19, 29. So this is a 29 plus 7. So total 29 plus 7 is a 36. So the cost reduction initially was 36. The cost reduction initially was 36, right? Now start expanding. Let it be, start with A, which is a source. The cost is 36. So here we are having only one source, so we need not go with the alternate. So that node will be expanded. So the next node or the next city to be visited is either B or C or D, right? So the traveling salesperson can visit from A to B or C or D. So we need to cost of B, C, D. So cost of AB, cost of AC, cost of AD, right? So let us take this value. Okay, I'll once again write here. So alpha infinity 0, 1 and 7, 0, infinity 0, 2, 0, 7, infinity 0, 0, 0, 0, infinity. So this is the matrix. Okay, from this we have to find out the cost between A and B. So we need to find the cost. So cost of A to B. What we have to do is we have to find out again the reduction matrix, and instead of taking the reduction matrix, first we have to consider this is a row and this is a column. So fill all the row values and the column values with infinity. So A row A means the first one, right? So fill all the things with infinity, right? And column B column is second one, fill with infinity. So the person can't travel from B to A, so this will also be infinity, B comma A. Okay, now fill the remaining values from this particular matrix. So here we'll get 0, 0, and here we'll get 0, infinity, 0, and here we'll get 2, 0, infinity. Now consider the cost reduction, row reduction and column reduction. So this is completely infinity, no problem. And here we are having a 0, and here we are having a 0, and here also we are having 0. From the column, this is 0, so this is completely infinity, okay? So here we are having 0, and here also we are having 0. So that means already cost, this is a reduction matrix. Now the cost of AB, the cost of A comma B will be the cost of parent plus edge, or the cost between A comma B plus cost reduction. So how we are getting the cost reduction? Previously we have seen adding all these minimum values and these minimum values. That means whatever the minimum values we are getting in the row reduction and the column reduction should be added, and that is the cost reduction. In this case the cost reduction is 0 because there is no minimum value, all the minimum values are 0, 6. Right, now what is the value of cost of AB? Cost of parent is nothing but 36. Cost of A comma B, so we should not consider this one, right? This is a cost reduction matrix. So we need to find out this cost of AB from A. So cost of AB, which is 0, plus cost reduction here, adding all the minimum values, which is again 0, that will be 36. So cost of AB is 36. So cost of AB will be 36. The same thing should be applied for C and D also. C and D. Okay, now I will write the cost of A comma C. So we need to find the cost of A comma C. So for this we have to first write down the matrix. Complete row A should be filled with infinity, and C, column C means the third one, should be filled with infinity, and the traveling salesperson can't go back, right, to the same node. So it will be visited twice. So C to A should also be infinity. Fill all the values from this one, right? 0, 0, infinity, 7 and 0, and 2, 0 and infinity. Now find out the cost reduction. So here, yes, infinity, and here it is 0, here it is 0, here it is 0, and here also it is 0, 0, infinity, okay, so it's 0. So here also the cost reduction is 0. Because already every row is having some 0 value and every column is having some 0 value. So the cost reduction will be 0 here also. Now the cost of A comma C will be cost of parent 36. Cost of A comma C from this one. A comma C cost is 1 plus cost reduction which is 0. So which is equal to 37. So the now cost of AC is 37. Okay, now find out the cost of A to D. So I'll write here. Okay, cost of A to D. Again, write down the matrix. So the complete row, A row will be infinity, and row D, column D will also be infinity, and the column D to A will also be infinity. And fill all the columns with respect to this one. 0, 0, infinity, 7, and 0, and 0, infinity, 0. Right? Yes. Okay. Now you can see row infinity, and second row 0, third row 0, fourth row also 0. First column 0, second column 0, third column 0, and fourth column all are infinity. Okay. Then this is also a cost reduction. Cost reduction is 0 here. Now the cost of A comma D will be cost of parent, which is 36 plus, right? Next, what is this one? Cost of A comma D. Here it will be AD. Cost of AD from this matrix. Okay, not this one, from this one. Cost of AD 7 plus cost reduction. So here all is 0. So obviously it is 0. So this will be 43. So the cost of AD will be 43. Right? So hope you understood. Now we are expanding based upon breadth first search. So we have calculated the cost of A comma B, A comma C, A comma D. So among these three parts, we need to find the least cost, and we need to expand that particular branch itself. So that's why we are not performing the complete state space tree. So we are calculating based upon boundaries. What is the bound here? So we are selecting the least cost. So least cost is the boundary. So with the help of boundary itself, we are reducing the state space tree. So here 36 is the least cost. Now we can expand the node B. So from node B, the next node can be either C or D. Again, we have to find the cost from B to C, B to D, B to C and B to D. So what is the B matrix here? So this is the B matrix. Okay, this is the B matrix. Now you can erase this one. This is a A reduction matrix, and we are expanding B, so we have to consider this one. If C is having the least cost, we have to consider this one. And if D is having the least cost, we have to consider this matrix. Now I am writing this one, right? Infinity, 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 infinity,
and infinity, infinity, 0, 2, and 0, infinity, infinity, and 0, 0, infinity, 0, infinity. So now this is the reduction matrix of B. So we are supposed to expand this one, okay, node B. So apply the same procedure to find the cost from B to C. So this is a B, okay. So we have to find the cost of B to C and B to D. So first B to C means write down the reduction matrix, consider B, row B with all infinities. So infinity, 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 and infinity. And C column, that's the third one, infinity, infinity, infinity. And again, C can't go to the first one. So C to A. So this is also infinity. A is already visited. So remaining values fill from this particular this one. So 0, 0, and infinity, infinity, and here also it is infinity, infinity, and 0 and infinity. See, all are infinities and zeros. So there is no reduction matrix. Okay. So here you can see yes, 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 and so here we are having a 0, and here also we are having 0. From column wise, this is having 0, this is having infinity, this is having infinity, and this is having 0. So this is already cost reduction. So what we have to do? We have to find out the cost from B to C. So cost from B to C, that is the cost of parent. Cost of parent is, so C parent is 36, so 36 plus cost of B comma C. Cost of B comma C, B, C, 0. So we should consider the cost of B comma C from this one, not this one. Plus cost reduction. So here all the rows and columns are 0. So don't worry if your graph is having a different values. Again, if for example, if here it is some 5, okay, so this row, this column will be having a 5. So we have to subtract this column with 5. So the cost reduction will be 5. For example, if it is 5, okay. Now in our example, it is 0. So we did not go with the reduction, right? So that's why I'm having a 0. So 36. So here also it will be 36. And coming to the next one, cost of B comma D. So what we have to do? Fill all the second row with infinity and fourth row with infinity, and the person can't go with D to A, so D to A will also be infinity. Now fill the remaining terms. So it is infinity, the third one it is 0, and this is completely infinity. What about this row? It is infinity, and 0, right? So here also the cost reduction is same, 0, and here it is infinity, here it is 0, and here it is infinity. Row wise it is infinity, accepted, and here it is infinity, accepted, and here it is 0, and here it is 0. So the cost reduction is 0. Then the cost of parent, which is 36, cost of B and D, B to D, which is a 2, and cost reduction is 0, so which is 38. So here it is 38. Okay, so again see, we have calculated the second level, okay, breadth first search. So B to C and B to D. Now again we have to find out the least cost, and we have to expand that particular node. So among these two, what is the least cost? This one. So this will be expanded. So A, B, C, and here it will be D. And this should not be expanded because this is a high cost, and this is a high cost, this is a high cost. So this should be expanded. Now we have to find out the cost of C to D. So C should be selected. So what is the C? This one. Okay, this one is the C, and we can erase everything else. So this is a C, and we need to find cost of C to D. So first what we have to do? We have to fill all the row C should be with infinity, and column D should be infinity, and DA should be infinity. Now fill all the remaining with this one, right? So infinity, infinity, and infinity, infinity, infinity. The third one also it is infinity, infinity, infinity. And you can see, so every row and column satisfies. Okay. So either it should be 0 or infinity, right? Okay. So what we have to do? Cost of C, D, the parent, which is 36 plus, okay, parent 36 plus cost of C, D from this one. C, D. See, you can see A, B, C, D, A, B, C, D. C to D, which is 0. 0 plus cost reduction here, again 0, which is nothing but 36. So it is also 36. And you can see all the 4 vertices have been visited here. All the 4 vertices have been visited. So you can check the path. The shortest path is A to B, B to C, C to D, and D to A. So this is the last vertex, and from here it will move to the A. Okay, so A to B, B to C, C to D, and here. You can observe here A to B, the cost is 10. B to C, your cost is 9. C to D, its cost is 9. And D to A, its cost is 8. So the total cost, you can observe 10 plus 9, 19, 28, and 36. So with this 36 cost, okay, so the person can visit from source to destination and come back to the source, right? So this is the procedure to find the shortest distance, okay, using branch and bound. So one thing we have to remember is we are finding the cost, but we are not getting all the possibilities. That means we are not expanding the complete state space tree. So we are just selecting the boundary, that means least cost as a bound, and we are restricting or we are reducing the state space tree. So in the first level, you can observe 36, 37, and 43, these three are the costs we got. And we are expanding only the node with the least cost, that is 36.
And then further, again we are having a two parts. One is 36 and another one is 38. Again we are expanding the node with the least cost, that is 36. So finally we have reached the destination. That is knapsack problem. So 0, 1 knapsack problem. So already we have seen what is this knapsack problem in our previous sessions, and again once again I'll tell you what is a knapsack problem and how we can use this, solve this knapsack problem by using branch and bound. So knapsack problem using BNB. So BNB stands for branch and bound. So branch and bound is an algorithmic approach which gives the optimal solution, so which is used to find the optimal solution among different solutions. And here also we are going to use or draw the state space tree, but we are not expanding each and every node. So we'll use some boundary values, and based upon that boundaries we are supposed to expand only those particular nodes. So the complete state space tree will be reduced with the help of the boundaries. Okay, and here we are using the least cost branch and bound. Least cost branch and bound. That means we'll find out the cost for each and every node, and we are supposed to expand the node which is having the least cost. And see here, in this knapsack problem, we'll be having a different weights and different profits, and there will be one knapsack, and we are supposed to push the weights into the knapsack so that finally we should get the maximum profits. And here everything will be the maximizations, but here we are considering the least cost. So initially we'll consider the complete profits with a negative value, and finally we'll get the positive. Okay, see, knapsack will be having one knapsack. That means a bag structure, okay, with a capacity, right, with a capacity, a fixed capacity, and we'll be having some profits and weights and the corresponding profits, and we need to add these weights into this knapsack so that the corresponding values should be more profit. Okay, more profit. So we can say it as a fill knapsack, which gives more profit. Okay, so here the boundary, so here what is a 0, 1 knapsack? 0, 1. So we are supposed to consider 0 as push, or consider the corresponding weight 1. Sorry, 0 for consider and 1 for consider. It's not consider and consider. For example, if we are having the weights as x1, x2, x3 and x4, and the profits with the p1, p2, p3, p4, then simply we will represent the solution with 1, 0, 1, 1. So how it represents means we are considering x1, okay, we are considering x1 and x3 and x4. So we are pushing all these three weights into the knapsack so that we'll get the profit as p1 plus p3 plus p4. That is a more profit. So if 1 represents considering the particular weight, 0 represents not considering the particular weight. So here 1, 0, 1, 1 means x1 is considered, x3 is not considered, so we have not written here. So p2 is also not available here, and 1, that means x3 is available, x4 is available. So for that representation we are considering, we are using this 0, 1. 0 means not considered, 1 means considered. So we need to expand the state space tree for both the cases. Okay, now we'll see an example of this knapsack problem. We'll solve that by using branch and bound. Okay, that's also least cost branch and bound. See, this is an example we are supposed to solve this. So profits are 10, 15, 7, 8, and the weights are 2, 3, 1 and 5, and the capacity of knapsack is 5. So we need to consider only the weights which gives the total weight 5 and which gives the possibility of more profit. For example, here you can see we can push the 2 and 3 into a knapsack so that the total weight will be 5. So the corresponding weights you can see 10 plus 15, which is nothing but 25. Okay, and there is one more possibility, pushing the last item only 5 into the knapsack, because the capacity is itself 5, right? What is the profit? 8. So we can fill the knapsack with a 5 weight. So that 5 can be filled with single, pushing only the fourth element into the knapsack, or the first 2 elements into the knapsack. So here we are having 2 different solutions. Among these two, what we have to consider? We have to consider the optimal. Optimal means with a high profit. So if you push the 4th element into the knapsack, the profit will be 8. And if you push 2 and 3 into the knapsack, the profit will be 25. So which is an optimal? So obviously this will be the optimal. So we have to find these optimal solution with the help of a state space tree. Okay, so in that we are supposed to find the least cost BNB. So initially we consider the profit as a negative values. So the negative values are minus 10, minus 15, minus 7, minus 8. Okay, now let us consider initial node, which is a root node. So from that root we are supposed to find the 2 paths. One is whether we have to consider the first element and we should not consider the first element. So we'll be getting 2 nodes. Okay, and here for each and every node we are supposed to find the 2 things. One is the upper bound and the lower bound or cost. So U for upper bound, cost is for lower bound. U is for upper bound, cost is for lower bound. And see, upper bound means the profits without fractions. Without fractions. For example, see, consider second and third elements. So 3 plus 1 is equal to 4. So still the knapsack can hold 1 weight. Okay, so it is 4. The capacity of knapsack is 5. So still there is a vacancy of 1 weight. So we can consider this 1 from the next element. So not the complete element can be pushed into the knapsack here, right? So here there will be some sort of fractions. So upper bound means the profits without considering the fractions. So we have to consider the complete element or we can ignore it. But coming to the lower bound, that is a cost, which is a profits of corresponding weights considering the fractions. Okay, so we'll calculate both, but we will be depending on the upper bound. So which node will be having the least cost, that will be expanded more. Okay, now we'll calculate the U and C for both the nodes. First, coming to this one. See, if it is x is equal to 1, that means we have to consider the first element. So what is the first element here? So 2 is the first element. So we'll consider the profit. If you insert this 2 into the knapsack, what is the profit? It is a minus 10. So there will be still 3 possibilities. I mean, the capacity of knapsack is about 3. So move to the second element, 3. If you push 3, we will get the profit as a minus 15. So check whether the knapsack has been filled or not. So 2 plus 3. So obviously it is 5, which is the capacity of knapsack. So no other element will be pushed into the knapsack. So if you add this one, the profit will be minus 25. Okay, minus 25. The profit is minus 25. So here we are not considering any fractions. So upper bound will be minus 25. And coming to the lower bound. So this is the upper bound, this is the lower bound. We need to consider the fractions if necessary. But here 2 is the first element and 3 is the first element. So there is no place in the knapsack. So there will be no fractions. And obviously the lower bound will also be minus 25. Okay, coming to this one, this node. So here we should not consider the first element. So without considering the first element, let us go with the cost. That means the lower bound. Okay, with fractions. So we should not consider first element. So push 3 into knapsack so that we'll get the profit as minus 15. Then there is again vacancy of 2. So push the next element, that is 1. Okay, so that we'll get a profit of minus 7. And see, again we are having one weight. Okay, but the next element is a 5. The next element is a 5. So we need to take 5. Okay, 1 from 5, 1/5. So that how we can take it as minus 8 divided by 5 into 1. So we require only 1. Okay, we need to get the profit of 1/5. Okay, so minus 8. So what it will be? So this is nothing but a 5. So 3, 1 and 1 from 5. So minus 15 minus 7. So minus 22. And here, what is this one? So 5, 8. Okay, so minus 0.4. Sorry, not 0.4. So 1.6. Yes, 1.6. So total it will be minus 23.6. That is the cost. Minus 23.6. Okay, hope you understood why we are getting the fractions. So here in this case, we didn't get the fractions because the first 2 elements fills the knapsack equally. So 2 plus 3, total 5. So there is no fraction. But here, coming to here, we should not consider the first element. We are not considering the first element. We should consider from the second element. So 3 plus 1, 4. And still there is a 1 element remaining, right? So we need to take 1 element from this 5 profit. So that's why we are getting here. And coming to the upper bound, we should not consider the profit. So if we have to insert 3 so that we'll get a profit of 15. And we'll insert 1, we'll get a profit of minus 7. And there is no other element to be pushed because here we are having 5. If you push 5, total it will be getting a 9, which is beyond the capacity. So we should stop here. And the upper boundary is minus 22. So here we should not consider the fractions. So it will be minus 22. So among these, which is the least? Now you can observe why we are considering the negative. So here these are the profits, maximization profits. We need to get a maximum profit. So that's why initially we are considering that as a negative. So you can observe among these two. So upper bounds, consider the upper bounds. What is the least cost? So minus 22 or minus 25? Obviously it is a negative. So minus 25 will be the least number when compared to the minus 22. So this is the minus 25 is the least one. So we need to expand this node. That means final solution will be including the first element. So we need to expand this one. So I'll expand here. So third and 4. This is the second stage. Here we need to consider x2 is equal to 1 and x2 is equal to 0. That means we need to find whether we have to consider the second element, not to consider the second element. So repeat the same process. We have to repeat the same process. So here we have to find the upper bound. Here we need to find the lower bound. Here we need to find the upper bound, lower bound. For example, so in the previous case we have considered the first element, right? So here also we need to consider the first element. So first element is fixed. So inserting 2 will return a profit of 10 plus, if you consider the second element 3, which will give the profit of 15. And see the total capacity of knapsack filled, right? So we have to stop here, and the profit is minus 25. But for both the upper bound and lower bound, it will be the minus 25 itself. And now we need to go with the second case where we should not consider the second element. So here we are not considering the second element. So you can observe we are considering the first element, we are not considering the second element. So we are considering the first element 2, insertion of 2 gives a profit of minus 10, plus we should not consider the second element. So this node is not considering the second element. So we need to consider third element, 2 plus 1, which gives a profit of minus 7. So is there any vacancy in the knapsack? Yes. The total weight of knapsack is 3. So there is a 2 more vacancy. So we need to take 2 from 5. So 2, 5. That means what we will get? Minus 8 divided by 5 into 2. Okay, so this will be minus 17 and plus how much we'll get? So previously we got some 1.6, right? So 3.2. So which will be minus. Okay, so which will be minus 20.2. Okay, so 8 by 5, which is 1.6 into 2, so that will be 3.2. Okay, 3.2 and 3.2 plus 17, 20.2, negative 20.2. So it will be minus 20.2. And here upper bound we should not consider the fractions. So we should not consider this one, right? So what is the cost here? Minus 17. Minus 17. Again, consider among these two nodes. So we should not consider this node. Okay, so among these two nodes, what is the minimum cost? What is the minimum cost? So here among this one, you can observe u is equal to minus 25, u is equal to minus 17. So minus 25 is the least cost. We need to expand 3 again. So in the third case, so we'll give 5 and we'll give 6 here. And we need to consider x3 or we should not consider x3. We should consider x3 or we should not consider x3. Both we have to find out. So we need to find the upper bound. We need to find the cost. Here also upper bound, cost. So here you can see x1 is equal to 1. So see, consider x1 is equal to 1, x2 is equal to 1, x3 is equal to 1. So if you consider x1 and x2, that means the first two elements if you consider, so 2 plus 3. And here the third case is we need to consider the third element also. If you consider the third element, the total cost will be 6, which is beyond the capacity. So we should not consider this. So we need not calculate that one, right? Because we should not consider. So here itself we got the total capacity. The knapsack has been filled. Coming to here, x3. If you are not considering the 3, see, considering 1, 1, 0. So 1, 1, 0. That means x1, x2, x3, 1, 1, 0. This is the case we are finding, right? So x1 is considered. So 2, we get a profit of minus 10. Plus x2 is considered. We get a profit of minus 15. And x3 is not considered. So x4 should be considered. So if you consider x4, the knapsack capacity will be beyond. So we need not fill this one also. Okay, right? So the value will be minus 25 itself. So here it will be minus 25 and here also it will be minus 25. And among these two, which one is the lowest? Obviously minus 25 will be the lowest. So again, expand. So here there is another case, x4. So whether we need to consider x4 or whether we should not consider x4. So here also we have to find the upper bound and cost. Upper bound and cost. So you can see here at this position, what is this one? x4, it is 1. So we are considering 1 and 2 and 4. So 1 is 2, 3, and we are not considering this one, and the fourth one is 5. So if you add this one, what is the knapsack weight? So it becomes around 10. But the capacity of knapsack is only 5. So we should not consider, and the weight will be minus 25 itself. And here also, if you are not considering the x4 also, okay, we should not add this one, right? So this cannot be expanded. We need not expand this one. Okay, and coming to this one, that means x4 is equal to 0. So we should not consider this one. So we are not considering this one. The knapsack weight is full. So with a profit of minus 25. So upper bound will be minus 25 and the lower bound will be minus 25. So that is the last step. So this is the solution for the problem. So pushing or considering the elements first and second will give the maximum profit. So previously we have seen the two cases 2, 3. Inserting 2, 3 will be giving minus 25 as a profit, and inserting only the 5, single 5 will give the profit of minus 8. So you can simply remove this minus. Okay, you can simply remove this minus, so we will get the optimal solution. The highest profit is 25. So you can see by considering 2 and 3 we will get the more profit. And here also the same thing, we have expanded. See, we have expanded, we are considering, so we have not considered the second one, fourth one, fifth one and seventh one. So we have considered the node 1, 3, 6, 8. So node 1 by considering x1 first element, node 3 by considering the second element, node 6 considering 0, not considering the third element, and node 8 not considering the fourth element. So 1, 1, 0, 0 will be the solution to get the maximum profit. And in this case, we are not giving the complete state space tree. We are not drawing the complete space state tree. So we are limited to the boundary. That is, we are considering the least cost value of upper bound, and we are expanding only that particular branch instead of expanding all the nodes. Right? So that's why we are calling it as a branch and bound. So we need to divide the branches. That means we need to draw the state space tree by considering the boundaries. And what is the condition? Least cost. And here we need to get the maximum profit. So obviously we are supposed to take initially them as a negative values, and finally we can ignore the negative values so that we'll get the optimal solution for this knapsack problem. Right? So hope you understood what is a knapsack problem, what is a 0 by 1 representation, what is a branch and bound, what is the state space tree, and what is the constraint we are using the state space tree to be expanded, the each node to be expanded. Right? So practice more problems so that you'll be getting strong knowledge on this branch and bound. Today we'll see one more concept in branch and bound, that is a 0-1 knapsack problem using FIFO branch and bound. So in our previous session also we have seen the same problem, but we have solved the problem by using least cost branch and bound. And now we'll see the FIFO branch and bound, that means a first in, first out. Okay, so let us see what is a 0-1 knapsack. So already we have seen in our previous session. Once again I'll repeat, what is this 0-1 knapsack? So here a knapsack is just like a bag or a container, okay, where we can insert some sort of elements. Okay, there will be two things. One is weights weights will be there, which are represented with let it be W1, W2, W3, etc. So these are the different weights. And the another thing is profits. So what is the profit we'll be getting if you insert the weight into the knapsack? So the corresponding profits will be represented with the P1, P2, P3, and etc. Right? So here the problem is we are having a container that we will call it as a knapsack with a small capacity. So we are supposed to place these weights into the knapsack, so which doesn't go beyond the capacity and getting the more profit. Getting more profit. That's a main constraint, right? So this is a complete knapsack problem, and we have to solve this by using a branch and bound, that is also FIFO branch and bound. And in this particular branch and bound, we are supposed to draw the state space tree in order to find the optimal solution. Okay, so some solutions will be infeasible, so we'll eliminate that one, and we'll get only the optimal solution by expanding each and every node of a state space tree. So here we are going to draw a state space tree. Okay, and here we'll be having a nodes. And at every node we are supposed to calculate the two things. One is a lower bound and upper bound. Lower bound and upper bound, right? So this is an knapsack using FIFO branch and bound. Okay, right. So every node we are supposed to find the lower bound and upper bound values. And here the lower bound values will be calculated with fractions. So fractions will be allowed here. And upper bound without fractions. So this should be calculated without calculating the fractions, right? So for every node, we have to calculate this one, and in this particular FIFO branch and bound, for every node, we have to check two conditions. So the first step is find upper bound. Find upper bound. Okay, upper bound value, which we usually call it as global upper bound. Global upper bound. So, right, global upper bound. And for every node in the state space tree, we have to compare with this global upper bound. We need to check two conditions. So the first condition, if the new upper bound is less than, I'll erase this one, less than global upper bound. So we are calculating the lower bound and upper bound, right? So once you calculated this lower and upper, we need to compare this new upper bound with the global upper bound, which is calculated initially, right? So if the new upper bound is less than the global upper bound, then update global upper bound, so I'm using small words like UB, with new upper bound. So that means we have to replace this global upper bound with the new upper bound whenever the new upper bound value is less than the global upper bound. So always the global upper bound should be the minimum value. So that is the first thing we have to calculate. And the second condition, two conditions we are supposed to use, and there's the first condition, and the second condition, if the lower, so every node we are calculating the lower bound. So if the lower bound is greater than the global upper bound, global upper bound, then we are not we should not expand that particular node. So if after calculating the lower and upper bounds, we have to compare this lower bound with the global upper bound, right? With the global upper bound. If the lower bound value is greater than the global upper bound value, then that particular node should not be expanded. So we have to kill that particular node. So then the node should not be expanded. That means kill the node, right? So these are the two conditions, most important conditions we have to check while solving the 0-1 knapsack problem using FIFO branch and bound. So initially find the upper bound and initialize it to the global upper bound, and now for each and every node we have to calculate the lower bound and upper bound, and if the new upper bound is less than the global upper bound, then update this global with the new upper bound, and if the lower bound is greater than the global upper bound, then immediately that node cannot be expanded. So that's a kill node. I mean, we have to kill that particular node. That means that node cannot be expanded. So with this, you can observe that we are not expanding each and every node of a state space tree. So at some particular point, we are comparing and we are deciding whether the node can be expanded or it can be killed. So the state space tree is not completely finding. Okay, we are not calculating the complete state space tree. Okay, so just remember these points, these conditions, so that we'll see the example. So whatever the program or whatever the problem we have taken in our previous session, the same thing we'll take, and I'll show you this one. So I'll write here the two conditions. So I'll write new upper bound is less than global upper bound, then update. So simply I'll write it as an update. And the second condition, lower upper bound is greater than global upper bound, then kill. So these are the two conditions we have to remember, right? Now we'll see the problem and we'll find the state space tree. We have to calculate the lower bound and the upper bound values. See, this is the problem we have solved in our previous session. That means using the least cost branch and bound. The same thing we have taken. So weights given, the 4 weights. So 1 is 2, 3, 1, 5, the capacity. And the profits, corresponding profits at 10, 15, 7, and 8. And here we are supposed to find the optimal solution. And here this is a minimization problem. So for that, we are just using the negative values. So I'm just putting the negative sign, right? So minus 10, minus 15, minus 7, and minus 8. Now the capacity of knapsack is 5, given as a 5. So we have to insert the elements into the knapsack so that the knapsack weight should not exceed the 5. Okay, so here also we are having two different solutions. We can consider 2 and 3, which gives a profit of minus 25, and considering only one element, that is 5 directly, which gives a profit of 8. So here we are having two different solutions, possible solutions. Among that, we have to go with the optimal solution, right? So we'll see. First, we have to calculate the upper bound and the lower bound, initial global value. So upper bound. So upper bound is without fractions. I'll write here upper bound without fractions, lower bound with fractions. So 2 things we have to remember. Okay, first let us take with the upper bound. The complete knapsack weight is a 5. So I am inserting the first element, that is a 2, with a profit of minus 10, and then 3 with a profit of minus 15. Okay, you can observe the weight of knapsack becomes 5. Okay, if you insert the third element with weight 1, the total knapsack total capacity will be 6, which is beyond 5. So we should not consider the third element. So upper bound value is minus 25. The upper bound value is a minus 25. So simply we can say the global upper bound value is minus 25. Okay, so consider the root, and now we have to check. Okay, we have to check whether we have to consider the element or we should not consider the element. So there will be 2 positions, 2 paths. So node 1 and node 2. So here x1 is equal to 1, and here x1 is equal to 0. So here 0 and 1 represents considering or not considering. So this branch is x1 is equal to 1. That means we are considering the first element, and this branch is x1 is equal to 0, which is we are not considering the first element, right? So node 1, see node 1, right? So here we need to calculate upper bound and the lower bound. Okay, so upper bound, coming to the upper bound, consider the first element. So I'll push 2 into this one knapsack with a profit of minus 10, and then 3 with a knapsack with a minus 15. So we can't put the third element, right? So the upper bound value will be minus 25. Coming to the lower bound also the similar, but here we can consider the fractions, right? So insert the first element with a profit of 10. So remaining, there is a 3 capacity remaining. So automatically the second element also is 3 with a 15. So there is no need of fractions, because after inserting first element and second element, the knapsack value becomes complete 5, right? So here also the lower bound is also minus 25. So you need to write it here. Upper bound is equal to minus 25 and the lower bound is equal to minus 25, right? Hope you understood. And the same thing we have to calculate for the second node also. So first in, first out. So we have to find this one and we have to compare. Okay, after comparison, then go with the next one. Now compare, after calculating the upper bound and lower bound, we have to calculate whatever the new upper bound less than the global upper bound. New upper bound is minus 25. Global upper bound is minus 25. So minus 25 less than minus 25. So it's a false. So no need to change. And if the new upper bound is some around 30, minus 30, you can know that minus 30 is the lowest value than minus 25. So we have to replace this minus 25 with minus 30. But in this case, it is minus 25, there is no change. Coming to the second one, lower bound is greater than global upper bound. So lower bound minus 25 greater than minus 25. That's also no problem. Okay, so we can expand this node. Coming to the second node, go with the second node. Okay, so you need to calculate the upper bound value and the lower bound value. So at node 2. So calculate the upper bound, calculate the lower bound. So this is the upper bound value, this is the lower bound value. So we should not consider the first element. Okay, for node 2, we should not consider the first element. So avoid the first element, inserting the second element. So with a profit of 15. And the knapsack still have 2 capacity, and the next one we can get it. So with a profit of minus 7 and 4, and there is still 1 remaining, but the third element is 5. So here we should not consider the fraction. That means we can't insert a part of element into this particular knapsack. So for example, if this element is having the 5 kgs, the weight is 5 kgs, we can't insert 1 kg among these 5 kgs to the knapsack. So that's a fraction. So that's not possible here. So we need to stop here, and the upper bound value will be minus 22. And that can be done in the lower bound. So lower bound also we are inserting the second element because we are not considering the first element. So 3 with a profit of 15 and 1 with a profit of minus 7 and then 5. So inserting 5 means, see how much capacity is still there, 1, right? So 1 by 5 into minus 8. Okay, 1 by 5 into minus 8. So which gives it as a 1.6. So minus 1.6. Lower bound will be minus 22 minus 1.6, which will be minus 23.6. So update the same thing here. Upper bound value minus 22, lower bound value minus 23.6. So check the 2 positions, 2 conditions. New upper bound minus 22 less than global upper bound. Global upper bound is minus 25. So minus 22 less than minus 25. So this is false. Okay, because it is a negative value, minus 22 is greater than minus 25. And similarly, lower bound greater than global upper bound. Lower bound is minus 23.6 greater than minus 25. So this is true because this lower bound value is greater than the global upper bound. What we have to do? We have to kill. So that means node 2 should not be expanded. node 2 should not be expanded, right? So that means we have killed that particular node. Only node 1 should be expanded. Now coming to the node 1, expand this one with the second element. So 3 and 4. So here x2 is equal to 1 and x2 is equal to 0. That means considering the second element, not considering the second element. So let us calculate for this one, node 3, upper bound, lower bound. Okay, this is upper bound, lower bound. So upper bound without fractions, lower bound with fractions. So what we have to do? So we have to consider the first element in both the cases. So I am considering the first element. So insertion of 2 with a profit of -10 with a profit of -10. What about the second node? Second element. So we are considering third branch. That means node 3 comes with the considering the second element. So second element, if you consider second element, then it will be 3 with a profit of -15, and here also 3 with a profit of -15. Now you can observe the weight of knapsack becomes 5 with a maximum capacity. So we can't insert the third element. So upper bound will become -25 and lower bound will also become -25. So update it here. Upper bound is equal to -25 and lower bound is equal to -25. So check out the condition. New upper bound greater than less than global upper bound. New upper bound is -25, global upper bound is -25. So that's a false. Next, lower bound is greater than global upper bound. Lower bound value is -25, global is -25. -25 greater than -25. Again, it's false. So nothing happens here. Coming to the node 4. Node 4. So in this node 4, what we have to do? So here we need to consider. Yes. See, coming to the node 4, we have considered x1, right? So that means we have inserted the second element with a profit of -10 in both the cases, and the second one we should not consider. So we have to consider only one. So the third one, right? So third one means 1 with a capacity, with a profit of -7, and here also with a capacity with a profit of -7. So what is the capacity of knapsack here? 3. Okay, only 2 is the remaining, but fourth element is 5. Here we should not consider the fractions. So here the total weight is -17. Okay, the profit total upper bound value will be -17. But here we can consider the fractions. So among these 5, we can go with the 2 by 5 third of value, right? So what we have to do, 2 by 5 into -8. 2 by 5 into -8. Okay, so this gives -3.2. Okay, -3.2. So the lower bound value will becomes -17 -3.2, which is -20.2. So update here, the upper bound value will be -17, lower bound value will be -20.2. Check out the condition. New upper bound value -17 is less than global value. So -17 is less than -25. So false, because -17 is greater than. And coming to the lower bound should be greater than global. So -20.2 is greater than -25. So this is true. -20 value is greater than the global upper bound. What we have to do then, kill that particular node. So we have to kill the fourth node. That means the fourth node cannot be expanded. So we are not supposed to expand the fourth node. We are killing that particular node. So only node 3 will be expanded right now. So expand node 3. So here the first come first serve means first we have to calculate for 3, then only we need to go with the 4, and then only we need to go with the next one. So here we are killing, so we are expanding here again. So it will be 5 and it will be 6. And the third element, x3 is equal to 1, and here x3 is equal to 0. And what we have to do, so first we have to calculate with the 5, and then we have to calculate with the 6. First in, first out. So node 5, right? So in this node 5, we are considering x1 is equal to 1, x2 is equal to 1, x3 is equal to 1. Okay, node 5. So this is the upper bound value, and this is the lower bound value. So this is the upper bound, this is the lower bound. So we are considering the 3 elements. Here we are considering the 3 elements. So considering the first element, what is the first element? 2 with a profit of -10, and then considering 3 with a profit of -15, and we can't insert the third element. So in this node 5, we have to consider the third element, but here if you consider the third element, the knapsack weight will be 6, which is beyond the maximum capacity. So this is infeasible solution. Infeasible. That means there is no proper path will be done. So this node cannot be expanded. So coming to the node 6, we have to calculate for the node 6, and in this node 6 we have to avoid this x3. That means we should not consider the third element. So we need to consider the node 6. So we should, for getting the node 6, we should not consider the third element. So if the upper bound will be -25, and coming to the lower bound also, we have to consider 1 and 2. So 2 with a profit of -10 and 3 with a profit of -15, and the knapsack becomes total weight is 5. So lower bound value will also be -25. So update this one. Upper bound is -25, and lower bound will be also -25. Right? Now check the conditions. New upper bound is less than global upper bound. So -25 is less than -25 false. So nothing should be updated. A lower bound should be greater than global upper bound. Then we have to kill. Lower bound is -25, and the global upper bound is -25. So -25 greater than -25 is also false. So we can expand the node 6. Okay, the node 6 can be expanded. If the value is greater than global upper bound, then this 6 should be killed. But here it is not the same, right? So we have to expand with the node 6. Okay, and here we need to consider the fourth element, and here we need to consider we should not consider the fourth element. Now coming to the calculation of upper bound and lower bound values for node 7. Okay, node 7. So here you can see x1 is equal to 1. In order to get it, x2 is equal to 1, x3 is equal to 0, and x4 is equal to 1. So we should consider 1, 2, and 4th elements. So consider the upper bound values and lower bound. We have to calculate the upper bound and lower bound. So consider the x1, 2 with a profit of -10, and 3 with a profit of -15. So there is no possibility to insert fourth element. If you insert 4, okay, if you insert the fourth element, so 5 will be inserted, which becomes the total knapsack as a 10. So which is beyond the capacity. That actually the knapsack capacity is only 5. So we can't insert this 5. That means fourth element. So obviously we can say it as a infeasible solution. Infeasible solution. So it can't be done, right? So we have to calculate the upper bound and lower bound for this 8, node 8. So node 8, and here also the fourth one should not be considered. Should not be considered, right? So this is upper bound and lower bound. Upper bound and lower bound. You can see we need to consider x1 and x2. So 2 will be inserted with a profit of -10, 3 will be inserted with a profit of -15, and the total capacity of knapsack becomes total 5. And we should not consider x3 and x4. So we should not consider the two weights 1 and 5. So upper bound value will be -25. And here also lower bound also we have to insert the first element with a profit of 10 and insert the second element with a profit of 15. So here also we'll get the lower bound value with a -25 because the total knapsack becomes 5, which is the maximum capacity. So here upper bound value will be -25 and lower bound value will be -25. So again check the condition, upper bound less than the upper bound false, lower bound greater than the global upper bound false. So this is the solution. And because we have considered up to the 4 elements, x1, x2, x3, x4. So 4 levels we have calculated. So if there are 5 elements, then again this 8 will be expanded. Okay, and again we have to calculate the upper bound and lower bound, and we have to check the condition. And this is a FIFO branch and bound for solving the 0-1 knapsack problem. And here the solution is considering, here the solution for this problem is considering x1 as a 1. So see, this is a solution. So this is x1, x2, x3, x4. So considering 1, 1, 0, 0. So that's what we have said this about 0, 1. 0 is not considering, 1 means considering. So in this is a solution, that means we are considering only x1 and x2, which gives the maximum profit. So what is the profit here? So the profit by inserting the 2 elements is -25. So which is the maximum profit. So here we should ignore the sign so that will be the maximum profit. So we are converting the maximization problem to minimization problem and finding the solution. So by giving some negations to each and every profit, and finally we are just discarding the negative value so that we'll get the maximum profit here. So by inserting the first 2 elements, we are getting the maximum profit. So this is the optimal solution. This is the optimal solution. So you can see x1 is equal to 1, x2 is equal to 1, x3 is equal to 0, and x4 is equal to 0. So this is the path where we can find the solution. And here we got the 2 infeasible solutions where we can't process further. And these 2 are the killed nodes. Node 2 and node 4 are killed nodes, dead nodes which are not being expanded. Right? So these 2 statements or these 2 conditions are most important, where for every node after calculating the upper bound and lower bound, we have to check with the these 2 cases so that the complete state space tree cannot be calculated. So some sort of nodes will be discarded here. So reducing the state space tree will be done. Disjoint sets. Disjoint sets. So we know that a set is a collection of elements, right? So a set is a collection of elements. So then what we call it as a disjoint sets. So if you consider any two sets, right? Let it be S1 and S2. So these 2 sets are having a different elements like 1, 2, 3, and here it is 4, 5, and 6. And when we say that S1 and S2 are a disjoint sets, so when the S1 intersection S2, that means the common element, right? So is equal to 5. That means there is no common element in both the sets, right? There is no common element. Then we can say these 2 sets are disjoint sets. That means no common element. So we usually, the intersection means we need to get the common element in both the sets, right? So there is no common element in S1 and S2. Then S1 and S2 called as disjoint sets. Disjoint sets. So there should not be any common element in both the sets. Right? Now, what are the operations that can be done on these disjoint sets? So the operations that can be performed is the first one, simple union, simple find. That means we know that union means combining both the sets. So we will combine both the sets and we'll get a new set with all the elements of both the sets, S1 and S2. So that's the union, simple union. That's a simple union. So there is no constraint, right? And next is simple find. So we need to find the parent of that particular element. So why we are calling it as a parent means any set can be represented in terms of a tree data structure. Okay, a set is represented as a tree data structure. So as we are calling it as tree, definitely there will be a root node. Okay, and usually we can call this as a parent node. Root node or a parent node. For example, let us take 1, 2, and 3. We can say 1 is a root node or 1 will be the parent of 2 and 3. Okay, so that's why we can call it as a parent node or a root node. So simple find means we need to find whether the element is available in the set or not, and if yes, we will return the parent node, the parent of that particular element. And the next one, weighted union. Weighted union. So there will be some sort of weightages, and based upon that weights we have to perform the union operation. And the fourth one, collapsing find. Collapsing find, which is a slight different from a simple find, which is a slight difference from the simple find. And in this session, we will focus on simple union and simple find. So how can we perform this simple union between the two different sets, and how can we perform the simple find operation? So one thing, we are working on the disjoint sets. Disjoint sets means we need to take more than one set, and there should not be any common element in both the sets. For example, S1 and S2. So let us consider S1 is having some A, B, C, and S2 is having some E, F, G. So these two are called as a disjoint set because there is no common element. For example, if this is having one more element like 3, 4, 5, 6, we can't say S1 and S2 are the disjoint because here S1 intersection S2 is having one element called 3. So if there is any common element, we can't say those sets as a disjoint set. If the intersection is 5, that means no element, then only we can say these two are the disjoint sets. Now it will be the disjoint sets. So 1, 2, 3 in one set, 4, 5, 6 is another set. Right? So hope you understood this one. Now we'll see the simple union and simple find. First, simple union. Let us consider the simple union. So simple union means we are supposed to apply the union operation between the elements. So simple union. So first what we have to do, we have to consider all the elements as a individual elements, right? So consider all elements as individual. So usually we will represent this one with a tree data structure. So tree data structure, right? So obviously there will be a root node or parent, right? So consider P of I is the parent of node I. So usually the P of I is represented as a parent of P of node I. Okay, if you consider any node, P of I will be represented as a parent. And let's see, initialize P of I is equal to -1 for root nodes. If the node is a root node, the parent will be -1. Okay, if it is a root node. So obviously if it is a root node, there will be no parent, right? So that will be the first node, right? So we have to initialize to -1 for such root nodes. And fourth, so we have to collaborate, or we have to perform the union operation with one by one. Okay, perform simple union for every element. And finally, update the parent after union operation. Right? So these are the steps we need to follow, right? The first one, consider all the elements as a single elements, individual elements. Next, let us represent the P of I is the parent of node I, and then initialize the parent -1 for as a parent. -1 for the parent nodes. That means a root node, and then perform the simple union for every element one by one. Okay. Then update the PI after union operation. See, for example, if you apply the union operation, so the -1 should be only for the root node. So only one node should have the -1, right? So remember all these points. Now we'll move on with the example so that you can understand that one. Simple union. See, let us take the elements as 1, 2, 3, 4, 5, and 6. These are all the different elements. So now what we have to do? So we have to consider the tree structure. 1, 2, 3, 4, 5, 6. So this is a tree. Now we have to find out the table of all the parents. So I'll write here. I'll write here. So 1, 2, 3, 4, 5, 6. This is the I value. This is the parent of I value. So this is the parent of I value. What happens? Now what we have to do? Initialize -1 to the parent. So here all these are the individual elements. So these are all the roots. Okay. So this is one tree with only one element. So what is the value of parent of this one? It will be -1 because it is a root. Parent of 2, again it's -1 because it's a single element. And it is also -1, -1, -1, and -1. Okay. Initially this is a -1. What happens? Now perform the union operation between 1 and 2, union operation between 3 and 4, union operation between 5 and 6. Okay, now you can take 1 as a root and 2 as a child, 3 as a root, 4 as a child, 5 as a root, 6 as a child. So that means we are joining, we are performing the union operations in between 1 and 2, 3 and 4, 5 and 6. We are combining the elements, right? Now update the value, update the parent of nodes. So what's the parent of 1? Here 1 is a root node. So parent of 1 is -1 only. What's the parent of 2? Parent of 2 is 1. So it will be -1, it will be 1. And parent of 3, -1. Parent of 4, it's a 3. Parent of 5, it's a -1 because it's a root. 6, it's 5. See, after combining this one, we got the values in this manner. Okay, so after completion of the union operation between 1, 2, 3, 4, 5, 6. Now what we have to do? You have to perform the union between these two things. So union of, okay, 1, 3. So what happens here? So 1 with a 2 and take one more child, which is 3, which is having 4. Which is having 4. So this is a union of 1, 3. Here 1 is a root node, 3 is a root node. 1 is a root node, 3 is a root node. So we are combining these two things. Okay. So now what happens? 1 becomes the root node. 1 becomes the root node. So update the parents. So the parent of 1 is a -1 because it's a root. Parent of 2 is a 1. Parent of 3 again it's 1. Parent of 4 it's a 3. Okay. And similarly this is a -1 and 5. -1 and 5. You can observe again we are having two -1s. But if you perform the union operation, what we have done, so only one root should be there. Only one root should be there. So again, we have to combine union 1 and 5 and 6. See, union of 1 and 5. So 1 is this one. So 1, which gives with a 2, another child with a 3, which is having a child 4, and now 5 and 6. One more child you can give, it's a 5, and it can give it as a 6 as a child. Now what happens? Again, update the parent table, which is root of 1, it is a -1. Root of parent of 2, it is 1. Parent of 3, it is 1. Parent of 4, it is 3. Parent of 5, it is 1. Parent of 6, it is 5. Right? Now you can observe there is only one -1 here. That means only one root. Only one root. So this is the root. So after joining all these things, after performing the union operation of all these elements, we got this particular tree, which is having only one root followed by different children. So for this, the algorithm will be simple, which is a union of I, j, which gives the parent of j is equal to I. That's it. So this is a simple algorithm to perform the union. So one by one, we have to join the elements. We have to combine the elements. That's called as a union. And the resultant after every joining, after every union operation, we have to update the parent table. We have to update the parent table, right? So this is how we can perform this simple union. So initially all these are the individual elements, so individual trees, only one root node is there. So gradually we are combining one node with another node, one set with another set. Okay, and we are updating the parent table. For every node we are giving the parents. So P of I represents the parent. So this is a simple algorithm for simple union. Now what we have to do, we have to perform the simple find. We have to find the element. So our next operation is simple find. So I'll erase all these things. I will erase all these things. See the final one is this one, 1, 2, 3, 5, 4, and 6. So the same thing here. Okay, the same thing here. I'm erasing this one also. So what we have to do? We have to find the element from this particular table, right? So see, the algorithm for this one is the find of I. We need to find I, and we have to repeat the steps while the parent of I is greater than 0. Simply what we have to do, so we have to initialize this parent of I to I and close, and finally you can return the I value. So this is a simple algorithm for find. See, you can check. First, if you want to find a 4, okay, so what's the parent of 4? What's the parent of 4? The parent of 4 is 3. 3, okay, which is not a -1. We know that the parent of root node is -1. We know that the parent of root node is -1. So we need to repeat this process. We need to find every element parent until it reaches to -1. So that's why we have written this one. So we have to repeat the process until the parent node is greater than 0. So if the parent is greater than 0, that implies there is another level of parent, right? See, for example, if you want to find the 4, the parent of 4 is equal to 3, which is greater than 0. What we have to do? So I is equal to parent of 4. So that is equal to 3. Now I is equal to 3. I is equal to 3. Now perform the same operation here. I is equal to 3. So parent of 3 is equal to, what's the parent of 3? It is 1. So parent of 3, you can see here. Parent of 3 is 1. 1, which is also greater than 0. So simply initialize the parent of 3 to I, which is equal to 1. Now I becomes 1, and see P of 1 is equal to, what's the parent of 1? What's the parent of 1? It's a -1 because it's a root node, right? So it is a -1. So which is less than 0. So simply what we have to do, so you have to return I. Return I means it's a 1. So 1 is a root node. 1 is a root node. So if you got that root node, that implies the value is available in our union. Okay, in our set of elements. So this particular find will return a root element. It will return the root element. So this is a simple logic for applying the find operation. So we need to keep on moving until the P of I, the parent of I, is less than 0. If it is greater than 0, simply we have to repeat this process. Okay, so whenever it becomes less than 0, immediately we can say that the root is I. The root is I. So this is a simple find operation. So simple union and simple find. Okay, so I hope you understood this. These two operations are in disjoint sets. So once again, the disjoint sets, when we call it as a disjoint sets, means if the intersection of both the sets are 0, that means there is no common element in between two different sets, we call it as a disjoint sets, and we can perform a few operations on the disjoint sets, that is a simple find, simple union, and weighted union, and collapsing find. So in this session, we have seen the simple union and simple find algorithms, and how we can find out the root of the element, and how we can perform the union of all the elements. So one thing we have to remember, we have to represent any node in this disjoint sets as a roots, as a tree structure. So we are using the tree data structure to represent the set. So in our previous session, we are discussing about the disjoint sets. What is the disjoint set? So if you consider two sets, if there is no common element between these two sets, then we can say that set as a disjoint set. And there are different operations that can be performed on disjoint sets. So that is a simple union, simple find, and weighted union, and collapsing find. So in our previous session, we have discussed about the simple union and simple find. So union means combining the elements from both the sets, two different sets. Okay, and find means it will find the index, that root element of that particular set. Okay, we can call it as a set representative. So whatever the root element in that particular set, so that will be returned in the find operation. So that we have seen in our previous session. Now we'll see the third operation, that is weighted union. Weighted union. So there is a slight difference between the simple union and the weighted union. So in the simple union, what we have done, so just we are merging two different sets and forming a single union. Okay, so we are merging one set with another set. So merging means here union, right? So, and we said that the root element, the parent node of root element will be -1 there. But here in the weighted union, the name itself indicates the parent of root element will be the number of nodes of that particular element or that particular set. Okay, for example, consider S1 is equal to 1, 2, 3, 4, and S2 is equal to some 5, 6, and 7. So we know that there are no common elements in between these two sets, no common elements. So that means S1 intersection S2 is equal to 5. 5 means an empty set. Okay, so we can say S1 and S2 are the disjoint sets. So these two comes under disjoint sets. Disjoint sets. Now, if you want to give a union S2, S1 union S2, that means combining both elements. So which should be given as a child to which set? So which will be the parent and which will be the child? So simply, if you perform this one in the weighted union, so if number of elements in S1 is greater than number of elements in S2, that means S1 is having more number of elements than S2. So here S1 is having how many elements? 4 elements. And S2 is having how many elements? 3 elements. So here this example reaches, right? S1 is greater than S2, then S1 will be the parent and S2 will be the child. So we have to insert or merge the S2, the elements of S2 to S1. That means the number of elements, which set is having the more number of elements, that will become the parent. And the set which is having the less number of elements, that will become the child element. Right? For example, consider the same thing. Okay, so remember this one. If number of elements in S1 is greater than number of elements in S2, S1 will be the parent and S2 will be the child. Else means if number of elements in S1 is less than number of elements in S2. So now more number of elements are in S2. So S2 will be the parent and S1 will be the child. So I'll give you an example. Let us consider this one. So as we discussed in our previous session, the set is represented with a tree structure. Set is represented with a tree structure. For example, I is the root element and here 5 is the root element. So S1 can be denoted as 1, which is a parent of 2, which is a parent of 3, which is a parent of 4. And the next one, 5, which is the root or parent of 6 and it's also parent of 7. Now the number of elements, this is a S1 and this is a S2. Now what happens? S1 union S2. So which will be the parent? S1 is having 4 elements, S2 is having 3 elements. So S1 is greater than S2. S1 is greater than S2. Right? Then S1 will be the parent, S2 will be the child. So what happens? 1 having a child 2, 3, 4. And 5 will be the another child. 5 will be the another child, which will be having 2 more children, 6 and 7. So this is how we will perform the union operation. So only one thing. So that means based upon the number of nodes in that particular set, we will be deciding the parent set and the child set. Okay. Now what happens? What is the root? Okay. What is the parent of that particular root? See, I'll erase and I'll show you. For S1, for S1, the elements are I and P of I. Let us consider I as an element, P of I as a parent. So how many elements are there? 4 elements. 1, 2, 3 and 4. So total 4 elements are there. Similarly, S2 is having I and P of I. I is the number of elements and P of I is a parent of that element. So 5, 6 and 7. Now consider the parent. So parent of 1, here you can see 1 is the root node. 1 is the root node. Then in normal simple union, we consider the parent of root node will be minus 1. But here, the parent of root node will be the count of that particular set. So parent of I will be minus count of I. That means that particular set. Okay, that particular set. So how much? It will be minus 1. And how many nodes are there? 4 nodes. So it will be minus 4. So minus 4 is the parent of node 1. So in simple union, we are giving minus 1 as a parent, right? But here we are giving the number of count. Okay. Then parent of 2, it is 1. Parent of 3, again it's 1. Parent of 4, again it's 1. Coming to here, the second set. Okay, the second set. So coming to the second set, parent of 5. 5 is a root node. So if it is a root node, what we have to do? We have to count the number of elements of the particular set. How many elements are there? 3 elements. 5, 6, 7. So the parent of 5 will be minus 3, as it is having some 3 elements. Parent of 6 is 5. Parent of 7 is, again, 5. Parent of 7 is 5. Now, what happens? See, S1 union S2. So what are the elements? 1, 2, 3, 4, 5, 6 and 7. And similarly, we need to write the parent. We need to write the parent of all these nodes. Alright. Now what happens? Parent of 1. Parent of 1 will be, so here we are performing the union operation. So these two becomes this one. Okay. Now parent of 1. How many nodes are there now? 1, 2, 3, 4, 5, 6 and 7. Total 7 nodes are there. So what happens here? Minus 7. Minus 7. Right? So that means what we have to do? If P of I is greater than P of J. Okay. If P of I is greater than P of J. So for example, here it is I and here it is J. Okay. I and J. So here you can check minus 4 greater than minus 3. True or false? False. That implies, so J is having less number of elements. J is having less number of elements. So what we have to do? We have to make the parent of J to I. Okay. So we have to make a parent of I to J. Right? See, what happens? 1, it will be now total elements are, I'll go with this, the next one. Okay. Yeah. So what happens here? Total 7 elements, so it will be minus 7. And what about the parent of 2? It remains same, 1, 1, 1. And what about the parent of 5? Parent of 5. So parent of 5 becomes 1. Okay, here it comes up. Parent of 5 becomes 1. And parent of 6 becomes 5 and 7 becomes 5 itself. So in this case, let us see, for example, I value is minus 4, J value is minus 3. Okay, so let it be P of I is equal to count, and similarly P of J is equal to minus count of J. Okay, minus count of J. So you can observe, this is minus count of I means total it will be minus 4 and it will be minus 3. So if you perform the union operation, what will be the total count value? So that will be, let us take temp is equal to P of I plus P of J, which will become minus 7. You can observe total 7 elements are there. Total 7 elements are there, and this minus 7 will be the parent of the root. Now we have to decide what is the root, either S1 or S2. So for that decision, what we are doing, simply you can check if P of I, in this example, we'll check in this example, is less than P of J. P of I less than P of J. P of I is minus 4. Okay, so here it is minus 4 less than minus 3. What happens? True. True. That means you can see I is having more number of elements. So here don't confuse about the less than and greater than symbol, because here we are saying P of I is less than P of J. That implies this is the negative values. Minus 4 less than minus 3 is obviously true. So 4 elements are having in first set, 3 elements we are having in second set. So what we have to do, what we have to change? We have to change the parent. Okay. Parent of J is equal to I. So parent of J will be I. So what is the parent of J? Parent of, what is the J here? 5. Parent of 5 will be I. I means 1. Okay, parent of 5 will be 1. You can observe now. And similarly, what about the parent of I now? Parent of I will be 10. After completion of union, it will be minus 7. Okay, hope you understood. Check this condition. P of I less than P of J. That means minus 4 less than minus 3. That implies, so this implies set 2. Set 2 is having a less number of elements, and I set is having more number of elements. Then simply what we have to do, we have to initialize I to as a parent of j. So what we have done here is like this, right? J is 5. Parent of 5 will be 1. Parent of 5 will be 1. 1 is nothing but I. And parent of I will be temp. Temp is nothing but total number of elements minus 7. So here we got it. Else. That means if P of I is greater than P of j, that means here we are having 3 elements, here we are having 4 elements. What it becomes? S2 becomes the parent, S1 becomes the child. So what happens here? P of I is equal to j. We have to initialize j as a parent of I. So we are merging S1 to S2. We are merging S1 to S2. And then P of j, this is the root node, which is nothing but a temp. So these are the two conditions we need to take care while implementing the weighted union. So only one thing we have to remember, so S1, if you want to combine or if you want to perform the union operation between S1 and S2, first we have to count the number of elements in S1 and S2, and which set is having the highest number of elements, that becomes the root or that becomes the parent, and the less number of elements set becomes the child. So that we have to update the values, the parent nodes, right? And as the name itself indicates a weighted union, the root node, the parent of root node will be the number of elements in that particular set. Now I'll write the algorithm here so that you can understand. So I'll erase this one. I'll write here algorithm weighted union, which takes the values I and j set. So initially P of I is equal to minus count of I. Similarly, P of j is equal to minus count of j. So here we are taking the number of elements. Now what we are doing? We are just combining these two things, P of I plus P of j. So after performing the union operations, we will be getting the total value. Now what we have to do? So we have to check the condition. If P of I is less than P of j, that means P of I is having a more number of elements than P of j, then what happens? We have to initialize this one. P of j is equal to I. That means we are assigning I value as a parent of Pj. That means we are appending the second set to the first set. And what will be the I value? P of I is equal to 10. P of I is equal to 10. So I'll erase this one also. And what about the second? That means else. So this means S1 is greater than S2. Okay, let it be I belongs to S1 and j belongs to S2. So then it becomes P of I is equal to j. Okay, that means, so this part S1 is less than S2. That means number of elements of S1 is less than number of elements of S2. Now S2 becomes the parent, S1 becomes the child. So S1 should be union, that means merged to S2. So that's why j value will be the parent of P of I. And similarly P of j is equal to 10, which is the parent of root becomes the total value. So this is a simple algorithm for weighted union. The only difference between weighted union and the normal union means, so here based upon the number of elements of a set, we are deciding which set should be merged to which set. So larger elements set will be the parent, lower elements set will be the child. So similarly, we have to change the parent of each and everything, and the parent of root will be the number of elements of that particular set. So we have to remember these points, and this is a simple algorithm to implement the weighted union in disjoint sets. Hello friends, welcome back to our channel. So today we'll see one more operation on disjoint sets, that is a collapsing find. So in our previous session, we have seen what is a disjoint set and what are the operations that can be performed on the disjoint sets. So in that we have seen the three operations, that is a simple union, simple find, and a weighted union. And the fourth operation is the collapsing find. So before going to the collapsing find, let us know about the simple find. So if the disjoint set in this format so if our tree structure is in this format, right? And if you want to find 70, so we know that in disjoint set, if you are performing the find operation of any particular element, if it is available in the set, it will return the set representative, which we call it as a root node. So the find of 70 will be the root node of this set 10. Similarly, if you apply the find of 40, then also it will return 10. And if you apply find of 50, then also it will return 10. That means the find operation will return the set representative, which is a root node. Now, what we have done in the simple find, so simple find of I, what we have done, so we are checking the parent node is greater than 0 or not. So we are checking the parent node, the parent of I is greater than 0. If yes, it is greater than 0, that implies I is equal to parent of I. Because in the disjoint set, so the parent node of a root, okay, the parent node of a root will always be a negative value. Either it can be -1 if it is a simple union operation, and it will be the total number of elements of a set if it is a weighted union. But it is a negative value. So that means we are always checking that the parent of I is greater than 0. If it is greater than 0, that implies that is an intermediate node, that is not a root node. So we are just iterating everything until the condition becomes false. That means until the P of I greater than 0 is false, it becomes negative. then we can say that the root node, it reaches to the root node. For example, find this one for this simple find. So find of 70. So what we have to do? So P of 70 greater than 0. That implies what is the parent of 70? So I'll write here the values. So 10, 20, 30, 40, 50, 60, and 70. So these are the values, and these are the I, and this is the parent of I. So what's the parent of 10, which is a root node, so which will be -1. Parent of 20, it is 10. Parent of 30, it is again 10. Parent of 40, it is 30. Parent of 50, it is 10. Parent of 60, it is 50. Parent of 70, it is 60. So this is the table of the complete elements and corresponding parents. Right? Now parent of 70 is 60. So 60 greater than 0. 60 greater than 0. It is true. Then I becomes parent of 70, which is 60. Again, now find of 60. Find of 60. So parent of 60 greater than 0. What's the parent of 60? It's 50. So 50 greater than 0. True. Then I becomes a parent of 60. So which is 50. Now becomes 50. I becomes 50. Now again, find of 50. So parent of 50 greater than 0. What's the parent of 50? It's a 10. So 10 greater than 0. It's true. Now I becomes 10. Now parent of 10 greater than 0. So what's the parent of 10? Which is a -1 or -7. So it will be -1 greater than 0, which is a false. So then I is a root node. I is a root node. It will return the I. So that we have done in the simplified algorithm. So here, how many comparisons we are doing? There are 3 comparisons we are doing. So in order to find 70, we are finding 60, we are finding 15, and then we are finding 10. So 3 comparisons are being done. Okay. So for find of 70, if it is a simple find, it requires 3 comparisons. It requires 3 comparisons. For example, in our logic, if it requires to apply 4 times, okay, if it requires some 4 times to apply the find operation, how many comparisons? 4 into 3, which gives a 12 comparisons. 12 comparisons, right? So what is the result? Obviously, find of 70 will be 10. Find of 60 will be 10. Find of 50 will be 10. So why not we change this tree so that 70 can be directly given as a child to 10? Similarly, whatever the intermediate nodes in this particular path, for example, this path we are having 50 and 60. So all those nodes can be associated as a children for that particular parent, so that the number of comparisons will be reduced. So for the first find, it requires 3 comparisons, and from the next find onwards, it will require only 1 comparison, because we are just collapsing this tree structure and we are giving 70 as a child to the parent 10. So directly from the next find onwards, we will be having only 1 comparison. So for doing such type of things, we need to change the algorithm. That means by using this collapsing find, the name itself indicates we are collapsing the tree structure. So what we are collapsing all the intermediate nodes of that particular path, and we are associating each and every node as a children to that particular root node, because always whatever the element we are finding, the result will be the set representative. That means only the root node. So if you find 70, it will be root node 10. If you find 60, it will be root node 10. If you find 50, then also the result will be 10. So that's why we are just collapsing the tree, all the intermediate nodes, and we are associating them to the root node. So for that purpose, we are just changing a small algorithm. We are changing a few things in the algorithm. See, let us write the collapse find. Collapse find. So first, let us take some root is equal to some I, and find out the root element. What is the root element? Because we have to assign the root as a parent of 70, right? So why P of root is greater than 0? Simply, we can say root is equal to P of root. So this is a simplified operation. And after that, simply check why root not equal to I. Root not equal to I. Then take some temporary variable, right? Some S is equal to P of I. The parent of node I will be assigned to S, and then the root will be assigned to the parent of I. The root will be directly assigned to the root of parent of I, and then I is equal to yes. So assign yes to I now. Okay, recursive call. And simply after completion of this, that means whenever the root becomes I, simply return the root element. That will be the result, right? So this is the collapsive find. What we are doing? So some operations we are doing, and again some operations we are doing, so that we are collapsing all the elements in the intermediate elements of that particular path, and we are assigning that to the parent. Now we will check with this one how the tree will be collapsed, how the elements will be collapsed by using this one, right? So let's check with this one. C find of 70. We know the result will be 10 because 10 is the root element. So what happens here? So I is 70 and root is equal to I, which is 70, right? So initially I is equal to 70, root becomes also 70, right? Now P of 70 greater than 0, parent of 70, which is 60, 60 greater than 0, true. What happens? Root is equal to P of root. Root is equal to P of 70. Okay, so P of 70 is 60. Now again find operation. So again go with this one. Parent of root is 60 now. Parent of root is 60. So now 70 becomes 60 here. So P of root 60 greater than 0. Parent of 60 is 50. So 50 greater than 0. True. Then what happens? Root is equal to parent of root. Root is equal to parent of root. Parent of 60. That's the parent of 60, 50. Now root becomes 50. Root becomes 50. Now
parent of 50 greater than 0. So which is parent of 50? It is 10. 10 greater than 0. True. That implies root is equal to parent of root. Okay, what's the parent of root? 10. Parent of 50 is 10. So root becomes 10 now. So now it becomes 10. Now parent of 10 greater than 0. So we know that the parent of root, here 10 is a root. So in this disjoint sets, the parent of root will be negative value. Negative value. Parent of root will be negative value. So that will be either -1 or the total number of elements in the set. So if you are applying the simple union, it will be -1, and if you are using the weighted union, it will be the count of elements, minus of count of I. So it will be negative value. So let it be -1 greater than 0, it is a false. So now the root value becomes 10. So I'm erasing all these things. Now the root becomes 10 after executing this step. After this executing that particular while loop, right? Now what we have to do, we find that root element is 10. Root element is 10. So we are not returning the root because we are collapsing the intermediate elements. Okay. So now while root not equal to 0, root not equal to I, root is here 10. 10 not equal to, what is the I value? 70. True. So what we have to do, you have to go with this one. S is equal to P of I. So P of I means parent of 70. Parent of 70 is 60. So S becomes 60 and P of 70 becomes root. What is the root value? 10. Parent of 70 becomes 10. So here I am updating here. Parent of 70 becomes 10. Right? And then I becomes, yes, what is the S value? 60. Now I becomes 60. Now what happens? Here this tree has been collapsed and parent of 10, it becomes 70. Okay, we are not stopping here. So again we are collapsing the intermediate nodes of this particular path. Now I becomes 60. Now I becomes 60. So what we have to do? So again check root not equal to I. So that implies root is 10 not equal to I means 60. True. So we have to enter into the loop. So S is equal to P of I. What's the I value here? I value is 60. So here 70 becomes 60 now. Okay, now P of 60. So which is parent of 60 is 50. S is 50. Now P of I. P of I means here 60. Parent of 60 becomes root. What is the root? 10. Root 10. Parent of 60 also becomes 10. Right? Now the tree structure has been collapsed and 10 will be the another chain of 10. Sorry, 60 will be another chain of 10. And what happens here? I is equal to S. So I is equal to S means here S is 50. Now I becomes 50. Now I becomes 50. Okay. Now again root not equal to I, which is nothing but root is nothing but 10 not equal to 50. True. Again it will enter into the loop. S is equal to P of I. I means 50. What's the parent of 50? It is 10. And then parent of I. I means 50. Parent of 50 will be root. So root means again it will be 10. So already 50 parent of 50 is 10. Right. Now what happens? The next one I is equal to S. That means S is here 10. So I becomes 10 here. So I becomes 10 here. Right. So now you can observe again root not equal to I. That means root is 10 not equal to 10. False. Then it will be stopped and it will comes here. So return root which is equal to 10. See which is 10. Now what happens? If you apply the same operation multiple times, that means the find operation multiple times. For example 70 and again find of 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 70. Right? Now what happens? If it is a simple find, it requires the 3 comparisons, 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 and it requires 3 comparisons. So total it requires 15 comparisons. 15 comparisons for simple find. Simple find. Now, if it is a collapse find, see for first find operation, it requires total 3 plus 3, 6 comparisons. Okay, this is the 3 times and this is also 3 times because 3 nodes are there. So 6 comparisons will be done, and here for the next time it will be 1 comparison, it will be 1 comparison, it will be 1 comparison, and it will be 1 comparison. So total 10 comparisons will be there. Total 10 comparisons will be there. Hope you understood. If it is a simple find, so we are only finding this one, right? That means so total 3 comparisons to find the root. So how many finds we are using? 1, 2, 3, 4, 5. So total 5 times it will go with the 3 comparisons. 5 is 15 comparisons. It requires around 15 comparisons. For example, if you implement the same thing using a collapsing find, so for the first iteration, for the first find 70, it requires 6 comparisons because this is 3 and this is also 3. Total 6 comparisons will be taken. But from the next find onwards, it requires only 1 comparison because directly 70, 10 is the parent of 70. Okay, 10 is the parent of 70. So for the next find, it will be only 1 comparison. Second find, it will be only 1 comparison. Next find, it will be 1 comparison. And next find, it will be only 1 comparison. So total 10 comparisons will be there. So automatically the complexity has been reduced. Okay, the complexity of our algorithm has been reduced. So we are also reducing, that means collapsing the tree structure. And all we are giving all the intermediate elements as a chain to the root node. Okay, so this is how we are using this collapsing find. If it is only one time we are using the find operation, then you can simply use this simple find operation. If it is more than 2 or 3 times, if your logic requires to implement the find operation 2 or 3 times more, then simply we can go with this collapsing find operation. Right? So hope you understood. So these are all the different operations done on disjoint sets. So simple find, simple union, weighted union, and collapsing find operations. Right? So let's stop here. And if you are having any queries regarding this procedure, feel free to post your doubts in the comment section. Definitely, I'll try to clarify all your doubts. And if you really enjoy my session, like my session, share my session with your friends, and don't forget to subscribe to our channel. Thanks for watching. Thank you very much.